How's everybody doing? My name is Roger Siegel, and I'm coming to you live tonight from Sarasota, Florida. And joining me tonight is my co-teacher. And go ahead.
Hi, I'm Christy Gonzalez-Vega, and I'm located in Frisco, Texas. And we are super excited to have this interaction with you guys and be able to come live every night. I know that I enjoy the feeling that there's somebody else out there, not just my family that I'm with every day. So if my students are out there, hello, you better be watching.
Excellent. Okay, well, great. Well, starting tonight and then for the next 27 weekdays, Kristen and I are going to be teaching you some of the things that your teacher might not have gotten to in your regular AP Physics CE class. And then we're going to review for you to get you ready for the exam. And so here we go. Let me open up my screen and start to show you a PowerPoint presentation. And this PowerPoint presentation is going to be available probably not tonight, but sometime soon in the comment section of this video. This video is being recorded, so you can come back later and look to it. If you'd like to come back later and print out the PowerPoint and go along, take notes with us, that's absolutely fine, and that's something that might really work for you, and we totally encourage that. Okay. All right, great. Well, the first thing I want to say is what we're going to be doing tonight, and that's what we're going to be talking about forces on moving charges and magnetic fields. Now, today the topic we're covering is one the colleges have asked all AP students to study, even if it won't be on the exam. You may have heard that some of this material is not going to be on the exam, and it's not. But the colleges have asked us to cover it, and so we're going to be doing that for the next tonight and the next 7 evenings. And after that, we're going to be doing a complete review of everything that will be on the exam. And as we go through every night, there's going to be some stuff to review as well. So it's going to keep you interested and give you the physics that you need. So the first thing that I want to do here is talk about what we're going to be doing tonight. And so you can see here, what we're going to be doing is talking about magnetism, and we want to try and accomplish these 5 things: calculate the magnitude, direction of the magnetic force, the interaction between a moving charged particle of specified charge and velocity moving through a region of uniform magnetic field. That's a lot to say, but basically a charged particle moving in a magnetic field, what happens to it? What conditions are necessary for it to experience no force? What kind of path would it take? A charged particle moving through a magnetic field. And then we're going to derive an expression to give us the circular path that it can take. And then finally, there are some conditions where both an electric and a magnetic field are perpendicular to each other, and the particle can go straight through, and we're going to study that as well. So the first thing we want to talk about is magnetic fields. And you've probably studied the gravitational field, you've studied the electric field, and you may have heard of other fields like the Higgs field or a gluon field. And this is the way that physicists describe the universe is through fields. So all fields are basically just values that exist in space. So the magnetic field is caused by a permanent magnet or by electromagnetism. Now, permanent magnet, you've certainly seen this before. Here's a nice magnet, and here's a scissors. Oh, there we go. And so that magnet works very well. But we're not going to really study a permanent magnet very much. We're going to study magnetic fields that come from electromagnetism. All right, so let's start with this idea of magnetic field. First of all, it has an interesting symbol, capital B vector. And so you can see right here, there's our magnetic field. Let me pull up a little pen here so I can do a little annotate. And so we have this capital B vector, and that's the magnetic field. Now, the gravitational field, you might remember, has the units of newtons per kilogram, and the electric field has the units of newtons per coulomb. The magnetic field has the units called Teslas. And if you think that sounds like the car, you're absolutely right, it does. And both the car and this unit are named after the famous physicist and inventor Nikola Tesla. So you've lived your entire life, from the time you're born right up until now, in the Earth's magnetic field. And so all evolution is happening in this field. You're used to surviving in it, and it is what covers our Earth. So and so that's the Earth's magnetic field. Let's talk about these magnetic fields. The magnetic field from the Earth is about 10 to the minus 5 Tesla, or 10 microtesla. The magnetic field from the Sun is about a nanotesla, 10 to the minus 9 Tesla. See that? A refrigerator magnet. I got this refrigerator magnet when I was in Boston and at the Science Museum. Can you see what it says? There you go. Good with numbers. So this refrigerator magnet is about 1 Tesla. About 1,000 of Tesla. But this magnet, the neodymium magnet, is about 1 Tesla. Okay. And then if you've ever had an MRI, that was probably 1.5 to 7 Tesla. So as soon as we start talking about magnetic fields, it's going to force us to do a kind of notation to better describe and draw the field. Now, you've probably seen a notation like this, where you had a 3-dimensional picture and you had 3 axes, and this is your x-axis, your y-axis, and your z-axis. And that's certainly a way to draw things. But we're going to introduce another concept here that physicists use, and that is the magnetic the field vectors that are either into the board, into the paper, or out of the paper. And so on the left here, these are showing me vectors that are pointing away from me or into the paper as I'm looking at them. And these are showing vectors that are pointing toward me, like right toward my eye, or out of the paper. And so we'll use those as we go through. Now, the best way for me to get you up to speed on the magnetic field is to take what you already know about the gravitational field and the electric field, review those, and then we'll jump into what that means for the magnetic field. All right. So the gravitational field, you may remember, is all around the surface of the Earth. We kind of symbolize the gravitational field as this downward field. All right. It's straight down near the surface of the Earth. And if you remember, it's about 10. So this is our gravitational field, points straight down, and its quantity, the magnitude, is 10 newtons per kilogram. And that field is near the surface of the Earth. It's pretty much there everywhere. Now, if we go far away from the Earth, it'll be less. And if we go far away from the planet, these field lines are not all parallel. If we zoom out, we see these field lines are radial, and you might remember that from your earlier physics class. But when a mass is in a gravitational field, it feels a force, and that force, F of g, is equal to mg. Okay. And so because of that, when it moves through that field, it either goes in a parabolic path or a straight line, but speeding up and slowing down. So when you throw an object up, on the way up it slows down, on the way down it speeds up, and so that's what happens in a gravitational field. The mass in the field feels a gravitational force regardless of whether it's moving or not. So imagine when you're sitting still, you still have weight, and that so you don't have to be moving to feel a gravitational force. Now the electric field we learned about in this class in an earlier unit, and that's this E vector. And look at how similar these are. F of g is equal to mg, F of E is equal to QE. A mass in a gravitational field feels a force, a charged particle in an electric field feels a force as well. Okay, so same thing. We've got this object, it's moving in a parabola, or it's in a straight line, but it's accelerating. Okay, the charge, electron or proton or whatever it is, it feels this electric force whether it's moving or not. And since both the electric field and the gravitational field can speed up or slow down a mass, both of those things can do work. Both of those fields can do work on an object. The gravitational field does work on masses, the electric field does work on charges. Now, this guy over here is very different than both the gravitational field and the electric field. These guys are like twin siblings. This one, step maybe. This one is definitely different. Let's take a look. So when a charged particle is moving through a magnetic field, it experiences a force perpendicular to both its velocity and the magnetic field. That's kind of weird. We're going to learn about how that happens with the right-hand rule. So we don't need to talk about it too much. You'll see how it's more intuitive than verbal. Now, but this is what's really weird. Instead of this particle in a field moving either a parabola or a straight line, it could either move in a circle, a spiral, which is also called a helix, or it could move at a straight line with no difference in speed. Okay. Now, this is the thing that I think you're going to find very strange. Both the electric field and the gravitational field exert forces whether or not the object is moving. In the magnetic field only exerts a force on moving charges, which is very strange if you think about it. Imagine if the gravitational field only exerted forces on you when you were moving. Every time you stopped, you would be floating because there would be no gravitational force. But this is how the magnetic force works. Okay. Now, since the magnetic force never speeds up an object and never slows down an object, that means it does no work. So it cannot change the energy of a moving object. All right. So let's go back to the PowerPoint and see what we have next here. Now, this is how we're going to talk about the force on a charged moving particle. This is the big enchilada of the lesson. That is, what is this force? Now, if you take a look at this, I'm going to show it to you on my doc cam here. This is the magnetic force on a charged particle Q moving through a magnetic field of magnitude v with speed v is given by this. So let's look at this. Fm stands for magnetic is equal to Q, that's the charge, velocity vector crossed with the magnetic field vector. Now, this is a cross product, okay? And you may have done a cross product before, probably in your math classes. It is not something that really comes up in the other parts of physics C, but it does come up here what the cross product is. And actually, it does come up in rotational inertia and rotational momentum. Sorry, but the cross product here is a vector quantity. Now, the good news for us is we only have to know the magnitude of this vector, not its direction. So instead of doing this cross product, we could say magnitude of V times the magnitude of the velocity, charge velocity, times the magnitude of the magnetic field, times the sine of theta, where theta is the angle between these two vectors. Now, that's a lot to talk about. I know it's a big mouthful. Let me show you how this works because it'll make a lot more sense. Now, the cross product is a right-hand rule. Now, I'm going to do something that I hope you find is very utilitarian. I hope it doesn't bother you too much. I'm going to write on my hand. And so I'm going to write on this hand. And on this hand, I'm going to write a V, and that's a velocity vector, okay? And I'm going to draw an arrow there. So whenever I've got an object moving, I'm going to point my hand in that direction. This middle finger, I'm going to put a capital B vector. And if you remember, the B vector is the magnetic field vector, okay? And then on my thumb, on the pad of my thumb, I'm going to put an upward arrow, and I'm going to put F for the force. Now, what we're going to do, and you have to do this with your right hand, which means you just drew on it with your left hand, which is not so easy. What you're going to have to do now is you're going to hold your hand in this very strange way, okay? You start with your hand like this, and then we leave this index finger, but we bend these three fingers like this, okay? And so anytime I'm doing a problem, and I want to know what the force is on an object moving through a magnetic field, I point my fingers in the direction of the velocity of the object. I let my three fingers here point in the direction of the B field, and my thumb gives me the direction of the force. All right. So the first thing we're going to do is we're going to talk about when the magnetic field is parallel. The first thing we're going to do is when the sine of theta is 1. That is, the magnetic field is moving perpendicular to the velocity is moving perpendicular to the magnetic field. Now, when that happens, what we have, I'm going to actually put this last. We'll get to this in a minute. Okay, put that right there. All right. So when that happens, what we have is this. I'm going to show you. So notice we've got a positive charge here, and this positive charge is moving to the right. So it's going this way. Now I'm going to zoom in, and I'm going to show you what happens. Now, as soon as this positively charged particle enters this magnetic field, remember we said this is pointing away from here into the page. So I'm going to put my fingers in the direction of the velocity. I'm going to bend my other fingers, and I'm going to point them such that they are pointing down into the paper. And now you can see my thumb is pointing upward. What that means is that when this object enters here, it feels a force in this direction. So this is the velocity, this is the force. Now, if you remember from kinematics or dynamics, when force is perpendicular to velocity, we get only a change in direction, not a change in speed. And so this particle is going to be pulled in that direction. But guess what? If we do a right-hand rule again, V cross V, now look at where my thumb is pointing. Now my thumb is pointing this way. And then I can continue around like this. And some of you are probably imagining, you can see what I'm doing, is what's going to happen is if the force is always perpendicular to the motion, you remember what we get? A circle. In this case, a semicircle. And that's what we get. Now we're going to talk about the size of that semicircle in just a minute. But first, let's just get the direction of the semicircle. Okay. So this is the first one, right? Let's look at the second one. Now this is a positively charged particle moving to the right. Okay. And I'm going to zoom out again so you can see my hand a little bit better. And so I'm zoomed out, and you can see here's my V vector. And now this B field, this magnetic field, is pointing out of the page like that. And so I'm going to put my fingers in that direction, and then I'm going to have my B field. My B field points up out of the page, which means look at my thumb, it's pointing down. And so now we get a semicircle in that way. And remember that this force is Q times V cross V. Okay. And so that force is always perpendicular. It always points towards the center of that semicircle. Now look what happens when we have a negative charge moving to the right. Now this negative charge, Q V cross V, since the charge is negative, that means even though I use my right hand and my thumb is going to indicate a direction of the force, I'm going to take the other direction. So some people like to use their left hand for this. I never have, but it is a left hand rule when we have a negative charge. So I'm going to say V cross V out of the paper, and that's going down, which since negative, it means we're going to have this upward force, and everywhere the force is toward the center. And then if we have this negative charge moving to the right, we're going to say V cross V, and that gives me an upward. Yes, V cross V, that gives me an upward force. So this one is now downward. All right, let's go ahead and talk about the size of that circle. Now, so when the magnetic field is perpendicular to the direction of motion, the charged particle moves in a circle. This radius is found by setting the centripetal force equal to the magnetic force. Okay, and so Fc is equal to force magnetic. Now, hopefully you remember from your earlier physics, either physics and mechanics, physics 1, or whatever physics you took, that the centripetal force is mv squared over r. And remember, the centripetal force is not a force per se; it is the sum of all the forces acting on the object. Well, guess what? Sum of all the forces in this case is the magnetic force. And look what happens. I have mv squared over r is equal to qvb, and this v cancels. Okay, and so now I can solve this for r, and I get r is equal to mv over qv, which is what we have here, and that gives me the radius of my circle. Now, because of time constraints, I'm not going to show you the simulation, but it is on the PowerPoint, and I think if you go there and you try the simulation, it'll give you a really good sense of what's going on. Now, sometimes the motion of the object is exactly parallel or anti-parallel to the magnetic field. So imagine we've got a magnetic field that looks like this to the right, and I've got a charged particle moving parallel to it. Well, I know that the force magnetic is equal to q v b sine theta, and theta is the angle between v and b. Well, the angle between these two vectors is 0, and the sine of 0 is 0. So this force is equal to 0, which means this object, if we see this problem, the charged particle is projected with its initial velocity parallel to uniform magnetic field. The resulting path is straight line parallel to the field, and it doesn't say that on here, but constant speed. Again, the magnetic force never speeds an object up or slows it down. It can't do any work. By the way, if here the angle between these two vectors is 0. If I had my object starting over here on the left and moving to the right, you can see the angle between these two vectors is 180. Well, the sine of 180 is still 0. So the force, whether we're parallel or anti-parallel, is going to be 0. Okay. Now, the last one I have for you before we try some more problems is talking about what happens when the angle between the v vector and the velocity is neither 0 nor 90 degrees. Okay. When that happens, when the angle of the b field, okay, is not perpendicular to v and b is not parallel to v, in that case, or anti-parallel, in that case, we get a very interesting case. We get a helix. And so when I say helix, what I mean is a spiral. And there is a GeoGebra simulation in the PowerPoint that you could look at to see the spiral. But this is what happens. And again, it's a spiral at a constant speed. This problem is rare to come up in AE Physics C, and it will not come up on your exam. All right. So I think we're going to send it over to Kristen in Frisco. And let me go ahead and stop sharing my screen. And Kristen is going to walk us through some problems and get us some more depth of knowledge here.
Thanks, Roger. Yes, we're going to go ahead and apply all those awesome concepts that you let us through and practice that right-hand rule along with kind of bringing it back to some of those other concepts that we learned earlier in the year. The first one we're going to look at here is a multiple choice problem. And in this problem, we have a region of space where there's a uniform magnetic field that is in the plane of the page, and there is no electric field, so only a magnetic field in this region. If we have a positively charged particle that is traveling with velocity v directed into the page, as we can see by the x here, right? The way that I kind of think of this is if this is an arrow, right? When you shoot an arrow, what do you see when it's going away from you? Well, you see those feathers. And what do you see when it's coming out towards you? You see the point of the arrow. So if it's coming out towards you, you see that point, and if it's coming away from you, you see the feathers. others. So into the page, we have that x. So if the velocity is into the page and we have a force that is diagonal here, then we want to know which of the following is going to represent the magnetic field. So I'm going to pause for just a second here. I'm going to let you get out those right hands and practice to see if you can figure out which way will the magnetic field be directed. Okay, you got it? So if we look at it, and I'm going to turn sideways here so you're not looking at a mirror image. If we know that the velocity is directed into the page, right? My finger goes into the page, and I know that the force is up at that angle, then my thumb goes up at that angle. Well, then I've got my middle finger here pointing down into the left. So you should have found that the magnetic field is pointing down to the left, which is answer E. All right, very good. So the next one here, I'm going to bring back some graphing. We love graphing in physics. So this question here wants to know if we have we got to be really careful. That's the first thing you always want to look for when you're reading a problem. Is your particle positively charged or negatively charged? Because that affects everything. So this time we have a negatively charged particle. It's still moving in a uniform magnetic field with a velocity v directed towards the right here. And if we use our right-hand rule, we would find that even if they didn't draw this path for us, that if our velocity is to the right and our field is into the page, if this is a negatively charged particle, like we heard before, you can either switch hands or you can just find what it is using your right hand and flip it. We would find that the force on that would be downwards. And so if we have that downward force, then it makes that nice circular path moving in that constant speed still. We want to know which of these graphs would best represent that radius as a function of the magnetic field. So we're going to derive it again really quick. Anytime you're asked to graph something, don't just try to guess what it is. You can find what that equation is, that relationship that will tell you what it is. So we know again that it's moving in a circle, right? So we can start off with, again, the magnetic force is acting as the centrifugal force. And if we know that's true, then we know that our QVD is going to be equal to our MV squared over R. Again, we cancel out one of those V's, and we know that Q times B is equal to MV over R. And if I then rearrange, we get that R will be equal to M times V over Q times B. So this is what I like to refer to as our working relationship. If I want to know what kind of relationship there is between R, I can look at what anything is. I can say, well, what is the relationship between R and M? If M increases, R increases. That's a direct relationship. But what we're looking for is a relationship between the radius and the magnetic field B. Well, if B were to increase, what would happen to R? It's going to decrease, right? That's an inverse relationship. So if you look back at our graph here, it becomes really easy once we get that relationship and see that B is the only one here that is an inverse relationship. All right, we good? Moving on. The next one here we have is again, what kind of particle? Positively charged particle. Moving with velocity initially upward here at point A. And that particle, again, due to that force, is going to curve to position B, where it has same velocity B. And if this takes a time of delta t to turn, we want to know which of these would best represent the magnitude of the magnetic field that would create that change in that amount of time. So this one, even though you don't see the whole circle, and we see this kind of in other ways in physics too, even though we don't see the whole circle, it's still a circle. It still is going to follow that circular motion. And really, we can see here that it's following really a quarter of a circle or a quarter of the circumference. So we're still using these circular motion concepts. So I still can say, well, my magnetic force is still my centrifugal force. So my QVB is still equal to my MV squared over R. But I want to know what the magnetic field is. And if I look at these, well, I don't have, even if I simplify this down and I say, well, Q times B is equal to M times V over R, well, I still can't have V in my answer, right? These are one of those where it's kind of, well, I got to get rid of that V. I have then the relationship, if we go and think about circular motion and velocity, it's still distance over time in a circle. If we just take the whole velocity all the way around, we have an equation that I know is familiar to you guys. And that's that if we look at the full circle, that we call that the period, right? And we know the velocity would be 2 pi times R over the period. But we're only making a quarter of a circle. So then we can say here instead that the velocity is equal to 2 pi over R over 4. And so period, we say that this is the time, which is delta t that we're told. And so if I plug that back in for my velocity, I get that my charge times my field is equal to M times V, which if I simplify this down is just pi times R over 2 times delta t. But don't forget, we still have this R here. And if I cross off those R's, then QB equals M times pi over 2 times delta t. And the last step, I want B by itself, so I bring my Q over. So we end up with M times pi over 2Q times delta t, which is always nice when you get that answer that's there, right? Okay. The next thing we want to talk about is kind of some applications where you actually see this in the real world, right? We do all this physics and we want to know what does it matter. So one of the machines that we can actually put this to use in is what we call a mass spectrometer. And a mass spectrometer is a way for us to analyze samples to see what's in it, right? What compounds are in a sample. And the way it works is we inject it into an injector, it's vaporized and ionized, and it's brought through a region we call the velocity selector right here. The velocity selector kind of weeds out different velocities that we don't want. And I'll show that in a minute. But we go through this area here that we call the detector, which where we can see there's a magnetic field. And that magnetic field is going to cause our ion to either curve down or curve up, depending on what its charge is and which direction the magnetic field is. So let's kind of look at what an example of one of those could look like. So let's say we have here, and the way that's made up of is we have a voltage source that is connected to some parallel plates. And so if we look at that, this would be the negative side of our voltage source, right? And this would be our positive side. And if those are connected to those two parallel plates, that means we're going to get a positive charge building up on this plate. And we're going to get a negative charge building up on this plate. Well, if I have those charges separated, then that's going to create an electric field in between. And that electric field is going to be running from that positive side up to that negative side, or upwards in this case. If we put in a charge here, let's put in a positive charge here that is traveling with some velocity, then it encounters this electric field, what will experience? We know that charges in electric fields will experience an electric force. And positive charges experience that force in the same direction as the electric field. Negative charges experience it in the opposite direction. So since this is a positive charge and our electric field is going up, then I know also that my electric force would be up. And if this were the only force acting on my particle, then that positive charge is going to curve up and it's going to strike one of those plates. But we don't want that to happen. We want it to travel through undeflected, straight through. So we also are going to introduce a magnetic field in this region to balance out those forces. So if we have an electric force going upwards on this and we want to go through undeflected, which way does that force have to be? Well, it's got to be down. So we know we got to have a magnetic force going down. So one question I would have for you is which way would that magnetic field have to be directed in order to create that force down? Right, so take a second, really quick, use that right hand rule again. If we know the magnetic force has to be down, which way would the magnetic field have to be directed? You got it? So if our velocity is to the right and we know our force has to be down, then we know that the magnetic field has to be going out of the page everywhere here. And if it's undeflected, we know that those forces have to be equal. There's no acceleration in that direction. So we can say that our electric force is equal to our magnetic force. And we know that the electric force is Q times E, the electric field. And so we can set that equal to our QVB. Well, charge cancels out. Look at that. Doesn't matter as it goes through that region. We can say that E, well, I'm not given what that E is a lot of times. Maybe you are, maybe you're not. Maybe we know that the voltage source is V. And I know that these are separated by distance D. So how can I relate voltage with my electric field and separation distance? Well, E is equal to that potential difference divided by that distance of separation. So we can say that is V times V. We do this all because this is a velocity selector. We want a specific velocity to go through. So if I rearrange, the velocity is equal to the potential difference divided by that distance times the magnetic field. And so that is what we can use to find the velocity as it goes through. But you're going to see this lots of different ways. Sometimes you'll be given the direction of the magnetic field and you have to determine maybe this, we don't know if this is a positive or negative plate. And you've got to label that on there. We've got to be able to say which way it's going to curve in the magnetic field. Maybe we don't know what direction that field is, we have to work all the way around. Or they give you which way it's curving and you've got to say which way the magnetic field is. You've got to be able to kind of apply all those concepts. Okay, so let's do one more practice with that velocity selector. So we've got a proton beam here and it's moving parallel to the x-axis, as you can see in the diagram, in that positive x direction. And we also have a region of cross electric and magnetic fields in that area. So it's going through undeflected. So if the magnetic field is pointed in the positive y direction, in what direction must the electric field be pointed? Okay, so again, I'm going to give you just a second here to see if you can think this through, and then we'll talk about it. Okay, so if you need more time, you can always pause, but we're going to move on. So if we know that the velocity is pointed in the positive x direction, and I know that the magnetic field is pointed in the positive y direction, well, if we use our right-hand rules, then we would find that the magnetic force would be in the positive z direction. So if our magnetic force is in that positive z direction, in order for this to go through undeflected, well, we've got to have an electric force bouncing that out. So we've got to have an electric force going in the negative z direction. Okay, so how does that electric force relate to the electric field? Well, again, we got to ask ourselves, is it positive or negative? Always checking back, positive or negative. If this is a proton beam, that's a positive charge, then we know positive charges experience forces in the same direction as the electric field. So if we know the electric force is in the negative z direction, then that means that our electric field also has to be in that same direction, which is that negative z direction. Okay, I hope this helps. Roger's going to finish this out here, so I'm going to throw it back to you and take us home.
Okay, thanks, Kristen. We talked about a lot today, but it all goes back to how particles behave in a magnetic field as they're moving through a magnetic field. And Kristen gave us a great view of the mass spectrometer, and I'm going to bring up my mass spectrometer picture. And what you'll see is this is one of the last pages on the problem that we're doing. Oops, I dropped my pen again. Excuse me. Okay, there it is. So this, by the way, all the problems that we do on this online course, we're going to try and tell you where they're found, and we're going to try our best to make sure that these problems are problems that are public. And by that I mean, if you go to the AP Physics C E&M website and you look up the exam website, we have all these exams are online and their solutions back to, I believe, I was going to say 1990, but it's not true. It's 1999. So this one is not on that website. Sorry about that. But we will try as best we can to put these on there that you can get. All right. So here we go. This is from the 1990 exam. And so it says, in the mass spectrometer shown above, particles having a net charge Q plus are accelerated from rest to a potential difference in region 1. They then move in a constant line through region 2, which contains a magnetic field B and an electric field E. Finally, the particles enter region 3, which contains only a magnetic field B, and move in a semicircular path of radius r before striking the detector. The magnetic fields in regions 1 and 2 are all uniform and have the same magnitude B and are directed out of the page as shown. Okay, now before we start doing this problem, I want to just kind of give you this whole anatomy of the mass spectrometer, what's happening in the different places. All right, so over here, this is where we are accelerating particles. So here the particles start from rest over here, and they get sped up through this potential difference V. And so this is our particle accelerator. All right, put that there. And then from here to here, this area in here, this is what Kristen just told us about. This is the velocity selector. And remember, what happens here is particles are moving through, and only particles that have a specific velocity will move through straight through. Those particles that are moving too slowly are going to be overcome by the electric field, and those particles that are moving too fast are going to be overcome by the magnetic field. And we'll talk about what that direction is. And then this part back here, this is really the business end of the mass spectrometer. This is where the spectrometer part happens. And because we saw that R was proportional to M, that means that the bigger the mass, the farther this goes. Now I want to tell you, these machines are very sensitive. What we're using them for is to find the mass of ions. So imagine an ion of water, and an ion of water has a mass of about 10 to the minus 26 kilograms, 10 to the minus 26, and that's what we're measuring here. So here's the mass spec part of the business end of the mass spectrometer. Now, the first part says, indicate the direction of the electric field necessary for the particle to move in a straight line through region 2. All right, so let's take a look at that. Again, I'm going to need my right hand because I'm going to do my right hand rule. Now I can see, I want to ask myself, what is the magnetic force on this? So again, we're going to say it's QV cross V. Say Fm is Q times V cross V. And that means the cross product is a right hand rule. It's a positive charge. So my finger is pointing in the direction of the velocity. These magnetic field lines, these vectors are coming out of the page, right toward me. And so I'm going to put my fingers, I'm going to turn my B fingers up, my middle finger, and you can see that the force is down. And so my particles in here are experiencing a magnetic force in that direction. So if I didn't do anything about this magnetic force, it can crash into this bottom plate or this wall here. So what I do is I want to have an electric force in this direction, okay? And so how do I get an electric force on a positive particle? Well, what I do is I have an electric field that points up. And so that gives me a force on a positive charge that's up. Now, if the particle is moving at just the right speed, it will cruise through here. If it's moving too slow, it won't have much magnetic force and it'll crash into this wall. If it's moving too fast, it'll have too much magnetic force and it'll crash into the bottom, okay? All right, so that is our first part A. In terms of any of all quantities, any or all quantities, Q, B, E, and R, determine the expressions for the speed of the charge. Okay, now the speed of the charge, that happens in the velocity selector, right? So what we're going to do is we're going to say down here, and Kristen already showed us this, but we're going to set the force electrostatic equal to the force magnetic, and that's Q, E, and that's Q, B, B. Also sine theta, but remember in this case, theta is 90 degrees, and so the sine of 90 degrees is 1. And so you can see the Q's cancel, and so the speed is now going to be E over B, okay? And so that's part B of my problem, the speed that these particles, and this is the speed that they come through the velocity selector at that speed. Part C says, what is the mass of the charged particles? Now the mass gets found out at this last part in the mass spectrometer. And we're going to do this derivation again, and you want to practice these derivations as often as you can. Every time you do a problem, start with the basics. FC is equal to Fm. It helps you to remember them. FC is the centripetal force, mv squared over r, and Fm is Q B B, okay? Now one of these V's cancels, and so the mass is going to be Q B R over V, okay? And now we look at that and go, okay, that's my answer. Be careful. Remember, AP Physics has told us there is no V in my answer. So that means I've got to go back here and grab this V. And now I'm going to say M is equal to Q B R over the V. Well, that's E over B. And so this whole thing is Q B squared R over E. And that's the mass of my object. So by putting this detector here and figuring out how far, what the radius of this circle is, that's what the detector tells me. Now I can find the mass of a molecule. All right, part D says the accelerating potential. Now, this is the accelerator. And this takes us back to unit 1 in this class where we learn about potential energy. And imagine here we start with 0 kinetic energy and we move through this potential. So what gives us the kinetic energy is moving through this change of potential. So for part D, I'm going to say that delta U is equal to delta K. Kinetic energy that I gain here is equal to the potential that I put through, okay, that I'm accelerated through. Now, if there's one thing that I wish I could get all students to remember in E&M, it's what the units for volts are. Because if you remember the units for volts as joules per coulomb, it's going to help you a lot. This is an energy term. Volts is joules per coulomb times coulombs gives me joules. That's the energy that I get from moving through this potential. And this is equal to 1/2 mv squared. Now, let's be careful about this. Notice that's a V for the potential, the voltage. That's a V for the speed. Don't confuse the two. That's why I put the little underline under here to show me that that's a capital V for voltage and that's a small v for speed. Now, I want to know what the speed, what the accelerating potential is. So we're solving for V. So we're going to say V is equal to 1 over 2Q times mv squared. Now, Q can be my answer, but M and V cannot. And so I'm going to pull those from over here. Here's my V, here's my M. And so this is 1 over 2Q times M, which is Q B squared R over E times V squared. And that's going to be E squared over E squared. Okay, that's M and that's V squared. Now you can see that the V squareds cancel, the Q's cancel. And one of these E's cancels. And so you can see what I'm left with is just an E and an R and a 2. And so this is going to be E R over 2. And that is the accelerating potential to get my charge moving faster. Okay, 2 more. Part E says what is the acceleration of the particles in in region 3? Well, they're moving in region 3 in a circle, and so the centrifugal acceleration is on your formula sheet. That's v squared over r. And so we know that v is, back over here, v was e over b. So we're going to say e over b squared over r, or e squared over rb squared. Okay? And so that is my acceleration of my object as it's moving through this region. Now, the final question asks me about the time required for the particle. I'll do this one over here. Now, the time required for the particles to move through this path. I know that speed is equal to distance over time. I learned that a long time ago. So what I'm going to do is I'm going to say time is equal to distance over speed. Now, this distance is 1/2 of a circumference. It's 1/2 a circle. And the speed is e over b. And so that's 1/2 2 pi r over e over b. The 2's cancel. And now this b goes upstairs. And so we get that t is equal to pi b r over e. Okay, that's a lot. Now, I think that the mass spectrometer problem is one of the most exciting problems in AP Physics C, one of the most exciting concepts because it teaches us so much. And mass spectrometers are some of the most amazing and impactful tools that human beings have ever created. So don't let us stop you. Keep learning about mass spectrometers. Okay, now finishing up, let's go ahead and see where we are and go ahead and take it home. So today our goal was to get you to, sorry about this, we'll get all the way to the end here. Today our goal was to get you through, here, well, I'll go ahead and put it up here, sorry. Let's try that again. Okay. So these were our 5 goals. Calculate the magnitude direction of magnetic force. And so that was Q times V cross V, but we usually did it as QVB sine theta. All right. Over here, the next one, describe the conditions that are necessary for a charged particle to experience no magnetic force. Either its velocity is equal to 0 or V is parallel to V. Describe the path of different moving charged particles. We said we had a circle, a helix, or a spiral, and a straight line. Okay. At a constant speed. All these are at a constant speed. Derive the expression for the radius. We did that. And so we did that by saying FC. I'll do it down here. FC is equal to FM. And so that's MV squared over R is equal to QVB. You see how easy this is? And so that means that the radius is equal to MV over QB. And then finally, describe the conditions under which a moving charged particle can move through a region across electric and magnetic fields with constant velocity. That's when the velocity is in this direction, the electric field and the magnetic field are perpendicular to each other. That's called a velocity select. Right? So that is our lesson for tonight, first of 28. And so we're really forward to seeing you tomorrow night. And we're going to talk about magnetic fields, the motion of wires, the forces on wires through magnetic fields. So we're going to sign off from, you want to go ahead and say sign off, Kristen?
Yes, thank you guys so much for listening and tuning in, and we will talk to you guys tomorrow.
And again, from Sarasota, Florida, thank you for joining us. We hope that this is helpful, and we can't wait to see you tomorrow. Thanks.
All right, good evening, everybody. We are going to be doing AP Physics C, Electricity and Magnetism tonight, and I'm Christina Gonzalez Vega. I am coming to you from Frisco, Texas, where I teach at Reed High School. I teach AP Physics 1 and AP Physics C, and am an AP Physics reader for the College Board. And we also have joining us.
Hi there. My name is Roger Siegel, and I teach AP Physics C here at the Pine View School in Osprey, Florida, which is really close to Sarasota. And we're really glad to have you guys here tonight.
Yeah, so welcome back. One thing I do want to say is that if you were here yesterday, you're going to hear this again, probably tomorrow too. We are going to be covering some topics that have not been discussed yet in class, maybe that are not going to be on the AP exam. But the reason for this is because colleges are supporting these AP tests this year in this modified, flexible way, and with the understanding that you guys are still going to learn the material before you get to school, right? So E&M, magnetism, is half of the course. So we're going to talk about those topics for these first few lessons, and then we're going to get into the review for the remaining larger chunk of the period that we're going to be meeting. So we will put out also a schedule coming up here on what exactly we're going to be doing on each of those days for review, so that you can plan ahead on when you want to make sure to tune in, which hopefully is still every day, so that you can see our smiling faces. Yesterday we did forces on moving charges in magnetic fields, and if you haven't watched that, it might be a good idea to watch that before tonight. We're going to make some references to things that we talked about yesterday. You'll be okay if you didn't, but it is still something you'll probably want to go back and watch. So tonight, though, we're going to talk about what happens if you have a wire, current carrying wire, that is in a magnetic field. So I have here a little virtual demo set up, and there's a really good video that MIT put out that is showing the same thing. But I have a drawing here of my battery, my sparkly battery, and it has a positive negative terminal. Therefore, there's going to be current traveling through this wire. If I put this wire in between this magnet here that's going to have a magnetic field, then it's going to jump up or maybe jump down. It depends on a few things, but it will experience a force that's going to cause it to jump up and jump down. And what that jump is going to depend on is not only how much current is traveling through that wire, which depends on the voltage of the battery, but also the strength of that magnetic field that's in between there. So what we're going to look at today is how we can find that. One of those things is how can we find the magnitude of that magnetic force on a straight segment of wire? How could we find the direction of that magnetic force on a segment of wire? And also what happens if you have a loop of wire in a uniform magnetic field. So we're going to review the right-hand rule, and we're going to see how this is going to apply tonight to our current carrying wires. Last night we learned the rule for moving charges, and what is current is moving charges. So it's not really a new right-hand rule. What we're going to use is our first finger now for the current. Current is moving charges. So just like we had moving charges last night, tonight we have moving charges. So your first finger is always still going to be the current. Your thumb is going to be the magnetic force, and your middle finger is going to be the magnetic field. They have got to be all perpendicular to each other. This is a 3D vector notation. So sometimes people do that kind of tilt bend, which your teacher taught you that. It's totally fine to do. I'm a 3-finger girl because I don't want to get confused on the bending. I got to keep it simple. So we're always going to keep them bent in those 3 directions. We always have the current, the magnetic field, and the magnetic force. And just as a reminder also, if you see a dot, that means that magnetic field or velocity or whatever it is, whatever that vector is coming out of the page at you. And if you see an X, that means it's going into the page. So let's look at our equation. On your formula, you have this kind of complicated looking equation that the magnetic force is equal to the integral of the current times dl across the magnetic field. So where does this come from? I like to kind of know sometimes where these equations come from. How do they come up with them? And really, how can we apply what we learned last night to make this equation? And how can we simplify it down sometimes to make it not so ugly? So what we're going to look at is, let's take a wire. And let's say that that current is traveling to the right. And let's say that it's in a magnetic field that is going into the page. Well, if I take just a little piece of this wire, just a little tiny sliver of that wire, not the whole length, we're going to say maybe the whole length of this wire is L, but I'm going to take just a tiny little fraction, a tiny little differential piece of that wire. And I'm going to say, well, this little tiny piece has a length dl. Well, what's in that little tiny dl of wire? There's moving charges. So we can find what would be the force on those moving charges in that tiny little piece of wire. Last night, we learned that the force, magnetic force, on a moving charge in a magnetic field is equal to Q times V times V, where Q is the charge, V is the velocity, and V is the magnitude of the magnetic field. If I look at this tiny piece of wire here, well, I can change, maybe I don't know what the velocity is, but we have a definition of velocity. If those charges are moving at a constant velocity, then I can really say that this magnetic force is equal to Q times, instead of V, I can say that it's the length. But what length is it traveling in this tiny little segment? It's traveling a tiny little length in a tiny amount of time. And really, this force on this tiny little part is not the entire force on the wire. It's also just a fraction of the force. So our small force created here, let's find the direction while we're at it. If the charges are moving to the right and the current is moving to the right and the magnetic field is into the page, if you use those 3 fingers and do that right-hand rule, you should find that the force is up. Okay, so we've got that upward force, that small little force, dF, still times our magnetic field. Remember, it's a cross product, so either it's the perpendicular component or we can multiply by the sine of theta, but here we're already perpendicular. And this is also not the total charge, this is also a small amount of the charge. So really we can say that dF is equal to dq times dl over dt cross b. And if you remember from your circuits, or maybe you haven't quite gotten it to it yet, I can isolate these two things. If I look at just dq over dt, well, what is the change of the rate of charge per time called? That's the current that's traveling in that wire. So I can simplify this down and say then that, well, the small differential force of that tiny little segment is equal to I still have my dl cross b. And that's one tiny little segment. But we have lots of tiny little segments all across this wire. So how could I find what the total force is on this wire? Well, we know from calculus if we want to add it or sum it all up, we have to take the integral of both sides. So then I end up with that the net force on this wire that's in the magnetic field is equal to the integral of I dl cross b. So I'm going to work out with that, right? So let's practice just some direction ones. I'm going to give you just a couple minutes. Let's look at just these first two for a second. I'm going to give you just a short period of time, and then if you need some more time, you can pause it and resume when you got the answer. Okay, let's look at the first one here. If we have current to the right, we want to put our fingers to the right. We have a magnetic field going out of the page, so I want to turn my middle finger to come out at the page, and then my thumb is pointing downwards. So we've got that magnetic force pointing downwards on that wire. If we look at the second wire, well, in this one my current is going up, the field is going into the page, so which way is my thumb now pointing? To the left. All right, let's look at this one right here, this third one. Oh, angles. We hate angles, right? I hate angles. It's not perpendicular, it's not parallel. We've got this current that's at an angle to the magnetic field, and the magnetic field is at an angle to the current. That's usually how I like to see it, is that how can we break up this magnetic field so that there is a component that's perpendicular to that wire and parallel to that wire. So this one magnetic field line, I could break it up into its two components. And so this part right here, this component is really the component that's actually going to be contributing to the force on the wire. So if we redo that right-hand rule using this as our B field, then I can say that my current is traveling kind of up to the right, my magnetic field is now going up to the left, and coming out at me is my magnetic force. Okay? And then we've got what happens if it's parallel. Well, we talked about this with charges yesterday too. If we have a charge that's moving parallel to the magnetic field, what was magnetic force? It was zero. The same thing happens here. If the sign is zero, when we plug it into that equation, zero, then here we have no magnetic force. Okay? And let's do one more here. If the magnetic field is traveling to the right and my current is going up, so current is up, magnetic field is to the right, then my thumb is pointing into the page away from me. Okay? Everybody good with that right-hand rule? Hopefully that gave you some good practice. The nice thing about current carrying wires is you never have to worry about switching hands. It is always right hand because we use conventional current, which is a positive charge. So let's put this to a little bit of practice. So I'm going to turn it back over to my colleague Roger, and you take it over.
Okay, thanks, Kristen. So yeah, let's keep practicing the right-hand rule. I'm going to share my screen with you guys so we can see where you are. Here we go. Actually, I'm going to come over here and share. And so this is a problem we want to look at now. What will happen to the loop of this wire in a magnetic field? So we can see that we've got a wire here, and it's got a counterclockwise current, and it is in a magnetic field, and these dots mean that the magnetic field is coming out of the paper straight at me. So I'm going to go ahead and open up my dot cam so I can draw on this, and so we can use the right-hand rule. Okay, now, so I'm going to have to stay wide on my picture so that you guys can see my hand as I do this. So let me pick a few points on the circle, and let's find the force at those points. So here's a point here, let's do a point here, let's do a point here, and a point here. And so we know, as we can see here, that Fm is equal to the integral of, and this is going to be IDL cross B. Okay, and so this is a right-hand rule whenever we do a cross product. And so again, just like yesterday, we're drawing my hands again. And yesterday we had velocity, magnetic field, and force. Today we're going to have current, my current I, again drawing with your left hand if you're a righty is a challenge. And the current is not a vector, but it does have a direction. That'll be our direction. Okay, and this is my magnetic field B, and so that is a vector. So I'll go ahead and draw the B with a vector sign on it. Okay, and once again, just like yesterday, on my thumb pad, I'm going to put a force, and this is the magnetic force, and that is a vector, and that's going to be in that direction. So once again, there's current, magnetic field, and force. And when I hold my hand in this somewhat awkward way, okay, where these my thumb, my index, my middle finger, and my index finger are all at right angles, that gives me the force. So we know that this is out of the board, so I have I in this direction, and then I'm going to turn my whole hand, sorry, I'm going to have a view, so that the B field is now pointing toward the camera out of the page, and that shows me that there's a force in this direction. So I'm going to put a force in this direction, and that is a magnetic force, Fm. Okay. Now I'm going to avoid any contortions, I'm going to turn the page, and let's look at this part. Okay, so now here we are, and the current is still in this direction. B is still out of the board, and so that means that the force again is in this direction. And we can repeat that on this side. We can say I cross B, the force is out, and I cross B, the force is out. And so on all of these, not just these points, but all points along this ring of current, there is an outward force active. So what's the total force? The total force net, is the sum of all the forces. And since we have a constant current and we've got a constant B field, so if the current is constant, the B field is constant. When we integrate around the circle, all of these are going to sum to zero. So all the forces are zero. If this were a ring that had some spring in it, it would expand. It would get bigger because of forces on it. All right, now let's look at another one, and you'll see the next one looks like this. Which way is the net force on the square loop of wire if the current is clockwise? All right, so let's take a look at that one. Okay, so here we have again our page, and again we're going to use the right hand rule. The right hand rule yesterday told us about the force on a moving particle through a magnetic field. Today we're looking at the force on a current carrying wire in a magnetic field. And once again, my right hand rule, I have I, D, and F. So I'm going to go ahead and see what the forces are. Now, first of all, in this part of the wire, this part of the wire, and this part of the wire, we are not in the B field. The B field starts here. Here's the B field. Okay, over here to the left, there's no B field. Since there's no B field, well, we know that Fm is equal to the integral of IDL cross B. Well, if B is zero, that means that the force is zero. So here there's no force. There's no force here. I'll just put nothing. No force, no force, no force. Here's where the force is, where we have a B field. So let's start up here. So we're going to say IDL cross B. And once again, I'm going to turn the paper so that I can push my index finger along in this direction. And these X's are telling me that the B field is coming out of the board right toward me, just like that. And so I'm going to do I cross B, hold my hand like this, and we can see now, I'm sorry, I'm totally backwards. Let me fix that. This means that the field is into the paper on this way. And so I cross B is going to give me a force in this direction. So I'm going to write that here. There's a force here, and I'll say M for magnetic force. Okay. Now let's look at this part here. Again, I'm going to turn my paper, and so we have I cross B, and that has a force in this direction. And I'll turn the paper again, and we'll say I cross B, and that has a force in this direction. So we have these three parts of the wire, each with a force, magnetic. Okay. And so because of symmetry, we can say that these two are going to cancel. They'll sum to zero. And so what does that mean about this current? What does that mean about forces on it? Well, it means that there's going to be a force, a net force to the right on this loop of wire. And if there's nothing holding it back, it will actually move to the right or accelerate. And by the way, we have a name for something that does that. It's called a motor. If we can turn electrical energy into motion, well, that's what a motor does. And so I wouldn't call this a motor, but it certainly is electromechanical. All right, excellent. And then let's do another one. This one says torque it out. I'll bet you can guess what this is going to happen. What's going to happen here? I think we might have given it away in the name. Okay, so here it says, what if our wire is on the fixed axis? So let's take a look at this. Now, looking at this, I think when I made this, I made a mistake. I would really think that I wanted the axis here in the middle. So let's go ahead and make that change. There's an axis. All right. And what does that mean? That means that this loop is free to rotate around this axis. Okay. And so it says work it out which sides experience a force. So let's take a look at this again, right hand rule, okay? I, B, and F. All right. So here on this first one, we look at this. I is in this direction, B is all the way back there. Wait a minute. I and B are parallel. We said this yesterday. Let's look at this. Okay. Sorry, a little backwards here. Fm is equal to the integral of I dl cross B. And remember that the cross product that we're looking at here, if these can be thought to be constant, which sometimes they can, this can become I times L times B times the sine of the angle between the sine theta. That's what cross product gives us. It's sine. Now, the sine is the angle between the I and the B. So if we look at this, B is to the right, the current is to the left. This angle theta is 180 degrees, and the sine of 180 degrees is 0. So here we would say that the B field and the current are anti-parallel, which means force is 0. And same way over here, we have parallel, force is 0. All right, now let's look at this one. Here, I'm going to draw that there's a current in here because I think that kind of got left out. There's a current there. Right? Can move this guy out of the way. And there's a current over here. Okay. And what is that current? Okay, well, I'm going to tell you something that's going to make your day a little bit easier. Right? About 90% of the time, this equation devolves into something much simpler. And the thing that it devolves into is I'm going to write it down here. Fm is equal to B I L or L. Okay. So that is we can do that when B and I are perpendicular and when they are constant, which is in again about 90% of the problems we do. So here we got this, and so I can say what is the force here? Well, again, to get the direction of the force, I'm going to use the right hand rule. So I'm going to say that my again I cross B. So here's I cross B, and that shows I don't know if you see my thumbs hidden, but it's pointing into the board. So what I'm going to write here is I'm going to write a big old circle with an X, circle with an X, circle with an X, all around this side of my wire. So on this right hand side of the wire, there's a force on the wire into the page. Okay. Now I'm going to turn the page around so I can do the right hand rule much easier. And so I'm going to say I cross B, and that you can see now my thumb is pointing right at the camera or out of the page. So here I'm going to draw a force here as a dot, and we know that that circle with a dot means that the vector is pointing out of the page. In this case, it's a force vector, and so here we have Fm on this side and Fm on this side. Now, what happens when there's a force on this pointing out of the page? There's a force on this side pointing into the page, and there's an axis around which this can rotate. Well, as I said, I think we can get it away. You're going to have what's called a torque. Okay, and so if we wanted to find out what the torque was, we know that the torque is going to be the sum of F cross R in this case. Okay, once again the cross product, and so let's go ahead and see what that is. The force is D, I, and L, the length of the wire, and the length of the wire is each. Okay, and so that is our force, and it acts a radius away of W over 2, and so that's the torque on this side, and we also have the torque on this side. So the total torque is going to be D I H W, right? And you can see that this is going to rotate, and so that's a beautiful problem there. Okay, one more problem I'm going to do for you, and then we will throw it back to Kristen in Frisco. And this one I love because it shows some of the things, our favorite problems back from AP Physics C mechanics when we were learning about springs and things like that. So you can see here, it's asking us in this problem to look at this, a wire that's connected to a battery at both ends, and it's hanging by a spring. The spring constant K, suspended in a region where the magnetic field is uniform to B. What would the force depend on? Okay, now I'm going to look you through this problem. I'm going to do it with a little bit of a help shortcut in there. I wouldn't do it like this if I were teaching it during the mechanics class, but we're going to look at this one. Okay, so here we go. We've got this this wire, and we want to go ahead and figure out what is the magnetic field. So we know that when there's no current through this wire, that this is hanging like here. However, when there is a current, it moves up. Okay, so it moves up because there's a magnetic force pushing up on it. Now, if I were drawing this, I would probably draw something like this. I would draw Fs, force of the spring, and force of the spring. All right, and I would draw force of gravity, and we would see that when there's no current, these are in equilibrium. Now, when I do send a current through here, look what happens. This little thing went up a distance of 0.02 meters, and now there's another force on it, and that is the magnetic force. And so we have a smaller spring force, Fs prime. I'll call it Fs prime, and we have the same force of gravity. That doesn't change. Okay. Now, what caused it to move up? Well, what caused it to move up was this little force. So in order to figure out what the B field is, we need to figure out what that force is, and that's not too hard to do because look here. What's the difference between Fs and Fs prime? Well, the difference between those two is delta F, and that equals to K delta X. That's a formula that we've learned when we learned about ideal springs. And so in this second picture over here, we can look at not Fs prime, but just 2 times delta Fs, right? The difference, and that's going to be equal to the magnetic force. So the two changes, whatever this little change in force made that happen, that's going to give that to us. And this becomes a pretty easy problem because the force of the spring, that's 2 K delta X is equal to, again, BIL. And again, most of these problems are going to devolve to that. And so we can now solve for B. And so B is equal to 2K delta X over IL. And when we do the work for that, what we get is, I'll go ahead and put the numbers 2 times 10 newtons per meter, okay, times 0.02 meters, and I'm going to zoom in a little bit, okay, all over I, which is 100 amps, times this length. Now, when I go back to this length, like many AP problems, there's a quantity in here that we don't need, this 2 meters. I'm concerned with how much of the bar is in the magnetic field, not the total length bar. And so that's 0.5 meters, so that's going to be 0.5 meters. And we do that, what we get is 0.008, and remember the units for magnetic field are capital T, which stand for Tesla. So that is a real fun problem. I love it because it brings together both the electricity, magnetism, and the mechanics. So I think at this point, we're going to send it back to Kristen, Texas with Kristen, and she's going to take us the rest of the way.
Okay, thanks, Roger. So let's do just a couple more practice problems here to kind of put this into practice. And I like how, Roger, you said that now it becomes easy. And I think that's kind of in general the way it works in physics. Is it all seems really hard when reading it, but if you can break it down piece by piece, set it up, it becomes easy. So let's look at this one here. If I have a square, I also wanted to ask you guys, which way is an extension here? Which way would the current have to be traveling through this bar? If we determined that that magnetic force acting on it had to be upward, so that those springs contracted, which way would that current have to be? Well, if our force had to be up, our thumb has to be up, and the field is into the page, well then, first finger current is pointing to the right. The current would have to be to the right. So just another little add on there. All right, so now the next one. We've got this square loop of wire attached to a power supply at the bottom here. It's exposed to a region of magnetic field uniform that is into the page, and the lengths of the wire are X and Y on the sides. We're just going to leave it for now in variable terms. So if the mass of the bar is M and the magnetic field is B, then we want to know what would the current have to be in this wire that would cause this to stay in equilibrium, right? So this is under the effects of the gravitational field of Earth. And so if it's in equilibrium, well, the first thing that I know anytime I see that word equilibrium is no net force, right? Equilibrium, no net force. So what are the forces acting on it? Well, we know that it's suspended in its gravitational field. So I know, depending on how you're looking at this, that there's got to be some gravitational force on it pulling it down towards the Earth. Well, if it's equilibrium, then I've got to know that also there's got to be some other force balancing that out. And the only thing that this could be in this case, we don't have any other fields or forces acting. It's got to be that magnetic force. So let's use that right hand rule again, just to practice here. So if this is the positive side of the battery, then we know the current's coming out, going around clockwise here. And we kind of figured now already we can make this shortcut that the right side and the left side are going to cancel out, right? Because the current's the same, it's traveling in opposite directions, but the magnetic field is staying the same. So those forces are going to cancel out. So the only part really that I'm concerned with is this top part here that's going to have the force. If I put my fingers to the right, magnetic field in, thumb's pointing up, so there is a magnetic force pointing upwards. There it is, bouncing up that weight. So if I go ahead and write that equation, that it's in equilibrium, so the magnetic force has to equal that gravitational force, then I can say that the force on this segment of the wire that is in that magnetic field experiencing that force is the current times the length here, which is just X, times our magnetic field B. That's got to equal the mg of the bar itself. And from then it's just algebra. We can find what the current is by dividing by xb, so I equals mg over x times b. Okay, just another application. Still goes back to lots of different kinds of forces. We never forget forget the mechanics even when we're in E&M. All right, so I've got two more problems here for you. One of them is kind of a typical AP kind of problem. So maybe not typical, it's maybe a little bit extra, but it's fun to do. So we've got this wheel, and it has 4 spokes, and it's in that magnetic field beginning of the page, and we have this attached to a power supply. So again, we're just going to deal with some variables tonight. So we've got the magnetic field that is B directed into the page. The radius of the wheel is R. It's centered about the center here, and it's connected to an EMF source. Let's just call that E. The entire circuit has a resistance of R, the entire circuit. So we want to look at the following things. Let's look at the current that's passing through one of these 4 spokes. So this is it's right. Remember Ohm's law. That helps us determine the current, the voltage, and the resistance of the circuit. So if we know that Ohm's law is V equals IR, then I can find what the total current traveling through the circuit is, because I is equal to the EMF over that total resistance R. But if I want to know what it is in just one of those 4 spokes, then I'm going to divide it by 4. So that would be our total current. So the current in just one of those spokes is going to be equal to E over 4R. Okay, and again, if we apply this potential difference to here and get this current going through, we've got forces acting on these spokes. And Roger kind of went over earlier what would happen with this outside part of that wheel. If we have that circular loop in the magnetic field, if it is not flexible and can be stretched, then the force on this, on the loop part, is going to be 0. So really all we care about is those 4 spokes. So if we isolate just one of these spokes, then I can say, well, there's a current traveling through that spoke, right? If there's a current traveling kind of down through the spoke this way, then we can use that right-hand rule and say, well, if there's a current traveling down through that way, and then the magnetic field is into the page, then there's got to be a magnetic force acting down to the right. Where can we say that's acting? We can say that that force is acting about the center of that one spoke. And so if we have a force acting on an object a distance away from the pivot point, what's that going to create? Well, I always tell my kids to say it and write it at the same time. We can start at that center and we can say R cross F. There's going to be a torque acting on that one spoke. So if we just look at one spoke at a time, then the torque on one of those spokes, we know the torque is R cross F. And in this case, what is the force? It's the magnetic force. This R is not the whole radius. The R is the distance from the pivot to that force where that force is acting. And so in this case here, the torque on one of those then would be R, which is really half of R over 2. And we know the magnetic force on this whole spoke is going to be I times L, which is R cross B. But I am not given the current in the problem, right? Which is why we have to do part A to do part B most of the time. If I know the current in one of those spokes is E over 4R, well, then I can plug that in and say then that my torque on one of the spokes is equal to R over 2 times the current, which the current is the EMF divided by 4 times the resistance, still times R cross B. And so if we simplify that down, then we can say that on one of them, the torque is equal to EMF times R squared times B. Oops, this is R over 2. Sorry, guys. So this is now over 8 times R. But again, that's only one spoke. So what we have to do, we have to multiply by 4. So if we multiply this by 4 times one of those spokes, then we can simplify this down to the EMF times that radius squared times B over 4 over 8, which leaves me with 2 times the resistance. So that would be the net torque acting on that whole apparatus there. Right, lots of fun, right? And we've got one more thing that we can talk about tonight, and this is the extra hard stuff. So this is the thing that is the above and beyond, but it's still something you're going to see in college. So it's something that I always like to show with my class, and that's what if we have a wire that isn't a total loop and it's not a nice straight segment? What if we have a partial curvy part of wire? So if we look at this one, first of all, I'm going to look and say, okay, I know that the current is going up on this side, so I'm going to draw a few more current arrows on here and back down and around. So if I want to look at the force, well, I know there's no force on any parts of the wire that aren't in the magnetic field. So really we're just going to focus on that part that is in the magnetic field. And I can kind of break it up into the straight part of the wire and the bent part of the wire. The straight part of the wire, well, if I look here on the straight part of the wire, I have a current going up and a field going in. On the left side of the wire, there's going to be a force left. And if I do the same thing on the opposite side, the current's now down, but the field is still into the page. Oh, that's acting the other way. So what happens with those two forces? If it's the same length of wire, the same traveling through that wire, and same magnetic field, they're going to cancel out too. So now really the only thing that we have is this bent part. So I'm going to zoom in here a little bit. If this wire is bent, we can kind of do the same thing with the straight wire. Rather than looking at it as one piece of wire, I can break it up. And I'm going to compare 3 different little segments here. I'm going to look at one segment on the kind of left-hand curvy side here, one segment on the right-hand curvy side here, and let's look at one segment on the very top. And let's see what happens with the force. So you do your right-hand rule, and you figure out what the force would be at each of those locations. And I'm going to do it, and I'm going to draw it down while you're doing that too. Okay, so on the left part here, this little DL segment of the wire, tiny little piece, would have a current that is going up to the right. The field is into the page, so it would have a force up to the left here. And it's a small force of the whole thing. And if we look at the top, that's going to be straight direct up. And if we look at the right side, the current's going down, field of the page, it's going to be up to the right. And this may start to kind of look familiar, not necessarily with the magnetic force, but when we talked about electric fields and we talked about those different charge distributions like the arc of charge or the ring of charge. If we look at these and I say, well, even though this force is up to the right, it's made of components going to the left and going up. And this on the other side also is made of components going to the right and going up. Well, if these are on the same spot on opposite sides of the wire with the same current and same field, what's going to happen with the X components here? They're going to cancel out. And really what we're looking at all the way around is only the Y component of that magnetic force. Well, how would I get just the Y component of this one force if I know the hypotenuse here is dF? Well, really I can say the Y component is dF times the sine of theta, that opposite side. So let's go back and set up our equation again. We know that if we look at this one segment and we can say that dF is equal to the integral of I dl cross B. I'm going to go ahead and add in that I only am concerned with that X component all the way around. So I need to multiply by the sine of theta. Okay, that's a good setup for us. Now we also want to look at, well, how am I going to solve for what the dl is? How do I find what that tiny little arc length is? I'm going to go over here and let's look at this a little bit closer. So this whole thing is my 1 dl, and we can say that the radius of curvature is r of that part of the loop. Well, how do I get the small arc length? Well, the whole arc length s is equal to theta r. So if I just want a small portion of the arc length, then I can say, well, dl is equal to, well, the radius doesn't change all the way around that semicircle, so it's r, but the angle is a very small angle. So I can say that the dl is equal to r times d theta. So let's plug that in over here. So now I get df is equal to the integral of I dl is now equal to r d theta times b times the sine of theta. And now I've got nice agreement between my thetas here. I've got lots of constants that I can pull out, and really all I'm integrating is for that sine. So df equals, I pull out the I because that's constant current. The radius is constant all the way around that circle. Magnetic field is constant, and I'm left with just the integral of that sine d theta. And we want to put on those limits, right? If I look at the semicircle, well, how much of a circle do I have? It's half of a circle. You can decide whether you want to put that in radians or you want to put it in degrees. You want to call it negative 90 to positive 90, 0 to 180, negative pi over 2 to positive pi over 2. But anyway we do it, if we take that integral and we evaluate each of those terms, we should end up that f, the net force on that whole wire, is equal to 2 times I times r times b. All right, so that was fun, wasn't it? It's always nice to kind of flex those brain muscles when they haven't necessarily been a while. We're going to end today with just a little announcement here. For those of you that have friends or know people who might not be able to be accessing these awesome lessons for all the AP subjects, there is a link that you can take a quick survey to let College Board know, because they're really working to help get solutions so that everyone is able to participate and have some way to access devices. So this is a link for that if you want to fill that out for a friend if they don't have a device, or pass that information along to someone who needs it. We just want to say thank you so much for joining. Roger, do you want to say goodnight?
Yeah, again, thanks for tuning in. We love getting to work with you guys every night. And tomorrow night we have an amazing lesson plan for what happens, or how does a magnetic field get created by a current carrying wire. So I hope you can tune in for that. So from Sarasota, Florida, I'm Roger Siegel.
All right, and from Frisco, Texas, I'm Christina Gonzalez Vega. Thank you guys.
Well, hello everybody, and welcome. My name is Roger Siegel, and you are watching AP Physics C, Electricity and Magnetism on the AP YouTube channel. This is our third night, and we're coming to you live. I am talking to you from my living room in Sarasota, Florida, and my friend and co-teacher, Kristen.
Hi, I'm Kristen Gonzalez-Vega, and I teach at Reedy High School in Frisco, Texas.
Wonderful. So just welcome tonight. If this is your first night with us, welcome. We have all of our shows are recorded, so you can go back and look back and see, and so you should be able to follow, and everything we're doing is right from the AP curriculum, which is on the AP website, so we hope you can follow along with us. All right, so let me go ahead and open up our PowerPoint for tonight, and that will be here, all right? And so here we are, AP Physics C, and tonight we're going to talk about magnetic fields from current carrying wires, okay? We'll review for a second, and we'll swing back to that. The first thing, I already told you my name, Roger Siegel, and coming to you from Sarasota, Florida, and Kristen is from Reedy High School in Frisco, Texas, all right? So the first thing we do want to let you know, and this could be your first tonight, is to know about the material we're covering. So today and for the next week, we're covering material that colleges have asked all AP students to study, even if it's not going to be on the AP exam. So most of what we're doing tonight, 95% of it, you will not see on the AP exam tonight. But we have an agreement with the colleges. We want to cover this and treat it seriously. We think it's important. It's magnetism. That's what we're working on. So it's going to be what we're studying. And that way, when you do go on to college, when magnetism comes up, you won't be totally a neophyte. You'll have had some experience with it. So that's where we're going with this. All right. So first thing I want to do is review and talk about the first 2 days that we've been here. So Wednesday night, that was Unit 4.1 Wednesday night, magnetic force on a moving charge. All right. And so for that one, you remember we had a moving charge, a charge moving through some kind of magnetic field. And the force on that charge is given by Q times V cross V, which gives us a cross product gives us the right hand rule. And we found that when we have a charged particle moving through a magnetic field, there's 3 different possibilities of its path. It is either going to go in a straight line. It will not curve one way or another. It will go straight line at a constant speed. It can go in a helix, a spiral at a constant speed, or it can go in a circle at a constant speed. And since all of these motions and changes in motions, if you will, do not change the speed of the particle, the magnetic force does no work on the charged particle. Okay, and so that's what we did on Wednesday. And then on Thursday, we talked about the magnetic force on a current carrying wire. Now, a charged particle is different than a current carrying wire on some level, but if we were to drill down and be able to look at a wire with current moving through it, we would see that there were moving charges. So these are very similar, these two ideas. And so here we have another right-hand rule. The magnetic force on a current carrying wire is the integral of I dot dl cross B. And again, a cross product gives us a right-hand rule. And often, and I'm going to say 85 to 95% of the time, often this formula simplifies to F is equal to BIL, and we will see that tonight. Right? Now, so what's new? That's what we've done. After today, what we're going to talk about today is, let me back up a minute. So day 1, magnetic force on a particle. Day 2, magnetic force on a current carrying wire. Day 3 is how do we generate a magnetic field? And so today, and moving forward a little bit, it's about the magnetic field on a current carrying wire, how a magnetic field gets generated. Now, what you're most familiar with a magnetic field getting generated is a permanent magnet. And so a permanent magnet has a magnetic field around it all the time, and that's a great way to store your pens. There we go. And that's a beautiful permanent magnetic field on it. Right? But what we study in this class is the magnetic field that comes from a current carrying wire. Right? So first we're going to calculate that magnetic field. We're going to have a new right-hand rule, a third right-hand rule, if you will, for telling us the magnetic field's direction. We're going to describe the direction of the magnetic field vectors at points near this wire. Okay? And we are going to calculate the magnitude of the magnetic field at various points near the wire, calculate an unknown current, and that's one of the problems that we'll do today. And then the force of attraction or repulsion between 2 long straight current carrying wires. And finally describe the consequence of attract or repel when 2 long straight wires, long straight current carrying wires have known current directions. That's a lot to talk about, but it actually is, it looks like more on this page than it really is. I think you'll be able to follow along just fine. All right, so first of all, let's review. The previous 2 days, we looked at 2 different right-hand rules. First, we had the right-hand rule on Wednesday, and this is the right-hand rule for the forces on a charged particle moving through a magnetic field. And remember, this was our Q times V cross. Okay, sorry about that. Okay, there we go. And over here, this is what we did on Thursday, and this is our current carrying wire and the force on it. And I want you to notice how similar these two are, extremely similar. And that should make sense to you because if we have a charge that's moving, that's going to be coulombs per second moving. Okay, if we have a current, well, you know the unit for current is also coulombs per second. So these are very, very similar. And so hopefully it makes sense to you like that. All right, now we've got a new situation. Instead of asking what's the force on a particle, what's the force on a wire, we're going to ask what is the direction of a magnetic field created by a current carrying wire. So this is our picture for that, and you can see what we have is this particular right-hand rule. And so let me go ahead and switch over to my document camera, and I want to show you. I've got this printed out, but I just want to be able to do this. And so we imagine that we've got a current. The wire has a current going through it. Right? And what you learned in probably your 7th grade physical science class, what we learned in this class, is that when we have a current going through that wire, that creates a magnet. It's called electromagnetism. And an electromagnet is just a magnet caused by a moving current. And we want to know how much magnetic field is created, and we also want to know what's the direction. Now, first, let's do the direction. Third right-hand rule. We take our current carrying wire, and we act like we're with our right hand. We're going to grab the wire with our thumb in the direction of the current. And what that means is when the wire is coming at me, that current is going, that magnetic field is going to have a counterclockwise direction. And if that current is facing away from me, then that magnetic field will have a clockwise direction. All right. Now we've got some good visualizations to help you see this. We're not going to just ask you to try and imagine everything we're talking about. We've got some good simulations. So let's go ahead and take a look. Go back to the PowerPoint at the next slide. Now the right-hand rule tells us the direction of the current carrying wire, but this formula tells us the magnitude. Okay. And so you can see this formula is the magnetic field B is equal to mu naught I over 2 pi r. Okay. Now that is a formula that you will not be tested on, and for some reason that formula is not on the AP Physics C formula sheet, even though it's probably the most used formula in magnetism. But there are reasons for that, and so we'll move on. But I did want to talk about this for a minute. Let's make sure you understand everything that we have here, everything that this is. So I'll bet I'm going to just kind of go back here, and I'll bet that everybody knows what, of course, 2 pi is. R is the radius or the distance from the center of the wire. Okay, and so you probably would imagine that as well. Okay, I of course is the current, and now we have something that I don't think you've ever seen before. I think this is the first time we've seen this quantity, and this is a fundamental constant of the universe. As much as capital G is a fundamental constant of the universe, or as much as epsilon naught is a fundamental constant, the vacuum permittivity that you learned about earlier when you learned about electric fields. When now we have magnetic fields, and we have the permeability of free space, or the magnetic permeability of a substance. All right, so I have a slide for that because I think it's important. What is mu naught? So mu naught is the measurement of the resistance, or permeability is the measurement of the resistance of a material against the formation of a magnetic field. Okay, so some materials are just happy to have a magnetic field flow through them, and some materials are like, whoa, not so much magnetic field, and that's how we measure that with the permeability. Now mu naught is the permeability of free space. Okay, and so this is the number that we're going to use, and this is on a formula sheet. So if we're doing problems with this is how we would find mu naught. It would be 4 pi times 10 to the minus 7, and units are newtons per ampere square. Right? I would not lose any sleep over trying trying to understand U naught. It's not really something you have to understand at this level. However, I would be remiss as a physics teacher if I didn't tell you something very interesting, because I know all your physics teachers will want me to tell you this, and that is this. When Maxwell derived his equations, Maxwell's equations, he found that these two constants, 1 over epsilon naught times mu naught, remember what those are? That's the vacuum permittivity of free space. That's how much free space resists an electric field. That's the vacuum permeability of free space. That's how much free space resists a magnetic field. That is equal to none other than the speed of light. And so that is a beautiful piece of how amazing our universe is. And if you go forward in E&M, you will see that show up again. It is an amazing idea. All right, let's go back and talk about what we have next. So we said that visualizing magnetic fields is, we're going to draw a vector representing the magnetic field at points marked. So let's look at these points. I'm going to switch over and see what we have. And so this means that my current is going into the board. And so I'm going to put my hand and my thumb in that direction. And notice that my fingers curl. And I'm going to go ahead and use a light color here. My fingers curl in this direction, right? Now, draw a few concentric circles here. And so what we imagine is that the magnetic field everywhere concentric to this is, again, notice I hold my hand, fingers curl in a clockwise direction. So the magnetic field at this point is this much. I want to write the formula again. E is equal to mu naught I over 2 pi r. Okay. Now, what does this r mean in the denominator? Well, it means the further we go away, the more or the less our magnetic field is. So that means if I'm closer, I'm going to have a greater magnetic field. And this one, I believe, is even closer. So it'll be even longer. And this one is even closer. And so it'll be even longer. So the magnitude of the magnetic field is greater the closer I am to the current carrying wire. And it falls off as I move away. The direction is given by, since the current is into the board, my thumb goes into the board and my fingers curl in the in the clockwise direction. The next one that we have is the magnetic field. But look at what's different here. Now we've got a dot. And that dot means that field is coming out of the board. So let's see. I'm going to start with a little, the one that's closest to a little pencil. And I'm going to draw a concentric circle around there. Okay. Let me draw another concentric circle around this one. I think this guy holds both of these. And let me draw it around this one. Okay. All right. And so I'm going to use the right hand rule. My thumb points out of the paper because that's the direction of the current. And so that means that all of these magnetic fields are pointing in the counterclockwise direction. This one is the closest, so it's going to be the longest vector. These two are a little bit further away, so they will be smaller. Again, counterclockwise. And this one's the furthest, it will be the smallest. And again, remember, we're using the formula E is equal to mu naught I over 2 pi r. And so that tells us how much, not only the magnitude of the field, but also its direction. Okay. So there's one more thing I want to show you before we start doing a few more problems, and that is the Falstad 3D magnetic field circuit simulator. Now, Mr. Falstad, I've never met him, but makes some of the most amazing physics and math simulations that you'll ever see, and I never go a year without teaching without using Mr. Falstad simulator. So as soon as we get these PowerPoints into the comment section, you can click on this. I'm going to take you there now, and this is again a website, so this doesn't cost us any money. And this is a magnetostatics application. And what we have here, I'm going to just have to move something around on my screen. Sorry. So what we have here is a simulation of a wire. Okay, now you can look and see if I can aim this wire so it's facing just straight right at us. Not as easy. It doesn't respond as quickly. Let's try this very slowly. Here we go. Okay. Now you can see this wire right here, and around this wire, these circles represent the magnetic field created by the wire. And this white circle means that we've got a higher, stronger magnetic field, and then the green circle means it's weaker and further we go out, the weaker it is. So you want to imagine these concentric cylinders surrounding the field, the wire, and that's what it feels. Okay. So we are going to send it over to Frisco, and Kristen has some great problems for us to work on.
All right, thanks, Roger. That simulation is pretty neat to see. We're going to look here now at what happens if we have more than one wire or more than one magnetic field that is occupying a region of space. So if we have here 4 wires, 1, 2, 3 of them are going out of the current is coming out of the page, and the fourth one, the current is going into the page. So we want to look at what happens if we have multiple magnetic fields. So we're just going to draw some lines here, and if you've done already, it is a good idea to get out some paper and be doing these with us. So I'm going to label them as different colors so that we can tell them apart. So if I look at the first one at the top here, the current is coming out at us, right? So it's almost summertime. So I use today to get out my pool noodles. So this is my wire, right? So if this is our wire, the current is coming out towards you. We can do this grip rule, right? Current is coming out. We're going to grip that wire around. So the current's coming out. It's going to go around counterclockwise around that wire. So I'm going to draw including P. So I could draw, we'll draw a few of them just to get it. But really what I care about is going through that point P, which way is the magnetic field. So again, if it was coming out and it's going counterclockwise at point P, it is tangent to that circle at any point. So it would be to the right. Okay. So we're going to do the same thing for all 3 of them. You do them so you can get ahead of me while I'm doing it. And we want to find out what would we do with those magnetic fields at point P. So I'm going to label this one number 2. And since this time our current is going into the page, fingers are pointing inside here. And now my fingers grip around and curl around clockwise. So now we're going to draw those around clockwise. And that means at point P, that magnetic field is going down. Okay. So if we look at wire number 3 here, again, this one's going out of the page. So thumb is coming out towards me, again, counterclockwise, which means at point P, that magnetic field is going to the left. And then lastly, let's do some sparkles. We have again, the current is coming out towards us. So again, it is going around counterclockwise. So if we go around, including point P, we also have the magnetic field going down at that point. So I just kind of redraw these off to the side here. We had at point P, 1 magnetic field going to the right. We had 1 magnetic field going to the left. And we had 2 magnetic fields both pointing straight down. So if the current in here is identical, right, we know the magnetic field is equal to mu naught I over 2 pi r. So if we look at the magnitude of these two, if the current is identical in those wires, then the current is going to be the same. We know that these are all constants. Those are all the same. And if we look at the distance between each wire and point P, what's true about that? Well, it's also the same. So if all of these things are the same, then the magnitude of these 2 magnetic fields is going to be the same. One is to the right, one is to the left. What happens? They cancel out. So what we're left with is those 2 magnetic fields pointing downwards. So we get 1 large magnetic field pointing down. Okay. Now let's look at if we have 2 wires that are crossed here and look at point P. So point P is at a distance of r from this wire and at a distance of 2r from the other wire. And we have the current directions there. So the first thing I want to do is look at each one and draw the magnetic field due to each of those wires. So if we look at the first wire, and we got that current that is going down to the right. So now I'm going to point my fingers down to the right, and as I grip around, well, on the one side it's coming out of the page, and on the other side it's going to be going down into the page. So we're going to be coming out of the page everywhere over here, and that's everywhere. It could go on and on and on. So I'm going to draw lots of dots coming out of the page for that magnetic field. And if we do the same thing with the blue wire, well, the blue wire has a current going up to the right. So again, if we point our fingers up to the right, we grip around, we're going out of the page, into the page. So we've got again out of the page and all of this region here, and into the page in this region here. So let's look at point P, and then I kind of want to talk about these other parts too. So let me fill in also. We did the out of the page, we didn't do the in the page here. Okay, so if we look at point P, let's take each field on its own independently. Right. So if we look at the kind of fuchsia wire here, then it would have a magnitude P, since the equation is 2 mu naught I over 2 pi r. Then what is our values there? Well, the I is I, the R is R, so we're good there. Let's look at the blue wire. The blue wire is the same equation, same current, but the distance away from point P to the center of the wire is 2r. Okay, so if we look at the magnitude of each of those two, now we want to look and see, just like we did with fields or any other vector, we want to look and see the direction of those. So if I look at point P, they're both coming out of the page. So if we have 2 vectors in the same direction, what do we do with them? We add together. Okay, well, we want to get a common denominator here, so 2 over 2, and we end up with 3/4 times mu naught I over pi times r, and that would be for point P. So let's look at these other regions here. If we look at, let's call this region 1. If we look at region 2, then what would happen? Well, there, since you've got one of those magnetic fields coming out of the page when we're going in, we subtract them. Okay, again in region 3, both going in the same direction, we add them, and in region 4, opposite direction, so we subtract those again. So even though you're looking for the field at one point, it's always still a good idea to draw a large region of the field so you can kind of get a big picture of what's happening. And where that's kind of most important is when we have two wires and we're going to talk about the force. So that's the field. And why is that field important? Well, if I have a wire that is in, has a current going through it that's in a magnetic field, what does it experience? It experiences a negative force. So if we look at these two wires, they're going to have a force on each other. And it turns out, and I'll show you why in a second, if your currents are traveling in the same direction, those two wires attract each other. And if your currents are going in opposite directions, they're going to repel each other apart. And so if we look at one of these examples, let's look at these two wires where the current is going into the page in both of them. So do your grip rule and draw me, let's use, so I always kind of like to use one of my wires as like a reference wire and then see what happens to the other one because of that. So let's call this guy our reference wire. And so I want you to draw me some field lines, magnetic field lines going around that wire. And then we'll talk about what's going to happen then to the effect wire, right? Or the second wire. So just a second to draw those. So if we look at that wire and the current is going into the page, right? So current's into the page, we grip around, it's going around in that clockwise direction. So we've got, I'll just draw a couple of them. Really what I care about is what's happening where that other wire is. So if I look at that other wire, let's put some directions on here. At this exact point in the center of that second wire, which way is that magnetic field directed? It's directed downwards. Okay, so now I'm going to ignore the other wire. It's almost like it doesn't even exist anymore. If I now look at just the wire on the right that also has a current going in, let's bring back our right hand rule and look at what would happen to the force on that wire. Which direction would the force be on this wire on the right? Well, if the current is going into the page, remember we've got our three fingers now, right hand rule. Our fingers are pointing in the direction of the current. Our middle finger is the field and our thumb is the force. So if this wire has a current that's going into the page, then my first finger is pointing into the page. My magnetic field is down. Well, look which way my thumb is pointing. My thumb is pointing to the left. So it's going to have a magnetic force to the left. And what's I going to do? It's going to draw it in towards the other wire. And we can do the same thing on the other one too. If I look at magnetic field due to now my effect wire, it's also into the page. So it has a magnetic field going around it as well. So again, into the page, clockwise. So if we look at just this one that's going to go through here, it has a magnetic field going up. Okay. So if that magnetic field is going up, B field going up. So if that magnetic field is going up, then we can do the right hand rule again to determine which way that force is on it. So if we go current going into the page, and now our magnetic field is pointed upwards, now which way is my thumb pointing? It's pointing to the right. So it would have a force directed to the left. And if these are equal currents, right? If we know that force is I times L times B, and we know that the B is mu naught I over 2 pi R, well, if they're equal distance apart and the current is the same through them, then we can say that they're equal amounts of forces acting on each other. Okay? So let's look at them real quick if they're opposite and what we would do for that. If I have the one on the left and it has a current going into the page, again, which way is the magnetic field going to be? It's going to be going around clockwise. So at this point here, we have that magnetic field going downwards. Okay? So let's look at how that's going to affect the wire on the right. Well, the wire on the right is in a magnetic field, so it's going to experience a magnetic force. So if the current is coming now out of the page, current's coming out of the page this time, my thumb's going to point out, I'm gripping around. Oops, sorry, we use a right hand rule. So if the current's coming out at you and the magnetic field is down, so current's coming out, I'm going to put my finger out and the magnetic field is down. Well, now that force is to the right. And so those are going to repel each other. The next thing we're going to look at here then is if we have a current carrying wire and we have our electron. So let's bring our moving charge back into it from the other night. So if the current is to the left in here and we want to find what the magnetic force on the electron is. So I'll give you just a couple of minutes, let's see if you can do this one. So you're going to draw the magnetic field around that current carrying wire and then I want you to use your right hand rule. What would the force be on the electron using your right hand rule? I'm going to tell you be careful on this one. Okay, so let's look at the wire and let's use our grip rule to determine the direction of the magnetic field. So if the current is traveling to the right, my thumb goes to the right, we grip around on the top of that wire, the magnetic field's going to be going into the page. If I keep curling, my fingers are going to come out on the bottom. So we got magnetic field in everywhere here, and we got magnetic field out everywhere here. Okay, so this charge is now moving in this magnetic field. What do we say in the day you have to be really careful about? When you read the question, the first thing you check is what? What charge is your particle? This is not a positive charge, this is a negative charge. So again, whether you're using your right hand rule flipping it or using the left hand rule, I use my left hand, but so if it's an electron, we gotta use our left hand or use your right and flip the sign. So the velocity of this is to the right. If our magnetic field is then coming out at you, which way is your force? It is up, kind of like my voice just went. So that experiences that upward force due to that magnetic field. Okay, so we get lots of interactions here, which is really fun. Hey, I'm gonna do one more and then we're gonna throw back for an AP style problem for Roger. So what if we have a square loop instead of that electron? And let's find what would the force, the magnetic force be on that square loop of wire. So again, I'm gonna give you just a second to think about this one. Draw me some magnetic field vectors above and below that wire. And what do you think's gonna happen in that loop? If you need more time, you can always pause, come back. So right hand rule, again, this time current to the right, into the page, out of the page. Everywhere in this whole region, into the page, out of the page. So if we've got that now magnetic field on the top here that's into the page, every part of that loop is in that magnetic field. So let's look at though how each side of the wire is affected. So we looked at some loops of wire yesterday and how that's affected by the magnetic field. So some of it we'll kind of go through fast and some of it we'll talk a little bit more about. First, we'll look at those two outside parts of the wire. If those two outside parts of the wire have currents that are equal magnitude, right? The current's the same everywhere in that loop. If the current's the same everywhere in that loop and those lengths of the wires are the same, and we know that the force is ILB, and every part of these equal sides are in the same part of the field, what's going to happen to the force on each of these sides? Well, if we still do our right hand rule and we have our current going up and our magnetic field going in, we got a force to the left on this side and to the right on this side, and those are going to cancel out. But what's not going to cancel out is the top and bottom. We can still do the right hand rule, look at the force in which direction it is on the bottom. If we have the current going to the left and the field is into the page, we've got a downward force, and since the current's on the opposite direction on the top, that's an upward force. But why do these not cancel out? Is the magnitude of the magnetic field the same on both the points on the top and on the bottom? No, because the magnitude of the field is mu naught I over 2 pi R. Well, maybe the same current, but what is not the same? The distance away from that wire that's causing that magnetic field. So here on the top, that magnetic field is a greater distance away. It's got an R, let's just call it of R1, whereas the bottom has an R of R2, and that's a much smaller R on the bottom. So if we decrease this bottom part, we have a greater magnitude of the field on the bottom part of the wire, therefore a greater part of the magnitude of the force. So the net force on this is going to be the same direction that the bottom part of the wire experiences, which is down. Okay, hopefully that helped a little bit there doing those examples. Now let's get into one that we may see later on, not necessarily on this year's AP test, but we may normally see on the AP test. So I'm going to throw it back over to Roger to finish up today.
Okay, thanks so much, Kristen. Great job. So the last thing we want to look at comes from an old AP for response question. And as Kristen said, it won't be on this year's exam, but there is a little bit in here that you can enjoy and look at. A little bit last year's, a little bit this year's. So I'm going to switch over to the .cam. But if you do get a chance to download the PowerPoint, we're going right to this problem now. Okay, so it says this is from the 2001. Let's see. Did I share my screen? I don't think I did. Let me go ahead and do that. Sorry. All right, there we go. All right, so now we're looking at the 2001 exam, and it says the circuit shown above consists, or it's to the right, of a battery PMFE in series with a rod of length L mass M and resistance R. The rod is suspended by vertical connecting wires of length D, and the horizontal wires that connect to the battery are fixed. All these wires have negligible mass and resistance. The rod is a distance R above a conducting cable. The cable is very long and is located directly below and parallel to the rod. Earth's gravitational pull is toward the bottom of the page. Express all algebraic answer in terms of the given quantities and fundamental concepts. All right, so first of all, I do want to remind you that the 2001 exam is a public exam that's available on the AP website. So if you want to look at this and delve into it a little bit more, that's certainly something you could do. But I'm going to switch over to the doc cam so I can work through this a little bit. And so the first question says, what is the magnitude and direction of the current in the rod? And so let's look. I'm going to zoom in here. And what we can see is that the rod is right here. And so if we want the magnitude and direction of the current in the rod, remember I told you that this is a problem that could be on this year's exam? Here it is. So this is actually, if we want to know the magnitude and direction of a current in a circuit, well, I think you know where that comes from. That's Ohm's law. And Ohm's law says that the current is equal to V over R, or in this case, we don't have V, we have the electromotive force E script E over R. Be careful, the capital R is different than the small r as this distance. Okay, and so that would be the first answer. That's the magnitude of the current. The question is, what's the direction? Well, hopefully you remember from unit 3 when we studied circuits that for conventional current, the current leaves the battery from the positive end and moves toward the negative. So that would mean that the direction of the current in the rod is going to be right to left. So that is the magnitude and direction of the current in the rod. Now, in which direction must there be a current in a cable to exert an upward force on the rod? Now, Kristen just showed us, and I'll remind you, that when we have two parallel wires that are current carrying wires that are parallel, that they attract each other. These two wires are parallel and they attract each other. But we want the cable to have an upward force, which would be repulsion. And so that means that we need two wires that are in opposite directions or where the currents are anti-parallel. And so that's when we get repulsion, is when we have anti-parallel. So these are both parallel, these are attraction, this one's anti-parallel, and we have repulsion. So here we're going to say that the second answer, in which direction must there be a current in the cable? We're going to say the opposite direction, or left to right. Okay. All right. One more part to this problem and we'll be home free. Okay. So the last part says, with the proper current in the cable, the rod can be lifted up so that there is no tension in the connecting wires. So no tension in these wires here, right here, D. In other words, if there's no tension in these wires, that would mean that the force magnetic, this magnetic repulsive force, has to be equal to the other force pulling the rod down, and that of course is the force of gravity. And so I'm going to do some algebra and set these equal to each other. Force of gravity equals force magnetic. Okay. Now the force of gravity does take us back to an earlier time, but that's always going to be mg. And the force magnetic, let's work through this. What is the magnetic force of repulsion between these? Well, yesterday we learned that when a current carrying wire is moving through a magnetic field, the force on it can be Bil. So this is going to be the magnetic field created by this wire, by the cable, and it's going to create a magnetic field right here, and that field, let's see, is going to be out of the paper. Here's this magnetic field that gets created. Okay. And what is the quantity of that magnetic field? Well, that magnetic field we just learned today is mu naught I over 2 pi. And here's where my little r comes in. The distance from this wire, the magnetic field that is created by this bottom wire at the distance r of the top wire, 2 pi r. All right. And so that is going to be times I times L. Now, be careful. These two i's are not necessarily the same. This I is going to be the I in the cable. This I is the I in the rod, IR. But we know from the earlier problem that that the I in the rod is equal to script E over R over the resistance. So that's mu naught I C times E over R times L. And this mu naught I C has a 2 pi r in the bottom. So we're almost there. One last thing to do is what we want to do is in this problem solve for IC. So what we're looking for. So I'm going to finish up my algebra. IC is equal to, and so you can see what's in the denominator over here is the 2 pi r and the r, and we're going to have mg. This is mg 2 pi little r big R, and then what's left is going to be here in the bottom u naught E L sigma script E L. And so that's our solution. If we have this much current in a cable, it's going to push up on this rod, and there'll be no tension in these wires. So that is the end of our lesson for tonight. I did want to remind you that we now have 3 right-hand rules. We've got the right-hand rule for a particle. We've got the right-hand rule for a current carrying wire, and now we also have the right-hand rule for the magnetic field from a current carrying wire. Okay. All right, so we hope that again you're enjoying these videos and that you can visit the AP Physics C Electricity and Magnetism website for more information. And so, Kristen, you want to give us anything?
I just hope you guys have a nice restful weekend. Enjoy your family and tune back in on Monday.
Excellent. And I would say the same thing. I hope you guys have a wonderful weekend, and I hope everyone is healthy and well out there. And we can't wait to have you back here on Monday for more AP Physics C. Have a great night.
Everybody, this is AP Physics C Electricity and Magnetism, and we are coming live to you. Tonight we're going to be studying section 4.4, which is Ampere's law and the law of Biot. So we are going to go over the lesson with my partner Roger. My name is Kristen Gonzalez Vega, and I am coming to you from Frisco, Texas, where I teach at Reed High School. And my friend here.
Hey everybody, my name is Roger Siegel, and I'm coming to you live from Sarasota, Florida.
Okay, so I do have a quick announcement. If you've been tuning in all week, then it's the same thing, or last week, it's the same announcement. But we're going to say, at least probably tonight, we are going to be doing some review lessons later on, starting next week. This week, we're going to wrap up the magnetism and induction material to finish the content for AP Physics C&M. The reason we're doing this is that even though magnetism is not going to be tested on the exam, is that colleges have been flexible and working with College Board to give credit to students with the understanding that you guys are going to be learning the material and prepare to move on to the next level if you do receive credit in your course. So we're going to be releasing what those topics are going to be on a weekly basis, so that you can tune in and kind of plan what you want to watch and you will go over once that review is starting. So today, I want to review with you what we've been talking about last week. So last week, we went over some different units. The first thing we talked about was what happens when you have a charged particle that is moving in a magnetic field, and that charged particle is going to experience a force, and that force is equal to the charge times the velocity times the cross product of the magnetic field. And
advance your slides, Kristen?
It is, but it's stuck. So I'm going to have to probably exit out my document camera here so that it is not stuck anymore. So you guys will just hold on with me just a second. I'm going to stop this share, and I'm going to exit out of something, and then we'll go right back at it. So the second thing that we talked about while we're waiting for that is that we looked at what happens if you have a current carrying wire. And if you have a current carrying wire, that wire is going to experience a force, and that force is proportional to the current times the length of wire that's in that field times the magnetic field. So if we go back in here, now we should be unfrozen. There we go. So that force, that magnetic force on that current carrying wire is equal to I times L times B. Truly it's numerical, but when we looked at that and we integrate across the whole length of the wire, normally it simplifies down to just that ILB. And then the last thing we talked about on Friday was how we found magnetic field at a point some distance away from a long current carrying wire. So we're going to extend on that today, and we're going to see how we got that equation that B is equal to mu naught I over 2 pi r. So what we're going to look at today is we're going to look at Ampere's law, and we're going to justify what we call an Amperian loop and how that applies to some different shapes of wires and different currents going through those. We're going to look at how we get that magnetic field using Ampere's law and symmetry arguments. We're going to give an expression for it using a solenoid, and then we're going to do some different conductors, some concentric conductors, and then we're going to look at what happens if we can't use Ampere's law, and we're going to look at the law of Biot. So we're going to start out, and I just want to again kind of look at some magnetic field lines. So if we look at a magnet here that has a north and south pole, remember all magnets have a north and south pole, no matter how many times I cut this up, I'm always going to have a north and a south pole. And if we draw the magnetic field lines, if I skip some of them here, those magnetic field lines are going to go out that north pole back into that south pole. And the further we get out, the more big those, or the bigger those are going away from the north into the south pole. And we're going to compare that just a second. If I look at a loop of wire, we'll look at our right-hand rule again. And that right-hand rule says that if we have a current that's going through our wire, then it is going to have, hold on with me just a second, guys, I can see it's lagging again. I'm going to do is I'm just going to switch over. We're just going to go right from the PowerPoint so that it doesn't do that again. So we're going to go in right into my PowerPoint again. I apologize about this. Think about everybody being home as everybody's online, and sometimes that makes it hard for us to use the internet. So if you look at our segment of wire here, we've got that current traveling to the right. If we use that group rule, remember you put your thumb in the direction of the current, your finger's going to curl around to the direction of that magnetic field. So in this one, that would be coming out of the page on top of that, and it would be going into the page on the bottom. But the thing that we want to look at is, even though it's going out now, I'm going to draw it just a little bit different. So we use the annotation, that vector notation, where if we are saying that it's coming out of the page on the top, then we're drawing circles or dots. And if it's going into the page, then we can draw X's. But I can also represent this by kind of looking, what would that look like? What makes those concentric circles? So if I drew it coming out of the page and going back into the page, and my mouse is gone. Okay. Roger, can you try to take control of it? Because for a second, my mouse is not letting me.
Yeah, let me go ahead and take it from here, and then we'll get you right back to Dallas. I'm sorry, Frisco in a minute. Okay, so let's go ahead and pick up where Kristen is here. And so Kristen is showing us the field lines. And so as we can see, I'm not showing you anything because I have to go ahead and share my screen. Sorry about that. Kristen, you're going to have to stop sharing your screen.
I don't know when I can't get my computer is not letting me do that.
Okay. If you want, you could, I believe, leave the meeting and restart and then rejoin the meeting. That might give it up. Try that.
Yep, I'm just going to have to restart. So I'll join you guys in just a second.
Okay, we'll see you in a minute. Thanks for being so patient with us out there in YouTube land as we work with the technology. In just a second, we're going to get to you. In a minute, I'm going to be showing you a problem with a coaxial cable. And so while we're waiting for that to happen, okay, I'm going to try now. Okay, let's try that. Looks like I'm sharing the screen. All right, and that's my screen. Okay, great. So make sure that that's happening. Okay, good. So as Kristen was saying, we have the magnetic field lines. Remember, they come. Let's try that again. All right, and they come out from the north side and into the south pole of the magnet, and their direction is from north to south. Remember, also inside of the magnet, those field lines keep going. Those field lines are always closed loops. Now, current carrying wire. If you remember last week, we said that if you have a current carrying wire, you're going to use the grip right hand rule. That is, with your hand, you grip the wire, and you put your thumb again of your right hand in the direction of the current. So I'm looking at this current in front of me, and it's pointing to my right. And so I'm going to go ahead and point my thumb to my right, and I'm going to let my fingers curl. And when I do that, you're like me, you're going to see that out at the top here, your fingers are curling, and what we're getting is we're getting magnetic field that's coming out of the paper here, and down here, that magnetic field is going into the paper. Right? And those are our field lines. Great. All right. Now, Ampere's law. Ampere's law is a very, very useful law, and we're going to take a look at it. Now, you might look at it and notice, gosh, it looks a little bit like a law I've seen before. Okay. And that law that you're recognizing is Gauss's law. And we're going to talk about. We'll see in a minute how Gauss's law works, but this is how Ampere's law works. Okay. We've got a current. Okay. We know that magnetic fields come from currents, and so we've got this current, and the current is moving in this case straight up. And so by using Ampere's law, we can figure out the magnetic field strength at a point here, or 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 at a point here. Okay. And the way we do that is we're going to first let's talk about what this means. This circle here around the integral sign, that means we're doing a closed integral. Now, when we did Gauss's law, that was a surface integral. In this case, it's a loop. So what we're going to do is we're going to draw a loop around this wire. All right. And we're going to walk around that loop. Okay. As a matter of fact, I think I'll switch over to the dot cam, and let's take a look at how that would do. Okay. So I've got a wire that's popping. Here we go in this direction, and there's my wire. Current is in there, and I know that using the right hand rule that my wire has a magnetic field coming out of the board here and going into the board there. Now, if I want to find out the magnetic field at any point through this wire, I can use Ampere's law, and I'm going to write it out here. And it's the closed loop integral of B dot dl is equal to mu naught I, and this is I enclosed. All right. Now we're going to get into this and kind of see what's going on, see if we can figure it out. In order to do this, I'm going to imagine that we're looking from right here. All right. So we're going to be looking from right here at this wire, and so here's a wire coming out at us, and you can see that there's a current coming out of the picture. All right. And so if I'm going to use Ampere's law to find the magnetic field at that point, the strength of the magnetic field, I'm going to at least first get a general sense of what the direction is. So again, right hand rule, I put my thumb pointing out of the page, and my fingers are curling in the counterclockwise direction. So that means I know that the B field, the magnetic field due to this current I, is going to be about that. It's going to be in that direction. So now the question that we're going to get to next is, what is that value? All right. And so, how are you doing, Kristen?
I'm back.
Okay, great. All right. So I'll finish this up, and then we'll throw it back to you, and then we'll get back on track. We were okay.
That's great.
So this is now we're going to draw around this current what's called an Ampere. I'm sorry, around this wire what's called an Amperian loop, and it's the cousin of the Gaussian surface. And so if I so what am I going to do? What I'm going to do is I'm going to go all around this loop, and at every point I'm going to have a tiny little dl. It's a vector, very short, and it points in the direction that I'm going around my loop. Okay. By the way, any direction you go is fine. So every one of these is a little dl. Right? It's a vector, and at every point I'm going to take the dot product of the magnetic field, which is in that direction, and we have B dot dl. Now there's a reason that I picked a circle and not a square, is because just like with Gauss's law, I'm going to use symmetry so that I never have to integrate this. And so what I do is I'm going to go ahead and say that this is again closed surface integral of B dot dl is equal to mu naught I. And if you remember from last week, you saw in the videos, we said mu naught is the permeability, vacuum permeability, which means that is how easily a magnetic field can move through a vacuum. And so since we picked one distance that's the same all the way around, if I drew this right, this radius is always the same, r, and so that means that the B field is the same everywhere. We established that last week. And so I can pull that out of B, and then I'm going to integrate all these little dls. This is a little length. And imagine if you added up the length all the way around this circle, well, what you get is you get the circumference of the circle. And so this is B times 2 pi r is equal to mu naught I. Remember, this is I enclosed. The I enclosed by the Amperian loop, or B is equal to mu naught I over 2 pi r. And so that is one example of Ampere's law. Okay, so I'm going to throw it back to Kristen in Frisco, Texas. And Kristen, what you got for us?
Okay, well, let's go ahead and compare. Now that you just told us about Ampere's law, let's look back at, and you said it's the cousin of the Gaussian surface. So let's look at the two compared side by side, because I think there are really good parallels in this. It's something that you should remember, right? If we look on the left here at Gauss's law was equal to that surface integral of E dot dA, and that equals Q enclosed over epsilon naught. So if we look at that left side, and that we had a closed integral, and we look at Ampere's law, and what Roger just said is now we have that Amperian loop, or that Amperian path that we were integrating across. It's also closed. It's a closed loop, and that's dependent on the magnetic field. And it really, the symmetry is what's really important, because you don't pick a Gaussian surface where your electric field isn't the same everywhere. everywhere, because then you got to do some ugly calculus, and that's not something we want to do, right? So we pick a Gaussian surface where it is the same everywhere, so then that's a constant, we can pull it out of the integral. Well, we want to do the same thing when we're picking our Ampérian path around our wire or in our slab, whatever it is that has that current going through it. We want to draw our Ampérian loop or Ampérian path so that the magnetic field is the same everywhere around there. That way, again, it's going to be constant and it can be pulled out of that integral. So the only thing that we're going to be integrating, well, in Gauss, the only thing we actually had to integrate was across our whole surface area. And if you integrate across the whole surface area, what you get is the surface area of your Gaussian surface. The same thing's going to apply when we go to Ampere's law. When we're looking at Ampere's law, when we take our loop around our wire, right? We have our wire, we have our Ampérian path. Well, if we integrate all those details out, we're just getting the circumference of that circle. Or if we're doing a slab and we're looking at a rectangle, that's all you're going to get. So you're not actually going to do any calculus with this if you're doing it right. If you pick that right symmetry, same thing with Gauss's law. That flux with Gauss's law depended on how much charge is enclosed in your Gaussian surface. And with Ampere's law, what our product of our B dot dl is going to depend on is that current that's passing through that surface of that Ampérian path. Okay, so there's a lot of parallels there, but then also some differences, right? So let's look at a solenoid. If we take a solenoid and we have the current going through, so it's kind of side view of the solenoid, and we can pull up my drawing tool here and just hope my mouse doesn't get lost again. So if we look at this is kind of that side view showing the current is coming out of the page on the bottom and going back into the page on the top, right? So I can kind of draw this whole thing. And what a solenoid is I have a big, large slinky here that can be a solenoid. A solenoid is just a coil of wire that's bent into a lot of turns. It could be a few turns, or like my slinky here could have a ton of turns to it. But we can pass a current through it. I can connect a battery to either the slinky and turn my slinky into a solenoid. So a solenoid is just that coil of wire that has a current passing through it. And if there's a current passing through it, then what do we know is going to be surrounding that current wire? There's going to be a magnetic field. And if we look at kind of one isolated part of that solenoid, and I gotta find see if there's something wrong going on here today. If I look at that one part and the current is going into the page on the top and out of the page on the bottom, then we can use our right hand rule and we can determine which way the magnetic field will be going around that. Well, the same thing's going to happen for our whole entire solenoid. Is they're going to have that magnetic field that's going around back in those loops. But really, if we compare the magnetic field on the outside of that solenoid to the magnetic field on the inside, it's such a difference. The magnetic field is so small on the outside that we can essentially say there is no magnetic field on the outside of the solenoid. Only thing that we're working with is the inside. And so we can use the ramp up. And again, I'm going to draw on the screen. I apologize, so we can find where it is. And we want to know what is the magnetic field that's passing at that point P right there. So if I kind of look at that, I want to make sure that I'm going to first always draw, well, what would be a good Ampérian path that would pass through that point P and where there'd be symmetry everywhere. And so I'm going to draw my Ampérian path, a nice rectangle that's going through point P and is also making that where I go along here, anywhere along this path, that magnetic field would be fairly constant. Now the thing is, if we actually look at the solenoid, it isn't exactly constant everywhere, because as we get to the edge, what do you notice about that magnetic field? It's curving to go out and around. And so we always are going to ignore in physics those edge effects, and we're only going to look at in the center where it's fairly uniform. And so if we go to Ampere's law, and we can say then that Ampere's law is that closed integral of B dot dl, which equals mu naught I through. So what current would be going through that? And if we put that in, this is really bad, Roger. I think I'm going to have to switch it back to you because you guys aren't going to be able to see this. So we want this to be good for you. So I need to figure out what's going on with my computer.
Okay. All right. So go ahead and if you'll unshare your screen, Kristen.
Yep.
Back up. Okay, great. So let's go ahead and take a look at where we are next. First, let me bring up the PowerPoint. All right, there we go. All right. So a solenoid. Now, what we have with a solenoid, as Kristen was saying, is at least in the inside of this, in the part of the solenoid, not over here and not over here, but in the long part of the solenoid, just like when we're doing a problem, sometimes we have a very long wire. The magnetic field is constant in here. It is constant. All right. And so we want to use Ampere's law to try and figure out what is the magnetic field in a solenoid. I'm going to derive that. So I'm going to reach across here. I'm going to get some of my notes out here, and let's go ahead and throw up the dot cam so we can see that. Okay. And so let's start with our solenoid. And our solenoid, we're going to think is we've got these dots here, dot, 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 and here we got these X's. And so we're looking at a side view. Like if I took a hacksaw and I cut my solenoid in half, so that I would be able to see where the current is flowing. And so here current is flowing out of the page up here, and it's flowing into the page here. And I'm going to turn mine upside down to be consistent with the PowerPoint. There it is. All right. So there we are. And so we've got this this B field flowing in this direction. Right now, we're going to use Ampere's law to figure out what is the B field inside this solenoid. And so we're going to start with the fact that the current here is I in this. Okay. So let's say that we have we're going to draw an Amperian path. And this is not really a loop. This is an Amperian path through this. And we're going to use Ampere's law to find the strength of the B field inside this solenoid. All right. So let's see if we can do that. So remember that Ampere's law is the closed loop integral of B dot dl is equal to mu naught times the enclosed current. Okay. All right. And we're going to use this to find B. Now I'm going to go around this loop in a clockwise direction, and I'm going to start here. Now as I go from here to here, what we said a minute ago is out here B is equal to 0. So there is no field here B going in that direction. There is no field here B going in this direction, and there is no field loops from here to here B going in that direction. Okay. So my B is 0 here, here, and here. Now let's look at these next three parts. Okay. This line, and this one. Okay. Now I'm going to call this let's call this length L from here to here. All right. Now how many so let's go ahead and see what B dot dl is here, here, and here. I'll call this the point A, B, and C. So let's go ahead and see A right here. What is the using Ampere's law, what is B dot dl? Well, if you look at this, look at my B field. My B field is pointing to the left. This is my B field. I drew it over here before. I'll draw it here, I'll draw it here. There's my B field. And my B field is perpendicular to my dl. So that means that as I go along this part of my Amperian path here, I'm going to have 0. There is no B dot dl there, 0. And the same thing here, B dot dl is equal to 0. So the only place where I have a B dot dl is along this line. And so what I'm going to say is that B, which is what we're actually looking for, times the dl, but when I add that up, that's the length L, is equal to mu naught times I enclosed. Now what is I enclosed? I enclosed is going to be the number of wires that I've enclosed. In this case, this is 3. And Kristen, do I use a small n or a capital N for that one? I don't think it's. Do you remember?
The small n is the number of turns per length. Big N would be the total number of turns.
Yes. Okay. So this is big N. Thank you so much. Okay. And so to be consistent, so that is N. So I've got 3 of those. And times I. So let me write that again. Sorry, that didn't come out right. B dot L is equal to mu naught N times I, or B is equal to, zoom out a little bit here. B is equal to mu naught I N over L. Now this N over L, that is the number of turns per unit length. And so B of a solenoid is equal to mu naught I little n, which is the number of turns per unit length. Wow. And that's how we find the B field inside a solenoid. So you'll find that in every physics book that you look into. It's one of the classic derivations of what we're working on. Okay. Now, Kristen, how are you doing over there? How's the technical situation?
Well, I switched over my wireless, so I think that it is okay.
Okay, good. So I'm going to throw it back to you. And so let's get back to Frisco, Texas.
Okay. So I'm going to have you stop sharing for me, Roger. So there we go. So let's look at another application of this. So let's look at a conductor, a wire. If I have a wire that has a current that is traveling kind of out at us like this, and we have a radius of r for the whole wire, and we want to know what would be the magnitude of the magnetic field in a couple different places. So this should kind of also bring you back to fun, wonderful memories of Gauss's law, except you're finding the electric field in inside of conductors and inside of insulators. So we want to find first, let's do if it is bigger than r, right? So if we have a distance away that is bigger than the radius, let's do that one first. So if we pick a point here, and let's say I want to know at this point P, what is that magnetic field? So the first thing I need to do is identify my Ampérian path that would give me symmetry. So how could I draw an Ampérian path that would give us the same magnetic field? And that would be if I draw my Ampérian path, it's that nice closed loop around my wire. And so if we say then that the integral of B.dl equals mu naught times I through, then if we look at that, we can say, well, if I go all the way around, my B field is the same, so B comes out. If I integrate my DL all the way around, what do I get? Well, I get a circle. And so then this is going to be equal to 2 pi times r. And what you're going to notice is I'm not going to use big R, because remember, big R is a very specific value. Big R is the actual radius of the wire. I want it as a function of r any distance away from that. So this r could be just outside here. It could be 20 kilometers away, right? It is for any r around that. And so that equals mu naught times, well, if we look at that Ampérian path, what current is going through the face of that Ampérian path? All of the current is being enclosed in that loop, so that would just be the current in the wire I. And so if we want to just solve for B then B would equal mu naught I over 2 pi r. Oh, that looks familiar, doesn't it? That's what we looked at the other day. And we didn't derive it, we just gave it to you that outside a long current carrying wire, the magnetic field is mu naught I over 2 pi r. And now you can see why we can use Ampere's law to prove that. But what if instead, and I'm going to erase this original one, I want to know what the instead magnetic field is if I have a radius smaller than r. So if we are anywhere inside of that, then what would be the magnetic field at some point in there? So again, we're still looking at what that Ampérian loop is. It's still a circle. I'm still going to start integral of B.dl equals mu naught times I through. So you're always starting there and you're looking at two different things. What is my Ampérian loop and what would that DL be, or what would that total length of that loop be? And then what also is the current that is going through your Ampérian loop. So that's where we have to get a little bit tricky here, right? It's still a circle. We're still using 2 pi r. It's still little r because I want to know for any r from 0 up into r. So on that left side of Ampere's law, we're always using little r because it's a function of any radius away. And that equals mu naught. We have to look at how we're going to get the I through there. And so if we say that the current density through here is uniform, if it's the same current at every point in that wire, it's kind of like when we looked at charge density. We have what we call current density. Current density is J, and current density is equal to, that current that's going through per area. Just like we had our charge density, which was the charge per area. So if we look at here, if the whole thing has the same density as the part, then we can set what we call ratio of those. So I could say that the J of the whole thing, the whole wire, is equal to the current density of just my Ampérian loop. And so then I could say, well, the area of this whole thing is equal to pi big R squared, and the whole current is I. Make that a little bit better to see. So we can say that the total current, which is I, over that pi big R squared, is equal to my current that's just going through my Ampérian path, just that part that I want, over the area of just that, which would be pi little r squared. And so then it's rearrangement solving for what that I through is in terms of the total I. So through is going to be equal to, well, if I look at my equation, my pi's are going to cancel out. If I bring my cross multiply, then my I through is going to be equal to I times r squared over big R squared. And that's what I can plug in for the I in the equation. And so when I plug that in, then I get this is I times little r squared over big R squared. And then if we solve for B will equal mu naught times I. Well, I can look and cancel out this r with the squared, and then I have divided by 2 pi times big R squared. And one of those little r still. So that would be what it would be for anything inside here. I could plug in any r from 0 to big R. And then the next thing we need to be able to look at is, well, can we graph that relationship? And so if I graph that relationship, and it's similar to when you were graphing the relationship, the electric field is a function of the radius. So it's not like you have to memorize what these graphs look like. We literally just derived what the relationship is. So we're just looking at what that relationship would be. So if we look at from anything between 0 and big R, what kind of relationship is there between the magnetic field, B, and my radius r? Well, where's r in the equation? Is r on the top, on the bottom? Is it squared, square root? Well, r is on the top, and not only is r on the top, it's just r. So the relationship between B and r would be a direct relationship. So as that radius increases, my magnetic field is increasing proportionally. It's a linear relationship. And then anytime we get outside of r, well, now I'm looking at my bottom relationship. And now the relationship between the magnetic field and the radius is an inverse one because r is now on the bottom. So then it's going to have that inverse relationship decreasing. Okay? And as we went further and further out, it'll asymptotically reach infinity, and that would be the graph. All right, Roger, you want to do the concentric one?
Well, yeah, let's see what we can do. I'm gonna take you through this. I'll tell you what I love most about getting to teach this class is that everything that you learn pretty much in kindergarten through 11th grade in math we're gonna use. So, and there's a lot of geometry here that we're gonna get into, but that's why it's so okay. So there is. Let me see if I can do this in 5 minutes. I'm gonna go kind of fast, but I think you'll be able to follow. Okay. So there is a kind of a cable called a coaxial cable that you, I'm sure, have seen before. And the reason I know you've seen it before is because you live in the modern world. Where's my coaxial cable go? Okay. Now, all right. Can we see myself right here? Now, this is a coaxial cable. You've probably seen it as it brings cable TV into your house. It's got threaded on one end, and on the other end, I want to show you.
You gotta share with us, Roger.
I'm not sharing. Oh my God! Thank you so much for telling me. Let me try that again. Okay, there we are. Okay, thank you. Okay, so you can see that this is a coaxial cable, and coaxial means coes. They have the same, and they have the same axis. And there are actually two different conductors in this cable. There's a little one in the middle, which you probably can't see as clearly as I wish, but it is copper. And then on the outside, we have these aluminum wires, and they're separated by a little bit of plastic insulation. And this brings the internet into your house, and it brings cable TV into your house, and things like that. Now, as far as finding the magnetic field at different points in this coaxial cable, well, when we apply Ampere's law, like Kristen just did, and we come out here and we measure to the outside, well, guess what? We're going to find that we are enclosing the same values that in this problem that we did in the last problem. In other words, the first two answers here are exactly the same as what Kristen just showed us. And so that is when r is less than a. I'll put this over here, and you can rewind the video to see it if you want to. We have that b is equal to mu naught I over 2 pi r squared times little r. And similarly, when r is between the inside conductor and the outside conductor, this insulator in here, we're going to have the same answer that Kristen had on the second part. And that's going to be that e is equal to mu naught I over 2 pi r. And that's because when we draw an Amperian circle or loop around here, we only worry about what's inside the loop. And that's why we have current enclosed. Just like when we did Gauss's law, we were only concerned with the charge that was enclosed in our Gaussian surface. Now in Ampere's law, we're only really interested in the current enclosed in our Amperian loop. Now, it does get a little tougher when we go between here and here. So this is where the fun comes. So let's go ahead and imagine that we have a circle that is here and its radius is little r from there to there. Okay. Now, in a coaxial cable, the current goes in opposite directions on the inside and the outside. There's a reason for that. And the reason is what it does is since you have opposite magnetic fields forming, any fields, magnetic and electric, that tend to form inside the insulator between the two conductors and not outside the coaxial cable. And so it becomes like a shielded cable that is very resistant to electromagnetic forces from the outside. Okay. Now, So let's see if we can do this. What we got to do is we're going to apply Ampere's law to this. And so what we're going to say here, let's see my notes here, is we have B dot the closed surface integral, and come over here, B dot dl is equal to mu naught times I enclosed. Now here's the hard part and the fun part is finding the I enclosed here. All right, so that's what we're going to do. We're going to take a second on that. So I enclosed is equal to, well, first we have this current in here in the middle. So that is I, and that's going to be positive, minus the current from the outside. Well, how much do we have? Well, we have the total current on the outside times whatever fraction of the hole is enclosed, whatever fraction of the hole is enclosed in this washer. In other words, we're going to put the area of this washer divided by the area of the big hole washer conductor. And so that is pi r squared minus pi b squared over pi c squared minus pi b squared. And that is our enclosed current. And so now what we're going to do is we're going to use that over here. Come back over here. And I'm going to say that B, and now dl is, again, when I integrate dl, I'm going to have a circle. So that's 2 pi r is equal to mu naught. And now we're going to have I enclosed. So we just said that I enclosed was I minus I times, and I'm going to cancel out pi's, r squared minus b squared over c squared minus b squared. Okay. And so this is going to be B dot 2 pi r is equal to mu naught. And now what I'm going to do, I'm going to bring the I out front here. Now I'm going to get a common denominator. So this is c squared minus b squared over c squared minus b squared minus r squared minus b squared over c squared minus b squared. And so we have B times 2 pi r is equal to mu naught I. And then let's look and see what we have here. C squared minus b squared minus r squared. We're going to distribute this. This is going to be plus the b squared. So we're going to end up with c squared minus r squared over c squared minus b squared. And so B is equal to mu naught I over 2 pi r times c squared minus r squared over c squared minus b squared. All right. Now, so there is that piece. And again, fun with geometry, right? So now the last part is when r is greater than c. Now, if r is greater than c, let's check it out. We've got, here's our current coming out of the page. Here's our current coming in the page. If I go out here, the total current enclosed is 0. And so here we have B is equal to 0. And so the last piece that I'm going to do before we throw it back to Kristen, Texas, is to fill in this guy. And this shows the B versus R for our previous problem. So again, the first two parts are exactly like what Kristen did in her first two. Right here, this value here is, that's capital A, and this is mu naught I over 2 pi A. Okay. And then we get to this point and we're decreasing, but then we start adding a negative current back in. So we decrease even more, and we get here to see it's 0. And I want to show you something that AP sometimes does. They want you to draw the 0. So don't forget, we went a little short on this graph, but AP won't. So there's a 0 there. We're going to make sure we draw it. Okay. That's a pretty cool problem. All right. I'm going to throw it back to Frisco and we're going to take it on home.
Thanks, Roger. We are going to look at one more thing. I'm kind of sad. Many of you are still watching, some with all this technical stuff going on. But we did not have a chance to do Savart, which I love doing. So we may be able to pick that up again later. It is if you cannot draw an Amperian path, maybe you don't have symmetry everywhere on that Amperian path, or that magnetic field is the same. Like here, if I were to look at this wire, well, if I try to draw some Amperian path here, the magnetic field's not going to be the same everywhere because of all these little elements of the wire that have their own current going through it that are contributing to that field. So we got to treat it a little bit differently, and it's kind of like when you have an arc of charge or line of charge, and you have to break it up into little parts. And so hopefully we'll have time to come back there. I'm going to set this up because I don't want to take you too long after class, but I want to just set up a really good problem, and it'll kind of be your homework. So I want you to look at this, screenshot it. You can access it. It's from the 2018 EM exam, and it's question number 3. And I love this problem. It's 2 wires. Those 2 wires are running kind of perpendicular to each other, and one is on top of the other. So you have both the side view and the top view of those 2 wires. And if we look at the side view, you can see that there's current going to the left on the bottom, and then there's current coming out at you on the top, right? So it's kind of like this. And we want to look at this point P, which is a distance D from wire 1, and also vertically a distance D from wire 2, what would be the magnitude of that field. So we're going to kind of just set this up real quick, and then I want you to work it out, and we can, if we look at these, let's take each individual wire on its own. Let's look at due to the magnetic field B at point P. Well, if we use that right-hand rule, and we say that we have our current going to the right, and we have our grip, then we're going to be into the page, out of the page. So up at the top, we would have a magnetic field going into the page due to that wire. And if we look at the wire on the top, that current is coming out at you. So again, thumb out, grip around, we're going around counterclockwise. So I'm going to that counterclockwise around I. That means at point P, the magnetic field is going up. So we have 2 contributions to the magnetic field at point P from those 2 different wires. And if we want to look at how we would use Ampere's law to derive that magnetic field due to just wire 1, let's look at just wire 1. I already really drew my Amperian path there by drawing that magnetic field around. And so we can set that up easy because we know that the integral of B dot dl equals mu naught times I through. We're looking at just wire 1 right now. So if we say, yeah, well, due to just wire 1, that would be magnetic field that would be constant everywhere on that path. So for circle, it would be I, but what the circle is D. And then the I, if we look on the problem, I1 is just I, it was 2I. So we're talking about wire 1, that's just I. So then we could say that B is equal to mu naught, just I over 2 pi times R is Hello.
Okay.
They booted me out. Yeah. Okay. I think there's too much Paw Patrol going on upstairs is really what it is. So we'll have to shut that down for tomorrow. So if we look at, we had that mu naught I over 2 pi d. If we look at what the net field would be there, well, that would be the contribution of both of them. And we've looked at when we have a book going the same direction or opposite directions and subtracting those fields. But here, these are perpendicular to each other, right? One magnetic field is going up, one magnetic field is going into the page. And so we've got that right angle. So what do we do with 2 vectors that are right angle to each other? We make use Pythagorean theorem. So that's kind of how I want to set you up. I want you to do the rest of it. We're going to let you get back to your families and dinner, and we will come back tomorrow to do a little bit more of the magnetism with you guys. So from Frisco, Texas, I am Kristen Gonzalez Vega. Thank you so much for being patient tonight. Tomorrow will be better. Roger?
Thanks so much for tuning in, and we hope these are helpful. Welcome, everybody. Thanks for joining us. My name is Roger Siegel. I'm coming to you live from Sarasota, Florida, and you're tuned into AP Physics, Electricity, and Magnetism. And my co-teacher tonight is, as always, Kristen. Hello, Kristen.
Hello, Roger, and everybody. Like he said, my name is Kristen Gonzalez Vega, and I teach at Reed High School in Frisco, Texas.
All right. Well, let's get started with some physics. Beautiful Tuesday afternoon. Okay, so we're going to start here, and the lesson for today is electromagnetic induction, including Lenz's law and Faraday's law. And so we are actually getting into the last unit, which we'll contrast that with previous work in a minute. Again, I'm Roger Siegel, and Kristen is joining me from Frisco. And we want to let you know that the material we're covering today is not material that you're going to be tested on the AP exam this year. This is material that the colleges have told us that they want you to be exposed to, and they're aware of the situation. So we're going to give you as much as we can about this and get you a good background so that when you get to college and someone asks you about a magnet, you don't feel totally clueless and you'll be ready to learn more about that. Right? All right. So the first thing I want to do here is review what we've done. And if you have tuned in or if you haven't, what we've been covering so far is Unit 4, and that is basically 2 halves. I would say there's 2 parts here. The first part is where we're looking at what is the result, what does the magnetic field do to moving charges and to current carrying wires. And then the second part is asking the question, how do I get a magnetic field? And if I have a certain current, how much magnetic field does it produce? And so that was Unit 4. And now today we're going to start to talk about magnetic induction. Okay. Now I want to go ahead and actually get back here because I want to look at you guys. So magnetic induction is when we have is actually how electricity is created. So electricity is ubiquitous, we take it for granted. But when you flip on the switch, electricity got created somewhere, it got generated, and it got generated in a power plant. And that electricity came to your home. So how does that electricity come about? How does it get generated? So that's the phenomenon called electromagnetic induction, and that's what we're going to study today. So Kristen has a really cool display here that she's going to show you, and so I want to let her take it from you.
Okay, so let me switch over here and show you what I have. I have set up a slinky, one of those big long slinkies, and I have connected the slinky up to an ammeter. So no battery, nothing else attached to it, simply connecting the slinky right to my ammeter. And as you can see right now, there is no current going through that slinky. But if I take a magnet here, our magnet, and I place that north pole of that magnet towards my slinky, I want you to notice what's happening to the current here. I'm going to zoom in just a tiny bit so you can see that just a little bit better. So I'm going to hold down the side of the slinky just so that it doesn't get attached to it because it is a magnet and this is metal. So as I bring that magnet into that coil, you can see that it's changing. And you can maybe notice what is the sign of that current when I bring the magnet into the coil and when I take it out. And you're looking at a mirror view of it, but you can still see that it is going negative when I put that in. But then when I stop it, it is in the middle of the coil. Look, it's zero current again. And then again, when I bring that magnet back out, it became positive. When I don't move it, that current's back to zero. So we can kind of move in and out, and we can see that current flipping back positive, negative, negative, positive. Okay. Is there anything else that you want to see, Roger?
No, I think that's great, but don't put it away because we might come back to it.
Yeah.
Okay, great, thank you. All right, folks. So let's go ahead and look at this, and we're going to look at simulation. We might go back to this demo, and we want to look at this a lot of different ways. So I want to go ahead and get my screen up, share it with you guys again. So we're back here, and let me a little bit ahead where I am. I want to go back to this. Okay, so there are two concepts that we've got to get our brains around that are going to allow us to understand electromagnetic induction or generating electricity. And those two concepts are first magnetic flux and then magnetic induction. Now, flux. I hope you remember the word flux, not just from the flux capacitor in Back to the Future, but hopefully earlier in the year you studied flux, and your teacher you learned about electric flux. Okay, and so electric flux is just the electric field that is perpendicular to the surface of a solid dotted with that area. And so this is what we learned earlier in the year. The flux, and this is our phi sub E, electrostatic, is equal to the closed surface integral of E dot dA. Right now, magnetic flux is basically the same thing. First, take a look at these two. Take a look at these two equations. They're almost identical. The E and the B are of course different. Something that you can't see though that is different is this is a three-dimensional structure, a solid that is truly three-dimensional. This is the surface of a loop of wire, and so that'll make sense as we get into that. Okay, so the first concept is flux. The second one is electromagnetic induction. And so electromagnetic induction means generating electricity. You just saw Kristen do that. And so here's what we're going to say about electromagnetic induction, and we're going to do some demos of that. So a current is induced in a loop of wire if the magnetic flux through that wire loop changes. All right, so let's take a look at that. I'm going to pull up a simulation, and if you're not familiar with PHET, these are some of the best physics simulations out there. They're just really, really good. And so I'm going to open up the PHET window and show you the simulation. And this one is called Faraday's Electromagnetic Lab. See this up here? And so this shows us an animation of a magnet, and you can see that we've got a compass. But what this simulation allows me to really do is to see the magnetic field. And so I can see the field. You see, I can turn it off. Magnetic fields, of course, are invisible, but this allows me to see that magnetic field. Okay, now I'm going to go to the next simulation, and this is called a pickup coil. Okay, now notice that there's the magnetic field. Now, the first thing I want to talk about around this pickup coil is let's just talk about flux first. I'm going to try and just capture this for a second because it'll help me to draw a little bit on here for you guys. So bear with me for a second. So you can see here that we've got this magnetic field, and this magnetic field comes out of the. Oh, that's not going to be good. Let me go ahead and move this. Try this white. Let's see. That's what we want. All right. So we've got this magnetic field that is coming through this loop. Okay, and it literally is passing through that loop. Now, when we multiply the perpendicular component times the area, and we add up all that area, that's the flux. So the first concept is just getting what the flux is. The second concept is getting how is it changing. Okay, so let me shoot back to the simulation here. And so watch what happens in the simulation. If I move the magnet near the coil, if I put it in there, nothing happens. But if I shake it, I hope you can see on your videos that we're getting a light bulb lighting up. And why is that? Because I'm changing the flux. I'm changing the flux through this coil. Okay, and so that is what we're looking at. Now, a couple different ways to change the flux. One way to change the flux. Well, let's go and just review for a second what is flux. We talked about that a minute ago. So flux is the area times the V field. All right. So let's go ahead and see this. We've got our area here. Get this back here. Here's our area, and here's our V field. Now, how do we change that? Well, one way to change the flux is to move the magnet. That's called an electromechanical change. Or we can move the coil because that also changes the flux that's going through my loop. Or instead of doing that, I could make the coil bigger. Now, you might not see this. I don't know how fast the refresh rate is on your computer through this recording, but I really want you to get to this simulation and give it a try. The PHET website. Watch what happens. You can see when I change the area of the loop, I'm also changing the flux. And I don't know if you can see it, but we are getting a little bit of light up here when we do that. So it's kind of simulating for us that we're creating light. Now, most generators actually have this kind of structure where we have a magnet that is spinning near a coil or inside a coil, and that is changing the flux, and that's what's causing our electric generation. All right. So let's go ahead and go back to our PowerPoint. Let's see what we have. So here is flux, and I want to talk about electromagnetic induction. What changes the flux? Okay. Well, the flux is B dot dA. So if either B changes or A changes, then the flux changes. And by the way, also the angle could change. Now, traditionally, most AP Physics C E&M questions have to do with either the B field changing or the area changing, and we're going to look at both of those. Okay. So is there a change in the magnetic field? That would change the flux. Is there a change in the area? Is there a change in theta? And that is a mistake. So we'll cross that out. All right. All right. Now let's take a look. The second thing I want to get to is Lenz's law, and Lenz's law is going to tell me the direction of the induced current. So remember, if the B or the A changes, I'm going to create a current in a loop. What is the direction of the current? Now, I'm going to read to you what it says on here, knowing full well that this is one of the most convoluted sentences in all of introductory physics. But we're going to play with it. You're going to see it does make sense after a while. All right. So Lenz's law says an induced EMF produces a current whose magnetic field always opposes the change in magnetic flux which caused it. That's a lot, right? It refers back to the future. Oh my goodness. So let's see if we can get a handle on what this looks like. Okay, and what this is. So I'm going to show you. I'm going to bring up my doc cam here, and I'm going to show you this slide. It says Lenz's law in action. I'm going to zoom in a little bit because you want to really see this. So let's zoom in. Lenz's law in action. What is the direction of the induced current in the circular loop due to the current shown? All right, now let's look at this. We have here on the top left, we have a current that is flowing to the right, and that current is increasing. Now, I know from my right hand rule, and we call it the grip rule, that if I have a current and it's moving to the right, I'm going to grip that wire with my hand or pretend that I'm gripping it, and my thumb is going to indicate the direction of the current. My fingers are going to indicate the direction of the magnetic field. So let's take a look at that. So hopefully you can see the magnetic field is coming out of the page on this side of this wire, and it is going into the page on the downside of the wire. Okay, so now we've got a current that is coming, going into the page, all right, because of the direction here. Get a little bit closer if I can. All right, now, what does that mean? Well, that means that there's a current, a B field coming through this wire. Of course, it gets smaller as you go further away, but it's going through this loop, and it's increasing. So my B field is coming, going into the loop, and I'm also going to say that B dot is into the page. That is, the change is into the page. As this current increases, this magnetic field into the page increases as well. And so as this magnetic field increases, B dot is into the board. That means B induced is out of the board, out of the page. That means that there's going to be an induced EMF going this way, opposite of these guys. And that induced EMF, I'll go ahead and draw here, dot circle, that's coming out of the board. That's my induced EMF, that's my induced B field. And I know that if I have a B field that is coming out of the loop, that B field, I'm going to pretend again the grip rule. I'm going to grab this loop on the left-hand side, and my thumb indicates the direction of the current. And so the current in this loop is going to be going clockwise, counterclockwise. Let's look at this one. The current is decreasing. I'm going to use the grip rule, and that means that the B field is coming out of the page here and going into the page here. Now, in here, I have a B field that is out of the page, but the B dot, the change in B, is into the page. It's the opposite of that because the field is coming out of the page, but it's getting smaller. So if B dot is into the page, Lenz's law says that B induced has to be out of the page. Okay? And so we've got this out of the page current that's getting smaller. It's going to create it out of the page. Out of the page field that's getting smaller. It's going to create it out of the page field. I'm doing the grip rule. And so again, we're going to get a counterclockwise current according to Lenz's law. Okay, two more real quick, and then we're going to throw it back to Kristen. All right, on this one, we've got an increasing current, and I'm going to use the grip rule. The grip rule tells me that my B field is coming out of the page here and going into the page here, and which means that we have this. And so B is out of the page. B dot, the change in B, we know that that's increasing. So it's B dot is out of the page, which means that B induced is into the page. And so we're going to get an induced current, an induced field, that is this way. And then you ask yourself, what current produces that field into the board? I'm going to use the grip rule. And I put my hands into the ring and I grip, and that shows me that I'm going to get a clockwise current. And so the last one here we have is we've got the current is increasing. Grip rule tells me that this is coming out of the paper here, and this is going into the paper here. Make sure that you can see why this is with your grip rule. And we know that since I is increasing, we've got a B field that is out of the paper, and the B dot is into the paper, and B dot is getting bigger into the paper, which means that B induced is going to be out of the paper. And so we will have this induced B field coming this way. And you ask yourself, what current would cause a B field in that direction? And again, that is the counterclockwise. I'll let the grip rule. Okay. Kristen, are you available yet?
Yes.
Okay, didn't see you, so I wanted to make sure you were still around. I'm going to throw it over to Frisco, Texas, and Kristen's going to get us through a few practice problems, getting us ready to understand how the induction rule works and how Lenz's law works. So take it away, Kristen.
All right, thank you, Roger. Yeah, so we are going to go back over and practice that with some practical things. And I want to review an equation that's kind of important to be able to reference back to, and that was how did we determine the magnetic field around a long current carrying wire? So we used Ampere's law, and Ampere's law gave us yesterday that B is equal to mu naught I over 2 pi r. So that's kind of how we can see how is that magnetic field changing. So like Roger was saying, if we are increasing the current, that is how we know that we're going to increase the field, right? I could also move my wire. So if we look at a region where I have a magnetic field and I have a loop, I can move my wire closer or further away from that, and that's going to change that R value. And as we decrease R, that's also going to increase the field. So we're kind of referencing back to that equation on how we know what's happening to that magnetic field. All right, so if we look at this example here, I have a spatially uniform magnetic field B. It is perpendicular to the plane of the page and exists in a circular region of radius r, 0.75 meters. So that is the whole entire magnetic field is at 0.75 meters. The loop of wire itself is a single loop, and it has a radius of 0.5 meters. It is in the center of that magnetic field, and the magnetic field is increasing into the page at a rate of 60 teslas per second. And we want to determine the induced EMF in that loop. So if we look back at our equation, we know that the induced EMF is equal to, truly we can say that it's n times the change in flux over change in time. And there's a negative sign in there, and what that's going to help us tell the direction. So the n is the number of loops. So if we only have one loop, it's one, and we don't have to worry about it. The only time you really want to make sure you're still looking at that is that if you have multiple loops. So if I had looking at my solenoid, right, that has multiple loops to it, but we have one loop here. And so then we also know that, well, I'm not given what the change in flux is, but I can relate that the change in flux is equal to, so I can plug in how we get the flux. So we can say that the induced EMF is equal to the change in flux over change in time, and we know that our flux is going to be B dot A. And so if we plug in and we say that this is changing at a rate of 60 teslas per second, and it's changing into the page at a rate of that 60 teslas per second, then I can also plug in so that is what our change in our magnetic field per time is. So that is what our dB over dt is. So the other thing I need to plug in then is the A, and that would be that cross-sectional wire area. Only the wire, not the whole magnetic field. It's the area of that loop that is in the magnetic field. So then we can say that the induced EMF is equal to that 60 teslas per second times the area. How do we get the area of the loop? We say that's pi r squared. So pi times our r of our loop, which is 0.5 squared. And if we solve that out, we get 47.1 volts. And if we want to say, well, what is the direction of that induced current? I'll give you just a second again to look at that. Hopefully you have some paper out and you're doing this with us this evening. So I now want to know what the direction of that be. So we want to look at which way do we have a changing magnetic field? Do we have a changing flux in order, and which way is it? So if my field is changing and it's changing into the page, right, and my magnetic field is already into the page, so what that tells me is I have a positive change in flux. So what I like to think and tell my students is that we always are going to induce a field that's opposing the change, right? So if I have an increasing change in flux, then I want to create a magnetic field that's going to oppose that change. So I need to create a magnetic field or induce a magnetic field that's coming out of the page, that's opposing that change. So if my B field is increasing, I need to create a magnetic field that's going to decrease that change. So the way that I remember how to do this is if you are going to have your loop of wire, then I point my thumb in the direction of which way that changing field should be. So if I want a magnetic field coming out of the page, my thumb points out, and my fingers are going to curl around the direction of that induced current. So if we put our fingers out at us, we're curling around counterclockwise. Okay? All right, moving on, let's do another one. Let's look at our moving bars. This is always kind of a popular problem in electricity and magnetism type problems. So we have a conducting bar here, and that bar is sliding down without friction. That is connected to two vertical conducting rails separated by a distance L, and joined at the top by a resistor of unknown resistance R. The bar maintains electrical contact with the rails at all time, and there's a uniform magnetic field B directed into the page as shown. The bar is observed to fall at constant terminal speed V naught. So what we want to determine is what is the magnitude of the induced current in the bar as it falls with constant speed in terms of BLG V naught and M. Yeah, we got one of those in terms of things, right? So we're going to be careful. So if we want to know what the induced current I is, well, the first thing I want to look at is what are some equations we can use, right? So thinking back to what we've learned today, some of them we have learned is that our flux is equal to the integral B dA. We know that our EMF is the change in flux over change in time. Okay? So if we also can look at this, I also know, use some different colors here, that what's really important here is that it's constant terminal velocity. So if this is constant velocity, what should be about the forces acting on the bar? They should be balanced out. So if this is sliding down, right, we know that we have mg acting down. But if it's sliding down at constant speed, I also know that I have a magnetic force that must be upward. And so if those are going to be equal, then we can set them equal and say, well, the magnetic force has to equal mg, where the mass is big M. We always want to be careful that we're using those variables correctly because little M is not the same as big M. And we also know that the magnetic force we learned on that segment of wire is ILB, where I is the current going through it, L is the length of the bar, which is L, and B is the magnitude of the magnetic field. And so if I want to know what current is, I is going to be equal to mg over L times B. Okay? Another thing I kind of want to look at while we're looking at this is what exactly is happening with the bar. There's another equation that we can use for the induced EMF of a sliding bar that's pretty common and is a good one to know. And if we look at this bar, and I zoom way in on this bar, well, if there is current traveling through that bar, we know we have charges within that bar. There's positive charges and there's negative charges in that bar. And we can say that if we have positive and negative charges in there, and those charges are moving, right? Maybe they're evenly spaced out throughout. If I just look at one of each of those, these charges are moving. Each one of these, because the bar is moving down, has a velocity down. That is moving at the same rate, right? So if these charges are moving and they exist in a region where there is a magnetic field, what do moving charges experience? They experience a force. So if we use our right-hand rule and look at which way those individual charges are being forced in that bar, let's take the positive charge first. The positive charge is moving down, and I kind of like to tilt mine. But so if the velocity of those positive charges is down and the magnetic field is into the board, well then those charges are going to experience a force this way. And we know that we could do either the left-hand rule or we do the right-hand rule and swap it. Those negative charges are going to experience a force to the left. And so we're going to get the separation of charge within that bar. All those positive charges are going to be forced towards that right side. All those negative charges are going to be forced to the left. And what happens when we get a separation of charge within a material, a conductor? Oh, we're going to get an electric field. So within that bar, we're going to have an electric field. Which way do electric field points? Away from positive towards negative. And so these charges are going to keep moving or separating in that rod until we get the electrostatic force on those balanced out by the magnetic force. Oops, Fm. And how do we get what that electrostatic force is? Well, the electric force on them is Q times E. And we also know that the magnetic force on a moving charge is Q V B. E is the velocity. Well, our charges cancel out, and we can say the electric field that will be formed between those two is going to be equal to the velocity of the bar times the magnitude of that magnetic field. So sometimes that might be useful information, but maybe not. Maybe I want to know about potential difference that's going to be induced because of that separation of charge. So what is the potential difference in the bar there? Well, we can relate to that to field because we know that the electric field is equal to the potential difference divided by the distance. So I can put in that E is equal to the potential difference, capital V, divided by the distance. And what's that separation distance going to be? It's going to be L, the length of that rod. And so that will equal VB. And so if I rearrange for what that voltage is, let's call that induced EMF, it's going to be equal to E times L times V. And this is an equation that we use a lot with induction with these moving bars or moving wires that we can reference back to. And so I'm going to even do a little bit more of an extension on here. Let's find what the induced EMF is, and let's find what the unknown resistance in the resistor is. So we can say that that EMF is B times L times V because we know all those things. Those are all given to us. That we can also use Ohm's law because we know that induced EMF is equal to IR. I know what my I is. It's mg over LB. And so I know what my EMF is. So I can say, well, B times L times velocity is equal to my current, which is mg over LB times R. And so I can find what that resistance is. So resistance will be equal to, if I multiply out, I get B squared, L squared times the velocity divided by mg. So lots of things that we can do with these moving bar problems. They're super cool. Let's also find what the direction of the current must be in that bar. So if we want to find what the direction of the current is in this bar, then we can look at, well, if we are changing that, how can we find what that direction is? Well, if I look at these charges and I want to know if this is moving down here and those charges are being forced through, which way would that current have to be? So if it's maintaining that constant velocity and I know that that force has to be upwards, then we can say that if the force is up on that moving bar, then the current has to be going around through it this way. Okay, and then we've got one more here, two more, sorry. So let's look at our rectangular loop. And so the rectangular loop of wire here has dimensions W and H. It's approaching a region where there's a magnetic field, again, into the page. And the magnetic field extends from W here to 3W. So it has a width of 2W. So that loop can go all the way into that field and it can be all the way out. So we want to look at if the interval after the right-hand side has entered the loop, but before it is totally into the field. So if we sketch that out, then we know that that leading edge is inside it only. What would happen if we have all of it inside, right? We can look at that too. But we only want to look now if part of that wire is in that field, then what's going to happen? So if we say that we want to know what the induced EMF is, well, we know that induced EMF is going to be equal to that same thing that we used last time. I can go back and say that it's BLV. So our magnitude of the field is V, our velocity is V, and the length of that is going to be affected is H. So we can say this is B times H times V. And in which direction will that be induced? Well, as this is approaching that field, then it is going to have an increasing flux. So we want to create a magnetic field that is going to oppose that change or is going to be into the page. So, or coming out of the page, sorry. So if it's coming out of the page at us, right? If I point my thumb, I want that magnetic field due to that induced current to be out of the page, then my fingers are going to curl around that loop counterclockwise. So the current is going to be induced upwards through that part of the loop. And lastly here, if we look at our loop of wire that has a magnetic field into the page, sometimes we're given some things that are changing, right? So we know that it's not always nice constant things, that we have things that are changing. So the induced EMF in the loop is given by the equation that the EMF is equal to B times A times T to the 1/2, where B is a constant, right? And A is that area of the wire. So we want to look at what could be the time varying magnetic field. So we want to solve for the magnetic field and what it could be due to this changing magnetic field or the changing EMF. So if we go back and we know again that our EMF is our change in flux over our change in time, and we also know that our EMF here is equal to our B times A to the 1/2. Well, I still need to plug in then how we find that change in flux. So really I can say that this is d over dt times B times A dot A, but it's perpendicular, so we don't have to worry about that angle, equals BA to the 1/2. So if I want to solve for B, I need to integrate both sides. And if we integrate the right side, we're left with that BA. And if we integrate the right side here, they said that B is a constant. Oops, I'm missing a T here. Sorry about that. So if we integrate that, I was like, we have all constants. So we have B and A, which are constants. So if we pull those out, really the only thing we're integrating is that T to the 1/2. And so what we're going to get here is we're going to get T. If I add 1 to my 1/2, I get T to the 3/2 divided by 3/2 or times 2/3, still times my BA. Okay, so if we look here, we got an A on both sides. So those A are going to cancel out. And we get that B could be 2/3 times B T to the 3/2, which if we look here is twice E. Okay, so we're going to turn it back over to Roger, and he's going to work one more really fun problem with us.
Okay, well, thanks so much, Kristen. I am excited about this problem. She's right. This is a fun problem for me. So this is one of my favorite ones. And it just it shows so much what's so great about AP Physics C. I can go on, but I'm running out of time. Okay, so let's look at this. This is actually the second part of the problem from the 2018 exam. And I actually ended up grading this exam in 2018 in Kansas City, this question. But anyway, so you can see that we've got a wire, and the current in that wire is decreasing linearly as a function of time. And so that's our current, 2I times quantity 1 minus, you probably can't see this, can you? I'm sorry. Shoot that up here to you guys. Okay, sorry about that. All right, so as I was saying, this is just is one of my favorite problems. So we have this current here, and the current current is going down. This I2 is some constant I times 1 minus KT, where K is a positive constant. So if you want to imagine what the current looks like in that wire, it looks like this. Here's I naught right there, and it decreases linearly like that. So the current is going down. All right, well, we know the current is at first moving to the left. And so I'm going to use the grip rule. I'm going to put my thumb to the left, and it shows that up here that the B field is into the board, and on this side the B field is out of the board. And I'll just put these here. But really what I'm interested in is what's happening here. And so I'm going to make these smaller. Now, you can probably imagine why I'm making them smaller is because, as you may remember from yesterday, the magnetic field here, B, is mu naught I over 2 pi r. And so what that means is, as I move further away from this wire, the magnetic field gets smaller and smaller. All right, now the first question says, what is the direction of the induced current in the loop? So let's look at this. We can see that the current in this loop, the B field, is coming out of the board. Wait a minute. I'm sorry, the B field is going into the board. Thank you. And it is decreasing. We said over here that the current is decreasing, so that means the B field is decreasing. So I've got a B field that is into the board, but its change, B prime, is the opposite because it is into the board but decreasing, so the change is out of the board, which means that the induced current has to be, the induced magnetic field has to be into the board, which gives me a clockwise. So I'm going to put clockwise current here. Okay. So again, we've got a B field that is into the board and decreasing, and so what we will induce is we'll induce a magnetic field into the loop, which gives me a clockwise. Now let's do the flux and see if we can get out of here to decent out. All right. Now the flux is, remember, the flux is how much B field is inside of this loop, and remember that flux is phi magnetic is the closed integral over a surface, not a solid, but a surface of B dot dA. All right. Now I love this problem because you see what happens here. This B is mu naught I over 2 pi r, where r is the distance from here. Let me go ahead and do this in a different color. Let's go ahead and get that distance, and that r is that distance from here to here. And so we have the B field is mu naught I over 2 pi r. Now the area, the dA, is kind of cool. Check this out. As I go from here to here, the B field goes down, and so I got to multiply the B field at every point along here because it's not constant. And so what I'm going to do is my dA is going to be this length here, L, times this tiny little width dr. So I'm going to write that as mu naught I over 2 pi r times L dr. And where am I integrating from? I'm integrating from this distance d to d plus w. So that's going to be d, and d plus w is what we have there. Okay. Now you may recognize this. I'm going to write it again. Sorry, because you can't see anything now. So we're going from d to d plus w, and we have again b mu naught I over 2 pi r. That's the b. The area is going to be L times dr, and that'll give us the flux. All right. Now notice we know that I changes as a function of time, but we are integrating as a function of r. We're integrating in space. So that I could come out front with the mu naught. So that's going to be mu naught I L over 2 pi r times the 2 pi times the integral of dr over r from d to d plus w. And so I'm sure a lot of you remember that the integral of 1 over r dr is the natural logarithm of r. And so what we get is mu m is equal to mu naught I is what we said it was before. And so that's going to be I naught times 1 minus kt. Okay, mu naught I, which is I naught over 1 minus kt, times L over 2 pi. And then finally, what I have is, remember, I have a logarithm here. And so I'm going to say that that's ln of d plus w over d. And so this now is our flux. Okay, and let me check that against what I had before. It looks right. Okay, now we've just found the flux. And I want to again pull us back to that. What did we find? We found the amount of B field through this area. Okay, now the last part is how much, if the resistance in the loop wire is R, how much induced current. So I know that I is equal to V over R, or that's 1 over R times the EMF. Now that can be written as 1 over R times d dt of V sub n. The time rate of change of the magnetic flux gives me the voltage or the EMF. So I'm going to write that one more time, 1 over R, and then I'm going to write d dt, and I'm going to rewrite everything that I wrote up here for the flux. Okay, and so I'm going to take the d dt of this flux, which is, and I'm going to write, let's see, we have mu naught I naught L over 2 pi ln of d plus w over d times 1 minus kt. Now that is the flux that we just found. All right, I just rewrote it. And so at this point, what we want to do is we want to take the derivative of that. Okay, and so I'm going to go ahead and I'm going to write this up here. I'm going to say 1 over R, the derivative of this. Now let's look at all these terms. So we're taking the derivative with respect to t. There's no t here. There's no t here. Okay? There is no, sorry, I forgot. There's a 2 here. I wanted to go back. I'm thinking I lost something. Is there a 2 there? 2 I naught. Yes. So sorry. Okay, there's a 2 there. I knew there was something that I lost. Okay, that makes me feel better. Now, so we have 1 over R. But let's look at this. What terms have a t in? This is the only term that has a t in there. I'm going to say 1 over R times mu naught I naught L over pi. The 2's are going to cancel. These two 2's. We have the natural log of d plus w over d times the time derivative of this term, which is just going to be negative k. Now, the negative just tells me the direction of my current. And so that is where I end up. And we'll usually find the direction using, well, we already found the direction using Lenz's law. Okay. Now, I know that was a long one, and I really appreciate you, being patient with me as I go through that. Now let's zoom out, and before we leave, I just want to say one more thing about this problem. Why do I love this problem? I love this problem so much because it shows the power that you students have to use calculus so powerfully, so freely. Because check it out. First, you're integrating with respect to space, and then you're differentiating with respect to time. All the same problem. That is some super advanced calculus, and I want you to be proud of yourself for following that. All right. So we have really gone the gamut today. We've gone through the whole thing. Let me go ahead and take us out of here. Debrief. So this is what we tried to do today to help you understand magnetic flux and magnetic induction. And maybe next time you turn on the light switch, you'll go ahead. So induction just happened. So we want to thank you so much for the hard work you're doing, following along, and we hope these are helpful. So keep tuning in, keep up the great work. So from Sarasota, Florida, and Kristen
from Frisco, Texas, and Roger, I just want to make one correction really quick because no, it was me. I made a mistake real quick. Can I drive real fast?
Go ahead and get out of here. Sure. Okay, give it a try.
This is when we know it's live TV, guys, right? This happens in class. I said the wrong thing for the direction of the current of the bar. I don't know what I was thinking. It should be to the right. And let's see why. As this is moving here, this is what our loop is. And so as this is moving, let's say the bar is down here, my area is bigger. So that flux is increased. That area is increasing in that equation that the flux is b dot a. So if that area is increasing and my flux is increasing, I'm going to induce a current that's going to decrease that field or be into the page. The only way I'm going to get field into the page is if I'm going around clockwise. Out of the page is if I'm going around counterclockwise. See, I almost did it again. So it really should be to the right. And I apologize for that, but it's to the right.
All right, Kristen. Well, I can honestly say I don't think I've taught a day without making mistakes. So that's the way it happens. Anyway, thank you so much for tuning in. Again, we hope these are helpful, and we'll see you tomorrow night.
Good night with AP Physics C, Electricity and Magnetism. And my name is Kristen Gonzalez Vega, and I am coming from Frisco, Texas. And I have my teacher partner and now friend, Roger.
Hi, Kristen. This is Roger Siegel, and I'm coming to you live from Sarasota, Florida.
Okay, and today we're going to be talking about capacitors and circuits. So today is going to be a little bit of a review. So we've been talking about magnetism and finishing out the content for the year, because colleges really are expecting that you know the rest of of material, even if you're not going to be tested on some of these topics we're talking about this week. But today is an exception. Today is a tested topic, and we like to put it in here because we're going to be getting into inductors next class tomorrow, and it's good to be able to kind of remember what happens with capacitors and circuits to be able to compare inductors tomorrow with circuits. So today is a review, and today is a tested topic. So if you want, you should probably have some paper handy so that you can kind of follow along with us tonight. We're going to be working through a lot of problems and doing some fun circuits. So again, my name is Kristen Gonzalez-Vega, and I am working tonight with Mr. Roger Siegel, and we are going to go through our objectives. After tonight, you should be able to calculate the equivalence capacitance for a set of capacitors, both in series or parallel or a combination of both. You're going to calculate the potential difference across an arrangement that involves capacitors and sometimes resistors. In addition to that, we'll also talk about the current going through resistors that are with capacitors and circuits. And we're also going to calculate the energy that is stored on a capacitor in a circuit. So those are the things we're going to be able to do. Hopefully those things sound familiar to you. And the first thing I want to go over is just review what a capacitor is. So a capacitor is a way that we can store energy. It stores energy in the form of an electric field. And how it does that is made of two capacitors. So they are separated, sometimes by nothing in between them, sometimes we insert material in between them called a dielectric. And I'm going to switch over here. I have a little simulation so we can see that in action. And it's a FET simulation. And on this FET simulation, we have a battery. And we also have these two parallel plates. So these are capacitors. So you can see this capacitor is two parallel plates. And we connect that to the battery and we close that circuit up. You can see a buildup of charge on each plate. So from that positive side of the battery, we have positive charge building up on that top plate. And we have negative charge building up on the bottom plate. And anytime we have that separation of charge, we go back to what forms in between there, an electric field. And in that electric field, that is how a capacitor stores energy. And so once this is fully charged, what I can do is I also have a light bulb here. And let's also look at real quick here. When this is fully charged, what will the potential difference across that capacitor be? And if we connect it up, we can see that it's 1.5 volts. Negative just because I have those terminals flipped. But it is the same potential difference that the battery has. Okay, so let's now then flip the switch over to the other side. So now we have a light bulb. And when we flip that switch over, now you can see that charge dissipating back up through the circuit, creating a current in that light bulb. And what these capacitors are really good for is they can dissipate that charge, that energy back to the light bulb a lot quicker than that battery can. And so these are good uses for flashes and disposable cameras and other flashes and things that need that energy in a quick little burst. So that's kind of a fun simulation to play around with. And let's go back and look at some more on the power. So if I have this circuit here that involves a EMF of E, a resistor that has a resistance of R, it has another resistor that's in parallel with a capacitor. And I have a switch that kind of can flip either way here. So if in the beginning here, I flip that switch over to A, let's look what would happen. We're going to flip the switch, is going to close the side of the circuit. We're going to get that current going out through the circuit. And so what we do is we can use our loop rule, and let's write an equation that would take us around that loop, relating the potential differences and the currents going through there. So if we use Kirchhoff's loop rule says that any potential difference gains in our circuits have to equal the potential difference that we lose within that circle. If it drops across each element. So we're going to go across the battery, that's a gain. So I would say, well, the EMF of that battery, I could say minus the voltage drop across this resistor. Hold on, let me connect back up here.
Did you get kicked off of your application, Krista? Oh, there you go.
Yeah, but I'm getting right back in. Okay. There, you can see it, right? Okay, so we've got the EMF of the battery minus the potential difference across that resistor. How can we get that potential difference? It's equal to the current through that resistor times that resistance. And then we also have the capacitor, and we can get the voltage drop across the capacitor because that V is equal to Q over C. And then we get back, and we should come back to zero there. And so if we then can rearrange this, and we think about it at time zero, what would be the charge when we first close the switch? What would be the charge that is built up on the capacitor? When we first close the switch, there is no charge on that capacitor. So this becomes zero. And so really we can say at time equals zero, when there's no charge on that capacitor, the EMF of the battery is equal to IR. And so we have that maximum amount of current going through that resistor. So when we first close that switch, that light bulb is going to be really, really bright. And so how does that capacitor act? Well, that capacitor really is kind of behaving like a wire. It's almost like it's not even there because there's no charge on it. And so we have that maximum current going through that light bulb. But as that charge starts to build up on our capacitor, well then what's going to happen to that current going through the resistor? If we look back at our loop rule, if that charge is now increasing, well that means that current going through my resistor has to be decreasing. So that light bulb is going to get dimmer and dimmer and dimmer until it finally shuts off when there is zero current going through that resistor. And we're going to derive these relationships and write the differentials another day. Today we're really just going to look at those steady state behaviors. So kind of like right when we flip that switch, what can happen in our circuit? And then after a very long time, when that capacitor is fully charged, again, kind of what's happening in that circuit. And we'll get to that in between a little bit later. So after a long time and that charge is building up and that capacitor is fully charged, there's no current going through the resistor. And so that means that we have kind of like an open switch. So we can kind of characterize the behaviors that when at time zero, a capacitor always behaves like a wire. And this is something you kind of want to memorize or just commit to your head there. Like at time zero, when we close the switch, that capacitor is like a wire. And how would that then behave in the rest of the circuit behave if that were a wire? And after a long time, we treat it like it's a break in the wire or it's an open switch. And again, look at the rest of that circuit. If that were an open switch, how will the rest of that circuit behave? So now let's look at what happens now we have that capacitor fully charged. And we have that capacitor fully charged, kind of like in that simulation. If I flip the switch over here to B, well then that charge is going to dissipate back out through the circuit and there'll be a current now through the resistor. That energy is going out through there. And so again, if we look at that loop rule, well, the potential difference across the capacitor, which is equal to Q over C, is going to turn into the voltage drop across the resistor. So we can look at some of those relationships as well. So we can kind of power that light bulb by discharging that capacitor. Okay, so I'm going to turn it over to Roger. He's going to go over some examples with us and what happens if you have multiple capacitors. Stop my share here. It's all yours, Roger.
All right, well, thanks. Great job. So now we're going to look at some problems that are going to help us understand what happens with capacitors. Again, when right after we close the switch and we start charging the capacitor, what happens in the circuit? And then over time, as the capacitor charges up and it becomes like an open switch, it acts like an open switch. Then what happens? And so that's called the steady state occurrences. And I'm going to go ahead and share my screen with you. And I'm going to start here on our OneNote. And so let me hit share. And so I think you guys can see that. Okay. And excellent. So let me get to the appropriate place here. And we want to look at this. Now, I love doing problems like this. These are some of my favorite ones. And these are how we treat capacitors when they're in series and when they're in parallel. So if you remember from the work we've done before, all right, let me see, is that working? Okay, great. So when two capacitors, so let's look at these capacitors. So you can see that we have this, each capacitor has capacitance of 4 microfarads. What is the equivalent capacitance between X and Y? So here's our X and here's our Y. And we want to know what is the total capacitance or the equivalent capacitance. Each one is 4 microfarads. Okay. Now, what are we going to do first? Are we going to first treat this as a series or first treat this as parallel? Now, when you're simplifying circuits, either with resistors or with capacitors, you go from the inside out. You take the smallest parts and you start to simplify them. You build out and you add and add and add until you just have one simple circuit. So let's go ahead and draw this little arrow down here. And let's try another circuit. And what I'm going to do in this other circuit is I'm going to combine these two here. And I'm going to combine these two here. And so this is still my point X. Okay. And now I'm going to have one capacitor here and one capacitor here. And there's my point Y. And what do I do to bring these capacitors together? And so, or maybe the more appropriate question is, how are these capacitors mounted? How are they hooked up so that I can join them? And I hope you can see, remember that these are parallel capacitors. And so for capacitors that are mounted in parallel, which you can see they're kind of mounted one to the other here, one to the other, it's the parallel nature, that CP is equal to the sum of Cn or C1 plus C2 or C3. In other words, we're going to add those together. And so what we have is 4 microfarads plus 4 microfarads. That's going to give me 8 microfarads and 8 microfarads on that. Okay. So that's our first simplification. Okay. We're deconstructing this, right? And so the next thing I'm going to to do is I'm going to say, all right, well, now how can I bring these two together, right? How can I make that into one? Okay, and so there's my X, there's my Y. And so you ask, okay, well, how are these two mounted, right? Because when we went from here we said these two are mounted or hooked up in parallel. These two are right, one right after the other, and that's in series. And so our formula for series is 1 over C equivalent in series is 1 over C1 plus 1 over C2 plus 1 over C3 plus dot, dot, dot. And so again, this is the parallel up here, and this is series, and these two are in series. And so that means that 1 over C equivalent is 1 over 8 microfarads plus 1 over 8 microfarads. And so 1 over C equivalent is 2 over 8 microfarads. The microfarads are at the bottom there. Or C equivalent is equal to 4 microfarads. So the answer to this question is that these four together equal one of them alone, which is a kind of tricky thing that physics teachers sometimes try and do with problems, is silly things like that. Probably something that an electrical engineer would do, but they don't have as much fun as we do. All right, so there's that one. That's the first one. I'm going to do two more problems with you. This one here is an RC circuit. RC circuit stands for resistor and capacitor. And so here's our circuit. Let me take a second. Thank you. And it says here that the EMF, that script E stands for EMF, which is another way to say voltage, you can see is 9 volts. And so we have a 9-volt battery here. And we've got a switch here. We've got capacitor 1, which is 1 microfarad. I'm not going to write the value of this capacitor because it doesn't become important in this problem, but it certainly is something we're given. Each of these resistors is 3 ohms. Okay, so we've got 3 ohms here and 3 ohms here. Sometimes OneNote does that to me. Especially if I try and draw something really tiny. All right, so 3 ohms, 3 ohms. And so the first thing is at t equals 0, or I would say right after t equals 0. You know, like right after I close the switch, right here, close the switch, find the current through RA and RB. Now, when, and of course, something we would start with is we would say that this is an uncharged capacitor. And I'm sure you assume that, but we got to say no charge on that capacitor. Now, an uncharged capacitor, when you start to apply a potential difference across it at the instant, it acts like a closed switch. And then slowly, as it charges up, it starts to act like an open switch. And it goes from letting a ton of current through to letting no current. And so we're going to look at the initial point when it acts like an open switch, a closed switch, and then the final point when it acts like an open switch. So we're going to look at this. Let's look at the circuit here. Now, when I first close the switch, again, this is now like a closed line here. And what that means is that the current is going to move. I'm going to go ahead and get another color here. The current is going to move around this circuit, and it's going to go exclusively in this loop, and it's going to totally bypass RB. And the reason that it's going to totally bypass RB is because when I first close the switch, there is no resistance here. And so basically, I have shorted out this resistor only for a second, just for the first second. Okay. So now we can tell you if we want to find the current through RA and RB. Over here, I'm going to say here RB is equal to 0. There's no current through it because I've shorted it out. And what about RA? Let's go over here. I'm going to go up here and do some work with RA and see what that current is. All right. I'm sorry, that's the current through RB, not RB is equal to 0. All right. Now RA, let's go find the current through RA, and I is equal to V over R. So when I first close the switch, I've got 9 volts and I've got a resistance of 3 ohms, and so that's going to give me 3 amperes. Okay. And so RA is equal to 3 amperes. 0 and 3 were the first part. Okay. Now let's go ahead and look at the second part. I'm going to go with green on the second part. Now on this one, remember this is now a long time after the switch has been this switch has been closed, and now this does not act like a closed switch. It acts like an open switch. Like there is no current going through here. Not like there isn't any current. So I'm going to try and erase this here. Let me see if I can do that. There we go. There is now no current. Okay, going through this part. And so what we have is we have the current. Let me get a thicker line here, and we've got the current going this way and this way. In other words, if I want to just real quick draw that circuit, what I have is a resistor here, a resistor here. So it's a simple 2 resistor circuit. Then I have these two resistors together in series, right? This is 3 ohms and this is 3 ohms. When I've got those together, that's going to give me 6 ohms. Okay. And so I'm looking for the current here. So I is equal to V over R, and that's going to be 9 volts over 6 ohms. Let me move up here. 9 volts over 6 ohms. And so that's going to be 1.5 amperes. And now you might say, well, 1.5 amperes. Notice that's these two resistors are in series. That's 1.5 amperes through each resistor. And so IRA equals IRB equals 1.5 amperes for a long time. And that's what we call a steady state problem. All right. Now, one more to do. And this is also, I hope this one takes you back. This is really old school. I know you guys love these problems. I love doing problems like this with circuits and taking the circuits and making them simple and complex. And so we're going to do that. All right. Now, what I got here is you can see I got this problem set up, and it says for t equals 0. Again, t equals 0 when the switch is closed. What do we have? All right. Now, when the switch is again first closed, that right after t is infinitesimally greater than 0, we have the current, and it's going to remember flow across here as if that were just a wire. That's the way it's going to be at first. So we are going to look at these things. We're told that this is 10 ohms. This resistor is 30 ohms. Oops, if I go too slow or if I go too small on that, things happen. And this resistor over here is 60 ohms. All right. So I've got all this. I got 36 volts. My EMF is 36 volts right there. And so now I want to figure out what's going on. I want to find the resistance. Well, the resistance is given. I need to find that, but I will find the equivalent resistance. I want to find the current, the voltage drop across each one of these, and I want to find the power dissipated in each one of these objects. Okay. So the first thing let's do is we're going to decompose this circuit, which means we're going to take it. It's got effectively 3 resistors, and we're going to break it down into two resistors and then into one. So the first thing I'm going to do is I'm going to come over here and let me make this a little bit bigger. Okay. And the first thing I want to do is I want to go ahead and draw this. We've got this one. Okay. 10, 30, and let me come down here. Sorry. Okay. Very good. Okay. Oh, I did gray instead of green. Sorry. Okay. Now that one. Notice the only thing that I did is I took the capacitor just out of the system, out of the equation, because it is not part of the problem at this point. So I'm going to leave it alone. Now the next thing I'm going to do is I'm going to now, and I have to go back to the green. Sorry. Okay. I'm going to now break this down into simpler components. So I'm going to usually I start far away from the battery, so that's over here. And so this is 30 and this is 60. And so I know that to find the equivalent resistance of that, we're going to say 1 over 30 plus 1 over 60, because these two are in parallel. You can see that each one is attached at this point and they're attached at this point. So they're attached to both sides of each other. They're in parallel. And so what that means is we have that's 2 over 60 plus 1 over 60, or 3 over 60 is 1 over R equivalent, which means that R equivalent is equal to 20 ohms. So these two together in parallel are now going to function as 20 ohms. So now I'm going to draw a new circuit here, and I've got back that up a little bit. And I've got oh, I did it again. Oops, I did it again. Okay. I've got the 10 ohm resistor here, and now I've got this 20 ohm resistor, which is really just the equivalent resistance from these two. And so of course that I don't think I have to draw that one out. That's 10 plus 20 because they're in series. And so when resistors are in series, we add them simply. And so this is now a circuit, a simple circuit with 30 ohms of resistance. All right. Now, and 36 volts. Now we can start to work backwards and see what we can learn and put it back in the table. Now the first thing I can figure out is that the resistance, my equivalent resistance, I said, is 30 ohms. Okay. And that means that I can find the current, and I is equal to V over R, okay, which is 36 volts over 30 ohms, and that's 1.2 amperes. So I'm going to put 1.2 amperes there. Okay. Now I'm going to work backwards using the potential difference. I can now, and I'm going to switch to another color so we can kind of see how I work backwards. I can find the potential drop across each one of these circuits because I know that this is 1.2 amperes through the main branch. And so V is equal to IR. Sorry. And so that's 1.2 times 10 or 12 volts. So that means that there is a 12 volt drop across RA. This is a 12 volt drop. Now, if I have a 12 volt drop across here and a 36 volt gain, that means that my drop here has to be the difference because according to Kirchhoff's loop rule, when I go around a loop, the sum of the voltage gains and drops has to be zero. And so plus 36 minus 12, this is going to be 18 volts. Now, this is my fictitious branch over here because there's nothing with 20 amps, 20 ohms in this whole circuit. But guess what? That's what these are in parallel. And remember, branches that are in parallel always have the same voltage drop across them. So that means that this is 18 volts as well. And you go to Kirchhoff's loop rule. This is, if I'm going this way, this is an 18 volt drop, and that would be an 18 volt. So around any closed loop, we have the sums here. And so now I can go ahead and find the current through each part of these. Now, I already know that this is 1.2 amps because that's the main branch. Okay, we already found out that's the 10 ohm. What happens when the current, oops, sorry about that. That does happen. What happens when the current, which is 1.2 amperes, going this way? What happens when it gets to this junction? Well, that's a different Kirchhoff's rule. That's Kirchhoff's junction rule. And that tells us that the sum of the currents entering and leaving any junction has to sum to zero. The sum of the currents entering a junction has to equal the sum of the currents leaving the junction. And that's an articulation of the law of conservation of charge because you can't invent charges. Otherwise, they would have to leak out or something. So if this is 1.2 amps, I can come back here and say, what's the current through one of these? All right, well, I'm going to do that over here. And so I is equal to V over R. Okay? And so we have 18 volts. And let's put that over 30 ohms. Okay. And you can see that 6 goes into 18 3 times. And so that's 3/5 or 0.46. And so what we have there, I'm sorry, that's incorrect. 3/5. Yes. So this is my mistake. I'm so sorry. This is my mistake. This is not 18. Please bear with me. Okay. Let me go back and fix this. What is 36 minus 12? It's not 18. It is 24. Of course. Okay. I check my notes. Sorry about that. So this is 24 volts divided by 30. And that's going to be much better. 5/6. Okay. And so that what we have here is we have 0.8 amperes. And if I have 1.2 amperes, 0.8 amperes going this way, what do I have coming this way? And that's going to be 1.2 minus 0.8 is going to be 0.4. And so that's going to be 0.4 amperes. Okay. Now the last thing that we want to do is look at power. And power, remember, is there's 3 formulas for it that will be on your AP exam. P is equal to IV. It's also equal to V squared over R and I squared R. And it's worth it to just have those guys in your back pocket. All right. So when we come here and we multiply the current times the voltage, 24 times 24, we get 9.6 watts. When we multiply our current here, 0.8 amperes times 24, we get 19.2 watts. Oops, 0.2 watts. When we multiply the 1.2 times the 12, we get 14.4 watts. And when we add all those together, we get 43.2 watts, which is also the product of these two current and voltage. Wow. Do you remember doing those tables? I'm sure you do. So I love doing that. That's a lot of fun. Don't worry about that if that felt a little rusty because before your exam, we're going to do a whole review session on circuits, but we wanted to bring you back to them. I'm going to send you back to Frisco, Texas, and Kristen's going to take us home.
All right, thanks, Roger. They kind of remind me of doing puzzles or like filling in Sudokus when you're doing those tables. So we're going to look at one more problem, and we are going to do a problem from last year's exam. And you can find it if you want to later. It is on the last year's exam, but it's set 2 of last year's exam. And it's question number 1. And it's this. We have a circuit represented above, composed of 3 resistors. One has the resistance of 2R, well, 2 of them have a resistance of 2R, one has a resistance of R. The voltage of the battery is V0, and we have a capacitance C on our capacitor. Also, there is a switch. We're going to close that switch, and after a long time, that circuit is going to reach steady state conditions. So this now we're talking about after it already reaches those steady state conditions, not those initial ones, those kind of after a long time. Answer the following questions in terms of the potential difference of the battery, R, C, and fundamental constants. So the first part is we want to derive an expression for that steady state current supplied by the battery. So in order to find that current from the battery, let's think, how does a capacitor act after a long time? Once we have reached that fully charged steady state behavior, the capacitor acts like it's an open switch. And so when we get to inductors, they have a different symbol too. One thing I tell my students is that inductors and capacitors behave how they look after a long time. So how does a capacitor look after a long time? Well, it looks like a gap in the circuit, right? So it acts like an open switch. So the only thing that we're really going to be looking at then is our loop around the circuit this way. And if we apply our loop rule again, well, then we can say that the potential difference in the battery V0 minus the IR through resistor 1, which is 2R, minus, we're going to go across that resistor here, which is going to be another IR, and that resistor is just R. And we get back, that's got to equal 0. Well, since we're looking at this one loop, we know that current is going to be the same there. And so really I can say that V0 is going to equal I times 3R. So then that steady state current from the battery is going to equal V0 divided by 3R. So that would be that current after a long time that is being delivered by the battery. Okay, part B says to derive an expression for the charge on the capacitor. So even though that capacitor is acting like an open switch, that doesn't mean that it doesn't have a potential difference across it or that there's charge. Like it's fully charged. And so it does capacitor, fully charged, it's got a potential difference across it. And what could we say that potential difference is? Well, if this is acting like an open switch, we know that the current through this guy is going to be 0. And so if we were to take this outside loop, well, the only potential difference we would have is that drop across the capacitor. And so that capacitor potential difference is going to be the same as the potential difference across that resistor in the middle. So I can say, if I go over to the side here, that the potential difference across the capacitor is going to equal the potential difference across that resistor R in the middle. And then we can go about finding what that potential difference across that resistor is. And so if we look at that one, since they're parallel, they have the same. So we can go back and rewrite our loop rule. And so I now know that I can say that V0 from the battery is going to be equal to, well, we can go back to this loop here now, and we can say that we now know the current through that one is equal to V0 over 3R times that resistance, which is R2R, and then plus the potential difference across the resistor here, which we're just going to call VR, because that's really what we want to know. If we know the potential difference across this middle resistor is the same potential difference across the capacitor. And so we can say then that my VR is going to be equal to the V0 minus my, I can combine these, the R's are going to cancel, and I'm left with 2/3 V0. Well, what is V0 minus 2/3 of V0? Well, that leaves us with that voltage across the resistor, which is also the voltage across my capacitor, is equal to just 1/3 V0, or V0 over 3. That's going to be the potential difference across that capacitor. Now, how can I use that to get the charge? Well, again, we know that the potential difference across the capacitor is equal to Q over C. So then we can say that my Q is equal to the voltage times the capacitance. And so then the charge is going to equal V0 over 3 times C. And that would be our equation for the charge that's stored on the capacitor. Okay, let's go back and look then at the next part. Derive an expression for the energy stored in the capacitor. And so on your formula chart, you have a couple of different equations for the amount of energy that's stored in a capacitor. So I'm going to write them both down, and then you kind of have to decide what you know, what you don't know, and which one to use. Right? So we know that the energy stored in a capacitor is equal to either 1/2 Q times V, or we can say it's also equal to 1/2 CV squared. So if we look at what we can have our answer in terms of, we can't have our answer in terms of Q because it's V0 R and C. Now maybe I could go in and plug in that Q is V0 times C over 3, and you could solve it that way. Or we could use this one right here. So this is the one that I went with. So we know that the energy stored in the capacitor is 1/2 C, which we know the capacitance of that is just C. And we know the voltage drop across that potential difference of that capacitor is equal to V0 over 3. Okay, so, but this is squared. And so then if we go ahead and solve and we square both those, we get over 9, V0 squared over 9, 1/2. So this becomes C times V0 squared over 18 is that energy that's stored in the capacitor. Okay, and then the last part is, right, but do not solve a differential equation that would relate the charge as a function of time on the capacitor. So whenever we're doing these, and we're going to solve this, again, we're going to go back and actually set these up and solve them when we're talking about capacitors and circuits in our review. But we're going to go through and set it up. And the way that we want to set these up is we're always going to use our loop rule. And so after this long time, if we go around and we look at just the loop here, because now the switch is opened, right? So the switch is opened at time 0. So I'm going to rewrite my circuit up here. It is opened. All we have at middle resistor R and our resistor here that is 2R and my capacitor once that switch is opened up. And so now if we go through and write our loop rule, well now we can say that the voltage, where's the voltage drop initially? What is supplying that potential difference to the circuit? It is the potential difference of the capacitor. So we can say that the potential difference of the capacitor is going to be equal to the drops across those resistors. So if we say I times R plus I times 2R. And so I can simplify that and say the potential difference across the capacitor is equal to I times 3R. Now that isn't a differential yet, but that's how we always want to start. We want to write that loop rule. And then where can we plug in a differential? Well, I can say that the potential difference is equal to, well, that's Q over C. But I want to say that it's any charge over the C as that function of time. And I can say, well, instead of current, I can say that I is dQ over dt. Excuse the space here, right? Still times that 3R. So I'm going to rewrite that over here. We can see it a little bit better. We can say that R Q over C as a function of time is equal to my dQ over dt times 3R. And on the exam, they are not picky about the signs always. And this year they weren't picky about the sign, but we know that one of these is a positive potential difference, right? And the other one is negative. But this, we can say that the amount of charge that the capacitor is losing is equal to that flow of the current that's going back through. So truly one of those sides should be negative. Okay, so that would be our practice for today. So to wrap it up, you should now be able to find what the equivalent capacitance of the capacitor is, right? They behave opposite of what resistors do. So if they are in series, we have to do the 1 over the equivalent capacitance. And if they are parallel, we can simply add them up. We were able to find potential difference in current in a circuit that has a capacitor and resistor in it. We found the potential difference in the capacitor in an arrangement and the energy source. And then we found the charge stored on the capacitor also. So that is all we have for today. Thank you so much for tuning in. And we will see you tomorrow to talk about inductors and circuits. Right, Roger?
Yeah, thanks for tuning in. Can't wait to see you tomorrow night.
All right, you guys have a wonderful night.
Well, good evening. Welcome to AP Physics C, Electricity and Magnetism, AP Online. My name is Roger Siegel, and I'm coming to you live tonight from Sarasota, Florida. And my partner in crime is Kristen. And say hello, Kristen.
Hello, everybody. I'm Kristen in Las Vegas, and I am a teacher at Reed High School in Frisco, Texas.
Excellent. So if this is your first night with us, welcome. If you're back for more, welcome to you too. The way this works is both Kristen and I are teaching. We're both AP Physics C teachers, and we're getting you through the year, and then we're going to start reviewing. Let me go ahead and start sharing my screen with you guys so we can see what we're going to be doing today. First thing, make this a little bit smaller. Okay. So first thing is today's day 7, and so today we're going to do topic 5.2, which is inductance and LR circuits. Now L is the symbol for an inductor. Okay. So when we say LR circuit, we mean a circuit with a resistor and an inductor in it. Okay. And again, my name is Roger Siegel from Sarasota, Florida, and Kristen Gonzalez Vega is coming to you from Frisco, Texas. Now we want to let you know that the material that we're covering tonight is not going to be tested on the AP exam at the end of the year. We're covering this material at the request of colleges who we want to preserve the integrity of our program. So while you won't have the full blown gamut of all of the magnetism that you normally would have had, you've been exposed to it. So when you get to your next class, you'll be ready to start. Okay. Starting next Monday, we're going to be doing all review for the exam. Okay. So since we started last Wednesday night, we've been dealing in unit 4 and 5. We started with forces on a moving charge, forces on a wire, then the field due to a long wire, the field from 2 different laws, Biot, Savart law, and Ampere's law. And so that was unit 4, and that's really saying, answering 2 questions: how do things behave in magnetic fields, and how do magnetic fields get created? And last night we did section 5.1, electromagnetic induction, and Faraday's law and Lenz's law. And that electromagnetic induction, I wish they called it something else. They should call it generating electricity, because that's really the way it feels to me. That's what makes all this wonderful electricity happen is magnetic induction. All right. So yesterday we looked at magnetic induction, and we said that the EMF, or also known as the voltage for most people, is the time derivative of the flux. And this is the magnetic flux that we studied, not too different from the electric flux. So if we say, how does that flux changing in time? That gives us the answer, that many volts. That's how much electricity gets generated. Now Lenz's law, you have to do it. You can't say it, but we have to say it. So it says an induced EMF produces a current whose magnetic field always opposes the change in magnetic flux which causes it. And so if that sounds weird, please go back to last night's video, watch it, and it should make more sense to you. Okay, now let's talk about what we want to accomplish tonight. So after tonight's lesson, you should be able to calculate the magnitude and the sense of the EMF in an inductor through which a changing current is specified. Okay, you're going to calculate the rate of change of the current in the inductor. You're going to calculate the stored electrical energy in an inductor, and you're going to calculate the initial currents and the final steady state currents of the conductor. And last night we looked back at the capacitor to understand more about inductance to be able to do this lesson. So tonight we're going to again look back at capacitor problems and see how those will help us to understand inductance problems. Okay, all right. So let's get started. So what is an inductor and what does it do? So an inductor is a solenoid, ladies and gentlemen. It is a coil of wire. Sometimes it's actually called a coil. If you're into cars, the name for this in your car is a solenoid or a coil. It's interchangeable word. But another word is a choke. And I want to talk about that. Here's what an inductor does. Okay, an inductor pushes back against change. An inductor is the ultimate conservative. It does not like change. So that means that if the current in a circuit through an inductor wants to go up, if I increase the potential difference to try and raise the current, the inductor will push back against that. And so it'll rise, but at a slower rate. Then the inductor doesn't like the other kind of change, a reduction in current. So if I have a current through a circuit and through an inductor, and I try and turn that circuit off right away, the inductor won't let me do that. It will only let it go off gradually. So that's the reason that an inductor is sometimes called a choke. Okay, so this is a picture of our inductor, and you can see the currents going in here and coming out here. And so it's just a coil of wire, right? But the most important thing to remember is the inductor opposes a change in current. Right? A couple other things about an inductor. Since the inductor's function is understood in terms of induced EMF, backwards and forwards, we're going to use, this is the formula. This is the formula sheet that's on your, this is the formula that's on your sheet on AP Physics C. And this is the voltage drop across a conductor. Now, sometimes we do a problem like this, like I think yesterday we looked at the negative sign. We said, don't worry so much about that sign because we're going to find that sign from the Lenz's law. But this is not the case. I want you to pay close attention to that sign because it means something really important. It means when I dot, when the rate of change of I is positive, that means when you want the current to increase, the EMF will be in the opposite direction. So that means if the current is trying to increase, there's going to be a back EMF pushing back against it. Conversely, if the time rate of change of I is negative, if the current is decreasing, the inductor is going to push back against that. The current will still decrease, but not as quickly. All right. Now, this is the energy stored in an inductor. And notice that that energy is dependent on the current squared. And I want to say something about that. We'll talk about it in a minute, but the inductor is storing energy in the magnetic field. All right, let's keep moving. Now, this is an RC circuit, and we want to review this. This is a long time, not a long time ago, but this is a while ago. And so this is our RC circuit, and you can see here that we have our EMF here, and we can say that that's a certain number of volts. We have our capacitor here and our resistor here. Now, when I first close the switch on this side, and there's no charge in the beginning, the current starts to circulate in this direction, and charges start to accumulate on these plates. Now, at first, there's no charges, so the current goes right through. Beautiful, easy. But as the charges start to accumulate, it's harder and harder for this current to move through. through, and the current goes down and down and down, and it goes to zero. So when we charge a capacitor current as a function of time, it looks like this. And this initial current right here is just E over R, because at the beginning, that capacitor does nothing. And then as soon as charge starts to build up, it goes to zero. Now, when I throw the switch to the other side, to this side, now what happens? Well, now I've got these positive charges here, right? And negative charges, and they're saying, I want to stay here. So they're going to start moving in this direction, and I'm going to create a current back the other way. So when I'm discharging from my capacitor, I have now a current going in the other direction, and it is discharging that way. I want to show you a simulation that will help you to see this, I hope. Okay, now this is the greatest. I love Mr. Falstad's physics simulation. Mr. Falstad, if you're out there, thank you. You've written some brilliant simulations. All right, so let's take a look at this. I'm going to be pointing with my mouse. And so you can see here that we have a battery. This is our circuit. And watch what happens when I close this switch. Okay, I get a current, but very soon it starts to slow to zero because charges are building up. And then when I click to the other side, it discharges in the other direction. So we get that opposite direction. Once again, charging and discharge. All right, and that's what an RC circuit does. So that's what we've done that before. Now we want to look at an R and LR circuit, or an RL circuit. Sorry. Now, at the beginning, notice that we have our switch in the middle. Nothing is happening. We just leave that switch there. We've got our EMF over here. We've got our resistance here, and we've got a certain inductor. And the value of that inductance, remember, is in Henry. So 5 Henrys or 10 Henrys. But the symbol is L. All right, now there's no current. There's nothing going on. I haven't hooked up anything. And the first thing that I'm going to do is I'm going to throw the switch over to this side. And when I throw the switch over to that side, right away, the initial current here, I naught, before I throw the switch, is zero. And there's no potential difference across here either. Okay, the voltage across here is originally zero because nothing's hooked up. But as soon as I hook it up, now I've got this potential difference. I'm trying to push current in that direction. What does the inductor do? It pushes back. Now, it doesn't push back as much as it being pushed forward. But remember, the inductor is the ultimate conservative. It hates change. And so it's going to push back. And so it'll push back a little. But then as the current keeps going, the change reduces to zero. When the change is zero, then we have full current going. Now, if this is now moving, all the current's moving around in here, you can see here, we've got a circulation of current in that direction. So now, what happens when I throw the switch to the other side? Well, remember, the inductor is the ultimate conservative. It hates change. So since there's already a current in this direction, as soon as I turn off the voltage, guess what? Now there's going to be an EMF not in the backward direction, but in the forward direction because it wants to keep pushing the current. Now, it's a lot less than the voltage of the battery, and it goes down over time, but that's what happens. I want to show you a simulation that's going to take you through this. And this is again, Mr. Paulson. Now, notice that we start with a circuit, and we've got a battery, a switch, an inductor, and a resistor. Now, remember, the inductor does not want change. It's at zero now. So when I close the switch, watch what happens. Slowly, the current starts to pick up, and there it is. And, I'm going to go ahead and put let me stop this for a second. Run stop this back here. I'm going to just throw an oscilloscope on here because that will help me to figure out what's going on. So once again, let's go ahead and throw that switch, and there we go. And so you can see, look at my current. It starts at zero, and it's going to approach its total value. Now, once the current gets to its maximum value, there's no more back EMF because the current is no longer changing. And so you can see that my current here is about 50 milliamps. Well, why is that? Well, I've got 5 volts divided by 100 ohms is 50 milliamps. Now, watch what happens when I throw the switch here. Remember, this inductor wants to keep the current doing what it's doing. So since it's flowing, it wants to keep pushing it. Watch this. Now, what changed right away, let me go ahead and pause this, is down here, the voltage automatically switched to the other direction. The current now decreases as so. So let's go back to our schematic here. When the current is increasing, when I first throw the switch over to this side and the current is increasing, then our current through the inductor looks like this. And so we have an exponential approach, and this is I, and this is T, and this value is E over, let me do it, come on, E over R. Now, when the current is decreasing, we have the current now starting at this maximum value, E over R, and now the current decreases exponentially. And that is what happens with an inductor. All right. So I just want to do one more thing, and then we're going to send it. We're going to do some practice problems. So one more useful thing to look at. It's useful, again, to go from something you know that you are more familiar with to something you're less familiar with, and you kind of bridge over, and teachers call that scaffold. And so what we learned is that capacitors are two parallel plates, right, that store energy in the electric field between the plates. Okay. And an inductor stores energy in this magnetic field in the inductor. Okay. So that's something they both store energy, but different ways. All right. Now, just after you start the capacitor, it acts like a closed switch. Lets all the current through. Just after you start the inductor, it's like an open switch. It lets nothing through. Now, over time, the capacitor closes. The capacitor opens. And so now no more current flows, and now I is equal to zero. Over time, now the inductor, it switch places, now acts like a closed switch, and it lets all current pass through. Okay. And then the voltage drop across a capacitor, when we're using Kirchhoff's loop rule and one of the voltage drop across a capacitor, we do Q over C. And so the voltage drop is really about the ratio of these two. The voltage drop on an inductor is due to the change in current, how much the current is changing. So this is how much charge I put on the capacitor. This is how much the inductor is changing. All right. So now we're going to throw it back to Frisco, Texas, and do some problems with Kristen. And I think she's ready to take us to the next level.
All right. Yes. Let's look at some practice problems here. The first one we're going to take a look at is the circuit right here where we have a voltage source. We've got one resistor and we've got our one inductor. And so we want to know at time zero, if the switch is closed in the circuit shown above, which of the following graphs would best describe the potential difference across the resistor as a function of time. So again, we want to think back to how does that behave when we first close that switch. So after a long time, they behave like they look. An inductor looks like a wire. So after a long time, it looks like a wire. At time zero, it'll act like an open switch. So if this is an open switch, then there would be no current going through that resistor and therefore no potential difference across it. But as time goes on, it's going to increase. So if we were to draw it here, we'd start with 0, and that would increase until we reach a maximum amount, which would equal that potential difference of that battery. So that would be B. And some relationships would go, the way we derive these is we look at how that goes around, right? So it always comes back to our loop rules and writing those loop rules. And I'll show you kind of how it works, but then we're not going to get into the calculus today. We're going to really just talk about steady states. But if we have time, Roger might be able to go into that a little bit for us. But if we take that loop rule around, we're starting with the EMF of the battery, and we know that gain has to equal the losses across the resistor and the inductor. So that would equal IR from the resistor. And then we also have that L times our DI over dt, that change in current. Okay, so then we can look and see and use that equation. And then we also will have an equation for that current and potential difference as a function of time. And it really goes back to the calculus of it. It'll curve off is not a linear relationship. Okay. The other one I want to do with you is this one. And I'm going to switch over to my document camera to write this out a little bit better and use lots of different colors.
You need to share.
I want to make sure it's up and working first. Here we go. Okay. So we have the circuit here, and we've got a potential difference E. We've got a switch S, and then we also have two branches. I've got one branch that has a resistor and an inductor on it, and I have one branch that has just a resistor on it. And so we're going to look at a few different things. The first thing I want to ask you is what is the current at point X immediately after I close that switch? So point X right here in the circuit. Immediately after I close that switch, what would be the current at that point? So I want you just a second to think about it and see if you can figure that out. A little bit bigger there for us. So again, how does an inductor act right after we close the switch? So then what kind of would be your loops or your paths in your circuit if that's behaving that way? Okay, so at time zero, our inductor is going to act like an open switch. So if I follow my loop rule, if this is an open switch, well then all I would have is my loop going around that outside. And so there'd be current in that outside resistor, and we can find what that is using E equals IR. So that would be equal to E over R. But there would be no current going through this whole entire junction because that inductor is there, and it is indicating that it can open switch at time 0. Okay, what about after a long time? What would that current be? So after a long time, well, now that's acting like a wire. So I'm going to redraw this here. The resistor, the inductor is that kind of curly coil in the circuit. So if we close that switch for a long time, let's find that current. And also, let's go back and find what that energy would be stored on that, in that inductor. Okay, so the energy we know is going to be equal to 1/2 L times I squared. So what we need to know is first, what is the current that will be going through that point? So let's find the current going through X. So if we take our steps, if I want to know the current going through here, well, after a long time, that inductor is not going to act like a wire. So now we have two loops going around. I've got my loop around on the inside here, and I've got my loop around on the outside. So let's find what the total resistance of our circuit is. We've got two resistors, and they are parallel with each other. So we can say 1 over the equivalent resistance is equal to 1 over R plus 1 over R. So if we invert that over, we get our equivalent resistance is equal to R over 2. Remember, when you add resistors in parallel, you're always decreasing that equivalent resistance. And then I can find what the total current is from our battery that has an EMF of E, because we know that E is equal to IR. So I will equal E over our equivalent resistance, which is R over 2. So really 2 times the EMF divided by the resistor R. So that's going to be our total current. That's the current being supplied by the battery. But it's going to get to this junction here, and using our junction roulette, current's going to split. Sometimes it's even, sometimes it's not. It depends on that resistance. Since each of these branches have the same resistance, and that current will split equally. So there will be a current of E over R going this way, and a current going this way of E over R. So now we can plug in and find what that energy is. U will equal 1/2 L, which we know the inductance of this inductor is L, times I squared. And I is simply E over R squared. So we can simplify that down to that U will equal E squared times L over 2R squared. That's how we can find that energy stored there. And the last thing we want to do is, after the switch has been closed for a long time, what would the graph look like of the current as a function of time if we open that switch back up? So at time 0, we're going to open that switch back up, and what will be the current at point X as a function of time? Well, we already know after a long time, we had that inductor that was a wire, there was current that was going through. So we know we are starting with current, but as that is changing in the inductor, that's going to decrease. And again, we can derive an equation using our loop rules to figure out what that equation is, but it is going to exponentially decrease down towards 0. So those are some practice ones there. I'm going to go ahead, and Roger's going to do an AP question with us.
Well, thanks so much, Kristen. Welcome back to Sarasota. Here we go. So I know you guys love FRQs. I love FRQs. So they really put us through our paces. So let's go ahead and take a look at one. I was going through my materials looking for just perfect FRQ, and I found one. And guess what it was from? 1987. Remember that year? Okay, so let's go ahead and take a look at this. So this is a problem, again, for the 1987 exam. Let's take a really good look at the circuit first. And so you can see that the circuit, we've got our 20 volts battery, we've got a 10 ohm resistor, a 90 ohm resistor, and we've got our 1/2 Henry, 0.5 H. Remember, H is Henry's. And that is our inductance. So we've got the switch, it's initially open, and currents are all 0. And we want the instant immediately after the switch is closed. And that's a giveaway. Remember, immediately after the switch is closed, let's think, what does the inductor do when it has no current and then it goes to, we have a potential difference, we want to put a current through it. Well, what the inductor does is it blocks that current in the beginning. I want to again draw for you for an inductor, I for I versus T. When you're increasing the current, the initial current of an inductor is 0 right there. And so if this is 0 current, I'm going to put an X through here. What is the potential difference across the 90 ohm resistor? Well, I know that V is equal to IR. So if I can find the current through the 90 ohm resistor, then I can find the voltage. Okay, now the current through the 90 ohm resistor, remember, this branch, it's almost like it doesn't even exist. I want to cross it off. We'll come back and make it. But at the beginning, right after the switch is open, it's blocked. There's no current going through there. So what that means is we've got a current of the total voltage over the total resistance, and I'll put a T for total, times just the resistance of the 90. Okay, and so that's going to be 20 volts over 100 volts. I'm sorry, 100 ohms. So the reason I'm saying 100 ohms is because we have these two in series. So that's going to give me 100 ohms. So I'm going to then say that this is going to be 0.5 amperes. I'm sorry, it's 1/5, so 0.2 amperes, and that is the current through this branch. Okay, 0.2 amperes. Now, what we want next is the rate of change of the current in the inductor. Now, there's only one formula that you have, actually two formulas you have with an inductor in there. One is that the EMF is equal to, let me zoom in a little bit here. Okay? And so the EMF, here, let's see, you know what, we're going to go over here, get some more space. All right, let's try it over here. And so what we'll say then is the EMF, try again, is equal to negative L di dt. And the U, oh my goodness, I'm not having any luck with this. Let's try again. The U of L is 1/2 Li squared. And so those are the, come on. Okay, thank you for your patience. So these are the only two formulas that have an inductor in them. If I want to know what the rate of change is, look at that, that's what I'm looking at. And so I'm going to say that di dt is going to be equal to E over negative L. Okay, now we already know that the voltage drop across the 90 ohm resistor, we don't know what the voltage drop across the 90 ohm resistor is because I didn't find it here. But we know the current here is 0.2 amperes. So this is 0.2 amperes. And at the beginning, this is also 0.2 amperes. And so that means that the voltage drop across here is 18 volts. Okay, because 0.2 times 90 is 18 volts. And so we have 18 volts is our voltage drop across here. But guess what? Look, this is in parallel with this. So they have the same voltage drop. And so, and then L is going to be just 0.5. Now, the negative I'll be able to put in later, but I know that the rate of change is positive. And so this is going to be 36, and it's di dt, so it's going to be amperes per second. So right at the beginning of this charge, the current is increasing at 36 amperes per second. If you wanted to ask what would that look like, or where does that show up, that's the slope of the line right there. 36, the slope, rate of change, is equal to 36 amps per second. Okay, so that's part B. Now, let's see if we can do part C here. Now, if the switches remain closed for a long time, what does that mean? Well, remember, that means that over time, the current just keeps going, and after a while, ladies and gentlemen, after a while, start again here, there is no, this is after the switch is open for a long time, the resistance here, or the back EMF goes to 0. And what does that mean when the back EMF goes to 0? Ladies and gentlemen, what that means is that this is now what we call a short circuit. There is no current. There is no resistance. There's nothing blocking the current. And so the current says, yes, please, I'll go this way, and completely bypasses the 90 ohm resistor. That's called a short circuit. This inductor is shorting out the 90 ohm resistor. And so that means that I is equal to V over R in part C. And the V, the voltage here, well, we have a voltage, let's see, the current, I'm sorry. So our voltage is 20 volts, and our resistance is 10 ohms. And so that means that our current is going to be 2 amperes. So now we've got this current of 2 amps going through the inductor in that direction, 2 amperes. Okay, and that's after a little bit of time, right after it comes to a steady state. Now D, the energy stored in this magnetic field, is 1/2 Li squared. So that's 1/2. L is 0.5 henries. I is 2 amperes squared. And so if we do 2 times squared, that's 4. And so 4 times 1/2 is 2 times 1/2 is 1. The answer is 1 joule of energy is stored. And where's it stored? It's stored in the magnetic field. It's so small you can't see it, but there's a magnetic field inside that inductor. That's where the energy is stored. Okay, we're almost done for the night. I know you can feel it. I can too. All right, one more thing, 2 more parts to this problem. The next part says, at a time later, T is reopened. So remember, we got at first, let me zoom in here a little bit. We got a current going in this direction. I want to remind us that this we said was 2 amperes after a long time, and at some time later, T naught, the switch is reopened. Now, remember, this is 2 amperes. The inductor is the ultimate conservative. It does not like change. So since we've got 2 amperes going down this way, as soon as I open this switch and I'm no longer pushing current, guess what? It wants to stop. It can't right away. And so for the instant, immediately determine the potential difference across the 90 ohm resistor. So watch this. The current is going in this outside loop like that. Current's going all around, outside loop, okay, outside loop. And all of a sudden I open this up. What's going to happen is right away, current can't go through this outside loop anymore because this is closed. So now the current's going to circulate here. And so we want to know what is the potential difference across the 90 ohm resistor. Well, guess what? Potential difference is IR. And the current we know is 2 amperes. The resistor is 90 ohms. Do the math, ladies and gentlemen. That is 2 times 90, 180 volts. Now I want you to check this out. We have a 180 volt potential difference coming from a 20 volt battery. What does that make you think of? Taser, of course. How do you get so much voltage from a little battery? And the way you do that is by having an inductor. You have to have that charge moving and then you interrupt it instantaneously and we get that giant jump. So this is one way that we can use an inductor to release a tremendous amount of energy. By the way, that's why if you don't know what you're doing, you should never open an electric component because you might think, well, I've unplugged it, so now it's safe. Well, it's not because there are capacitors in there and inductors and they can hold a lot of charge. So always be careful when you open up the back of electronics. All right, so we've got this giant 180 volts. Goodness. And so now the last thing is to go ahead and find the value there. Let's see. So this is our potential difference, and here we go. And so what is the potential difference first? Well, we know it starts off at 90 ohms. I'm sorry, for T is greater than T naught. So yeah, as soon as I close the switch, my potential difference goes up to 180 volts, and then it's going to trickle down like that. How do I know? Well, I know that the current is going to trickle down I, and V is equal to IR. So they should have the same shape. Okay. Now you know what an inductor is. Okay. So I love teaching inductors. I'm glad we got to do this. So let's take a look back and see did we think we got done what we tried to do. So what we tried to do was to calculate the magnitude and sense of the EMF in an inductor through which a changing current is specified, and we did that in one of the problems. We calculated the rate of change of the current. That was our di dt. Remember? And so we did that. That is di dt. We calculated the stored electrical energy. That is UL is equal to 1/2 Li squared. And then we calculated the initial currents and final steady state currents. And one thing I want you to remember that phrasing, the instant after the switch is open, the instant after the switch is closed. That tells us to treat either the capacitor or the inductor as, if it's a capacitor, a closed switch. If it's an inductor, it's an open switch. Okay, so that is our show for tonight, and we're so glad that you joined us. We love teaching physics, and so more is better. So I want to thank you so much for working so hard with us. I hope these are useful. And then tomorrow we've got Maxwell's equations before Monday when we're going to start reviewing for your final exam. All right, Kristen, how's it going in Frisco?
It's awesome, Roger. It was a great lesson tonight. Thank you guys so much for tuning in. And yes, we're going to go over Maxwell's equations tomorrow, which is super interesting.
Okay, wonderful. So thank you again, and we will see you tomorrow night, same time, same YouTube channel.
Happy Friday. This is AP Physics C, Electricity, and Magnetism live lessons. My name is Kristen Gonzalez-Vega, and I teach at Reed High School in Frisco, Texas. And joining me, I have my friend Roger.
Hello, everybody. My name is Roger Siegel, and we're coming to you live from Sarasota, Florida. I'm glad you could join us, and we're looking forward to learning about Maxwell's equations tonight.
Yes, and just a side note, today is our last lesson on electricity and magnetism. So starting Monday, we will be reviewing, and I'll kind of go over that first week schedule with you at the end of class, but make sure that you're tuning in and telling all your friends that we will go back and start review from the beginning of electricity and magnetism on Monday. So today, we are kind of tying everything together, and we call a set of equations that's called Maxwell's equations. So Maxwell's equations, again, my name is Kristen Gonzalez-Vega, and I have with me Mr. Roger Siegel. And tonight, we're going to be able to explain how a changing magnetic field can induce an electric field, and vice versa. And we're going to associate Maxwell's equations with an appropriate physical consequence in a physical system containing a magnetic or electric field. So I'm going to go through and review some equations with you that are important, that kind of help to combine to make Maxwell's equations, and we call them Maxwell's equations, but really they're other people's equations that he kind of put together into one equation in the end. So what we have is we have Gauss's law for electric flux, which if you recall is the integral of E dot dA equals Q enclosed over epsilon naught. So we can determine what that electric field is looking at that charge enclosed in our Gaussian surface. We can also say that we have magnetic flux, and we can relate Gauss's law for magnetic flux, and that is the closed integral of E dot dA equals 0. And so what that really means is if I look at a magnet that has, we say, a north and a south pole, right? We determine that there are going to be magnetic field lines that run out from that north end of that south pole. And so if I take any kind of surface, maybe I change my colors here, maybe I draw a cube, maybe I draw a sphere, whatever I'm drawing, right? If I draw this cube here, if I look at a surface, well, I've got magnetic field lines going in, magnetic field lines going out. So when we look at that closed surface, we always have closed loops. There's always the same amount of magnetic field lines going into our surfaces out. So for that closed surface, our magnetic flux is always going to be 0. Okay. We also have Ampere's law, and Ampere's law states that the integral of E dot dl equals mu naught times I. So that was when we looked at our long wire, and we took a nice Amperian path along that wire, and we said that, well, we can determine what that magnetic field is by taking that integral around, or we can, and looking at the current going through that wire. So it's proportional to that current going through. We also have Faraday's law. Faraday's law that we discussed the other day was that the changing magnetic flux will lead to an induced EMF in a wire. So if I change the magnitude of the field, I change the area of my wire, we could change all those things. But if we had a change in magnetic flux, then we got an induced EMF. But we also know that potential difference is equal to the integral of the electric field with respect to that line. So if we put those all together, we can say that Faraday's law is the integral of E dot dl equals that change in flux over change in time. So this last one, as we see it in that top part, is a little bit new, but not really, because we can use those concepts that we've used before. So what Maxwell did is he came along, he said, well, if we have a change in magnetic field that creates an electric field, right? If we go back here to Ampere's law, if we have a change in magnetic field, or Faraday's law, then we'll create an electric field. Well, should the inverse also be true? If I have a changing electric field, should that induce a magnetic field? And so that's what his work was, to look at those equations, what people came up with, and put together and see if it works both ways. And the way that he really did it was by looking at capacitors. So I'm going to kind of come back to this, but I want to look at this slide right here. So this kind of combines everything together. If we look, Orsted said if we have a current carrying wire, there's magnetic fields lines that are going to circulate around the wire. Then Ampere's law put it all together by saying if we take the integral of that magnetic field all the way around, it's proportional to the current that's going through that. Well, if we take let me get my pen here. Well, if we take a closed surface, what that means is really physically what is that current that is penetrating through that surface? But I don't have to have just this circular surface here. What if I drew this kind of drum sack shaped surface and I look at that instead? Well, if I look at the current, it's still going to be the same that's going through all the surfaces, right? The current's not just stopping anywhere in there. So what if we look at a capacitor? And let's look at this bottom one here. So if I have that surface that's extending in between that capacitor, well, if I look at we'll reference this again. If I go back to Ampere's law and we look at that same surface, right? So I'm just going to add in a capacitor here. And I'm going to extend my surface into that capacitor. Well, if I look at Ampere's law, let's look at both sides of that. If we look at the left side, right, we are going to have a magnetic field along that if we integrate around that path on this surface here. So this side is not 0. My integral B dot dl will not be 0 for this case. But if I look at the right side here and I look at the surface here, here, in between that parallel plate capacitor, there isn't any current that's going to be penetrating through that side. So this side is equal to 0. And so Maxwell says, well, how is that true? How can I have one side that is equal to 0, one side that's not equal to 0? And so he said, there's got to be something missing. There's got to be some other term over here that's going to give us something that's not equal to 0. Okay? So if we look at that, let's look at on that capacitor. So if I go back and I look at that parallel plate capacitor, and if we are, let's say, flipping a switch, and we've got that current that's going to start to flow to that capacitor, well, we know we're getting charge that's building up on that capacitor on both of those sides. And so I can say, well, that charge on that capacitor is going to be equal to the capacitance of that capacitor times the potential difference. And I also know that the capacitance of any capacitor is epsilon naught times A over D. So I can say Q is equal to epsilon naught A over D, still times that potential difference. And I can relate the electric field and the potential difference between here because I know that the potential difference is equal to the electric field times that separation distance of my plates. And so if I plug E times D in for my potential difference, well, those D's are going to cancel out. And so then I get that Q is equal to epsilon naught A times E. But that Q is a constant, right? As we flip that switch and that current is passing through, that charge is building up, there's a change in the charge on the plates. So I can say, well, really, it's dq over dt. But if the charge is changing, then the electric field is changing between the plates. And so we can say then that dq over dt is equal to epsilon naught times A still times that dE over dt, that changing electric field with respect to time. And we know that now that changing electric field, just like a changing magnetic field is magnetic flux, our changing electric field is going to be our changing electric flux, right? So A times dE is that electric flux. So really we get that I, because dq over dt is the current, is equal to epsilon naught times dE over dt. And this is what we call the displacement current. And it's not a real current because it's not actually physically charges moving through like they are in the wire, right? That's what we call our conduction current. So this is what we call our displacement current because it's resulting from that changing electric field between the plates. So that was where we got that last term, is because of that displacement current. And so this is really our full equation that Maxwell came up with and put together using all those other equations. So we get that our integral of B.dl equals mu naught I enclosed, that traditional kind of Ampere's law, plus that additional term counting for that displacement current because of that changing electric field. So it's kind of a lot of concepts to put together. But the good thing is it has real use because if I have a changing electric field and I have a changing magnetic field, that is how we get electromagnetic waves. And so I have here a simulation to show us, right? So if we look at, for example, an antenna has an alternating current that's going to flip that current from one direction to another direction. Well, that's going to change the electric field, and that's going to cause a changing magnetic field. So we get these waves, both these. So if I show them one at a time. So here's just that electric field due to that changing current, and that changing current or changing electric field is going to create a magnetic field that is changing. And if you kind of look at just like one green and red, that's our electromagnetic wave. And so you can see they are perpendicular to each other. So on our spectrum, right, our electromagnetic spectrum, that's how we get our microwaves and our light. That small light part of the spectrum is due to these changing electric fields and magnetic fields. And I just have another picture of it here showing those two fields. So that's kind of the basics of what Maxwell's equations are. And so Roger's gonna give us a couple of examples on how we can apply it. So I'm gonna turn it over to Florida and Roger.
Kristen, welcome back everybody to Florida, beautiful Sarasota, Florida. So let's keep going with Maxwell laws. I'm going to share my screen here, and let's go ahead and take a look at my note here. And here's some things that are hopefully help us understand now. Remember, this idea is that we have a capacitor. We have a current when we're charging the capacitor, and if we put an amp in there, we're going to see that current. Okay, well, we're going to focus on what's happening in there causing that current. All right, so we got this. This is a circular capacitor like that, and radius r, and separation is small compared to the radius. And so we've got a constant current I that flows into the capacitor. So again, that's our ammeter here, over here, and we can see that there's current as we go through there. That's I. So what rate does the electric field increase? So that rate to me, that is dE dt. So if I just could figure out what's E, then I can figure out what's dE dt. Let's see what that is. Now, time ago, really, this is going back, guys. So you guys can remember that when we have a single plate, let's just start with a single plate. And so if we've got a single plate capacitor, a single plate of charge, and so these are all positive charges, remember this, and this is sigma, that the electric field here in this direction is sigma is E is sigma over 2 epsilon. And so in that case, we've seen that one. But actually, the wrong formula. I'm so sorry, people. I'm so sorry. I said we get the right formula on there. So we have that our electric field between two parallel plates, and this is on your formula sheet, right, is E is equal to Q over epsilon naught. So that's our electric field. We've seen that show before. And so in this case, Q is equal to epsilon naught. What's the area? Well, if the radius is r, then that's pi r squared. And so that is the electric field. So what is dE dt? Well, that's the rate of change with respect to time of Q over epsilon naught pi r squared. When we look at this, we say what in this parentheses is changing with respect to time? And the only thing that's changing with respect to time is Q. So that's going to be 1 over epsilon naught pi r squared. And then we have dQ dt. Oh, yeah. Oh, that's nice. And let's see if I can do that. dt. There we go. And what is dQ dt? Well, that's the current. That's I. And so we can say that dE dt is I over epsilon naught, rate of change of this electric field. And we want you to take away from this lesson, it's not the numbers and formulas, it's that there's a changing electric field in here due to that charge building up, and that acts like a current. And that's what we call this. All right, let's go ahead down to one more here, and let's see what we have here. All right, so we've got a capacitor, and again, we've got these parallel circular plates, and so parallel circular plates, and the radius is, let's say, r meters. And suppose we've got a constant current of I, we'll just call that I, flows into the capacitor. All right, now, let's see if we can understand what's happening. What is the displacement current between the plates of the capacitor? What is displacement current? Remember we said a few minutes ago. Displacement current. All right, look, if you put an ammeter on here, and you're charging this capacitor, you're going to get the current. We know what that looks like when it's charging. It looks like this. All right, we talked about that 2 nights ago. I think we talked about it last time too. And so we've got a current that's going through there while it's charging. Well, can you put an ammeter in here? No, of course you can't. That's a vacuum. You can't put an ammeter in there. And if you did, it wouldn't measure anything because it wouldn't be hooked up to anything. If you hooked it up to the plates, it wouldn't be a capacitor. And so what we do is we have this concept called the displacement current, which is really the same as this conducting current or the real current. All right, and so what is the displacement current? Well, ID is equal to I, or in this case, just that, whatever that happens to be. That's what we do. That seems to be pretty obvious. Now let's go ahead and try the next one. It said, what is the value of dE dt at which the electric field is charged? And so I'm not going to bore you with that problem because we just did it right before, it's on previous page. And so we'll just say, see previous slide, but we'll put the answer. And so that is dE dt is equal to I over epsilon naught pi. All right, now, what is the magnetic field strength at a distance? And let's go ahead and say r meters. Well, we already have a minute here. I got to make sure that I have the right R here. This has to be capital R. I forgot to do that. That's important because you can All right, so what is the magnetic field strength? The distance small r meters from the axis of the capacitor. So here's our capacitor. And we're talking about a distance greater than the radius of the plate. So that's a distance like out here, that far away. And so what is the magnetic field there? Well, what we're going to do is we're going to use Ampere's law. Okay, and Ampere's law says that the loop E dot dl is equal to U naught times I, and remember this is the I enclosed. Okay, so this is I enclosed within the within that space. So let's zoom in here. And so what I'm going to do is, if you remember what we call it when we go around a current to find out the magnetic field, we call that an Amperian loop. So we're going to go ahead and imagine that we're drawing a big, a big circle right around this space through that point, and that's our Amperian loop. And so what we'll say then is we know enough about the uniformity and the symmetry of this setup, and that's why, by the way, we have circular plates. It just makes sense to me now. So the reason, so we have these circular plates, and because we have the symmetry, we can say that this B field is the same everywhere and equal distant from the center. And so when something's the same and is not changing in space, and we've got a spatial integral, we pull it out front, and so then we're going to say dl, okay, is equal to U naught I enclosed. Now, what is this dl? Well, ladies and gentlemen, when you take a walk around this circle, and you add up all the tiny little dl's around there, what you have is what we call this. And so this is 2 pi r. And over here we have U naught. And what is the I enclosed by our loop? And this is where we have to remember there's no real current, but there's something that acts like current, this changing electric field. And so that is our same current as the I in the wire. The I in the space is the same as the one in the I wire. And so you're going to see something, and you're going to say, well, that's pretty familiar. You've seen this before. And you're right. This is what we've seen before. So that's how that was. One more, and then we'll send it back to Frisco, Texas. Right now, what if we had the magnetic field? We asked, what is the magnetic field strength? But not a big distance r from the not a big distance r from the center, but a small distance. So in other words, imagine that we got that guy. All right, now, well, here's what we can see here. Our displacement current, this thing that we're calling the displacement current, is where? Well, because of uniformity, the displacement current is everywhere. It's here. You see if I can, it's going to be tough because it's so small. So I'm going to zoom in and see if I can draw without getting one note too upset. Okay, so this is this displacement current, and where is it? It's pretty much everywhere. So if my R value that I'm looking at, and I'll come back and hit this again, if my R value is just between here and here, then I can only, if I want to know the magnetic field here, I can only count the changing electric field, right, which is our displacement current that's inside of that. So we're going to start again with B dot dl equals U naught I, and this is the I enclosed. Now remember, it's just enclosed in here, and we can't look at this one. We have to kind of pull that away. So what we're going to do is, again, the symmetry, let's hold the B out front. This is a spatial integral. We're integrating in space. It's the same everywhere in space, that distance. And so we're going to pull the B out, and we're going to say the dLs, and then that's going to equal to U naught. Now, what is the I enclosed? Well, it's the total current through the entire part from here to here, the total current. But, I'm sorry, say it differently. It's this ratio of this part of the current to the bigger part of the current. In other words, we've got to find a ratio of areas. And so the little area is pi little r squared, and the big area is pi big R squared times that current that we talked about with the displacement current. Now, same as before, we go around the circle, and so this is B times 2 pi r, and then this is going to be U naught. And what I'm going to do is, you can see the pi's cancel. So we have R squared over big R squared times I. And so that means B is equal to U naught R squared over R squared times I divided by 2 pi little r. And so that means that finally we can say our B field, one of these r's cancels. And so this is U naught I little r over 2 pi big R squared. And I want to show you, before I hand it back to Kristen, which I'm going to do in just a second, I want to show you something interesting about this answer. Notice that the constants, and everything is a constant except for little r. And what does that mean? Why am I pointing that out? That means that as we go from 0 to my value of big R, that's my little r. As I go all the way out, the current, the B field increases linearly. And we see this all throughout the problems we've done all year in Physics C. That when we have this uniform field that we then integrate through, we get this linear relationship again. So isn't the universe a beautiful place? It sure is. I'm talking too much. Kristen, take us home.
No, that's great, Roger. I think it's awesome to link it back. And yeah, when we have a uniform charge, we're trying to graph the electric field as we go out to that radius. Yes, it's that same relationship. And so we see it again and again. It's really cool. Okay. We're gonna finish off with one more problem. This is not really Maxwell's equations, but we are wrapping up magnetism. And so I just wanted to do another one that I like to do, and that's another moving bar problem. But we're gonna push it just a little bit more today into add a little bit of calculus. So I know you guys are missing some of your harder physics problems. So we're gonna take care of that today. Not that it's harder, but you get to flex your calculus muscles. So I have a parallel conducting rails separated by a distance of L. So we're just gonna leave all of these as variables for today. And they're connected by a resistance R and a magnetic field T directed vertically upward that exists between those rails. A bar of mass M is set on the rails and can slide without friction. So the bar is given a momentary push, so that it has an initial speed of V naught at time 0. So if we look at what's happening here is that if we have this bar that's sliding across these rails here, and those charges are going to be moving, remember we're going to have that separation within that bar of those positive and negative charges. And we derived a relationship for how we could find what that current induced in that rod is. And so we got that EMF is equal to BLV. And real quick, I'm just going to run through it one more time to make sure that we feel good about it. So as these charges are moving through this magnetic field, moving charges are going to experience magnetic force. So positive charges, if we use a right-hand rule, if the velocity is to the right, magnetic field is up, then they're going to experience force one way, and the negative charges will experience force the other way. And we create that separation of charges within that bar, which is going to create an electric field. And so those charges are going to move until we have a balanced out electric force on those to the magnetic force. So remember, we could say that QE is equal to QVB. Our Q's canceled, and we could say that E was equal to V times B, but E is V over D. So we rearrange and we get what that induced EMF is BLV. But I want to know what the current is. So how can we relate the induced EMF to the current? Well, Ohm's law. So I can say IR equals BLV. If I want I, I'm going to divide, and so I equals BLV over R. And so part 2 says the net force on the bar. Oh, wow, let's talk about the direction of that current too, right? So which way would the current be? Well, if this bar is sliding, remember we want to look at what is happening to that flux, right? So if we know that the flux relates to B times A, well, if this is sliding and that area is increasing of my loop, well, then we have an increasing flux. And if that magnetic flux flux is increasing, then we know that we have to create a magnetic field that is going to oppose that change. So if that field is upwards, then we need to induce a current that is going to create a magnetic field pointing downwards. The only way we're going to get that magnetic field pointing downwards, if I'm looking at my loop, if I want a downward magnetic field, my fingers are pulling around in a clockwise manner. So that current will be going down through the bar this way. Okay? And then if we want to find what the net force on that bar is, then we can say if we're using rightward as being positive, okay, then we know, well, what is the force that's acting on that bar? The force that's acting on that bar is the magnetic force. But the magnetic force is opposing that motion, going the other way. And so we have to say that it's negative, and we can use the right hand rule to see that too, but it's going to be negative I, L, V. Okay? But I want all of these in terms of V, right? So I'm not done here. I got to plug in somehow that I can get V in here. Well, I just solved for I. That's another rule, right? Once we solve for something, we can't just not use it anymore, right? Once I solve for what I is, I can't just leave it as I. Here's the problem. So we can say the magnetic force is equal to my I, which we just discovered was B L over R times V, and where L was capital L times V. And so then we get then that the magnetic force, the net force on the bar is negative B squared times L squared over R times V. Okay? So if we use that right hand rule with the current, we know the current is going to the right. We can also see that that force on it is going to be to the left. Okay? Next we got what is the speed of the bar as a function of time after the push. Well, if we're looking at how the speed is changing as a function of time, that always going to tell me I need to go back and be able to put in some kind of relationship with that force and the velocity. So we know in general that net force, since we found net force here, net force is equal to ma. Well, our net force is that B squared L squared over R times V. That equals ma, but I don't want things in terms of a. I want them in terms of how the velocity is changing. So what can we put in for acceleration? Well, the definition of acceleration is it's the derivative of the velocity. Okay, so I'm going to rewrite this off to the side because we're probably going to need a little bit more space. So I've got that B squared L squared over R times V equals m times dv over dt. Okay, so if we want to solve for the velocity as a function of time, well, we've got to separate our variables, right? So if I want to bring my v with my dv and everything else with my dt, then I'm going to end up with dv over v is equal to my B squared L squared over R times my m still times dt. And really truly we still have that negative, which I should have been carrying through here. Okay, well, dv over v is going to give me the natural log of v equals my negative B squared L squared over m times R dt. And when I take, oops, we're left with just t here. And then if we want to solve for v, I gotta get rid of my natural log. So I'm going to say this is and still plus a c. So if I take this to the e, then I get my v equals c times e to the negative B squared L squared over mr r to c times my t. And so we look at the constant. So at time equals 0, what was our velocity? We gave an initial push. It had an initial velocity of v naught. So really our constant is that initial velocity. So then we get that v is equal to v naught times e to the negative B squared L squared over mr times t. So some good math in there, some good physics in that one. And then the last one, what is the power dissipated in the resistor as a function of time? So we have lots of equations we can use for power, right? We know that power equals I times v, or we can use Ohm's law to substitute in to get rid of I or v. But also, if we're thinking forces here and we're thinking velocity, I also know that power is force times velocity. So I can say, well, power equals, I know my force is B squared L squared over R times v. We found that in part 2 here, times v. And so really this becomes v squared. And if we want this as a function of time, well then I've got to plug in for what we just solved for v instead of leaving it as v. So when I plug in that for v, I get that the power is equal to B squared L squared over R times my v naught e to the, and since this is v squared, this becomes 2, negative 2 B squared L squared over mrt. Big long answer there. So that's a good challenge question for us to wrap up magnetism with. We are now done going over that new material. We have finished out the year for E&M, so you have a nice basis when you get to your advanced classes. We are now going to get to go into review and go over the year of E&M. So today you were able to see how that changing magnetic field induces an electric field and vice versa. We looked at an application of Maxwell's equation, and here's a sneak peek of what we're going to do next week. So make sure that you are joining us, and we are going to first talk about on Monday the electrostatics, charge, and Coulomb's law. And on Tuesday we're going to do how we can induce charge, polarization, electric field, drawing those field lines. Wednesday we're going to get into looking at the electric field due to a point charge. We're going to talk about Gauss's law on Thursday, and we're going to look at some other charge distributions on Friday. So there is the schedule for you for next week. If you want, you can see the whole rest of the schedule for the month on the College Board website. You should have it on there, and you can kind of plan out when you want to join us. So Roger, you want to say goodnight to everybody and take us out?
Yeah, well, I just want to say to you guys, thanks for another great week. It's just so much fun to get to work with you. We hope this is helpful, and can't wait to start reviewing, getting you ready for the exam starting on Monday.
Yeah, so everybody have a great weekend. My name is Kristen Gonzalez-Vega, and I am coming to you from Frisco, Texas, and today we are again doing AP Physics C, Electricity and Magnetism. I have my teaching partner with me, Roger.
Hello, everybody. This is Roger Siegel coming to you from Sarasota, Florida, where I teach physics and calculus at Pineview School.
All right, so tonight we have a very fun lesson. It's one of my favorite lessons to do. I wish we were in my classroom to do more, but we're going to talk about how we induce charge, polarization, electric fields, and field lines. So it's all kind of conceptual today, and lots of fun. So again, my name is Kristen Gonzalez-Vega, and we also have Roger with us from Florida. I wanted to go over a couple of things about the AP exam that we have learned. First of all, the date. Our AP Physics C is going to be on May 11th, both the mechanics and the E&M if you're taking both. The E&M is in the morning, and the mechanics is after that. And you can see the times here on the screen for those corresponding time zones. As far as the timing goes, you're going to have 45 minutes for the exam. There's going to be 2 questions. You're going to have 25 minutes to read or respond to question 1, and then you'll have 5 minutes to upload your response. You're going to be able to either type up your responses or handwrite and submit those responses that you have handwritten. So after that time, you're going to move on to question 2. And question 2 is a 15-minute question with again another 5 minutes to upload your response. You cannot go back to question 1 after that time is over, and everybody is going to be taking it at that same time. A little bit more on those questions. Question 1, since it is a longer question, is worth a little bit more. It's 60% of the weight of the exam. And question 2 is 40%. The 2 types of questions, we have a long free response and a short free response. That long free response, you should be able to analyze representations of physical situations, determine scientific methods, analyze quantitative data and in graphs, and develop an explanation or scientific argument. So that kind of gives you an insight on what kinds of things you can expect on question 1. It's going to have an emphasis on the physics C, electricity, magnetism concepts, and not as much focus on the calculations portion. So we're going to start incorporating a lot more of the conceptual type questions as we're doing this review, and you're going to see less and less of those calculation type questions. One example you can look at for this type of question is question number 3 on the 2017 AP Physics 1 exam. Question 2 is going to be a question that's going to assess your ability to design an experiment and design and evaluate a lab experiment. Use graphical analysis of data to find physical quantities and identify physical sources of experimental variation. And that's going to be similar to question 2 on the 2012 E&M exam. So the units that are up for grabs on this are anything between 1 and 3. So that's electrostatics and Gauss's law. It is potential and capacitance, and it is circuits. So today we are going to go through in electrostatics how we can charge objects. You should be able to draw an electric field diagram from a single point charge. You should recognize that excess charge on a conductor resides entirely on the surface. That is a super important concept. Describe the process of charging a conductor by induction. Describe net charge residing on conductors during the process, and explain how a charged object can attract a neutral conductor. So if we look at these different types of charges, I'm going to give you kind of the basis of it, and then we're going to kind of go through and look at some examples. So we have 2 different kinds of materials. We have conductors and we have insulators. So in a conductive material, those electrons are free to move throughout the material. An insulator, those charges are fixed in one place. Right? So when we have 2 uncharged objects, let's take a balloon and a piece of hair. You can take those 2 objects and you can rub them together, and that friction between them will take electrons from one material and deposit them on the other. And there are some materials that tend to want to give up electrons, and there are some materials that tend to want to gain electrons. So hair happens to be a material that wants to lose electrons, and balloon or rubber is something that tends to want to gain it. So when I rub these two together, this is charging by friction, and they're going to become oppositely charged. Okay? And so I could then bring this again close to the hair, and I don't know if you're able to see this, but you can see that hair kind of raising up towards the balloon. So you can see that they have become oppositely charged. So that's charging by friction. That's one way that we can charge objects. Another one that we can do is charging by conduction. And so this is when you have an object that is charged, like my balloon now has a negative charge onto it. If I touch it to another conductor that is neutral, then some of those electrons will jump onto that material. Right? Those electrons don't want to be close together. They want to be spread apart. So if I can give an outlet for those electrons to go, they will go. We can charge by induction. And induction is when you bring a charged object close to a neutral object, not touching it though. And so that's going to cause a separation in the material, right? So if my balloon, let's say a metal sphere, and I bring a charged object towards it, well, we know the hair is positively charged. So that means all of those negative charges want to be close to that positive charge, and the positive charges want to be away. So it's going to create a separation of charge in that material. If I bring another balloon close to it and touch it, then again, it'll give an outlet for those charges to move. And so those electrons can come in or go out depending on those charges. So even though those two conductors are touching, my actual charged object never touched it. So that's charging by induction. And then lastly, we have polarization. And polarization is when you have a charged object that's brought near an insulator and the atoms shift. So my wall, and I'll show you this with water in the video, but my wall is a little bit textured, so this doesn't work as well. But what you can see is the balloon goes slowly down the wall. I have a projector screen in my classroom that's really good to actually stick to it, but we can see if the balloon will stick to it. If it not stick to it, you'll see that it'll kind of slowly coast down the wall. Ooh, hey, it worked. Okay, so this is polarization. Now the wall is not a conductor, but the wall is made up of atoms that have positive charges and negative charges. So while my balloon has those excess negative charge, well, the atoms can shift in the wall where those positive charges will want to be close to the negative charges, and the negative charges will be further away. So it creates that kind of separation of charge within that insulator where it's not charged, but there is that temporary attraction to it. Okay, so I have another simulation to show that too. So I'm going to switch my share here. And so I have a simulation. I have a neutral sweater. I have a neutral balloon. And I have a neutral wall. Right. So if I take my balloon, I rub it on the sweater, as you can see, we're picking up those negative charges onto the balloon. So the balloon is now negatively charged. My sweater is positively charged, just like my hair balloon that we saw a second ago. If I let the balloon go and it's close to the sweater, what's going to happen? It's attracted to that because it's absolutely charged. If I bring my balloon close to the wall is an insulator. Those electrons are not going to actually transfer through the material, but you can see we get that separation of charge in the wall here. Those positive charges are close to the negative charges are further away, and we get that attraction between the wall and the balloon. That's the polarization part. Right? So we had charging by friction, and we had polarization there. So if we go back, let's kind of draw some of this stuff out. So if we have two metal spheres, and we have them far apart, sphere X, sphere Y, and they're far apart from each other, and they are both at the moment neutral. But I'm going to bring a negatively charged rod close to that sphere X. I want you to think about what that's going to look like. If you have paper, I want you to get that out, and I want you to sketch what you think those spheres are going to look like as I bring that negatively charged rod close to it. I'm going to switch over here to my iPad so I can actually draw it out better. So when they're far apart, well, let's zoom in here. I've got positive and negative charges. I'm going to draw like 3 positive charges and 3 negative charges on each one. And as you notice, those charges are spread out, and we can't really see it here on the screen. But where those charges always lie on the conductor is on the surface of material. So there's never going to be any charges in that space in the center of the conductor. It's always spread out through the surface. It can be the inside surface or it can be the outside surface, but never in the space between. In an insulator, those charges can be distributed throughout evenly, or we can have different charge densities. But for the conductor, remember, it's always on the surface, outside surface or inside surface, and both. So if I bring that negatively charged rod close to it, these are still far apart. That's not going to affect sphere Y, right? So sphere Y will still have positive and negative charges. But if we look at sphere X, those negative charges don't want to be close to that rod. So those negative charges are going to run away. I mean, I say that like they're actually people. We know they're not. But those charges are going to separate out away from that rod, and the positive charges do like that negative charge. So those positive charges will shift to the left side, still on the surface of that sphere. Right? But then we can touch those two conductors together. And since they're conductors and those electrons are free to move, they sure are going to move. So those negative charges want to be as far away as possible from that negatively charged rod. So all of those negative charges are now going to lie on that right side of that furthest away sphere, which is going to leave us with a net positive charge on the other sphere. Right? It's the negative charges that are doing the moving, but since the negative charges are leaving the other sphere, there's now a net positive charge left. Okay? And then if we take sphere Y far away, still leaving that negative rod close to it, what are we going to get? Well, we're going to get still all of those positive charges on the left there, and we're going to get the negative charges on the right. But where are those charges going to be? Since this far away, those negative charges don't want to be close, they're going to spread back out on the surface of that sphere. And then we take that negative charge sphere away, and now we can have that evenly distributed positive charge too. So we get two oppositely charged spheres in the end. Right? So this is charging by induction. We never actually touched that negative rod to the sphere to transfer the electrons between the two, but we did touch those two neutral atoms together, neutral conductors together, and end up with those two oppositely charged ones. Okay? Let's see what happens if we introduce a ground. So what a ground is a way to create a path for those charges to flow. And on your house, at least here in Texas, I'm sure everywhere, we have, if you look around your house, you will see somewhere on the base of your house a little green wire that's running from the house into the ground. And that's got to go like 6 feet deep into the ground. And what that does is it grounds out all of your wires in your house. And so if we introduce this ground, then we can look and see what's going to happen. Right? So we have the same thing kind of here to begin with. We have our negatively charged rod that's brought close to these two spheres that are touching. So again, we're going to get positive charges here, and we're going to get our negative charge sphere on the other side. Okay? So if we connect that rightward sphere to the ground, then we're allowing for those charges to be able to leave or come in. Right? We can also have negative charges coming in, we can have negative charges going out. In this case, since we have this negative rod, those negative charges are going to want to leave. So they can go out the ground, still leaving our positive charges here. Okay? So we remove that ground away, and we're left with all of those positive charges close here. And then if we take that negatively charged rod apart, then we have those positive charges that are going to equally spread out. And we separate them, they spread out on the surface. And then we're going to bring them closer back together and connect the ground out to the left side. So the positive charges are not going to flow out, but the negative charges can flow back in. So if we look at that one on the left, we're going to have our negative charges coming in through that ground, and we're going to still have that right sphere. It's not touching anymore, nothing's going on. That still has a positive charge, and that positive charge wants to be close to that negative charge. So introducing that ground allows for those electrons to flow either in or out of your material to create those neutral or same potential of the objects. Okay? The other thing we can look at is an electroscope, and I'm going to stop my share here, and I'm going to move my camera so that we can see I built an electroscope. Okay? And we can see that there are 2 aluminum foil leaves here. I think that's the best way view there. And so I have 2 foil leaves. It's connected to a copper wire that comes out and goes around here. So we have one nice kind of flow here. Back a little bit so we can see a little bit more of it. And so I want to see the leaves really close. So what I'm going to do is I'm going to take my PVC pipe here, and I have some fur that I'm going to charge up that PVC pipe. And so you can see now those leaves and everything is neutral, right? All right now there's no charge on anything. If I bring that PVC pipe close to it, back up so you can see, I'm not touching it. I'm only bringing it close to it. You can see those leaves start to separate. And so the reason that it's doing that is because even though it's neutral, there are still positive and negative charges in that metal. And so when I bring the negatively rod close to it, then those electrons want to go far away. So where do they go? They go down to the leaves and the electroscope here. And so when the electrons go down to those leaves, they want to be together, so those leaves leads are forced apart. So we can use an electroscope for lots of different things. We can tell what the charge on an object is. We can induce a charge on the electroscope and test out different things. So let's look at a diagram here. So we've got our electroscope, and as you can see, those leads are spread apart, which means that electroscope has a charge. If I bring a negative rod close to it, we want to know what charge did that electroscope have to have in the beginning. In order for those, you can see what happens to those leads. Do those leads get close together, or do those leads spread further apart? Well, if we compare the leads here to the leads here, well, these leads have spread even further apart. So I want you to think for a second, what charge does this electroscope have to have on it in order for those leads to spread further apart? Anybody know? Yeah, it's negative. I know you're all saying it at home. Because if we have, let's say, a net negative charge on the electroscope, well, if I bring this negative rod towards it, well, they want to go even further down here away from that negative charge here. So there's even more negative charges on those leads. So they have a further force, right? Remember, force is related to, if we have 2 point charges, K2 over R squared. So the more charge we have building up on that object, the greater that force between those two leads is going to be. Okay? So we remove that rod and it goes back to normal. So we bring a positive rod close to it. So why does when we bring the positive rod close to it, why do those leads now go closer together? Well, when we bring the positive rod towards it, we have some of those negative charges that are going to want to be close to that positive charge. And so we don't have as much charge left on these leads. So there is still some repulsion. You can see there's still some separation between those leads, but it's not as much because there's not as much, there's not as much negative charge left on the leads themselves. Okay? And let's look at just one more thing here. We have an uncharged electroscope. And so what we're going to do is we're going to make a positive rod towards it, then we're going to touch the electroscope with our finger, and then we're going to put the finger away and then remove the rod and look at the leads. So I want you to think for just a second at what you think the flow of those charges would be in each of those steps, right? What would the charge distribution look like in the first step? What would that charge distribution look like in each of these steps? So give me just a second here to think about it. Okay, so we know it's uncharged. So that means there are positive and negative charge evenly distributed throughout here. Okay, so there is no force of attraction or repulsion between those leads. They're just hanging there due to gravity like mine was right now. But we bring that positive rod towards it and those leads separate. So what does that mean? Well, that means that I have electrons moving up close to that rod on that metal top part. For me, it's a little cute curly cube here, but a lot of times you'll see like a metal sphere on the top of an electroscope. So negative charges are building up here. What do we have left then? Well, we have a net positive charge on the leads. And so those leads repel because they have a net positive charge on it. But if we go in this next step, if I introduce my finger here, let's kind of use this diagram. If I touch now the top of that, well, now I'm giving a path, right? That's for the electrons. So electrons can either flow into or out of. Well, if I have a positively charged rod close to it, what do you think wants to happen? Do you think the electrons want to leave? Well, no, they like being close to the positively charged rod. Those electrons are attracted to that. So that'll give a path for electrons to enter into the electroscope. So now we have electrons on here. So if I take my finger away, I have more electrons, but they're still built up close to the top. But if I take my finger away, we have a net negative charge left on the electroscope. Okay? So again, we have charged it by induction by touching that sphere when that positively charged rod is close to it. Okay, so I've got one more thing to show you here. I was playing around outside with my girls today, kind of showing them this. So we took a video, and it's not like as good as I usually can get it in my classroom, but you can still see here the example of polarization, because we all know from chemistry that water is a polar molecule, right? So if water is a polar molecule, we know it's made of hydrogen and oxygen. It has a partial positive and a partial negative side to it. So you'll have to excuse my quarantine attire here, my t-shirt that I rock every day. But I'm going to show you these two different views and see if you can notice what happens when we bring that charged rod towards that water stream. What do you notice? You notice that water bending around that rod. And that's because you have a shift in those molecules, and you have that positively charged hydrogen that likes to shift towards that rod, and you have those negatively charged oxygen molecules that want to shift away. And so you get that kind of curve in the water, which also helps us to see that polarization. One more time. All right. So the other thing we're going to talk about now is electric field. So around these charges, we have a region of space, right? And we call that what around those charges there is an electric field. So if we think back to gravity, around any massive object like Earth, we have the gravitational field. Well, the same thing will be true around charges. On charges, we have an electric field. So what happens when we have a mass that's introduced somewhere where there's a gravitational field? We'll experience a gravitational force, right? Well, if we introduce another charge into a region where there's an electric field, it's going to experience an electrostatic force. So the way that we draw these field lines is they always are going from high potential to low potential. We'll talk about potential later, but really what that translates to is those field lines point away from the positive charges and towards the negative charges. We draw together, they are, meaning the greater the electric field, the further or the less, or the further away the charges are, the smaller the electric field. The more lines we have, that means the greater the charge, and the fewer lines means the smaller magnitude of charge. So if we look at some examples here on the left, we can see what the field lines look like between two oppositely charged atoms or molecules. We can look at what it looks like if they have the same charge. So if it's positively charged, you can see all those field lines pointing away in all directions. And you can see where there's no field lines here at all, that's where the electric field would be zero. Okay? We can also look at the electric field between two parallel plates or between a parallel plate and a charge. Sorry. Okay, so those field lines point away from the positive towards the negative, and we can map out those field lines, and then we can also talk about what potential field, the potential lines would look like too with those, which is kind of what those dotted lines are. But we'll get into that a little bit more later. Okay, so here's a couple more. So what I want to know is A, what is the charge on each of these charges, magnitude-wise, positive or negative? And also, one of these has a greater charge than the other in each example. So can you tell me what the charge is, positive or negative? And can you tell me number one and number two, which one has a greater magnitude of charge? So take a second and look at all four of those diagrams. Okay, so if we look at the first example here, first we want to look at which way the field line's pointing, right? So if we look at these field lines, they're pointing away from charge number one. That tells me charge number one is positively charged. And they're pointing away from charge number two. That tells me it's positively charged. If I look at the number of field lines, look at how concentrated these field lines are very close to that number one. There are a ton of lines really close together. That tells me that charge one has a greater magnitude of charge than charge two has. Okay, if we look at the second example here, now the field lines are pointing towards both those charges. So those are going to be negatively charged. And again, charge one has a whole lot more lines coming out of it that are going into it than charge two does. So it has a greater magnitude of charge. And if we look at the bottom, hopefully you'll recognize that charge one is positive and charge two is negative. And we can look at the number of field lines and see that number one has a greater amount of field lines around it. And then the last example, we can see the field lines are going away from charge two and pointing towards charge one. So charge two is positive charge and charge one is the negative charge. Okay, so I'm going to turn it over to Roger. I talked long enough, and Roger's going to go over some examples with us.
All right. Thank you so much, Kristen. You're right. This is one of the most fun units to teach, static electricity. I really do love it. All right. Well, let's take a look and see where we are. I'm going to start sharing my screen. Don't want to make that mistake. And so I'm going to be working in OneNote here. And so we just got through here looking at the electric field lines. Now, I love being able to look at these concepts and kind of compare them with the gravitational field. We'll talk about that more later. All right, so here's our first problem. I think you're going to find this one's pretty easy. And so what we have is we've got these two metal spheres. They're initially uncharged. And of course, they're sitting on these insulating rods. And now a negatively charged rubber rod is brought close to it, does not make contact with sphere X. And then we're going to take sphere Y and we're going to bring it close to the opposite side and let it touch. So I'm just going to connect these for a second. And imagine I'm connecting them with a wire. That's a stand-in for having this touch. And what's going to happen when that happens? Well, let's go ahead and kind of draw that whole thing out if we can in a series of steps. Okay, so the first thing is what we have is when I bring this negatively charged rod near this metal sphere, a lot of negative charges are going to go here to the other side, and that's going to leave the left side acting positive. And why is it positive? Because all these electrons that are free to move in this in this setup got as far away as they could. So the electrons here moved to the right, and what they did is they left this side with fewer electrons, which that made that side positive. Now the next thing that happens is, let's say we'll connect them with a wire and or touch them. It's the same thing if we connect them with a wire. Now these electrons before the wire was here, the furthest they could get away from this was this far, but now look at what they can can do, they can start to migrate. And so those electrons are going to start going even further away. And they're going to, again, move all the way to the right. And so now what's happened is we've now left, now we've got excess positive charges on X and excess negative charges on Y. All right, and then what happens next is the rubber rod is now moved far away. So we're going to remove the rod, take that away. And we'll go ahead and stop the spheres from touching. And so we'll go ahead and break that so they're not touching anymore. And so now the question is, what is the charge on each sphere? And so we can see the X is a positive charge, so one of these two, and Y is negative, which means it has to be that. Okay. So again, thinking about what the charges are doing, what's causing them to do that, that's what we want to leave you with. We expect a lot of conceptual questions on your AD exam this year. All right, now this one I really love. I'm so glad we have it tonight because, and we're going to continue looking at this concept, but this is the first night we're going to get to it. So we've got this charge of Q plus on a small sphere. There's my charge of Q plus, and it's lowered into this metal. It's a metal can, but it's insulated. So the metal only goes to here, and then the electrons can't go. If the sphere does not touch the inside of the can, there will be a charge on the outside of the can. What? Okay, so this requires us to draw a picture, and so I'm going to draw a picture of my can, but I'm going to emphasize the fact that the can has an outside surface and an inside surface. So I'm really super emphasizing this, right? The thickness of the can. And inside of this can, we've got a positively charged sphere. Okay, we'll go ahead and put a plus charge there. All right, now this can is metal. It says it's a metal can, and that means it's a conductor. That means that the electrons that are associated with the atoms of the can don't have to stay with those electrons. They can, with those atoms, they can move anywhere they want. And so what I'm going to do is I'm going to draw a little line that's going to delineate the outside from the inside of the can. Now you might argue, well, what about, where does the outside stop and the inside end around here? We're not going to split any hairs over that. Now, one of the properties of a metal is that we can't have any electric field inside the metal. Now, if I just had this positive charge and there was no other charges, well, the electric field would go right through that metal if there were no other charges. But that's not what happens because there are other charges. And so what's going to happen? Well, since there's a whole lot of negative charges here to be had, right? There's no shortage of negative charges because they're electrons. They can go anywhere. And so what's going to happen is we're going to get a bunch of negative charges to kind of move to the inside of this can, to the inside surface. Now, the can started out as neutral. It started out with no charge. So what that means is in order for the can to remain neutral, it has to have a positive charge on the outer surface. And so there's a positive charge that's now all around this outer surface. Now, if we look at the entire can, if you just look at the can, and I'm going to go ahead and I'll erase this in a minute. I'm going to draw this kind of with a big hand. Okay. If you look at just the can, it's neutral because it has equal numbers of positive and negative charges. And if you look at the inside of the jar has now also been made neutral. And so that is because we have positive and negative charges. So let's back out for a second and see. The question originally said, if the sphere does not touch the inside of the can, there will be a charge on the outside of the can of what? And that charge is going to be Q plus. And the reason I know that's going to be Q plus is because we're going to have Q minus. All of this together, all of these guys, they all add up to Q minus, which means these all on the outside add up to plus. Isn't that beautiful? Okay. I think I've got one more here, and then we'll throw it back to Frisco, Texas. So we have these field lines from 3 different charges. And so the first question asks us, what is the sign, the SIGN, of each of these? So I'm going to go ahead and take a look at that. Now we know that the electric field around a positive charge, the field lines point away from positive charge. And if I have a negative charge, then the field lines point toward the negative charge. So all I have to do is look and see where the field lines pointing toward. And so 3 is going to be a negative charge. That's going to be negative because it has field lines pointing towards it. And 1 and 2 are going to be positive charges because they have field lines pointing away from that. So that's both of these are positive. Okay. Now the next thing that we're going to do is we're going to draw vectors at each point to represent the direct direction of the electric field at that point. This is going to be pretty easy because the electric field is always parallel to the field line at the point. So if we start with A right here, if I look at this field line and this field line, I can pretty much estimate that the field lines are in that direction at A. Okay. And I could then look at B and this one, and so the field line again is the electric field is parallel to the field lines. At part C, that would be here. I'm not going to draw it right over the C because I won't be able to see the letter if I do that. But there's a field line there that's near the C. Okay. And then D is in this direction. There's D, and then E is in. Let me a little bit off there. And E is in this direction. So the direction of the electric field is the direction of the field lines. Okay. So we got that. Now mark X in a position where the electric field is 0. So the electric field is 0, where the positive and negative vectors cancel out, and you can see that happens about right in this area. So I'm going to go ahead and put an X there, and that's the spot where the field lines are 0, or the electric field is 0. So if I could put a charge there, it wouldn't feel a force in any one direction because all the field lines perfectly balance and cancel at that spot. Which charge has the greatest magnitude? Well, the way we get the magnitude of the charge is, remember, these lines are a stand-in for a density function. It's not like we have there's electric field, there's no electric field, there's electric field, there's no electric field. No, there's electric field in a continuum around here. But by drawing the field lines, it allows our human brains it's a code for something. And so here, the closer the field lines are, that's code for how large the electric field is, the magnitude of it. And so if we look at this, if I put a little mark here and I go around, I can see that we have 1 starting there, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 arrows around this circle. Okay. And so I'm just going to put a little 24 there next to 1. Now I know that this isn't very much. 1, 2, 3, 4, 5, 6, 7, 8. There's only 8 around 2. But 3 looks like it could have close to 24. Let me put a mark here and count. 1, 2, 3, 4, 8, 9, 10, 11, 12, 14, 15, 16. So that's 6. So the largest magnitude charge is charge 1, and the smallest magnitude charge is charge 2. Okay. And then what letter point is the field the strongest? So the field is going to be the strongest where those lines again are closest together, are densest. And so I think if I look, it looks like it could be 2 places. I'm going to highlight each place. It looks like it could be C. You're pretty close there, or it could be B. And I got to say, it looks like B is denser than C. So I'm going to go ahead and put B is the place where the field is the strongest. I think that's going to get us there. So these field lines tell us a wonderful story. As Kristen said, tomorrow. Let's see. I forgot one more. I almost better wrap it up, and I got more to do here. In what direction would the force on a proton be if it were placed at E? So let's take a look at it. So the field line tells us the direction of the force on a positively charged object. So a proton is a positively charged object, and since the field is in this direction, then the force on a proton would be along the line of the field, not the motion, but the force or the direction. If you might think about that, the direction of the acceleration. And now it says the next part. Oh no, that's not good. We are going to pause for a second and let my OneNote catch up. And I think Kristen, are you ready? Because I'm having technical issues, so I think we can hand it back to you.
Yeah, I am.
Okay, thanks.
So we're going to do one more example here to wrap it up for tonight. And I have kind of been looking through physics 2 problems that are good to use. So they gave us a physics 1 problem for kind of to show us an example of the type of question. So I've been kind of looking for some conceptual physics 2 problems, and I found this one that I think is still good for physics concepts. So we have here a sphere. I'm going to zoom in on the word so you can see there's a sphere hanging from a string. This is sphere 1. And we're investigating electrical charging of objects. So we have our conducting sphere that's suspended from an insulating string. We're going to rub the sphere with a cloth to charge it. And we want to determine if the sign on that charged sphere is. So we also have conducting spheres of various size that can be also hung on strings. And we have a pair of parallel conducting plates, each of which can be given a positive or a negative charge. So we want to describe a procedure the students could use to determine the sign of the charge on the sphere, including the measurements to be taken or observations to be made, right? So we want to know what the charge on this guy is. We have this other stuff, what can we do? Okay, so I'm not going to really pause just for time's sake tonight, but if you are going back and doing this, which I suggest you do if you're watching live, or if you're not watching live, take a minute to pause this and see if you can come up with a procedure on how you would determine what the sign of the charge is on sphere 1. So I'm going to say I'm probably going to use the parallel conducting plates. You can use the conducting spheres too, but I like the plates. So I'm going to take my plates and I'm going to put my sphere down into those plates, right? We know they can be given a positive or negative charge. So I'm going to connect those plates up to a power source, charge those plates up so one side's positive and one side's negative. Well, since that sphere is charged, it's going to be repulsed or attracted to that other side. So I look and see, well, if I put this sphere into it, does it deflect away from the positive side and towards the negative, or does it deflect towards the positive side? And we know if it deflects towards the positive side, then it's got to have an oppositely charged charge. So it's got to be negatively charged. And if it deflects towards the negative sign, then that's got to be positively charged. So I'm looking for which way it deflects, and it will be, then that means it has the opposite sign. Okay, so then we want to know whether the same amount of charge is deposited on the sphere each time we rub it with the cloth, right? So I rub it with the cloth, I get a little bit of charge. Q. I rub it in the same way that I rubbed it before. Does it now have 2Q? Right? We want to know, does the same amount of charge accumulate on there every time I use that cloth? So we're going to carefully rub sphere 1 with the cloth, the same motion each time. Then we're going to touch sphere 1 to an identical sphere, sphere 2. So we're going to introduce a second sphere here that's fixed in place. They then release sphere 1, and as you can see, the sphere 1 is going to be repelled up at some angle away from sphere 2. The students are going to measure the angle theta that the string makes with the vertical. They discharge the spheres and repeat the process each time, counting the number of times they rub sphere 1 and making sure the distance d between the spheres is the same. Okay? Each time sphere 1 is rubbed with the cloth, the same amount q of charge is deposited, and that after n number of rubs with the cloth, the net charge on sphere 1 is n times q. Right? So we're going to accumulate n times q amount of charge. So we want to know what is the net charge on spheres 1 and 2 after they have been touched together. Indicate what property of the spheres is responsible for the distribution of charges. Right? So I'm starting with n times q amount of charge. I touch them together and then separate them back out. So what would be the charge then on each one? Well, the charge is going to flow until they reach the same potential. Again, we'll talk about that again. But the other way you can think about it is look at the surface area of these spheres. We know charge wants to evenly distribute out across that surface of the conductor. So if these had, let's say, different sizes, if one conductor was much bigger than the other, well, I could spread more charge out on the bigger conductor than I could on the smaller conductor. So if we touch them together, then that charge would flow until they reach the same potential, but the charge 2 would end up having a greater amount of charge on it. But these two spheres are the same size, and so if they're the same size, then they are going to end up with the same amount of charge on each one. Okay? But we can't have more charge than we had to start with. So if we started with q times n amount of charge, then that means that each one would have half of that amount of charge. Okay? So what property is responsible for that? Usually you can talk about the surface area. Since they have the same amount of surface area, those charges are going to spread out evenly and each have the same amount of charge. Okay? The next part, we want to show that the angle can be related to the original charge q on sphere 1 by the equation that the tangent of theta equals k n squared q squared over 4m d squared times g. So if we look here, that comes back to those forces, right? If I look at sphere 1, well, there's a force down because it has weight. It has a tension up because of the string, and since these are being repulsed, there's a electrostatic force pushing away from sphere 2. But once it reaches equilibrium, well, we can look at what those forces would be in relation to each other. Once in equilibrium, we know that the write it down here a little bit. We know that the tension can be broken up into its x and y components, and so I know that the y component tension up has to balance out that weight down. So that would be, well, since theta is up in the corner here, that would be ft times the cosine of theta equals mg. And I also know that the x component of that tension has to balance out the electrostatic force. So ft times the sine of theta has to equal ft. Right? Well, I don't like tension in there, so I got to get rid of tension. If I rearrange equation 1 for tension, then ft equals mg over cosine of theta, and so then mg over cosine of theta times sine of theta. Well, sine over cosine is tangent, so this leaves me with mg tan theta equals, we know the electrostatic force, we learned that equation yesterday, Coulomb's law, is k q1 times q2, and each of those charges is n over 2 times q. So really, it's n over 2 times q squared, because they each have that same charge, divided by our distance squared. And so then if we rearrange for tangent of theta, then tangent of theta will equal k times, now this becomes n over 4, which really 4 can go on the bottom, times q n squared times q squared over 4 times d squared, and then to bring the mg over, we divide, so times mg. So now we've got this relationship that we can use. And what we want to look at now is something that we have to do a lot in physics, and that is say, well, what could we graph in order to determine something we don't know? Right? Maybe I want to know what that charge is, or maybe I want to know what the gravitational acceleration due to gravity is in that room, right? I love having my kids find gravity all different ways, but we can use this relationship to determine a constant. So if we identify these variables and these constants, the first thing I really want to discuss with you guys, though, since you guys are physics C students, and I know that when you're reading this question, you're probably asking yourself, how can they keep that distance the same if they're changing the charge and theta is changing, right? So that's the first thing that's stuck out in my head is how can we keep that distance the same? And so I am going to get rid of this d in my equation because we cannot keep that distance the same. The more charge you build up, the greater that force of repulsion is. They're going to be further and further apart. So I'm going to put in, instead of that, I want to look back at my triangle here. If this is L and this is theta, then instead of saying d, well, I can say the sine of theta is d over L. So then d is equal to the length of the string times the sine of theta. So then d squared is going to be L squared sine squared of theta. So really, tan of theta equals k n squared q squared over 4mg times L squared sine squared theta. So this is my working equation. So anytime you linearize data, you do it the same way. There are some different ways you can do it. Sometimes you can say y equals mx plus b, and you can fit to that equation. What I like to do, what I always tell my kids to do, is you identify your constants and your variables, you separate them to opposite sides, and then whatever you're left with on the left, which is the variable side, is going to be what your graph, and anything left on the right is the slope. So we're going to set this up real quick, and I promise I'll let you go. So we want to look at what are our variables and what are our constants. So what did we change in the experiment? Well, we changed the number of times we touched that balloon with cloth, which was n, right? So n is one of my variables. What else did that change? Well, the minute I change the number of times that I am charging that balloon, it's going to change that charge, which also changed theta. So we're going to say we're going to keep that tan theta together, and the sine squared theta is our variable. So we put our constants on one side, variables on the other. So if I move my variables to the left, then I'm left with tan theta times sine squared theta over. I'm going to move my n squared over, and when I do that by dividing, so I'm left with n squared on the bottom equals I'm left with k times q squared over 4mg. So everything on that right is constant. I could find anything in there. Everything on that left is what our variables are. So we go back to the rule that's always true. Whatever's on the top goes on your y-axis. Whatever's on the bottom goes on the x, and whatever's left on the right is equal to your, well, what's y over x equal? The slope of your graph. So we could graph that. And if we want to know how we could tell if it has the same charge on each, if it does deposit the same amount of charge each time, how can we know that by looking at the graph? Well, once I graph that, if it deposited the same amount of charge each time, what should our graph look like? Well, that should be a linear relationship. Okay? So that's an experimental type question. I hope you have time to go back and really pause it and go through that and try to answer it on your own, because those are the kinds of things you're going to be seeing on the exam, is being able to say, or maybe write an experiment or analyze data. And so we're going to try to practice that a lot. But we're going to get you out of here. The only other thing I want to remind you of is the rest of the week what we're going to talk about. So today we did inducing charge and polarization, electric fields, basics. Tomorrow, Roger's going to take us through how we can calculate what the electric field is due to point charges. So maybe 1 point charge and multiple point charges. Then Thursday we're going to go into Gauss's law, which is kind of a shortcut to finding the electric field. And then Friday we're going to do the other distributions, which line of charge, arc of charge, rate of charge, and how we can find the electric field, do those things. So I hope you enjoyed spending your evening with us and doing some of these fun experiments. And from Frisco, Texas, I hope you have a great night. Roger.
And from Sarasota, Florida, thanks again for joining us. Can't wait to see you tomorrow night, and thanks for playing. Physics C live. We come to you live every night at 6 p.m. for lessons getting ready for your AP Physics C exam. My name is Roger Siegel, coming to you from Sarasota, Florida. And with me tonight, as always, is my teaching partner, Kristen.
Hi guys, my name is Kristen Gonzalez Vega, and I teach in Frisco, Texas, where it is 5 o'clock.
Great. Well, thanks, Kristen. And again, welcome everybody. Really excited to have you. So we find ourselves with a whole new test, a whole new opportunity this year, and so we're excited about getting you ready for the exam. And I want to talk first about some things that we want to make sure we look at every time we do this. And so let me start off here and get my PowerPoint going here. So again, this is I'm Roger, and this is Kristen's with me. And the first thing I want to make sure you know about is the fact that this year's AP exam is different than it's ever been before. Last year, we would have had a normal year. We would have had 45 minutes for multiple choice and then 45 minutes for free response. This year, since you're taking your exams at home, we are only going to have a 45-minute total exam. Okay. So first of all, the time we've moved the date back a week, and your time is going to be Eastern time. I'm sorry, our time is going to be Eastern time 2 p.m. or depending on where you are, one of these times. Now we said you only have 2 questions. Your first question is a 25-minute question. You're going to read it, respond it, and then you're going to take 5 minutes to upload. After that, you're going to have a second question, 15 minutes, and you're going to have 5 more minutes to upload. And that's it. That's your AP exam. You are done, and that's how it's going to go down. Now, as we get closer, we're going to give you more drills and things to kind of get ready. But please stay abreast and also visit the AP website to catch up on what's going on. Now, as far as Kristen and I are concerned, our job is to get you ready for the E&M exam. And so here we are. This is our review schedule. And so far, we've looked at Coulomb's law. We started looking at electric fields and field lines yesterday. And today we're going to do more field lines due to point charges. And so today we're going to look at the field lines. We're going to define the electric field and the quantities that have to go with it. And those quantities, we'll talk about charge, force, field, and the direction of the field. And we'll be able to calculate them in an electrostatic system. We're going to calculate the electric field to a single point charge. We're going to describe and calculate the electric field due to a dipole or configuration of 2 or more static point charges. We're going to determine the qualitative nature of the motion of a charge particle of a specified charge and mass placed in a uniform electric field. And we're going to sketch the trajectory of that field, although probably more of that tomorrow. Okay, so starting now, remember last night and the night before we talked about Coulomb's law. And what is Coulomb's law? Coulomb's law tells us that if you have 2 charges in the universe, if you have a universe with only 2 charges in it and nothing else, those charges are going to exert a force on each other. It doesn't matter how far apart they are. It doesn't matter how much they are. As long as those charges are not zero, they will exert force on each other. If they're both positive, they will repel. If they're both negative, they will repel. If one's positive and one's negative, they will attract. And so this is the law and the mathematical relationship that we have for Coulomb's law. And as you can see, this is the electrostatic force. This is Coulomb's law constant, 9 times 10 to the 9 meters per Coulomb square. And this shows us a couple of things. First of all, we have this is an inverse square law, and you've seen that before. You saw it in gravity. And we can see here that as we double the distance from the object, that force is going to come down by 4. So that's something that we've looked at. That is Coulomb's law. Now we're going to talk about a field today, and I want to pivot from a force to a field. Okay, so a force is an interaction between 2 objects. You must have 2 objects to have a force. When we first teach force in physics, I don't know about your teacher, but when I first teach force for the first week, I make the students always write force of the Earth on the block. We can't write force of gravity. We have to write force of one object on another. Now later on, I'll let them draw the second subscript. But that second subscript is so important because it locks in that idea that forces are always interactions between 2 objects. If you have fewer than 2 objects, you have no forces. A field, on the other hand, only needs 1 object. And so, you may remember when you study gravity that if we have something with a mass, that it creates in the universe a gravitational field everywhere. And if it's spherical and uniform, it will have these radial gravitational field lines that show us that this mass has created this gravitational field, and we symbolize it with small g. Now, what about an electric field? Okay, an electric field, if we have a charge, say it's positive, that electric field creates around it. And where do I mean by around it? I mean everywhere in the universe. It creates a field. Now, we draw the field lines like this, and in a little bit we'll go into why we draw the field lines like this. We started this last night, and that is our demonstration, or that's how we symbolize the electric field, is by these lines. So important: a force, 2 objects; a field, only 1. Now, let's go ahead and talk about this electric field. So the electric field in electrostatics is said to exist in space near a charged object. The charge that causes the field is the source charge. To measure the electric field, or to detect it, I should say, we place a small test charge in the field. All right, so I want to show you a simulation that is going to help us to understand this, and that simulation comes from a website called PHET. And PHET is probably the number 1 stop for high school physics understanding simulations. It's really, really helpful. Now, we're going to start off here talking about how we know that we have an electric field. Now, you can see here I've put a charged particle here, and that charge is a positive charge. And I'm telling you that there's an electric field there. How do I know there's an electric field there? Well, this little charge is very small compared to the other, and it's a test charge. And I put it in the near the object, and it feels a force. And you can see that it feels a force that's away from the object. And that test charge, as I go further away, the force gets less. As I get closer, it gets more. And so that is what tells me that I have a field, is what the test charge is doing. And so the test charge is how I measure the field. It's my indication. Now, ask any physics teacher, and they'll say that one of the things that we wish in order to be able to teach this is we wish the fields were visible, that we could see these fields, that we could see electric fields, gravitational fields, magnetic fields, and you could spray an aerosol into the air and make it visible for a second like we do with lasers. Well, you can't do that, and that's why the simulations are so helpful. So take a look at this with me. I'm going to go ahead and reset the whole thing. And now I said, well, I wish I could see the field. Well, let's look at it. This is a way to see the field. Now, again, this is our best way to symbolize it. So let's see what we see here. What we see is the field is always pointing away, and the way this setup is, the way this simulation symbolizes it, the further we are away from the field, the more these fade, the less the magnitude of the force. Now we see that with this by the length of, with the test charge, by the length of the force vector. So as we get closer, you can see the force vector is stronger, longer, and as we get further away, the force is less. So that gives us an idea of an electric field. I want you to play with this and really have some fun with it. It's a very useful way to study the electric field. All right, now let's go back here and talk about the electric field for a point charge. Here's where the fun starts. This is the formula that tells us if I have a point charge and that charge is charge q, and I'm a distance from that charge, say I'm a distance x. Well, I'm sorry, a distance r. What that means is the magnitude of the electric field is given by kq over r squared. And notice that force was kq over r squared. Well, what did I do? I divided out a charge. So the units for the electric field are newtons per coulomb, and they also have the units of volts per meter. Now we'll get into that one later when we define volts. But for now, know that these are both units for the electric field, newtons per coulomb. Now this, I have to spend a minute here with newtons per coulomb because I think it might help you. Now imagine, let's look at the gravitational field analogy. If you have a gravitational field strength g and you put a mass in there, m, which is in kilograms, the units for g are newtons per kilogram. We know that near the surface of the Earth, that g is about 10. For every kilogram of mass we put in the field, we feel a force of about 10 newtons. So in the same way, if I have a charge q, okay, and that is measured in coulombs, and I have this electric field, this vector field E, which is in newtons per coulomb, well, you can see when I multiply those together, the coulombs cancel. So that is a little analogy between the gravitational field and the electric field. All right, now I wouldn't want to tell you about a new quantity like the electric field and its unit without giving you some examples of it. So here's some examples of different electric field values, and notice that they go from smallest to largest. And I love this one because if you learn anything about sharks, you study that one of the things we know about sharks is their skin is covered with electric field sensors, and so they can actually sense very small electric fields. And as a matter of fact, we're talking about 0.5 microvolts per meter. Remember, it's either volts per meter or newtons per coulomb. Here we're doing volts per meter. That's the same thing as newtons per coulomb. So that's the field by the that's a shark. The cosmic background radiation or cosmic noise has a strength of about 10 times that right? It's like about 20 times that, about 10 microvolts per meter. And we go higher and higher. The field inside a typical home is 1 to 10 volts per meter. Don't believe the ghost hunters. There's plenty of electric field in your house. And then you can see thunderclouds. We go to 100 kilovolts per meter. Notice biological membranes. You might say, well, how come the electric field in a biological membrane is so much bigger than the electric field in a thundercloud? That sounds crazy. Well, remember, this is per meter. And think about how thin a membrane is in, say, a nerve cell. It's very thin. So that's why we have such a large electric field. Okay, I'm dawdling here too much. Let's move on. So those are some different electric fields that you can see. Now, there are two kinds of electric fields in general that we're going to look at. We're going to look at radial fields where we've got point charge, and we're also going to look at uniform parallel plates where we have these charges that are uniform and parallel. All right. So that is all I can tell you right now about electric fields. And so we are going to send it now over to Frisco, Texas, and Kristen is going to help us to understand some of these problems with these concepts with some really good problems. So thanks for taking it from here, Kristen. Can you hear me?
Probably a good thing to unmute. So let's look at a couple of questions here applying that. So we know that the electric field is now KQ over R squared. And we also know that the electric field is the amount of electric force per charge, right? So sometimes those come in use when you either know what the field is, you're trying to find what the force is, or vice versa. But that's kind of where we get this one right here. Okay, so here we have a situation where we have a point P that is above the axis here. This is not going to be the question that I'll zoom in. There are two equal charges, positive Q, on the x-axis placed at positive A and at negative A. And then we have point P, which is at a distance B above the origin. So we want to know what each of the following terms is in terms of the given quantities. So we want to know what the electric field is at the origin. And then we also want to know the electric field is at point P. So let's get a little bit of a closer look here and see what's going on. So I have 2 point charges. That means there's going to be an electric field surrounding those 2 point charges. So I'm going to draw them 2 different colors. And I like to draw really big long fields because then I can talk about lots of different regions of space. So not just at the origin or but if we draw, we know that the electric field is going to point away from positive charges. So if we're going to label this left charge as kind of our green charge, then there's an electric field going away from it at every point. So if I make that really big, what that means is at the origin, the electric field due to this one is pointing to the right. Okay? And if we do the same thing with the charge on the left, it's also positively charged, which means there'll be an electric field going out in every direction. So again, if I extend it at the origin, the electric field is going to the left due to that second charge. And so we have a field going to the left, we have a field going to the right, so we know we need to subtract that. Since they have the same magnitude of charge and they're equal distance away from that origin, then we know we could find that this field here due to charge 2 is KQ over, well, the distance from that point, which is the origin to that, would be A. But the other one is also that same magnitude. So we would say minus KQ2, but that has the same charge over the distance between that point and Q, which is also A. And so that means those two fields, since they are equal magnitude of charge and they're the same distance away from that point at the origin, we would have no electric field. Okay? But let's look at point P because there would be electric field at point P. So I'm going to use just a second if you need to catch up. If you're ready, you're taking notes, and I'm going to erase and we're going to start fresh from point P. So go back if you need to, but let's look at now point P and see what's going on. So if I look at point P, again, I want to look at one charge at a time. So we're going to ignore the charge on the right at that positive A location. We're going to look at just that negative A charge. So it's a positive charge, and I want to know what at point P, which way would that field be? Well, it's going away from that positive Q in every direction, which means if I extend that out, at point P, the electric field is pointing up and to the right. And if we do the same thing with our charge 2, again, the electric field is radiating out in all directions, which means if I extend out at point P, it's going up and to the left due to that second charge. So we want to look at, well, what would be the field of just one of those? So let's look at just the blue one, since that's what I have right now. So if we look at that electric field here, E2, how can we find that? Well, we know E is KQ over R squared. We've got to put it in terms of things that we know, right? So if we have our rectangle here, the R is the hypotenuse here of our triangle. So we've got A here, we've got B here, and so then our R is going to be equal to the square root of A squared plus B squared. But this is our squared, so that means that the electric field due to this point charge would be K times Q over A squared plus B squared. And then the electric field due to this other one would be the same thing because it's the same R distance away, switch over to my green, the same R distance away, same magnitude of charge. So really I could say, well, I got 2 of these, but that's at an angle, right? And we don't like to combine vectors unless we break them up into their components. So let's look at one side here. If we look at just our electric field due to our charge 1, the green charge, well, there's an X component to that electric field and there's a Y component to that electric field. And what do you notice if we compare the X component of the blue charge or charge 2? Well, since the same charge, same distance away, the magnitude of that field is the same, then those X components would be the same. And so the X components are going to cancel out. And really all we're concerned with is the Y component. So how are we going to get the Y component here? Well, if we call this theta, well, that means we can find the Y component by multiplying by the sine of theta. Okay? But again, I can't leave it in terms of theta because that's not something I do here, right? The only thing I know is A and B and the charge. And I can have constants like K. So if I want to get rid of the sine theta, well, I've got to, if I extend my triangle down here, say, well, this theta here would be the same as the top theta in my green triangle, right? So it's alternating angles there. And so I can put that in terms of this triangle. I'm going to redraw here. So this is my R, my A, and my B. And so if I want to find that, instead of saying, well, I want the sine of that, well, we can say that the sine of theta is going to be equal to A over R. Well, we can't use R, so we have to say that's equal to A over the square root of A squared plus B squared. Okay? So we're going to plug that in over here. So this becomes 2 times K times Q over, well, I got to plug in that A squared plus B squared with R there times the sine of theta, A over the square root of A squared plus B squared. So it's probably going to start to look familiar to you guys, because this is a pretty common thing we do. We're going to see it again with our ring of charge and things. So I need to combine these together. So the square root of A squared plus B squared is really the same thing as A squared plus B squared to the 1/2. And A squared plus B squared is really the same thing as 2 over 2. When we multiply those exponents, really we're adding that. So 2 over 2 and 1 over 2, really this becomes 2 times K times Q times A all over. It becomes A squared plus B squared to the 3/2. And so that is what the magnitude of the field is going to be at point P. That net field is going to be upwards and have a magnitude of 2 times KQA over A squared plus B squared to the 3/2. So we combine those together, we look at those X and Y components and see what's going to cancel out and what is not. Okay? We've got another one here where we have 2 positive Q charges, one at a location of 2 and one at a location of 4 on our X-axis. And we want to know if we were to graph the function of the electric field versus that X distance, what would that look like? So again, I'm going to draw in what would those fields be on the axis through these 2 charges. So again, I'm going to make the left one here my green charge. The field would point to the left on the left side and to the right everywhere on the right side. And if we look at the second charge, it's also positive. That means the field's going away. So here we go. I'm going to draw just under here to the left here, to the right here. Well, let's look at what's happening on both sides. Like what's happening to the left of the charge at location 2. Let's look at what's happening to the right of the charge at beyond 4. And let's look at what's happening in the middle. So if I look anywhere between 0 and 2, well, both of those electric fields are pointing to the left. So those fields are going to combine. If I look at to the right of location 4, those are both also pointing to the right. So here they would also combine. But if we look in the middle, and I'm just going to again look at draw it here. Well, due to this green charge, the electric field is pointing to the right, but due to the red charge, the other positive charge, the electric field is pointing to the left. So the field there is going to subtract. And we know our relationship for E is KQ over R squared. So look at these graphs here, and you tell me what you think would best fit what's going on. There's a couple we can eliminate right off the bat because we know if these are subtracting, we know the electric field's got to be 0 in between. If these are the same magnitude of charge, we know exactly where it's going to be 0. If they're the same magnitude of charge, the electric field's going to be 0 right smack in the middle at 3. So that means I can get rid of B, I can get rid of C. The only ones that have an electric field of 0 are the other 3. Well, now we want to look. If I am really close to this charge, if R is really small, well, that means the electric field is really big. So close to these charges, we should have really big electric fields. Well, that gets rid of D, And we know that it's not a linear relationship because it's related to r squared, right? So let's look at A. We look at A as we start at 0 and we get closer to 2, the electric field is increasing, which is what we want to see. And then after we get past 2, where there's subtracting, it's starting to decrease all the way to become 0. And then it's going to increase again as we get close to 4, and then decrease again as we get further out because as r goes up, E goes down. So we have that relationship there for A that fits our data. Okay, I got one more here. We have another axis, and we've got two charges, Q1, Q2. Q1 is at location of 0 on the x-axis, Q2 is at positive 12, and Q1 has a charge of negative 1 Q, and Q2 has a charge of negative 25 Q. And so we want to know at what point is the electric field going to be 0. So I'm going to let you first draw out for me which way would the electric field be everywhere on the axis due to charge 1, which way would the electric field be due to charge 2 everywhere on the axis. And then I want you to think about what would happen, what would be going on with the electric field over here. Let's break it up into these three regions. And is the electric field going to be adding, subtracting in those three regions? I have to take a second, draw those field lines and say whether you add or subtract the fields of 1 and 2. I'm going to slowly draw it in while you guys are doing that. Okay, so if we look at our Q1, the blue charge here, well, since it's negatively charged, we've got electric field pointing towards it. So there's a nice long line going towards it everywhere. And if we look at charge number 2, that's also negative charge. Again, we've got lines going towards it everywhere. If we look at region 1, I've got electric field going to the right due to Q1 and also to the right due to Q2. So that means we're going to add up those E fields. If we look at region 3, we've got both those electric fields going left. So again, we're going to add up, right? These are the conceptual things that we need to get really good at because these are things that we can be tested on, right? We're going away from the more mathy focus, more based on the concepts. But if we look at the center, we've got electric field going to the left due to Q1 and to the right due to Q2. Well, if we go in opposite directions, we have to subtract those vectors. So we know that it's going to be somewhere in here that it's going to be 0. And when is it going to be 0? Well, that is when the electric field due to charge 1 is going to be equal, but in the opposite direction of the electric field due to the second charge. So I can say, well, KQ1 over R1 is equal to KQ2 over R2. But I also know that those are not exactly the same R, right? So I can't just solve for that R. But I also know that the distance between them is 12. So I know that R1 plus R2 is going to have to equal 12 because we're someplace in the middle here. So let's look at those charges because where you can make this easier, you can set up a system of equations and solve it, but that gets something squared here. That gets really difficult because that's squared in there. So what I like to do is I like to reason through with ratio of charge because I know that Q2 is 25 times greater than Q1, right? So if Q2 is 25 times greater, well, in order to cancel out that field, we know that the radius also has to be 25 times big. So we know that R2 is going to have to equal 25 times R1. So then we can plug that in now to my equation here because I can get rid of one of those R's because I know R2 is 25 times R1. So R1 plus 25 times R1 equals 12. Okay. Oops, so this is squared. So we don't want it to be 25. We want it to be 5 times greater because we want R squared to also equal 25. If the top is 25 times as big, the bottom is 25 times as big. What squared gives us 25? 5. Sorry guys. So we've got 1 R1 plus 5 R1. That gives me 6 R1 equals 12. So I know that R1 is 12. So that means R1 is the distance from Q1 to where that point is. So it's 2. So over 6 is 2. So that puts me right here would be where my electric field is 0. Okay, so we can set up that ratio, look at those charges, and also look at what the total distance between them. Okay, Roger, back to you to finish us off.
All right, thanks, Kristen. Well, as Kristen said, we are putting our heads together here at AP, trying to figure out exactly what the test is going to look like, and we think it's going to be very conceptual. So we are trying to pivot to a more conceptual problem. So I've got some that I think are going to push us in the right direction. Let's go ahead and take a look at this problem. All right, and as you can see, we've got 3 particles. So sorry about that. 3 particles, A, B, and C. They have equal positive charges, and they're held in place at the vertices of an equilateral triangle with length L, as shown in figures below. The dotted lines represent the bisector for each side. The base of the triangle lies on the x-axis, and the altitude of the triangle lies on the y-axis. Okay, point P1, the intersection of 3 bisectors, locates the geometric center of the triangle and is one point where the electric field is 0. On figure 1 above, draw the electric field vectors EA, EB, and EC at P1, each due to the 3 charges. Make sure your arrows are drawn to reflect the relative magnitude of the field. And that's important. When they say that, make sure that you take good account of how long your vectors are. All right, so let's try start with A. And so the electric field due to A, I'm going to say is that long and in that direction, since they told us that these are positive charges, and so that means the electric field from A, and I'm going to label it EA. Okay, and remember that's important. Draw the electric field vector. All right. And then for B over here, well, B is going to create a positive charge, so it creates an electric field away from it, and I'm going to make that exactly as long as EA, and I'm going to make this one exactly as long as both of the other two. And this is my E from B, and this is my E from C. And make sure that you always label these. Most of the time the problem says draw and label. So now let's see what we have next. Now there's another point where the E field is also 0, and this was point P1. This is the new point, and the field is also 0 there. So again, here they want us to draw the electric field vectors. Now notice for EA, I'm further away than I was at P1. Here I was closer to EA. Here I'm further. So I'm going to draw this line, and it's going to be a little bit shorter than my previous line because I'm further away, and so that's labeled EA. And then I got an EB. Now this is pointing away from B, but the question is it closer or further away? Well, it's actually closer. So I'm going to have a bigger E field line there, and that's EB. And then over here on the other side, I'm also going to have an E field line, and it will be longer than the previous, but I want to make sure that these two are the same length, and so that's going to be EC. All right, and I think I drew them pretty close, but I also put this little hash mark here, and that's a symbol for more. So we can see that EB and EC got longer, we're closer to B and C, and EA got shorter because we're further away. Now it asks us to say, well, what happened to each of these? P1, P2 are the same. And so EA we said was less, and EC were each greater. And that's it. It does not ask us to explain, so we'll move on. All right, now the next part says, explain why the x component of the electric field is 0 at any point on the x-axis. All right, now here's where you've got to really think of writing a sentence. So it doesn't say a paragraph length response. This is a short answer. Please try and do this in less than 3 sentences. 2 is usually enough, but don't write a whole paragraph because you're going to be stretched for time. So why is the x component of the total electric field 0 on the y-axis? Well, first of all, charge A is on the y-axis and creates no field in the x direction. So that is the reason there is no x component of the total electric field due to charge A. Charges B and C are equal and symmetric about the y-axis, and therefore their x components cancel. All right, so remember, try and be as clear as you can so that it makes sense. And again, practice writing. Don't just roll over these, go, oh, I know what that is, because in the heat of the moment, you've got to get this on the paper. All right, let's look and see now. Here's a different problem. And this one says we've got a square of side A, and it contains positive point charges of Q plus on the lower left and negative point charges on the other 3 components. Indicate with an arrow the direction of the net electric field at point B. Now they want the net field, and I'm going to draw the net field here. So I'm going to have to draw a little workaround over here. This is my scratch sheet. So I'm going to call this A, B, C, and D. And these are positive, negative, negative, and negative. Now when something has a negative electric field, that means that its field line is pointing towards it. So this is the field line from B towards it. Here's the field line from A towards it. Here's the field line from D toward it. And then here's the field line from C. That's positive charge. That's going to point away. And so what we can see is these two fields cancel, and what we're left with is these two in this direction. So the net field is going to be in that direction. So it says indicate with an arrow the direction of the net field. Nothing about the magnitude or where it came from. I don't have to label it. There it is. It is just an electric field. I'll label it that. All right, now the next part says derive an expression for the magnitude of the electric field at point P. Now again, there are 4 charges here that are all contributing to the electric field. We've got, again, I'm going to label these A, B, C, and D. And so we've got A, and because charge A is negative, points towards it. Charge B negative, charge C negative, and charge D, and charge C is positive, so it points away. Now the electric field we've learned is equal to KQ over R squared. So I know that these two are going to cancel, and I'm going to have 2 of these. I've got one from C and one from B, and because of symmetry, the distance here and the distance here, those distances are the same. And so I can go ahead and figure this out. Now let's do a little bit of geometry and see what is the distance between each of these. Okay, so the distance from here to here. Well, if you see this, I'll draw this little triangle actually, and notice that this triangle is a right triangle, and the legs, because of the symmetry of the square, are the same. And so that's a 45, 45, 90 right triangle. So if this is A, well, I know that this is the square root of 2 times more than this. So this distance is A over the square root of 2. All right. So my electric field from B is K capital Q over A over the square root of 2 squared, which is 2KQ over A. So that's from B. Now, what about from C? We said that we had from B and from C. So the E from C is also KQ. Distance is the same, A over root 2 squared. And so this also gives us 2KQ over A. So when I add them up, I get 4KQ over A. And that is A squared, sorry. And that is the total electric field in terms of the given quantities. All right, let's keep going. The next one says a positive charge is placed at point P. The positive charge there, okay? And it is moved from point P to point R in this direction. Okay, so we're gonna move this from here to here, which is the midpoint of the bottom side of the square. As the charge is moved, is the work done on it the work done by the electric field, positive, negative, or zero? Now before we answer this, we have to review what does that even mean. So if the work done by a force, remember, work is done by a force. In this case, we're saying the field, but the field exerts a force. So the work done, if the work is positive by a force, what does that mean about the object? Do you remember that? That goes back to something you probably learned in mechanics, and that is that when we do positive work on the object, we increase its kinetic energy, so it speeds up. Okay, and so if the electric field would do positive work, what does that mean? That means that if I moved in this direction, or if I let this move in this direction, it would speed up on its own. So does it speed up? In other words, does it roll in this direction in general? Does it roll downhill? And remember, if the work is less than 0, that means that you're having to do work. You're having to push against a force. All right, I like to say this is like uphill. So is the force doing negative work? When you push the ball uphill, gravity is doing negative work. It's working against you. All right, well, let's take a peek at this and see if we can figure it out. We learned in the previous part of this problem that at this point the electric field is in that direction, and so I've got a positive charge. What happens to a positive charge if I release it in an electric field? Well, it wants to accelerate in that direction. That's that's downhill, right? That's rolling on its own. It wants to get away from me and accelerate. So if it rolled in that direction, that would be the electric field doing positive work. However, to move it from here to here, you see, I'm moving in the direction opposite of the direction of the electric field. So that means I'm having to pull that charge from here to here. I'm not pushing it, or I'm not letting the electric field take it. I'm pulling it, which means I'm doing positive work, which means the field is doing negative work. Now that is a lot of talking, but this is something that you have to really parse and try and break down to get it. And so don't speed through these conversations. All right, and then finally, the last question we have for today is describe one way to replace a single charge in this configuration that would make the electric field at the center equal to 0. So it says replace a single charge. And so, well, if this were negative, then all of my electric field lines would point away from the center. They would be equal in magnitude and opposite in direction on the from the 4 corners. And so what I would say is that I would replace the positive charge with a negative charge. And so you have to describe what you'll do, okay? And then justify, that's what I would do. And why would I do that? Well, a negative charge would cause all the fields to sum to 0 at the center. I'm going to say would cause the opposite corner fields to oppose each other, because I looked and I saw what I just written is actually what the question is asking. So let me never just answer the question by restating it. So it would cause the opposite corner, there it is, charges to cancel. There we go. And so that is a great way to answer that question. I think that'll get you there. Now, what do we want to talk about? Debrief and summary. So we've looked at the electric field now. We compared it to the gravitational field. Just remember the point formula for an electric field is KQ over R squared. I don't believe that one is on your formula sheet, but since you can make your own formula sheet for this exam this year, you don't have to worry about it. Make sure you write it down. I'm looking at the formula sheet right now, and it is not there. But what is on the formula sheet is E is equal to F over Q. And so both of these are correct. This is correct only for point charges, and this is correct for any kind of field I can think of if I put a point charge in it. So that is what the electric field is. Tomorrow, we're going to start talking about potential. And when we start talking about potential, what I want you to shift your thinking, I want you to start thinking about electric field as a steepness, okay? And that'll make sense more tomorrow when we start to figure things out. So I want to thank Kristen for being with us tonight. Are you there, Kristen?
Yes, I'm here. We're not actually going to get to potential for a couple more days, but we're going to do Gauss's law tomorrow, and then we're going to get into potential.
Right, okay. Well, thanks so much. Thanks for tuning in. We hope these are helpful. And make sure that you come back tomorrow night for more physics, and have a great night.
AP Physics C, Electricity and Magnetism. And we are reviewing you for the AP test. Today, we're going to go over electric flux and Gauss's law. And if you have not watched kind of our first couple of videos with charge and Coulomb's law and finding electric field, it might be a good idea to watch those first. But tonight, we're going to do Gauss's law. My name is Kristen Gonzalez-Vega, and I'm with my friend Roger.
Hello, my name is Roger Siegel, and I'm coming to you from Sarasota, Florida.
All right, so what we're going to go through today is we're going to state and apply the general definition of electric flux. We are going to calculate what that electric flux is through an arbitrary area. We're going to calculate the flux through a rectangular area when the electric field is perpendicular. And then I highlighted this one, so it's kind of a big one here. We're going to qualitatively apply Gauss's law to a system of charges or charged region to determine characteristics of the electric field flux or charge contained in the system. And we're going to state and use Gauss's law in integral form to derive unknown electric fields for planar, spherical, and cylindrical symmetry charge distributions. So it sounds like a lot, but really it all kind of relates. So the first thing we're talking about is what is electric flux. And so not even necessarily electric flux, but what is any flux? So a flux is a flow of some quantity through a surface. So I like to kind of use the analogy first of light. So we look at the picture here, we can see this light streaming in. You can see those light rays streaming in. And so that amount of light that is flowing into the church is the flux of the light. And so we can change the amount of flux by changing those windows. So what could you do to change the amount of light? Let's say I want to increase that flux of the light coming through. What can we do? There's a couple of different things we can do. Think about the time of day. In the morning, like maybe let's say this is afternoon. So in the morning, would you get the same amount of light streaming through the windows as in the afternoon? No, that angle that light is hitting at affects how much light gets through. What about the size of the window? Would that affect the amount of light that gets through? Yes, the bigger the window, the more light is going to stream through. And so we can relate that amount of flux to both kind of the surface area of the window, the angle which the light is hitting, and also the intensity of the light that's coming through. So We'll look at some examples down the bottom of the page here. And we have sunlight shining in one side of the building and out the other on that lower left. And if we look at that flux, the net flux is that total in and out light, right? So if we have light coming in and light going out, like we do here, we have no net flux, there's no light is staying in, or we don't have any net flux that's going out. And so we say generally that positive flux is when you have a quantity that's flowing out, right? So if we had light inside the building that's flowing out, like the middle picture, that would be a net positive flux. But the first picture, we have just as many light rays going into our building as going out, right? Let's imagine this is a glass greenhouse, just as much as coming in that is going out. And so that would be, we can come out here, that would be zero net flux. So there's the same amount going in as there is coming out. In the middle, we have light that is originating on the inside, and so the light rays are only leaving the building, there's nothing coming in. So that would be a positive flux. And then we combine the two, and we have light on the inside coming out, because that light bulb is on, but we also have sunlight coming through the building. Well, if we look at the sunlight, again, that's like the first one that's zero, but the light inside is a positive, that gives us still an overall positive flux. There'll still be as much, there's more light leaving that building than coming in. And so we can use that analogy now to talk about how we can use this for charges. So I have a couple of different surface areas here, right? So it's the flux again is the amount of, here we'll say field lines that are going through our surface that we choose. So let's just kind of practice, is there a net inward or outward or any kind of net flux on our surfaces? So let's take a look at this one here. So I draw this surface area, and if we look at this surface area, let's look at the electric field lines. Well, I've got field lines going into the surface, so that tells me I would want to have a negative flux. But then I also have those same lines going out through my surface, and everywhere in that surface, any field line that's going in is also going out. So that means here we have no flux. Right? But if I look at the surface area that's surrounding this positive charge in the center here, well, we look at the field lines, we have field lines that are, and this is my whole surface, right? This whole thing is my surface. So there are field lines only leaving the surface everywhere around. So that would give us a positive electric flux. Okay, you guys start to get with me here? So let's look at these three down here. I'm gonna give you a minute for these three surfaces. You tell me positive flux, negative flux, or no flux. We got those two, and then we got the big one all the way on the outside. Okay, so take a second. This would be number one, number two, number three, positive, negative, or zero. Okay, what about number one, the one on the left? Well, we have field lines only going in to our surface here. So that for number one would give us a negative flux, right? Positive flux going, yeah, negative flux going out. What about with the positive charge here? We have only field lines going out. Well, that would give us a net positive flux. And if we enclose both those charges, well, we have field lines going in and we have field lines going out, and we have just as many going out. As you can see, they kind of loop back around and come back in. So that third one would be zero. Okay, so let's look at what this really means then as far as like putting a quantitative amount to it. So how can we actually calculate what this flux is? So that amount of flux, as you can see, depends on the electric field lines. It depends on that surface too. So if we imagine this one charge in the center here, and I'm going to draw an imaginary surface around it, right? Or if we think of like a balloon with a point charge inside of a balloon, if I break the surface up into tiny, tiny little pieces, and I can do lots and lots of them, right? So we have a tiny little differential surface area on our surface. And if we think of what's normal to that surface, then we can look at the electric field lines going through each of these surfaces, right? And since it's like a three-dimensional surface, they're going to be coming out in all different directions. We'll be coming right out at different sides. And so we can find, well, what would be the flux of just this one, right? Well, since it's not the whole entire surface, we're looking at just a little piece of the whole surface. We can say, well, that's a small differential part of the flux. And so we can look at the electric field going through that one surface area times our tiny little surface area. So that would be the electric flux through just that one tiny little differential surface area. And if I want to know what the entire flux is over the whole surface, what we have to do? Well, we have to add up all of those tiny little fluxes. And so we end up with that the net flux across our whole surface would be equal to the integral of E dot dA. And that's for any surface, right? So you get to pick the shape of your surface. And it's important to remember, like when we talk about these surfaces, we call these Gaussian surfaces. It's not a real physical thing. It's just a region of space that we're enclosing around our charge that we want to turn the electric field of. So sometimes we'll have spheres. I could have a rectangular prism here and look at the flux through this one. We have cylinders as well. Those are kind of our three common shapes that we use are the sphere, the rectangular prism, and the cylinder. So if we look at this rectangular prism down here, we want to look at which surfaces have flux. Because sometimes when we draw a Gaussian surface, there may be some surfaces that have no flux. Because if we look at it, this here, in order for there to actually be flux, the field can't be running parallel to the surface. If my sun is coming straight down on top of my house, it's not going to enter the window, right? So there would be no flux there. There has to at least be some angle. So we're looking at the component of the electric field that is normal to that surface area. So if we look at these front sides of my rectangular prism, well, that surface area is running parallel to the electric field. So there would be no flux on those front sides. Same thing with the top side, with the back side. But where there would be flux, we can look at the two end sides here. But we have field lines going in one side and coming out the other. And if this field were the same or it was a uniform electric field, then there would still be no flux here. Now, if the field is different, then there would be. But if we're saying this is a uniform field, still no electric flux through that surface. So that's one way we can find electric flux is we can relate the electric field through the surface area. Okay? But the electric flux also depends on the amount of charge that's enclosed in our surface, right? So if I go back and we look at these ones again, you can see, well, what inside that surface? Well, here we have a positive charge inside. That's what's affecting also the flux. So there are two ways we can find the electric flux. We can use that integral of E dot dA, which when we actually draw right now Gaussian surface, we have to integrate across the whole surface. That's going to be a closed integral. So we can use that. That side is the electric flux, but also the right side is the electric flux. So we can also find it by finding the charge enclosed divided by epsilon naught. And what epsilon naught is the vacuum permittivity constant. That's going to equal to 8.85 times 10 to the negative 12 squared per Newton meter. Sorry, but it's also the same thing. We can relate it with K because what you know that you've heard of K before, right? That Coulomb's law constant. K is equal to 1 over 4 pi epsilon naught. And so we can also relate epsilon naught to K. So the rules for being able to use Gauss's law. So this is Gauss's law, and we can use this to find the electric field. We found the electric field with the point charge. We're going to derive it here in a second. Gauss's law, but Gauss's law is kind of our shortcut or our easy way to find electric field around charges. But there's some rules that we have to follow in order to use it because we can't use it all of the time. The first thing is that your Gaussian surface, right, that region of space that you choose around your charge has to have the same shape as your charge distribution, right? So if I have a point charge, and our point charge is a nice sphere, then my Gaussian surface that I choose to enclose my charge also has to be a sphere. I cannot use a square. The reason for that is because in order for this to be true, in order for us to be able to do this integral, we want the electric field to be constant everywhere on my surface. Well, that gets us with the square because if we know that electric field relates to the distance away from the charge, the corner of a square or a cube is further away than say the midpoint on that cube. So the electric field would be the same everywhere. And the last thing is the electric field must be tangent or normal to the surface. Right? We don't want to be dealing with angles and things like that. So we choose that symmetry that's the same as our charge, so that it becomes easy for us to solve for the electric field. Even though it's an integral, if you are choosing your Gaussian surface right and applying Gauss's law right, you will never have to do any calculus. Sometimes we for the charge, but not for actually Gauss's law. So let's use an example here. And I'm going to really quick try to switch over and see if I can draw on my iPad. So that is easier than trying to draw here on the PowerPoint. So I'm going to read this. I've got a point charge, positive Q, and it is, we want to know what is the electric field at some distance r away from the point charge. So we're going to derive it. We got an equation yesterday for the electric field to a point charge. So we're going to see how we got that. All right, so I'm going to switch over here because we've got it working out. There we go. So we have our point charge here. First thing we have to do, and here's our stats on how we apply Gauss's law. And it's the same all the time. Every time you're working a problem with Gauss's law, you solve it the same way. The first thing you want to look at is what is your charge? What is the shape of your charge? Because then that's what you're going to use to choose what your Gaussian surface is. Remember, your Gaussian surface is that region of space that we're going to enclose our charge in. Because we want to know, let's just say that I want to know what the electric field is at this point here. which my screen is frozen, so I'm probably gonna have to switch back over. Gotta love technology. All right, I'm gonna switch back over because that's taking way too long to pop up. So let's go back to the PowerPoint. So let's say right here, I want to know what the electric field is. So the first thing we need to do is we need to determine what Gaussian surface we're going to use. Well, what shape is our charge? It's a sphere. So I'm going to draw a Gaussian surface. There's a nice sphere surrounding that charge. Okay? The second thing we're going to do is we're going to write Gauss's law. So we know Gauss's law is the integral, the low surface integral of E dot dA that equals Q enclosed over epsilon naught. So then we address, well, if we look at our surface, right, and we integrate all the way across, what will the integral of that, all those D dot dAs always be? That's going to be the surface area of your Gaussian surface, always. So if I look at this, I am equal distance away from my point at every place. So that means my electric field is going to be the same everywhere on my surface. So now E is a constant. That's the other reason why I always pick a symmetry. E should always be a constant. It should never be different on different points on your Gaussian surface. So really, this just becomes E times the area. What is the surface area of a sphere? Well, 4 pi r squared. So if I want to know for any r way, we're always going to put that little r. Unless you're looking for a specific point. If you're just looking for an equation for or a function of the electric field for that radius, then we're always going to leave this left side of Gauss's little r. So that equals, okay, well, our next step is then to address what part is the Q enclosed. Well, here it's easy. What amount of charge is actually inside your Gaussian surface you draw? And here, what's inside? Well, it's Q over my epsilon naught. So if I rearrange for E becomes Q over 4 pi epsilon naught r squared. And remember, we know that 1 over 4 pi epsilon naught is K. I believe it is this, or I can put it in terms of K and say that it's KQ over r squared. That looks familiar. That's the equation we used last night. Okay, so that's for our point charge. Let's now look at if we have a conductor. Okay, so I put in parentheses here nice and big. Always remember where the charge exists. So let's see if we can set up here our Gauss's law equation. Let's look at when we are at a distance r of less than big R, right? So we're inside. So again, I'm going to draw my Gaussian surface. You can draw it inside. It doesn't matter if you draw a small circle, as long as your Gaussian surface is going to be less than R. Okay, so we're going to write it out. We know the Gauss's law. Integral of E dot dA equals Q enclosed over epsilon naught. Okay, we're going to write address the two things always. What is the surface area of my Gaussian surface, and what is my Q enclosed? Well, it's still a sphere. We're still dealing with the sphere here. So we've got E times my surface area, which is 4 pi r squared equals what is the Q that I've enclosed here? Well, here's where we have to look and always pay attention whether you're dealing with a conductor or an insulator. Because remember, an insulator, the charge can be evenly distributed or unevenly distributed, but it's throughout the whole material. But on a conductor, where do we say the charge always is last night? It's always on the surface. Inside surface, outside surface, always on the surface. So that positive charge will be distributed around the surface of that. So what charge is on the inside of the conductor always? Nothing. There's never charge on that inside space of that conductor. Therefore, what will our electric field always be on the inside of the conductor? 0. Okay. And the next one, if R is greater than R, so I'm going to redraw that Gaussian surface. I'm going to change color. So I want you to redraw your Gaussian surface. See if you can solve for what the electric field is at an R anything greater than big R, the radius of that conductor. Okay. First thing, we draw our Gaussian surface. Again, it doesn't matter if you're drawing it way outside or just outside. We always want to follow our symmetry. So it's still a sphere. It's just now a bigger sphere that's enclosing the whole conductor. Okay. So we still go back to Gauss. You get to quite a bit, but you still always want to write it out. You always want to use your full steps here, right? So now our surface area is still the same. So E times 4 pi r squared. Even though we're outside, it's still little r because I want to know for any r, what can I find the field? So this left side can be for any r. What Q have I now enclosed? Well, now it's all inside my surface, everything. So now this becomes Q over epsilon naught. So again, we're left with that E is equal to Q over 4 pi epsilon naught r squared again, or KQ over r squared. Okay. And we've got to be able to draw this, right? So we have to be able to say, well, what would this look like on a graph of the electric field? And I'm going to put in here that at this location, it is big R. We're right up here at the edge of that conductor. So the only thing you have to do is you have to look at your relationship. What relationship does E have to R in our equation when we were looking at it for less than R? Well, E was 0 the whole time, right? And then the minute we jump out here, look at the relationship between E and R. Well, R is squared and it's on the bottom, so it's an inverse relationship. So when we get outside here, the electric field is going to jump way up. It's going to be the biggest it's going to be. And then as we go further and further out, the electric field is decreasing exponentially by that 1 over r squared relationship. Okay. So we also need to think about what is that charge enclosed, what surface area, what Gaussian surface am I going to draw? Okay, let's look at one more here. So now we're going to look at an insulator. Okay? Our insulator though has a uniform charge density. So I'm going to go through these different densities with you because we're going to have to know what our different charge densities are. We can have 3 different types of charge density. I can have the what we call linear charge density. So that would be if I have like a really thin object or thin line, and that's equal to the charge per length. That's lambda. We can have sigma, which is the area charge density, and sigma is equal to the charge per area, right? The area charge density is the amount of charge per area. And then we can also have rho when we're talking about our 3D objects here, and rho is equal to our charge per volume. So those are our 3 different kinds of charge densities we can have. So we're told here not always what the total charge is. You may be told that it just has uniform charge density rho, or you may be told what the total charge is. You have to be able to kind of relate them both. And so if I know here that the total charge is Q and that it's uniform charge density, then we want to look at what is the electric field at less than R and greater than R. So if we start at less than R, we're going to draw Gaussian surface. What shape are we still dealing with, guys? It's still a sphere. So I'm still going to draw my nice sphere Gaussian surface. So we're going to write down Gauss's law, and then again we're going to plug it for both sides. Where it's going to get complicated here is with that Q enclosed, right? You guys see that? So it's still a sphere. The left side still the same. 4 pi little r squared because I want it for any r from the center all the way out to here. Okay? But now we have to look at how am I going to get how much charge is in just this part of my Gaussian surface. Well, it comes back to I know that just like if I take a ruler and I break it in half, the density of one half of the ruler is the same as the density of the whole ruler. So I can use that here too because I know that the charge density of the whole like insulator here is equal to the charge density of whatever I'm enclosing. That density is the same. And so then I can say, well, that means that the charge of the whole thing, which is Q, over the volume of the whole thing, well, it's a sphere, so the volume of the sphere is 4 through pi r cubed. But this is the whole thing. So here we are going to use what R? Big R. That's got to equal the charge that I'm enclosing, so Q enclosed, over the volume of just my enclosed part, which is 4 thirds pi little r cubed. But now we can just solve for Q enclosed. My 4 thirds pi is going to cancel, and so my Q enclosed is just going to be equal to the total charge Q times my little r cubed over big R cubed. And so that's what I'm plugging in for my Q enclosed here. So I get big Q times little r cubed over, I still have my epsilon naught times big R cubed. But if we solve here, I'm going to divide by my 4 pi r squared, so I can cancel out the cubed with r squared here, and so I get that E is equal to Q over 4 pi epsilon naught times r times big R cubed. So let's put that on a graph here. So anywhere between 0 and R, what relationship does the electric field have to the radius? That would be little r, right? Well, where's the r? It's on top and by itself. We saw this when we were looking at magnetic fields. It's going to have a linear relationship until we get to that outside. It's a direct relationship and increases. Okay, let's look then at when we are r bigger than r. So let's see if you can set that up. It probably should be pretty easy at this point on what it is. But if we draw a Gaussian surface bigger, which mine is not super circular, I apologize, and we set up our equation, still a sphere. So it's still 4 pi r squared. But what charge are we now enclosing? We're now enclosing everything. It's still little r on the left, as you noted, because we want it for any r. It's not a specific r that we want it at. So that's just Q now over epsilon naught. And what do we get again? We get that E is equal to Q over 4 pi epsilon naught r squared. So we go back to that inverse square relationship. So from there on, we're back off. Okay, so those are kind of our sphere shapes. Roger's going to show us a couple other charge distributions.
Yes, thanks, Kristen. Well, let's do, we've just done a sphere, so let's go ahead and I'll share my screen, and let's do a line of charge. All right, so let's see, this guy is actually, hold hold on a second. Okay, great. So let me come back here. All right. So Kristen alluded to this earlier. If we have a line of charge, okay, now I don't mean a wire where the charges are moving. I mean I've got some plastic, something that's an insulator, and I'm embedded charges in there so that my charges have this density lambda, and the units for lambda are coulombs per meter, and that's why it's called a linear density. All right. Now, if we want to find out what the electric field is a certain distance away from this, what we're going to do is we're going to use Gauss's law and we're going to create a Gaussian surface. So Gauss's law is E dot dA is equal to Q enclosed over epsilon naught. Now, what kind of Gaussian surface do we choose? Well, with a point charge, we chose a spherical Gaussian surface, or with a spherical charge, we chose a spherical Gaussian surface, because at every point on that Gaussian surface, the electric field was exactly perpendicular parallel to the area vector. So let me show you looking on. This is my looking from the edge here, and so if I look at this, my electric field lines are going straight out. Okay? And so, what kind of Gaussian surface would I want to create such that my area vectors are always parallel to my E field vectors? And I'm going to create for these sides, I'm going to create a cylinder. And why a cylinder? Well, because and the body of the cylinder, the E field and the E vector and the A vector are parallel, and so that means that E dot dA, and that's a dot product. That's going to be that's E dA times the cosine of the angle between them, and so the cosine is 0, and so that works. Now on the edge here, the A vector is again the area vector is always perpendicular to the surface, but the E vector again is radially outward. These two are perpendicular, and the cosine of 90 degrees is 0, which means there is no flux through either of these faces. So if I'm going to draw a net diagram of my cylinder, okay, we know that this is R, and through each of these sides, the flux electric is 0. Here the flux electric is 0 for these, because again the area vector and the E field vector are perpendicular. And here the flux is the integral of E dot dA, and that's equal to the Q enclosed over epsilon naught. Now, well, the B field is, I'm sorry, I said the B field. I'm in the wrong unit, ladies and gentlemen. That is another formula. This is E dot dA. Sorry about that. And so for this E field, we want to figure out what this is. And so we're saying, again, everywhere on here, the E field is parallel to dA. And so this just is uniform. This just becomes E. The area of this part of a cylinder, well, this is, I didn't draw this here, but the length of the cylinder from here to here is L. And this part of the cylinder, you may remember from earlier, is 2 pi r. It is the circumference of the circle. So this middle part, when I integrate the dA, I get 2 pi r. And over here, I get the Q enclosed over epsilon naught. Now, just like in the previous problem, the Q enclosed is the most challenging. What is the Q enclosed? Well, remember that my charge density is lambda coulombs per meter times however many meters gives me the charge. That's going to be lambda times L. And you know what I forgot here, ladies and gentlemen? I forgot that the area is 2 pi r times L. So when we come down here, the L's cancel. And so E is equal to lambda over 2 pi r L epsilon naught. And that is our E field, a distance r away from a long line of conductor. All right, let's do one more, and then we're going to send it back to Frisco, Texas. And that is the plane of the charge. Maybe we'll do more than one. We'll see. Now, again, when you're choosing your Gaussian surface, the reason you're choosing it is you're choosing a specific surface such that either the area vector and the E field vectors are parallel or perpendicular. Now, a lot of times, this is taught, again, by using a cylinder around this. And you can see here, it's kind of the opposite case. So let's take a look at this and see what we have. We've got this cylinder. And now, in the previous problem, okay, the E field was parallel at the ends to the A field, and so the ends contributed nothing to the flux. We have just the opposite here. Notice that the A vector and the E vector here are perpendicular. That means that on our net diagram here the flux electric is 0, because E is perpendicular to dA. Everywhere along here, everywhere on the body of the cylinder, E is perpendicular to dA, to E field. However, at the caps, notice E is parallel. And so what we have here is we have pi r squared here, and we have pi r squared here. And so when we add up, when we do Gauss's law, E dot dA, and we sum that up, Q enclosed over epsilon naught. Now let's talk about, let's do this left side, and then we'll come back and talk about the right side. Now here we have, again, the electric field is uniform. The whole point of doing Gauss's law is to not have to integrate. And so we're going to pull that out. And now what is the area when I integrate over this whole thing where I don't get 0 flux? And that is pi r squared, and I've got 2 of them. So there's 2 pi r squares, and that's equal to the charge enclosed over epsilon naught. Now let's look at this. I failed to drill down here for a minute, so I want to come up here. It says we've got an infinitely charged plate. It's very, very big, and the area density is sigma. Now that is different than lambda, different than rho. Remember, lambda is coulombs per meter. Sigma is coulombs per meter squared. It is the area density. And so I've got this very, very thin plate with sigma coulombs per meter. And so I'm going to go ahead and come up here, and what do we have? We have the charge enclosed, and so that's sigma. And the charge enclosed, if we look back down here, how much charge have I got? Well, I've got a little cookie cutter. Look, I've cut out this much charge. And so how much is there? Well, that's pi r squared times sigma. The area times the density will give me the charge that is enclosed. And so that's going to be, I'll say E times 2 pi times pi r squared, those are the two end caps, is equal to pi r squared times sigma over epsilon naught. And so this becomes E, look at this, the pi's cancel, the r squared cancel, and E is equal to sigma over 2 epsilon naught. Now, I just want to pause for a minute, because this is important. What is missing from this formula? What are we saying that the E field depends on? Well, really, there's only one thing, and that is the density. And more importantly, more crazily, what does it not depend on? Well, strangely enough, the E field does not depend on the distance I am away from my plate. The math gives it, and there's other ways to prove it, but it's something we can certainly show. Also, it's on MIT's Lewis and Physics. It's very well demonstrated as well. Now, we've got some more to do, but we're going to throw it back to Frisco. Are you ready back there for me, Kristen? Because I want to make sure we get these kids out at a decent time.
Yeah, sure. I think we should probably do the conceptual part of the question, right?
Okay.
Scroll through. Let me show you what I'm talking about.
Yeah, let me go ahead and release my screen.
And I'm back in business with my Apple Pencil, so my handwriting is going to be much better than my clicks of my mouse. I apologize again for that. So what we're going to look at is a pre-response question. We're going to skip the first parts of this because of what we were deriving earlier with me, that we have a non-conducting sphere, and we're looking at what is the electric field at meridian of an A. We've already done that. I think we're good on that. But what I want to look at is, if we scroll down here, is this conceptual part, because that's what we want to practice the most. If we have here 4 point charges, Q1, Q2, 3, 4, in the plane of the page here, and we want to imagine this 3-dimensional closed surface, right? This kind of globby 3D surface that is shown in our diagram. And we want to know which of these charges is going to contribute to the net electric flux, and which is going to contribute to the net electric field, and are they the same or not, and why? So I'll give you just a minute here to think about that. Which of the charges are going to contribute to the net electric flux, and which ones are going to contribute to the electric field at point P right here that lies on that surface? Okay, so which one is going to contribute to the net electric flux through the surface? Remember, what is that flux equal? The electric flux is equal to either an integral of E dot dA or equal to Q enclosed over epsilon naught. So one thing we can look at is the flux only depends on the amount of charge enclosed. So which ones do we care about? We care about the ones that are enclosed, which are only Q2 and Q3. Because the other ones, our field lines are going to go in one side of the surface and out the other, right? If you look at Q1, that takes a positive charge. And our field lines go away from positive, so it's going to go, well, it's going in one side of the surface, out the other. It's not contributing to the net flux. The only ones that will are Q2 and Q3. But which ones will contribute to the electric field at point P? Well, even though Q1 and Q4 are not within our surface, they don't contribute to the flux, but they will contribute to the overall electric field. field. Because if this is positive charge again, well, at point P, there would be an electric field due to that charge kind of going off at that angle there. So the answer is all of the charges will contribute to the electric field at point P, which is why this would not be a Gaussian surface that we could use to find it, right? These are point charges. We wouldn't be able to draw a Gaussian surface that had symmetry where the field is the same everywhere that we could apply Gauss law to. And so why are they different? Well, they're different because really we're not talking about the same quantities, are we? Flux is different than the electric field. Flux depends on charge enclosed, while the electric field depends on all the charges in that space around it, right? So kind of defining what those two things are and why they're different quantities. Okay, if the net charge enclosed by a surface is zero, does this mean that the field is zero at all points on the surface? So what that means is if we say that this is, say, a positive 1 nanocoulomb and this is a negative 1 nanocoulomb, well, what we're saying is that charge enclosed is zero. That we have a net zero charge enclosed. Does that mean that our electric field has to be zero everywhere on the Gaussian surface? What do you guys think? Well, the answer is no, it doesn't have to, because the electric field is not the same everywhere, right? If we look at here, at this point, well, the electric field at this point, which is due to all of these charges, is not going to be the same as the electric field on this point on the surface. So this goes back to, I mean, if you want to show, some people may want to say, well, because Gauss's law is the integral of E dot dA is Q enclosed over epsilon naught. If the Q enclosed is zero, that means the field has to be zero. Well, that's only if you can use Gauss's law. And we can't use Gauss's law here because the field is not the same everywhere on the surface. So no, it's not true. And so some things that we could say there is the field is not the same everywhere. Okay. We also could have like an electric dipole on there, right? But really this all goes back to the electric field is not the same on all points on the surface. And then there was one more too that I didn't put on here that I want to ask you before we go, and that is the reverse true, right? So if the electric field is the same everywhere on our surface, does that mean that there has to be no net charge enclosed? So if the field is zero, go over here. So if the electric field is zero everywhere, the Q enclosed is zero. And that is true. The only way that we could get that zero electric field there is if our Q enclosed is zero everywhere. Okay, so that is Gauss's law for tonight. Hopefully conceptually you can explain what surface you would choose. I can see that being asked on exam this year, absolutely, is given a charge distribution or shape, what Gaussian surface would you choose? Looking at what charges are contributing to flux or contributing to field, kind of like that end question here that we dealt with, and understanding the concepts behind it and not just kind of the derivations of all of the E fields that we derived. Is it important to be able to do that? Absolutely, because math can still explain concept, but understanding that basis of what is Gauss's law, what kind of surface would you choose is really, really important for the exam. Roger, anything you want to add in? You want to unmute yourself?
Thank you. I just want to unmute myself and say thanks for working so hard. We really, we know you guys are working hard getting ready for the exam on the 11th, and we hope that you keep joining us every evening and we can do this together.
Okay, we will see you tomorrow.
Well, good evening, everybody. Welcome to AP Live. Every night we come to you with, for this particular channel, AP Physics C, Electricity and Magnetism. My name is Roger Siegel, and I teach at Pineview School. We're coming to you live tonight from Sarasota, Florida. And my friend and co-teacher is Kristen. Hello, Kristen.
Hi, everybody. I am Kristen Gonzalez Vega in Frisco, Texas, where I teach at Reading School.
Excellent. So Kristen and I go back and forth with the lessons every night, and we're here to hopefully get you what you need to be ready for the AP exam on May 11th. So the first thing that I want to do is I want to start sharing my screen with you. That doesn't do that, sorry. Here we go. All right, share. All right, good. I'm going to share my screen with you. And I'm going to come over here and let me get started with where we are tonight. Okay. And so that here looks like this. And so here we go. Sorry. Tonight is day 5, review day 5. We started on Monday. And tonight we're reviewing section 1.5 from the course and exam description. And it's electrostatics, field of other charge distributions. And we're going to look at the electric field from a line charge and in different shapes. This tonight could be one of the most specific and directed lessons that we do the whole season, because it's just about this one particular concept and how it works. Before I get started with that, I wanted to go back and finish a problem from last night. And last night we were talking about Gauss's law and how we could figure out the charge in different places using Gauss's law. And so I wanted to come and take you back to this page so that we could get you some more, just this one last bit done. Okay, so up here we have a solid cylinder of radius A is concentric with cylindrical shell of inner radius B and outer radius C. Both materials are conductors, and that is very important. That is extremely important. We'll come back to that in a minute. The inner conductor has a net charge of Q, and the outer conductor has a net charge of Q, capital Q. Both conductors have a length L, ignore Fx. All right, good. Now, they want to know, determine the electric field at a distance R from the axis. So here is our distance R, okay, and R is going to go from here to somewhere. Now, notice we first have, A is my inside cylinder, and then to B is the inside surface of my outer cylinder, and C is the outside surface of my outer cylinder. And we're going to go to some R between those. And so what R is that going to be? Well, first we're going to say R is less than A. So that means that we're looking right in here at the charge. Now, I'm going to go back to here because I said this was important, conductors. And this is why this is important. If I have a conductor, all of the excess charge of that conductor lives on the surface. All of the excess charge. So what does that mean? Well, we were told here that the charge on the conductor is Q, is inside conductor is small q, right? So I've got this small q charge. And where is that charge? Well, it's all on the outside. And so since it's Q and it's Q plus, I have all of these plus charges on the outside. Now, when I say that, I want to be very clear. There are still electrons here on the inside. Okay? There's still protons and neutrons and electrons in there. What we have on the outer shell is the excess charge. Anything that is above, once there's an extra electron for every proton, it will go to the outside. Or if there's not enough electrons, then we have an extra proton on the outside because it's unshielded. So that's what we have. So all my charges on the middle. So I'm going to use Gauss's law to go ahead and figure out what is my electric field. And so remember, Gauss's law says the closed surface integral of E dot dA is equal to Q enclosed over epsilon naught. Now, this is the interesting part. This is the excess charge enclosed. How much excess charge is enclosed if I am within A? 0, because all the excess charge lives on the outside. And so that means that my E field here is indeed 0. Now, if I am between A and B, if I am here, for example, my radius is here, what is the electric field in here? Well, for this one, remember, the way we do this is we create a Gaussian cylinder around my inner charge. And so that Gaussian cylinder has, if I look at the net diagram of my Gaussian cylinder, and you might want to go back and look at last night's work for this. When I enclose a cylinder with a Gaussian cylinder, I get 0 flux at the end, and my flux here, this is the length of the cylinder, and this is 2 pi r, the circumference of my cylinder. And so what I have then is, let me turn down here, is some space. I have that closed surface integral of E dot dA is equal to N, that's my charge enclosed, over epsilon naught. Both of these are constant. The E comes out. My surface area of my cylinder that has a flux through it is L times 2 pi r, the length of the cylinder, times the radius 2 pi r. And that's equal to the charge enclosed. Well, that also is the length times, or well, I'm sorry, let's see, we'll make this just as big as it needs to be, because in this problem we're ignoring edge effects. And so we just have, well, we do have our length here, and this is going to be length times Q over the length, or total Q, and that's E naught, the L's will cancel. And so we're going to get E is equal to Q over 2 pi r L, and that's the length of our cylinder. Now, the reason, one of the reasons I wanted to come back and do this one, actually, let me go ahead and finish. Now, if I'm here between B and C, that means that this charge here, remember, is Q plus, and that's on here. Now, one of the laws of the way charges behave is that the electric field inside conductor has to be 0, must be 0. And so how do we make the charge inside conductor 0 if I've got this charge, the electric field inside a conductor 0 if I've got this charge. Well, the way I do that is this Q is going to pull a Q minus out of this metal, out of this surface. And so this outer shell is going to donate a Q minus to the inner shell. Now, where did it get that Q minus? Because what did it have to begin with? It had capital Q. And so now what we have is the rest of I am failing on this one, so I am going to go back to my notes and punt, but I will come back to this and we will keep moving. Now, what I want to tell you about this a minute ago, the reason I wanted to look at this problem is because notice what they're saying. They're saying ignore edge effects. All right. Now, this is important because in order to use Gauss's law, we have to have a perfectly symmetric setup. All right. And if we don't have that symmetric setup, we can't use Gauss's law. So tonight's lesson is really about these times when we can't use Gauss's law. So what we're going to do tonight is we're going to look at the fields of other charge distributions, ring, line, and arc. So after today, and I did say a minute ago, this is going to be perhaps the most directed lesson we do. It's very specific and very prescribed. We know exactly what we're doing. And it says derive expressions for the electric field of specified charge distributions using integration and the principle of superposition. Examples of such charge distributions include uniformly charged wire, a thin ring of charge along the axis of the ring, and a semicircular part of this semicircular part. Now, here's where we're going to talk about the limits of Gauss's law. Gauss's law is true. There's not a time when it's not true. However, we can really only do this integration easily. It only becomes doable when we have a perfectly symmetric charge distribution. Now, yesterday we talked about there were 3 perfectly symmetric charge distributions. One was a point charge, okay? And a point charge, we put a sphere around that, and so we have an imaginary Gaussian sphere. Okay. Our second charge we looked at was a line charge, either dimensionless line, or we could have a cylinder. And as long as it was long, as long as our cylinder was really long compared to how far away from it we were, then we would have that would be a cylinder or a line charge. Okay? And as long again as this distance were small compared to this distance, a very long cylinder, then we would use a cylindrical Gaussian surface. And then also, and you'll see this if you look back at last night's work, we talked about if we had a really big sheet of charge, we would also use a cylindrical surface, Gaussian surface. By the way, that can be done with a rectangle as well, but we're not going to have to do that tonight. So Gauss's law is true, but we only apply it in the most rarefied air form. We don't use it in very other instances. And if we do have another instance where we don't have symmetry, it forces us to do some integration. So some charge distributions require that we integrate. And so what we do is we just basically integrate all over. We use the point charge equation, but instead of Q, we use dQ, a tiny little differential Q. So I'm going to do one of these, and Kristen's going to do one, and you're going to see that this is something that is going to really make you feel good about all the calculus you've studied in your life. All right, so this says a thin line of charge Q is uniformly distributed along the length L on the x-axis, A units to the right of the origin. What is the electric field at the origin due to this charge? Okay, so let's take a minute and just make sure we see what we've got. We've got this this line of charge. It is uniformly distributed. It's the same everywhere, this Q, and it starts here at a distance A to the right of the axis, and it ends a distance L from that. It's L long. Okay, now let's go ahead and take a look at this problem and see how we do it. And again, you're going to feel very good about the calculus you've done. Now, the way we do this problem is first, we're going to figure out a way to instead of, let's talk about for dq, what we're going to do. Now, since this charge is spread out in space, we can't use the point charge and say this vector plus this vector. We have to do an integral and add up an infinite number of these vectors. So I usually just start with E is equal to the sum of a whole lot of tiny dEs. So look, here's a dq here, and it makes a little field here. That's a dE. That's from that little bit of dq. And then maybe this dq over here, okay, it's a really small part. It's further away, so it makes an even smaller dE. And if I can find all the dq's and add them up and add up all these dEs, then I'll get the total electric field. So that's what I'm going to try and do. And so first thing is, after we get here, we want to say, well, what's dE? Well, dE is equal to k dq over r squared, just that. So we have to take, again, every little dq. And so what we need is to figure out how far that dq is from the origin. And the distance that it is, we're going to call x. And remember, this is a little dq. Now, how do I know how much dq is? Well, what I'm going to have to do is I'm going to have to take my total charge here, q, and I'm going to have to divide it by the length. And that's going to give me what's called, I'm going to use the symbol lambda, and that's called the line or linear charge density. Okay? And that is coulombs per meter. Okay, so that's my linear charge density. Now, yesterday we looked at a lot of different charge densities. Just to remind you, I'm going to put a little star over here. I'm going to bring that up here. We looked at lambda, which was our linear charge density or our line charge. The small Greek letter sigma is our area density, and the Greek letter rho is our volume density function. Now, this one is a line charge, a linear density function. And so that's how much my linear density is across here. And you're going to see why I need this in just a second. Now, one more thing we're going to do before we're going to take this all home. The distance from here to here, this tiny little dq, is made up of a little bit of length called dx. That is my differential. Okay. Now, here's where the magic happens. dq is equal to lambda dx. Now, let me just stop for a minute and try to impress on you how important it is to understand that point before we move on. If I can know now what the q is in terms of x, now I can integrate all along x. And so each little bit is just the length times the density, each little short. And so I'm going to bring this guy down, and I'm going to say that dE is equal to k, and I'm going to say that my dq is lambda dx, and my distance r is actually this distance x, so that's x squared. And so you can see that the lambda comes out. So let's go ahead and integrate this. And so that means that E is equal to the integral of all the dEs going, and so this is the integral of k lambda dx over x squared. And the question now, what are my limits of integration? And he always asks that. And so my smallest value of x, you can see, is here at a. So x is going from a to this distance over here, which is a plus l. And so I'll go ahead and go from a to a plus l, and it's just going to take us a second to finish this. You can see hopefully here that the lambda and the k come out front, and so I'm going to finish this over here. This is k lambda, integral of dx over x squared from a to a plus l. And this, when we integrate this, we're going to get negative 1 over x, k lambda over here, negative 1 over x going from a to a plus l. Now, this negative, right away, I know what the direction of my electric field is. I'm going to ignore this negative. I apologize if that's not everybody's happy about that, but let's keep going. All right, so that's going to be what we have is k lambda times the quantity, and this is going to be 1 over a plus l minus 1 over a. And so that's going to be k lambda, and we're going to get a common denominator, a over a times a plus l minus a plus l over a times a plus l. And so what we end up with is k lambda times, in the numerator, we get a minus l, and again, ignore the minus sign, over a times a plus l. Now, last thing before we send it over to First Texas. Sometimes, a lot of the times, but not all the time, you can look at an answer and ask yourself, does it make sense? And so let's take a look at this answer and say, does it make sense given what we know? Should the electric field equal to k lambda times l over a times a plus l? Now, first of all, we would imagine that if lambda, and I need to do something here, goodness me, noodle, that's k lambda, and remember lambda is q over l. So that's going to be Q over L times L over A times A L. And so again, this is now Q. All right, so the question that I have for you is, does this make sense? How would we increase the electric field? So if I increase Q, would that increase the electric field? Absolutely. What if A increase? All right, and notice there's two A's in here. I have an A squared plus A times L, right? So if I increase A, not only does this part get further away, but this does too. So I decrease my E field by more than 1 over the increased square. Also, look at the L. If L goes up and A doesn't, I get a bigger rod here, which is now this part is further away than this, and so it would contribute less if I had the same charge. So it's always good, not always. It's often a good exercise to look at a problem and say, look at the answers. Does that answer make sense? The way a problem is playing itself out. All right. So we've got a few more to do for tonight. Hang tight, Kristen. Are you ready for them?
Yes, sir.
Okay, take it away.
Okay, so we're gonna look at a ring of charge and what happens to find the electric field. And I'm going to show you a shortcut actually. But first thing I'm going to do is kind of show you the long way to show all the steps. So then you can see when I say what the shortcut is, you can understand that it does work out the same way. So I've got a thin line of charge Q, where the charge is uniformly distributed along the ring, and we want to know what the electric field is at a point on the axis of the ring X away from the ring. And so the first thing I want you to do is I want you to take a couple of points on the ring and break it up for me. So we're going to make a couple of different little DQs. So let me tell you where I want. Let's look at this little section right here on top of the ring. And let's look at this tiny little section on the bottom of the ring. So if the whole charge is Q, then I know that my tiny little sliver up here has a charge of DQ, and the tiny little charge on the bottom here also has a charge DQ. So what I want you to do is at this point right here, I want you to draw me two different field vectors. What would the electric field be at this point due to the top little DQ, and what would the electric field vector look like due to the bottom DQ? So draw me two vectors. Which way would they be? Which way would the electric field be due to the top charge and due to the bottom charge? And so we want to know what charge this is. What's the magnitude of the charge, right? If this is positive Q, then we could say that the electric field due to the top is pointing, well, it's kind of right there for you, isn't it? Down and to the left. So we're just going to call this E from the top, ET. And if I look at the bottom one, it's going to have an electric field up to the right. We'll call that EB for the electric field from the bottom part of the ring. Well, if this is a DQ, right, this is the tiny little differential of the whole charge, and really I don't want to call it E, it's not the whole electric field, it's the DE due to those charges. Okay, so let's look at how we could find just one of these. Let's take this top one right here. How can I find what that one DE is? Well, we just learned a minute ago that we know that DE is K times DQ over R squared. Right? But we've got an angle here, right? We don't like angles. We're going to look at the components here, and let's look at which of the components are going to be significant. Right? Both or just one of them. So I'm going to break this up into an X component and its Y component. And I'm going to break the bottom one up into an X component and its Y component. What do you notice? I know you see it. If I look at the Y components, I've got positive Y and a negative Y. And if I'm taking the exact same little DQ here, then those would be the same components. So our Y components are going to cancel out. And we can do that all the way around the ring. The only thing we're going to have left with is our X components. So I'm going to redraw this here so that we can see our geometry and trigonometry here and what we're going to look at. So here we know this is theta. It's like on the side of the screen here. So this is R and this is theta and this is X. And so this is also going to be theta. And we want to multiply by what? What do we want to multiply by to get just that component? We want to multiply by the cosine of theta. And so that will give us that first one here. Okay. So if we want to then solve for what that is all the way around, well, we got to address what is the DQ, what is the R, right? So you always want to be looking at when you have these different charge distributions, what variables are changing and what variables are constant in your equation, right? Because that's what you're looking to see. How are you going to integrate the different charge distributions? There are different things that are changing. And the one before we had that changing X across. Well, in our ring of charge here, well, we know that the R is staying constant as we integrate around our ring. Okay. So if we also know that angle theta is going to be staying constant. If our X is constant, and our R is constant, and our theta is going to be constant. Okay? But we don't know what theta is, so we need to plug in for theta. What can we plug in for that cosine of theta? Well, cosine of theta is going to be adjacent over hypotenuse, or R over our R. And what would our R be in terms of our X and our big R that we know, the radius of the ring? So those are things we want to be plugging in. So we're going to say this is DE equals K DQ over, we know that R is going to be equal to the square root of X squared plus R squared. And so we know R squared is just going to be X squared plus R squared. Okay? And then we can plug in the cosine. We're using this. Our cosine is going to be equal to X over R, or F over the square root of X squared plus R squared. And this probably isn't starting to sound familiar from last night because we did a 2-point charge where we were using the same kind of ratios. And so if I combine these in, then I get DE equal K DQ times X over, this becomes X squared plus R squared to the 3 halves. Okay? So we're all set up now. If I want to find what the net electric field is going to be there, now we're going to integrate. So if I'm integrating both sides and we're integrating all around that circle, well, the X is constant, the R constant. The only thing that's changing is that DQ. And if we integrate all the way around, what do we get when we sum up all the DQs? We get just Q. So E is going to equal K times Q times X over X squared plus R squared to the 3 halves. So here's my question. If we had just taken this as 2-point charges, I need a different color here. I mean, we use this one instead, actually. Let's use a fresh one. If I were to take this as just 2-point charges instead of my ring, and each point charge had a Q of our total charge over 2, half the charge was on the top and half the charge was on the bottom, well, we would get the same thing because remember, we got this equation last night, but since each of them really had Q over 2, but there was 2 of them, well, we end up getting that same thing. So that's kind of a shortcut on the ring, is you can treat the ring like it's 2-point charges, and where each of those point charges is equal to half, say, let's use little Q, right? Each of those is equal to the total charge over 2. So just a little shortcut there. Okay? And then we've got one more question here with the ring. At the time, we had half of the ring has one charge, isolated, and it has an insulator between, so that we can have the top half be negative charge and the bottom half is positively charged. And we want to know what is the direction of the net electrostatic force on an electron located inside of the circle. So if I placed a little electron in the very center of the circle here, which way would the electrostatic force be on the electron? So I know that you can reason through this, but what I want you to do is I want you to write me a sentence, right? We practice already. Write me a sentence not using that the negative charge wants to be attracted to the positive or repelled by the negative. I want you to write me a sentence where you are using that electric field to explain which way the force is. So A, determine which way the electric field is, and then B, tell me how you know then which way the electrostatic force would be on that electron. I'll pause just for 1 second here. Have a drink of water while you're doing that. And so let's first look at which way the net electric field is going to be in the center. So if I'm looking at the top half of the ring here, we know that we have a negative charge. We know the electric field is going to be pointing away from positive and toward negative. So if I'm breaking it up, let's just look at kind of 3 different spots here. Look at that field. So we've got negative charge here. So we've got an electric field pointing towards the right upwards. We've got an electric field straight up, an electric field up to the left. Again, what do you notice now about the X components? Well, now the X components are going to cancel, and we're left with a net upward electric force due to the top half of the ring. Let's do the same thing with the bottom half of the ring. The bottom half of the ring is positively charged. Let's again take just a few little segments here. And if this is positively charged, then our DQ here is going to give us a DE this way. If we look at this one this way, and the very bottom straight up, again, what do you notice? X components are going to cancel. We're left with a net electric field pointing upwards. So we're going to combine for one big net electric field upwards. So what does that have to do with the force on the electron? Well, we know that the force is related to Q times E. But positive charges, remember we said forces in the same direction as the electric field, and negative charges experience forces in the opposite direction. So the net electric field is pointed upwards. Which way the electrostatic force be? It would be downward. Right? So making sure that you can explain this lesson different ways using physics, not just repelling or attracting, like kind of going a little bit deeper than that if you can. Okay, so that's all I've got, Roger. If you want to finish us off here.
Yes, I want to. Okay. Well, great. All right. Thanks, Kristen. Well, let's go back to some more problems here, and let's do a couple more before we call it a week. You guys are doing great. So here we have, this is a wonderful problem. It says a rod of uniform linear charge density lambda, there it is again, is equal to 1.5 times 10 to the minus 5 coulombs per meter, is bent into an arc of radius 0.1 meter. The arc is placed at its center at the origin of the axis shown, determine the total charge on the rod. Well, the total charge, Q, is going to be the charge density times the length. Actually, I'm going to call it S, because usually when we do an arc length, we call that S. And so that's our arc length from there to there. And so that's going to be lambda. And the arc length, since I've got 60 degrees and 60 degrees, that's 120. That's a third of a circle. That's going to be 1/3 times the circumference, 2 pi r. So we're going to do lambda times 1/3, 2 pi r. And when you plug all the numbers in here, what you get is 3.14 times 10 to the minus 6. And that's going to be Coulomb. And by the way, that is 1 micropi, if you want. I've never seen an answer come out like that, but that's a micropi. It's 10 to the minus 6 pi's. Okay. So then the next piece says determine the magnitude and direction of the electric field. Now here is where we get into, again, the geometric integration. And so we're going to go ahead and integrate this thing geometrically. And so let's put a circle in here. Let's put an XY, make it easier for me to do this. And let's see what we can get from this. Now, what we're going to say is, again, we're going from here to here. And just as Kristen showed us before, I'll bet I can convince you that when I add all these up, the only component I'm going to have is going to be in the x direction, because all the components in the y direction are going to cancel. And so I only really care about x. And I know that dE in the x direction is equal, again, to dE cosine of the angle theta. Okay, so that's the x direction, and that's the angle, that's theta. And so once again, this one's a little bit tougher, though, than the one before, and I'll show you why in a minute. So we're going to say this is going to be dE cosine theta. And what is our dE? Well, that is k dq over r squared cosine theta. And now, again, that's dE in the x direction. Now, before we changed the theta to a number, to a variable x and y, but I want you to notice what's different here. The r here, the radius, the distance to my dq is always the same. So that's going to be a constant. I can pull that out. But what is my dq? That's what's a little tricky geometrically, but I bet some of you remember how to do this. So I've got a tiny little angle here, and that's my d theta, okay? And dq is going to be this little ds times lambda. That's lambda times the little bit of the arc. But what is that little arc length? Well, that's going to be r d theta. So what we're doing is we're going from the geometry formula that the arc length is equal to r theta. So ds is going to be r d theta. So what we then have is we have k, and then dq is going to be lambda r d theta over r squared cosine theta. And I'm going to integrate that from, now I could go from negative 60 to 60. That would be my cosine. But because of symmetry, I'm going to get even easier. I'm going to go from 0 to 60. All right. And so if you look here, one of the r's cancels. Everything else is a constant except for the cosine and the theta. So what I get then is I get 2k lambda over r times the integral of cosine theta d theta from 0 to 60. And so that becomes quickly, that's 2k lambda over r sine of theta from 0 to 60, and 2k lambda over r. The sine of theta is the square root of 3 over 2. Now k is 9e to the 9th. That is our Coulomb's law constant. Lambda is 1.5e to the negative 5 coulombs. We have our radius, which is 0.1 times the square root of 3 over 2. And so when I'm all done, I get 2.3 times 10 to the 6 newtons per coulomb. All right, that's a fun one. I want to do one more for tonight, and I want to move on to skip this one here, and I'm going to skip it. And by the way, and let's go down to this one. All right, so because this is one of the things we talked about tonight, why can't I use Gauss's law? So notice here we've got this lambda, and notice my setup. Here's my y is equal to c. Here's my point. Here's my charge right here. So I've got this charged rod, and again, it's got this linear charge density of lambda, and that's going to be lambda coulombs per meter. All right, is there a single Gaussian surface that can be used with Gauss's law to derive an expression for the electric field? Now I think I already gave it away, because at the beginning of the hour, that's what I talked about. So the answer is no, you can't use Gauss's law. Now I want you to just try and think in a sentence or two, why can't we use Gauss's law? I hope that one of the words that you think that you're going to use to say why we can't use Gauss's law is the word symmetry. And the fact is that there is not symmetry in this problem, and since it's not symmetric, we can't use Gauss's law. So Gauss's law requires a high degree of symmetry of the electric field. To use Gauss's law, C would have to be much greater. C would have to be much less than A plus B. Now, when we did this last night, we talked about an infinite line of charge, and then we used Gauss's law. Or we did a problem at the beginning of the hour, and it said to ignore the edge effects. And again, that's code for it's okay to use Gauss's law. When they tell you to ignore the edge effects, it means you can kind of fudge on the lack of symmetry. They're saying don't worry about the lack of symmetry. Go ahead and use Gauss's law. But in this problem, the lack of symmetry is a signal for us to not use Gauss's law. And the last thing before we go is I want to look at this one. And we have no idea what this year's test is going to be like, but this is a problem that I think really a lot of students struggled with it when it came through, because they weren't used to doing the integration. And it says one of the two expressions is not correct for the horizontal and the vertical component of the electric field. Which one? And so this is going to be our last problem for the night. Let's take a look. Which one of these do you think is wrong? Now, I think from the work that we did last night and the work that Kristen just did, we keep seeing this distance to the 3 halves. That is a consistent, a recurring part of our solution. It's this one that's wrong. Okay, so which one is not correct? The vertical. Now, look at how these guys at AP, I tell you, they always make it so hard. 2 mistakes, and you're like, wait a minute, 2. I thought it was just because it was this one. But take a good look. Take a really hard look. When you integrate, which way do you integrate? When you're solving for the horizontal, here's our DE. Here's our horizontal component. Here's our vertical component. Okay. Now, when you're solving for that, you're always doing what? Well, you're marching across from B to A. And since you're going from B to A, ladies and gentlemen, or I'm sorry, from negative B to A, you're going dx, not dy. Look at that. So if that kind of problem came up, don't forget to look at the differential, because it could show up. All right. Next week we are going to keep working on our review of electrostatics. We are going next week to start looking at potential. I think on Tuesday. So potential is a really big challenge for a lot of students, but we're gonna get you through it. I think it's called but we'll come back to that. We hope that you have a great weekend. Kristen, how's it going in Frisco?
It's great. It's Friday night, almost time for some dinner, and hope you guys have a wonderful weekend.
Excellent. So again, thanks for joining in. We hope you're having fun. We hope you're finding this helpful. And if you need any more resources, see the AP website, because they've got so much to help you study for this exam. Can't wait to see you on Monday. Thanks a lot. Bye-bye.
Well, hello, good evening and welcome. My name is Roger Siegel, and I'm coming to you live from Sarasota, Florida, and welcome to AP Live. Tonight, this is AP Physics C, Electricity and Magnetism. And joining me is my friend and co-teacher, Kristen. Say hello, Kristen.
Hello, everybody. My name is Kristen Gonzalez-Vega, and I am a teacher here in Frisco, Texas.
All right, well, wonderful. Well, it is, as I said, it's great to have you guys here. So since last time we were together, we did learn some new things from AP about the dates of the test and the format of the test. So as we get more information with that, we'll continue to share that with you. But we want to let you know that you can go to the AP website and find updates on all tests, their dates, and how any changes that you might know about. I would say the most important update for us is, besides the time, is the fact that we're going to have an open note and an open book test. And so that really gives us a lot of opportunity to leverage all the information that we've gathered all year, whether that's notes or how your teacher has laid out for you. But AP is counting on you to have access to that. Not like they're asking you to, but they imagine that you will. And so I think as we get studying and reviewing, and this is our first review session tonight, you want to think about organizing your information almost like a control panel, so that when you sit down to take that test on May 11th, you know where every piece of information information is, you know what unit that's from. So if you have to look for something, you can do it really fast. So anyway, we'll talk about that more as we get into this. I know I'm really excited about creating some opportunities for my students in that way here in Sarasota, and I hope you guys can have fun with that too. All right, so I'm going to jump in and start sharing my screen. And as I said, tonight is our first night doing review and getting you guys ready for the AP exam. Now, I did say May 11th, the AP, all of your AP exams have been pushed back 1 week from their original date. So yours was going to be on the 4th. Now it's going to be on the 11th, on Monday. And so we're going to, between now and May 1st, I'm sorry, we've got 4 weeks for Chris and I. We're going to go through the entire curriculum and get you ready for this exam, and that starts tonight. So we're really excited. Okay, so tonight we're going back to day 1, and this is probably day 1 of your class, whether you're taking a year-long or a semester. This is day 1 for you, and electrostatics, charge, and Coulomb law. And so if you, let's just get started. So first, I want to say some things that you're going to learn from today. So we're going to talk about charges and positive charges and negative charges, and static electricity, electrostatic forces, and how they interact with each other. And we're going to explain and describe the behavior of these neutral object near a charged object, and then we're going to apply Coulomb's law. Okay. So this, of course, we assume that you have had this. This is review, so we assume you've had this class, and so we're going to kind of go through this real quick and then get to the meat. So first of all, we know that all objects have charges because all objects are made up of electrons and protons and neutrons. However, most objects have the same number of protons and electrons that are neutral. If we change that balance, an object can be either positive or negative. If it has too many electrons, if it has more electrons, protons, negative, and vice versa. And if an object is negative, it will be attracted to a positive object, but it will repel negative objects, and also positive objects will repel positive objects. So like repels and unlike attracts. The things that allow charges to move, generally objects or substances allow charges to move really easily, are conductors, like metals. And objects or substances that block the flow of charges are insulators. And one of the most important insulators is air. Air is a fantastic insulator. It's very hard to get a current to go through air, get charges to move through air, rubber, glass, plastic. These are all insulators. Okay. So electrostats. So I want to talk about this. And this actually, you know what, we're not going to talk too much about this. I just want to talk about attraction and repulsion because I know tomorrow night we're going to get into this in a lot more depth. But let's move on to our next little thing. I want to do a demonstration for you guys. So I'm stuck at home because we're in the middle of our quarantine here in Florida, as you probably are where you are, most of the world is. And so I was thinking, how am I going to demonstrate static electricity? Static electricity is one of the things that I've been demonstrating since I was a little kid, since I learned that if you rub your hair, rub a balloon with your hair, you can get the balloon to stay on the wall, to stick to the wall. That was pretty cool, right? So guess what? No balloons in my house, and I don't think that's an essential thing. So I didn't go out to get balloons, but I did go online and I saw somebody do this. So I'm going to show you what I have here. Let me kind of lean in here and take a look at this. And so this is a Coke bottle, and on top of it, we have just put a little needle or pin actually coming out of the top of the Coke bottle. And I have a paper straw here, and I don't know if you can see this. I don't think so, but I've cut a little slot in the straw so that I can just balance the straw on it. And so with a little bit of finessing it, kind of like move it back and forth, you can get this thing to balance so well that we have a super low friction bearing. I mean, look at that. It's starting to already move a little bit. So I don't know if the air conditioning's on in here. Could be that. Always an issue when you have sensitive equipment. But look at this. We create a really sensitive device. Now, how do you make static electricity? Well, one thing you can do is I said you can rub your hair with a balloon. I have neither hair nor a balloon. So, and I don't have a lot of sweaters here in Florida. So one of the best ways to make electricity is with Scotch tape. If you take a piece of Scotch tape and you put it on top of another piece and then you pull them apart, you can create some good static electricity. So watch what happens. This is now a charged object. This is a neutral object. And watch what happens when I bring this close. Oh, look at that. Wow. See that? We've got some attraction right there. Let me try that again. A little bit of attraction. Oh, there's some attraction. Right from this side. That's a track. Oh, there we go. And so you can see here that we can easily have these interact. And this is charging. This is a positive charge. This is neutral. Why is it attract? Well, even though the straw is neutral, it's made up of trillions upon trillions upon trillions of atoms. And those atoms have electrons, clouds around the outside, and nuclei in the middle. And when this positive charge gets close to these atoms that make up this paper, those atoms elongate a little bit, and the positive charges the negative charges get attracted. And so every little atom's electrons out gets a little dipole, gets pulled apart. And so even though this is a neutral object, it'll still be attracted to a charged object. And so we'll play with that a lot more tomorrow. I think that's going to be a lot of fun. So that's what we do at our lockdown. That's teacher lockdown. Okay, now let's see. So the next thing I want to talk about is Coulomb's law, and then we're going to do some problems. So Coulomb's law is one of these fundamental laws that describes the interaction between charges, and it's fundamental because it's a force law. It's field law. It tells us about over distance how two things can interact with each other. So here we go. Coulomb's law. 2-point charges exert force F on one another. It is directly proportional to the product of the magnitude of the charges Q and inversely proportional to the square of the distance R between their centers. In other words, the force electrostatic is equal to KQ, KQ1, Q2 over R squared. What's that mean? If I have a charge here and a charge here, and this is positive, say, and this is negative, well, they're going to attract each other. And how much attraction is going to depend on how much charge is here, how much charge is here, and the distance between their centers. And we usually call that distance R. Now, I'm hoping, oh, and by the way, this K is called the Coulomb's law constant, which this should be a large C. Sorry, Mr. Coulomb. Okay. So this K is Coulomb's law constant, and it is 9.0 times 10 to the 9 newtons meters squared per Coulomb squared. Of course, it's on your formula sheet, and it's readily available to you. Now, so that is how Coulomb's law works. The last thing I want to say before we start doing some problems is I want to talk about, hopefully, when I was explaining Coulomb's law, I really hope that some of you went, wait a minute, that looks familiar. Did you say that? It does, because that is, check out, this is gravity. Now, we studied gravity in AP Physics C mechanics, and I'm sure you studied it in other classes if you didn't take that one. But the force of gravity, check this out, is some constant times the mass of one object times the mass of the other over their distance squared. How similar are these two relationships? That's interesting, isn't it? Coulomb's law and the law of universal gravitation are essentially are mathematically the same. What's different is the substance. This is about how two masses interact. In the universe, if you've got two masses, they will attract each other. This is about how two charges interact. If there are two charges in the universe, they will either attract or repel each other. End of statement. Okay, so of course, none of this means anything until we start to try to do some problems. That's really how we do that formative work, to really think about, okay, how does this make sense? So we're going to throw it over to Frisco, Texas, and Kristen's going to take it from here.
All right, thanks, Roger. And if you look at what those constants are, the magnitude of those constants, and I love comparing that too, because if you look at the universal gravitational constant, that's 6.67 times 10 to the negative 11, and you look at the Coulomb's law constant, 9.0 times 10 to the 9, you can see really like what the difference in those forces is and the magnitude of those forces. Okay, so let's do a couple practice problems here. So we have here two particles, each of charge positive Q, and they are on opposite corners of a square that lies in the plane of the page. We're going to put a positive test charge, little q here, at the corner of the third corner on the square. So we want to look at this, and we want to know what direction is the net force on that test charge. So we need to look at them all individually. So I'm going to kind of color code these here. We're going to call that charge 1 up in the upper left-hand corner, and I'll color that red. We're going to say that the bottom right corner is charge 2. Okay, so if we want to know what the force on that point charge is, well, there are two interactions here going on. We have one interaction between Q on the top and Q on our test charge Q. And if we want to draw the force on that, well, if they're both positive charges, then that test charge on the bottom is going to experience a repulsive force, right? Like charges repel. So there will be a downward force on that. So I'm going to call that force 1Q. You always want to develop a way that you can identify these different forces or interactions when we're talking about fields later on with charges or potential or whatever it is, energy. You always want to develop your system of keeping everything straight. We have multiple things going on. We want to have an identifier. So I always will do force with a subscript of what my two charges are in that interaction. Okay? And then we also have the interaction between little q and the bottom big Q. Again, we look, are they both positive? Is one positive or negative? If these are both positive, again, there will be another repulsive force on that touch charge, F2Q. So if we now just draw that off to the side here again, I've got a force to the left, I've got a force down. Well, if we look at these same charges, we know that force is KQQ, which would be little q, over the distance between them squared. Well, if we compare these two forces, they have the same amount of charge, same distance apart, so the magnitude of those forces will be the same. So if I have two forces that are at a right angle, how do we find that third vector? If we draw tip to tail, then our resultant will be down to the left, which would be KC here. If we go one step further here, how could we find what the magnitude of that force is if the force between each one of these is F, right? So if we redraw, we had that force down, we had that force to the left. And so if these are the same magnitude of force, how would we find that resultant force? Well, we'd use Pythagorean theorem. So the net force squared would be equal to the force between 1 and q squared plus the force between 2 and q squared. The magnitude of those two forces are the same. So really we can say that that net force is 2 times that force squared. And so then if we want to find if this is squared, if we want to find what that net force is, we just square root both sides. And so we get 2 times the square root of F, which is D. Okay, so a lot of times we see these kind of problems like this, or we may see a triangle with the forces, but finding each of those forces, and still important to always draw your free body diagram first. Okay, let's bring in a little bit here of mechanics into play. So I've got a small sphere of charge big Q, 2.5 times 10 to the negative 5 coulombs, placed at the bottom of an insulating tube. A fifth ball of mass 0.04 kilograms carries a charge of 1.6 times 10 to the negative 7 coulombs, is gently lowered into the tube until it reaches equilibrium. What is the distance D the fifth ball from the small sphere will be when it's in that equilibrium? Okay, some important words here, right? If it's in equilibrium, then we know the net force on that fifth ball is 0. So if we take a look at what those forces are, well, the fifth ball has mass, so we have that gravitational force acting down on it, mg. Then we also have this charge down here, and since there's two charged objects, there's going to be that electrostatic force between them. So we want to look to see, do these objects have the same charge or an opposite charge? Because we want to know which way that force is. So these vector quantities, it's really important to look at that direction. So if these are both positively charged, then we have that electrostatic force going upwards. And if it's in equilibrium, then we know they're equal. So we know that the mg down will equal that electrostatic force. And then we can plug in, well, the electrostatic force is simply k q over r squared. In this case, we're going to say that's d squared. And so if we want to solve for d, we got to rearrange, and we get that d is going to be equal to the square root of k q over mg. So if we substitute that in, d is going to equal the square root of 9 times 10 to the 9th newtons meters squared per coulomb squared times my 2.5 times 10 to the negative 5 coulombs times my 1.6 times 10 to the negative 7 coulombs over the mass, which is 0.04 kilograms times gravity, which is 9.8 meters per second squared, or always also acceptable 10. So usually for in-class work, I always use 10 because it's easier to do the math. But if we plug that in and we solve, we should get a distance of 0.3 meters. Now, if you notice, here I just use positive, but I also want to talk about what if one of these were negative, right? So obviously, if one of these were negative, then there'd be an attractive force and it wouldn't be in equilibrium. But when we're doing these equations and you're looking at these forces, we never want to plug in, or at least the way that I work through them, you can do different ways, but I never plug in the negative into my equation. I draw my free body diagram, I determine which way those forces are, do I add or subtract them, and I put them all in as positive, because drawing the free body diagram is going to tell you which way those forces are, and whether you're adding or subtracting them. What I mean by that is, let's look at an example if I had 3 charges, okay? And let's say I want to know what the net force is on this center one. Well, that's due to those other 2 interactions, right? We've got an interaction between the positive and the negative here, which would be an attractive force on this one, so let's call this 1, 2, 3. Between 2 and 3, but there's also an attractive force between these 2 here, 1 and 2. Well, if I want to know what the net force is on that middle one, if those forces are in opposite directions, I got to subtract them. The net force on this guy would be equal to force 1, 2, 3 minus force 1, 2. But when I go and plug in those charges, I'm not going to put a negative in my equation because I've already determined that direction of those forces, and so now everything becomes absolute value. So we're only determining the magnitude of that force at that point. It's kind of like when you're dealing with forces in kinematics, and if you've drawn your free body diagrams and know that mg minus ft, then we don't put in negative for the gravity in our equation. So same thing with the charges here. You draw the free body diagrams to determine which way those forces are, and we add or subtract, and then everything in the equation becomes positive. Okay? And then we've got practice 4 here. So we've got our charge ball, big Q, 9 times 10 to the negative 6 coulombs set on an insulating stand. A small sphere of mass 0.57 kilograms, charge negative 5 times 10 to the negative 6, hangs on the string. The distance 0.3 meters above the ball. We don't know what the tension of the string is. So maybe just a second, I want you to draw me the forces acting on that small sphere that's connected to the string. So draw me the forces, which way do they act? Hopefully you've got some paper there and are working along with us. And then write me a net force equation. So if you need more time, you can pause. But the first thing I always want to identify are those charges, positive or negative. I'm going to always label on my diagram. So the bottom charge ball is positive Q, and my top one is negative Q. So the first thing I'm going to draw in, well, if that's a negative and positive charge, there's going to be an electrostatic force going down. But this also has mass, so there's also that gravitational force going down, and it's connected by the string, so there is tension going on. So if this is an equilibrium hanging here, then we can say then that the FT up has to equal the electrostatic force plus the gravitational force going down. So tension will equal K big Q times little q over that distance squared plus mg. So if we plug that in, again, we get our 9 times 10 to the 9th times our big Q times our little q. Again, I'm not plugging in negative because I've already determined that direction. So that would be the gravitational force part plus our mg. Our mass is 0.57 kilograms times our acceleration due to gravity. So when you combine and add those together, you should calculate that the tension in the string is equal to 10.2 newtons. And so what would happen if we switched the charge, or if we changed the magnitude of the charge? We would change the amount of tension. So we'll kind of be doing a little bit more conceptual practice as we get closer to the test. But that's one thing that is going to be different about the exam this year, is that we are going to have to be able to explain things a lot more, because there will be less focus on calculations on the problems and more focus on the conceptual what's going on. Okay, which is kind of what number 5 is doing here. So number 5, we have 2 small spheres that each have a charge q and are separated by a distance d. If force on each sphere by the other has a magnitude of f, right? Newton's third law. If the sphere on the left has a force on it due to the sphere on the right, then the sphere on the right also has a force equal magnitude as the other one. So they each have a force on them that is f. So we want to know if the charge on each sphere is doubled and d is half, what will happen to that force between them. Okay, so yeah, I'm going to give you a second so you can set that up and get an answer, and then we will talk about it together. Okay, so first thing we want to look at is our equation. Our relationship is that electrostatic force is K over d squared. So we want to put in a little coefficient. What's happening to each thing, right? So if each charge is doubled, well, I'm going to put in a 2 in front of each of those charges. And if the distance is halved, well, I've got half the distance. But we got to be careful because that bottom is squared, right? So we want to look at what's going to happen to the left side of the equation here. If I have 2 times 2, well, the top is going to be 4 times as much. But I have half the distance squared, which means 1/4. Well, 4 divided by 4 means 16. Well, the right side of the equation is changing by 16 times as much, 16 times bigger. And the left side of the equation has to be 16 times as much as well. Okay, so hopefully that gives you some good practice on those Coulomb's law equations. And I'm going to toss it back here to Roger to do some more AP style questions.
All right, thanks, Kristen. Well, great. Well, let's go ahead and do a couple of great problems to take us home for tonight on this beautiful Monday night. I hope you guys are doing great wherever you're listening from. So I have a couple of problems here to look at. Here's the first one. And this is just like the problems that Kristen just did with you. This particular problem has the force of gravity involved. So we're never far from force problems when we're doing physics. So here you can see we've got 2 small spheres, each of mass m and positive charge q hang from these threads of length L. And the thread makes an angle theta with the vertical is shown. Derive an expression for the charge q in terms of ml theta g and the Coulomb's law constant. All right, so let's take a look at this and see what we can do. The first thing that I would hope that you would want to do is I would hope you would draw a force diagram, because clearly this is a force problem. And so I say, well, let's pick one of these, and the symmetry of the problem will allow us to solve it just once. Okay, so if I look at this one on the left, this particular one
triangle, and I draw it over here. Well, what are the forces that are acting on it? Well, there's the tension is pulling up at this angle T. Since this is happening on the Earth, this is the force of gravity, Fg. And then there's got to be a force pulling this to the left, otherwise it would be accelerating to the right, and that is the electrostatic repulsion, Fe. And so that's your first step. Take your time and draw a good force diagram. Now, as soon as we get this, we know, that this is in equilibrium. It is not moving, not accelerating, and therefore all these forces have to sum to zero. And when your forces sum to zero, that means you get a closed polygon. And so this is T, this vector plus this vector equals zero. Fe, T, and Fg. And we also know that this angle is theta. Now, another thing we do know is we know the length of this, but I wouldn't put the length on this triangle because this is a force triangle. We might need that in a minute. We'll see what happens. All right, so we want to find the charge. And so you always want to ask yourself, where is the thing that I'm looking at? And the place where the charge would be found would be in the electrostatic force. I don't know the tension. The tension is not one of my given variables. So I want to kind of stay away from that. So I'm going to go ahead, just kind of take him out of the game. We're not going to deal with tension. We'll just leave it over there. We'll see if we need it. All right, so now how do I relate these? Well, theta is one of my variables, so I can use that. And so I can say that tangent of theta is equal to Fe over Fg. And remember, we said that the thing we're looking for, the Q, is inside of Fe. So let's solve for that. Fe is equal to Fg tan theta. All right, now this is the electrostatic force, and we said that that is bound by Coulomb's law. So that's K Q1 Q2 over R squared. Now, I don't know what R is. R is not one of my variables, but I'm just going to hold it there for now. Later on, we'll have to come out and figure out what R is in terms of those variables. All right, and that's going to be equal to Fg, which is mg. Those are some of my variables. And so I'm going to solve this for Q. Now, each of these Q's, they have the same charge and the same mass. So that's going to be actually KQ squared over R squared is equal to mg tan theta. All right, keep going. Now, we're solving this for Q, so that means that Q squared is equal to R squared mg tan theta all over K. All right, now, we're close, but I said we can't use R. So let's go ahead and look and see, where is R? Well, R is the distance between these two. And so R is this distance from here to here, the distance from these two centers. Well, let me just look at this value here. Let me call that value right now. Let me just call it X, which is half of R. Well, that is related to theta, right? And this is X, this is my distance, and this is L. And so I said a few minutes ago, let's hold off on L. It doesn't go on the force triangle, but it does go on the space triangle, on the spatial relations triangle. And so let's go ahead and see what X is. And so it looks like the sine of theta is equal to X over L, which means X is equal to L sine theta, which means that R is two of those X's, or 2L sine theta. So let's just put a little box around there. So you'll see that came later, okay? And so we're going to go ahead and add that in there. And so we'll say Q squared is equal to, well, let's just say Q. I don't want to say Q. And let's solve this for Q. And so let's say the Q is equal to the square root of all this. So that's going to be R times square root mg tan theta over K. And so R is 2L sine theta times square root of mg tan theta over K. All right, so that is our charge in terms of the other variables. So again, don't get bogged down in the math. It's not about the math. Make sure you understand the diagrams, and though they have to be understood first before you start to pull everything else into it. All right, last problem of the night, of this beautiful Monday night, in wherever you're listening from. All right, so we've got two identical point charges, Q plus, sit on the y-axis at position 0b and 0 negative b. A different charge, Q plus, is on the x-axis at position d0. What is the net force Q from the two on Q from the two Q plus charges? Okay, now let's go ahead and take a look at this and see if we can make some sense of it. We've got these two charges, and we want to know how they're affecting this charge over here. Well, since these are both positive, this will feel a repulsive force in that direction, force electrostatic, from this charge, and this small charge Q will feel a repulsive force in this direction, actually symmetric from this charge. And so each charge exerts this force. Now, our job is going to be to find out what that force is total, the net force. Now, I hope I can convince you without too much trouble that when we look at this, this electrostatic force, it's made up of a vertical component and a horizontal component, as is this one, made up of a vertical component and a horizontal component. And I'd like very much to convince you that these two cancel out, and that what we have to do is we have to look at this electrostatic force electrostatic, extract the x value, Fe in the x direction, and then double it, because we have two of them. We have the x value here, and we have the x value here. And so I'm going to say that F net is 2 force electrostatic in the x direction. All right, so I'm going to start there. Again, one of the things I love so much about teaching physics is we get to use astronomy, we get to use algebra and calculus and geometry all together. That's great stuff. So this is 2 Fex. Now, what is Fex? Well, I'm going to put this angle theta here. Okay. Now, if you were to say to me, Mr. Siegel, there is no theta over here, so we can't use it either way. However, when you're doing a problem, you have to sometimes put some shortcuts in there. So let's let that be a placeholder. We'll hold on to the theta, and we'll come back and fix it later, just like we did in previous problem with the distance with the r. All right. So, well, this is theta, and these are related by cosine, because the cosine of theta is adjacent over hypotenuse. So that's Fex over Fe, and so that means that Fex is Fe cosine theta. All right. So that gives me my relationship. So I'll come over here and put that here. That's 2 Fe cosine theta. Okay. Now, what is the electrostatic force from either this one or this one? Right. It really doesn't matter which one I do, because I'm just going to take one and double it. Symmetry allows me to make that shortcut. So, well, the electrostatic force is given by Coulomb's law. So that's going to be K Q1, which is little q, Q2, which is big Q, all over the distance between them squared. Again, I don't know what R is yet, but I will know in a minute times the cosine of theta. Let's just take those one at a time. We can't put R in there. We can't put a theta in there. We'll do them one at a time. All right, getting there. We're really close. Now, this is 2K Q over R squared. Now, what is the distance between this dot and this charge? Well, if this is D and this is, I'm sorry, that's not correct. This distance here is B and this distance here is D. Well, that means that this is, by Pythagorean theorem, the square root of B squared plus D squared. And so that's going to be the square root of B squared plus D squared, quantity squared, because I'm squaring the distance, and the distance is the square root of B squared plus D squared times the cosine theta. I promise we'll figure out theta next. All right, now we're almost there. So this is 2K Q over, when I square this, I get B squared plus D squared. Now, what's cosine theta? Well, I'm going to come back over here, and I'm going to point out a few things to you. This is our theta, which is the same theta that I have here, which by vertical angles is the same theta here. So the cosine of this theta, cosine theta, that same theta, is going to be adjacent over hypotenuse. And so that's going to be cosine theta is going to be D, adjacent to the theta, over the hypotenuse, square root of B squared plus D squared. And so that means that my final answer is going to be 2K Q over quantity B squared plus D squared. When I multiply B squared plus D squared to the 1 power, let me go ahead to the 1 times B squared plus D squared to the 1/2, I add the exponents, and I get B squared plus D squared to the 3/2 power. Now, one of the reasons that I really wanted to do that problem for you guys is because that is a problem that we see over and over again. The geometries that we see in this problem are geometries that you've probably seen before, even in other kinds of problems sometimes. So hopefully that got you something and reminds you where we are and where we're going. All right, so today we said we're going to describe the behavior of charges, systems, and interacting with each other. And we said we would describe the behavior of neutral objects, the presence of charged objects and systems of charges, and apply Coulomb's law. I think we did that. And so, really, again, thank you so much for showing up and for the hard work that you're putting in. It's really always an honor
honor to work with such great students to be an AP teacher. Kristen, what are we going to do tomorrow?
Tomorrow, we are going to learn how all these charged objects became charged and what different ways we can charge objects. And we're also going to explore electric fields and drawing field lines.
Excellent. Wonderful. So that's what we have for tonight. Thank you again for tuning in. I'm Roger Siegel from Sarasota, Florida, and happy physics.
Have a great night. Good evening, everybody. My name is Kristen Gonzalez-Vega, and this is AP Physics C, Electricity and Magnetism Live. We are back. It is Monday, and I have my friend Roger here. Roger, you want to say hi?
Yeah, hi everybody. My name is Roger Siegel, and I am coming to you from Sarasota, Florida.
Okay, so today we're going to do a little bit more of Gauss's law. So we did some the other day. We did a lot of conductors. Today we're going to focus a little bit more on insulators and also kind of touching back on what exactly is electric flux. Again, I'm Kristen Gonzalez-Vega, coming from Frisco, Texas, and we have Roger with us from sunny Florida. So our objectives today are similar to what they were the other day. We want to be able to calculate the flux through an arbitrary area. We want to qualitatively apply Gauss's law to a system and state and use Gauss's law in an integral form. So just as a quick little review here, let's talk about what electric flux is. We used the analogy of the sunlight the other day on how we can compare, and that flux is really just a flow of some quantity through a surface. So electric flux is the electric field through a surface area. So we can find flux two different ways. We can find flux because it is the integral of the electric field, dA. We can also use the Q enclosed over epsilon naught. So there's two different ways we can find that electric flux. And if we put both of those sides together and equal them, that gives us Gauss's law. So Gauss's law is that the closed integral, surface integral of our Gaussian surface of E dot dA is equal to the Q enclosed over epsilon naught. So we're going to do a little bit more practice here. I have a charge Q that is far from all other charges, and we have two surfaces drawn here. Right? These are two Gaussian surfaces, S1 and S2, and they are spheres centered on Q. The radius of S2 is 4 times the radius of S1. So I'm going to go ahead and label that this. We'll just call this R, and I know that this one is 4 times that R. Okay. So I want you to take a second here and explain to me how the electric field compares at surface 2. Right? If we know that the electric field at A is E1, let's just call it. You tell me what is E2 compared to E1. Okay. And then also compare for me the flux through surface area 1 and surface area 2. I'm going to give you just a second here. If you can give me those two answers, and then we'll go over it. So compare those electric fields and compare the electric flux through those two surfaces. So if we want to be able to compare the electric field, we need a relationship, right? Anytime we want to go back and forth and compare quantities, if we're changing one variable to another, we've got to know what our relationship is. And so we've got to first use Gauss's law to get an equation for the electric field as a function of radius. So I'm going to do up here, I have a little bit more space. So if we start with Gauss's law, the integral of E dot dA equals Q enclosed over epsilon naught. We're always looking at those two things that we got to plug in for Gauss's law. It's always just those two things. So if we take the electric field, and if we draw this, if I draw a little bit more 3D, right? If I take one little surface area here or one little surface area here, and we look at that electric field going out, then anywhere on that one surface, if we're equal distance from that charge, should have the same magnitude of electric field. So the direction is going to be different, but the magnitude of the field should be the same. So that is why if you apply that symmetry correctly, and you use the right Gaussian surface, you should never ever have to actually integrate across your surface to the electric field because it should be a constant. And so that just becomes E. If we look at the A, if we take the integral of all of the little surface areas across that, it's the whole surface area of our Gaussian surface. And since this is a sphere, then we can say that this is 4 pi r squared for any r. That equals, if I look at what charge is enclosed in my whole Gaussian surface, it is little q. So that becomes E is equal to Q over 4 pi epsilon naught r squared. So we look at the relationship. What kind of relationship do the electric field and the radius have? Well, it's an inverse square relationship. So if the electric field is E at point A, and this radius is 4 times as great, well, if I put in a 4 over here, and that radius is squared, then the charge isn't changing, so that stays as a 1. So 4 pi epsilon naught, that's all constant. So we're really looking at 4 squared, which is 16. So the electric field at position 2 should be 1/16 the electric field on that first surface. Okay, but what about the flux? Let me erase some of this here. Let's compare the flux on the two surfaces. How can we get flux? Well, there's two different ways we can look at it, right? So I was going to write them both down, and then I look, well, what do I know? Which one's easier for me to use? Right? So we know the electric flux is either two things. It's either the integral of E dot dA, or I could also use Q enclosed over epsilon naught. The easiest one to always go for if you can is the Q enclosed over epsilon naught, because all you need to know is the charge, because epsilon naught is constant. We change the field, we're going to change the area. But we can look at that too, because I already know what happens to the field at that part. So I know that the area is related to 4 pi r squared. So if this has 4 times the radius, well, r squared, that means it has 16 times the surface area. But we already determined that it has 1/16 the electric field. So we can see 16 times 1/16, we get the same amount of flux. Let's check the Q enclosed over epsilon naught side. If I look, what charge is enclosed by surface area 1? It's little q. Well, what charge is enclosed by surface area 2? It is still little q. So the charge is the same in both cases, which means our flux is the same. So if it was just flux the first time, it's still going to be just that flux. Same flux, so we multiply by 1. Okay? So I'm going to toss it back to Roger to do a couple more practice problems with you guys.
All right. Well, thanks a lot, Kristen. All right. So we are going to share the screen and bring up the slides here. And so what we want to look at now is a couple of problems. First one is a problem here. It has to do with a line of charge. It is a very long rod, carries a uniform charge density lambda. We talked about that last week. And just to recall, lambda is a charge density. It's coulombs per meter. Okay. All right. So two Gaussian surfaces shown are S1 and S2. We can see up here are cylinders that are concentric to the rod and have the same length. The radius of S2 is 5 times as much as the radius of S1. So you can see here's the radius of S2 all the way out to here, and you can see this is not to scale. All right. So the first question says the electric field at point P on the lateral of S1 has a magnitude of E. What is the magnitude of the electric field at point Q? All right. Down here, which is on the lateral side of S2. So here are our two cylinders, our two cans, and we're going to find the electric field. And so what we're looking for here is what is the electric field? If the electric field here at point P is what did we say that was? That field is E. Then what is the electric field from the same charge, from this charge at this point? What is that field? You know, what is its relationship? How much more? How much less? Is it say? And so what we would do is we would look at our Gauss's law. Now remember, Gauss's law, we have to have symmetry. And so what's symmetric around a long linear charge is a cylinder or a can. And so our cylinder is here, and we can see that the ends of our cylinders, because of symmetry, because of the radial nature of the electric field, the ends have no flux through them. And so when we use Gauss's law, E dot dA is equal to Q enclosed over epsilon naught. We set up symmetry so the E can come out front, and then we're going to add up all the dA where we do have an electric field. And that is all along the lateral or the side of the can, if you will, the cylinder. And if we recall from previous problems, this is pi r squared L. If I call L this distance here, now you can say, well, how can you put an L there if it's not already in the problem? And here's what's going to happen. It's going to go away. And so that is our area. And on this side, we have our Q enclosed is L lambda, because that's length times charge per unit length. So that's the charge, and epsilon naught. And I told you a second ago that the L's were going to cancel, and indeed they do. And so we get that E is equal to L. I'm sorry, did I do that? I sure did. I canceled the wrong thing. Let's see if we can back that out. Okay. All right, let's cancel the correct thing. We are canceling the L. And so we have E is equal to lambda over pi r squared epsilon naught. So what does that tell us about the, I'm sorry, this is incorrect. Let me fix this. I gotta look at my notes. I said that this was the area, and I made the mistake of putting the area of a circle instead of a circumference. So this is 2 pi r. Okay, there we go. And so let's come back here. And so we can see that the L's cancel. And so this is, I knew that was wrong when I saw the R, because the answer to this is r to the 1. The previous one was r squared. Why? This is a cylinder. The other one was a sphere. And so that is our reliance. So if we have a 5-fold increase in the radius, what do we have in the electric field? Well, that's going to be E over 5. Now, the next part we can do very quickly. What did we just learn in the previous problem up here? We saw in this problem that the flux was the same through A, the same through B. Why? Because the flux depends ends, even though Gauss's law is over on this side, E dot dA is equal to Q enclosed over epsilon naught. This is Gauss's law. Don't forget this is a flux. This is the electric flux. And so if we can say what that is, we can easily figure out, well, as I get a bigger cylinder, I'm not changing the Q enclosed, so the flux is the same everywhere outside of the radius of our charge. Okay. Now the next one we have is a little bit tougher. I'm going to take a little bit take this one a little bit slower because it involves a three-dimensional integral. Okay. So we're going to take a look at this. There's a lot of symmetry. We're not going to have to integrate 3 times, but you'll see. Okay. So the problem says a spherical cloud of charge has a radius r equals 5 meters, carries a positive charge that is not uniformly distributed throughout its volume. The charge density is given as a function of the distance r from the center by rho is equal to 30 pi r if r is less than r and 0 if r is greater than r. So what are we saying here? I'm going to draw a graph whose axis is the same as this big r, and so out here we have big r. And I'll go ahead and zoom in a little bit so we can get this kind of big. All right. So now what are we saying about r? What are we saying about the density here? Well, you can see that the density is 30 pi over r. So I'm going to go ahead and write that there. Density is 30 pi over r. So what does that mean? Well, you can see that's an inverse function. So here this goes to infinity at its asymptotically infinity, but it falls off as an inverse function. So what does that mean? Well, we can actually do that a little bit different. So that means that as I go out, I have a less dense charge. So how does that mean? How am I going to figure out how much charge I have enclosed? Because I'm going to have to use Gauss's law to figure out how much charge I have enclosed. Well, that's the first part of this problem, is finding out how much charge we have enclosed. And that's kind of challenging. What we have to do is we have to take these tiny little drs, right? We're going to integrate, and each little thickness of this is a very, very thin dr. And at that thickness, we know the density. And so what we will do is we will make a spherical shell. We're going to integrate these by spherical shells. All right, so let's give this a try. I'm sure this is something you've seen in your calculus class, and we're excited to do it again here. Find my notes. All right, so the first thing I want to say, it says write expression for the total charge. So let's get started here. So the total charge Q, okay, is equal to, actually let's say that the total charge will be capital Q. The total charge capital Q is going to be equal to the density times the volume. Now that's the density if it's the same density uniform everywhere, but we know it's not uniform. And so what we've got to do is we've got to find out every little dq to find the charge and add them all up. And so that's going to be rho times dv. All right, now let's talk about what this is. This is our density function, 30 pi over r. This is a tiny little volume of a spherical shell, and its volume is the area of the sphere, which is 4 pi r squared. That's the surface area of my spherical shell times its thickness, this tiny, tiny little thickness. And if I had more time, I would be peeling an onion out for you, and I would take a real translucent layer of an onion. I would say, see how thick that is? That's what we're talking, very, very thin. And so if we can add up all these dqs like this times this, we can then get our charge, our total charge. So what we're going to say is over here, we're going to add up q, and that's going to be the integral of rho. Well, let's go ahead and say what rho is. Rho is 30 pi over r. I'm sorry, 30 pi times r. How could I have done that wrong? All right, so sorry, ladies and gentlemen. Let me fix this. I didn't look at my notes. Okay, so my r is increasing as I go out. The reason I thought it differently is because I was thinking of a more natural situation. Okay, here we go. This is mathematical, not physical. All right, so that is, let me fix that. That is 30 over pi times r, and then we have our area, which is 4 pi r squared times dr. And we're integrating that from 0 to some radius r. I don't want to call it a radius r. Let me call it x for this. I don't want to change this. I could change this to x, but I'll go ahead and set this here. Now what you can see is the pi's are going to cancel. I'm going to get 120 out front, and I'm going to have the integral of r cubed dr from 0 to some outside distance x. We'll change it to r in a minute. And so this becomes 120 times 1/4 r to the 4th from 0 to x, or 30 x to the 4th. Now I'm going to change it back to r. So I'm going to say q as a function of r is equal to 30 r to the 4th power. Okay. And when we look at this, that should make sense, because as we go up over here, as we move out, we have more density. We have a denser situation, and what that means is more density, and we also have a bigger surface area the further we go out. So we expect this to increase by r to the 4th. All right. So now let's see what happens if we go over here and we have r is greater than r. Well, once I get bigger than once I get past the outside of the sphere, what happens? Well, my density is 0. It's right here. My density is 0. And so since my density is 0, what I'm going to do is I'm going to say that we have q at r is equal to or greater than r is 30 r to. All right. Let's get through this. We're almost home. Now we can use Gauss's law, because we've got the same situation, but now we want to find the electric field. And so we're going to use Gauss's law. And so Gauss's law says that the integral, closed surface integral of E dot dA is equal to the charge enclosed over epsilon naught. So let's imagine now that we're within the sphere, big R, we're less than big R. And so we want to find the electric field. Well, we know that because of symmetry, we can pull this out and we can add up all the dAs, which will be a surface area. Now, what is my charge enclosed? Well, from the previous problem, I know that this is 30 r to the 4th power over epsilon naught. And so this is E times, well, this is an area. And what is it? It's 4 pi r squared. It's the area of a sphere. And that's going to be 30 r to the 4th over epsilon naught. And you can see here that we've got a 2 here. That's going to go away. That's going to become a 2. And what we have then is E is equal to 30 over 4 or 15 over 2 pi epsilon naught times r squared. And so that is our solution for E as a function of r. And this is E as a function of r when r is less than r. Now, what happens when I'm all the way here at the outside of my circle? Well, I'm going to have the same Gauss's law, E dot dA. And this is going to be, again, we said this is 30 r to the 4th over epsilon naught. That's my charge enclosed. And so this is E times 4 pi r squared is equal to 30 r to the 4th over epsilon naught. And you can see once again that my r's, this goes away. I'm sorry, this is a capital R. And so we can say that this becomes a 0, this becomes a 2. And so then we get E is equal to, again, 15 halves r over pi, 15 over 2 pi. And we have r squared, capital R squared over epsilon naught. Our last part of the problem before we hand it back to Frisco, Texas, is r is greater than r. Now, here's one thing I want you to stop integrating and stop using Gauss's law. Because why? Because we've got a spherically symmetric charge, and now I am past the point of any charge increasing. And so what does that mean? That means that I can use my formula for the E field from point charge, and that's kq over r squared. We did that a few days ago. Well, k, and this is on your formula sheet, is 1 over 4 pi epsilon naught. We talked about it the other night. Q, we found out, was r to the 4th. Q is 30 r to the 4th. Okay, and r squared is going to be, well, wherever I happen to be. And so we can see here that we have 30, and so we have 15 over 2 pi, and we have r to the 4th over r squared. There's an epsilon naught in there, and I don't want to forget that. That's how we do this problem. Now, if I were you, I wouldn't be able to follow it that fast. I have trouble. But we want to get a lot in tonight. So don't forget, take a second, pause the video, try it, and see what you can do with this. And it should make a lot of sense to you. We're going to hand it back to Frisco, and I think we've got some real doozies for you coming up. Stay tuned.
So hopefully not too hard though. So we're gonna do a couple, and I'm gonna try to adjust them to tailor to us practicing a little bit more towards this year's exam. So I took a question from, I think it was 2 or 3 years ago, the E&M exam, and I've changed it a tiny bit to kind of get a little bit more conceptual, to have you writing and thinking a little bit more. So we have here a very large non-conducting or insulating slab with a uniform positive volume charge density rho naught. It is fixed with the origin of the XYZ axis at its center center as shown in the figure above. The thickness of the slab is d, the length is L, the width is W, where L is much, much bigger than D, and W is much, much bigger than D. So the large faces of the slab are parallel to the XY plane. So what that means is it's very, very like wide and girthy, right? But not as much height-wise. So we can think of it almost like it's infinitely long compared to its thickness. And so that can tell us a little bit too about the electric field and the electric flux. That's just a little bit of a hint. So I want you to tell me these two things. You're going to write down for me what Gaussian surface you could use to determine the electric field at points R and S within the slab. So this is our side view here, and we can see that we have point R and point S within that slab. And I want you to tell me what kind of Gaussian surface could you draw to determine what the electric field is at either of those points, and then which of the surfaces on your Gaussian surface would have electric flux. So what surface would you use and which sides would have flux? I'm going to tell you there is more than one option actually with this one. Okay, so remember one thing we said you could do is you can use the same symmetry as your charge. So this charge is a rectangular prism. So the thing that comes to my mind first would be to draw a rectangular prism that goes through R and S. Okay, and then the second thing is which of the sides of my rectangular prism would have. So I'm going to draw a little bit here too, so we can kind of see that shape. So which sides of my Gaussian surface would have flux? Well, if this is very wide this way and this way, well then we really couldn't take those into account as having flux. So the only sides that are going to have flux is at those top and bottom sides of my Gaussian surface. Right? If we're looking at it this way, it would be the top side and the bottom side here. Okay, what other surface could you use? Well, I think when Roger did his slab the other day, he used a cylinder. So there are some people that like to use the cylinder instead for their Gaussian surface on the rectangular prisms, and that's totally acceptable path also. It's actually what they gave you on this, right? So this problem did not have originally that first part there. It kind of went right and gave you these shapes, right? So let's consider a Gaussian cylinder with a cross-sectional area A and a height h, right? So if I draw big over here, we've got the cylinder that has a surface area A and a height h. So this position along its axis is shown in the figure below. So if we look at that side view, we can say it here that goes through R and S. So I want you to describe the direction of the electric field at point R and at point S, or say that it's zero at either of those points. So which way is the electric field at point R? Which way is the electric field at point S? What's that first thing you should be asking yourself? Is it positive or negatively charged? And if we go back to the beginning of the question, it is positively charged. So if it is positively charged at point R, the electric field should be pointing away or up, and at point S, it should also be pointing away or down. So at point R, you could say up, you could say in the positive z direction, and at S, you could say down or negative z direction. Okay, next step, let's use Gauss's law to now derive some expressions. Let's find what the total flux is through the Gaussian surface shown. So if we want to know what the flux is, how do we get flux again? We know it's either side of Gauss's law, right? So I'm going to write them both down, and then we're going to look at which side we should use. Okay, and like I said, let's always try to use this charge side if possible, because the only thing we have to worry about is the charge. We don't have to worry about what the field is, because we actually have to know to actually find the flux. We have to know what the field is and what the surface area is. That's not as difficult, but we don't know what the electric field is yet. So we got to use that right side. So we got to find what is the Q enclosed on this Gaussian surface, right? So if this is a cylinder. We know that the slab has a uniform charge density rho, right? Volume charge density. So what does that mean? Well, volume charge density means rho naught, which is equal to Q over the volume. Okay? Now they don't give us the volume of the cylinder, but they do give us that the cylinder has an area A and a height of h. So I can say, well, what is the h? It is right h over 2 here and h over 2 here, so that's just h. So I can say really Q is equal to rho times the area times the height. So if we plug that in here, then our Q enclosed is going to equal rho naught times A times h over epsilon naught. Okay, and then next, let's derive an expression for the electric field as a function of z for any position, right? So this is kind of like what we were doing the other day with like as a position of r, but here we're using that z plane here. So as a position of z, we want to know, zoom in here, right? As we go out here, give us a function for the electric field and show that it is equal to E, which is equal to rho naught z over epsilon naught. So we're trying to derive and get that one. So where do we always start? We start at the start, which is Gauss's law. Okay, we're going to address our two sides. So what is our surface area here? We used that cylinder. Which of the sides that had flux? Remember, we're only going to look at the sides that have flux. We had no flux out those sides because it is so large. So really the only place we had flux were those top and bottom parts of the cylinder, those two areas. So really I can say that this is E times 2 times the surface area, which equals, well, let's plug in our charge that we need to have as a function of z, right? So we got that our charge is rho times A times h. So let's look though at what that h is. We want it as a function of z. Well, as I go out from the center, again, if I zoom way in here, if I go out from the center here, well, if I'm going out a distance of z here, my whole surface though is also changing a distance of z on the other side. So what would that total height be? It would be 2 times z. So when we plug in for our q here, instead of saying h, we need to say it's really 2 times z. So this is rho naught times A times 2 z, 2 times z over epsilon naught. Okay, well, we got an A here, I got a 2 here, and a 2 here. So that leaves me that E is equal to rho naught times z over epsilon naught. Okay, so we start with Gauss's law. What is the shape of your Gaussian surface for that surface area? Do all of the sides have flux? If not, you're only looking at the surface areas that have flux to plug into Gauss's law. And then what is your charge that you're going to enclose? Okay, so let's look now. Instead of just our slab, we're going to put that slab in between two parallel plates. So our large metal plates are separated by a distance of 0.01 meters, which is approximately the thickness of the slab, right? So it's taking up the whole space in there is what that means. But the slab does not contact either metal plate. The metal plates are charged, and they give us those charged surface densities. Remember sigma. First thing I want you to be thinking about in your head when they give you these is that per length, per area, or per volume. So this is sigma, and sigma is charge per area. Right? I'm always thinking these things, jotting them down as I'm reading and identifying. So top is negative, bottom is positive. What sticks out in your head when you know which plate is which charge? Well, I kind of think in my head which way the electric field is in between those two plates. I'm not going to draw it yet, because I want you to do this next part. Assume the charge distribution remains unchanged by the presence of the charged plates that the slab's volume density is. So now they're giving us rho. We're still going to keep everything in terms of symbols. We're not going to plug and chug. We know you're not going to be doing that on the exam. So the magnitude of the electric field inside the slab is 0 at the x-axis at some position z naught. So they're saying somewhere along the z plane, the electric field is going to be equal to 0. Okay? So you're going to tell me where that is. Where would the electric field be 0? What would have to be true in order for it to be 0? And you tell me, is it greater than 0, meaning it's in the top half here? Is it right at 0, or is it less than 0, meaning the bottom half of the slab? I want you to take a second, think which way that would be, and how do you know that's where it is? Justify that answer. First thing you better be doing is drawing the direction of the electric field due to the slab and due to the plates. Okay? So we already know the slab, so let's do that first. I know that the electric field of the slab on the bottom portion is going to be downward. I'll label that ES, and I know it's going to be upward in the top portion because this is positively charged. Okay? Next thing I'm going to look at then is my slab. This is my parallel plate. This is negatively charged plate. This is positively charged plate. Well, the electric field is going to run from the positively charged plate to the negatively charged plate, which means everywhere in here, draw a couple of them so we can see it. Maybe one right next to these others. The electric field is upwards. If you look at these top, what do you notice about the electric field due to the slab and the electric field due to the plates? They're in the same direction. What would we do? We would add those together. So it's going to be a pretty big, comparatively, electric field in that region. Okay? What if we look on the bottom half though? In the bottom half, we got electric field downwards and electric field upwards. So what do we do with those? We would subtract them. And if we're going to subtract them, that's going to be in a region where the electric field will eventually become 0. So that would be at the E is less than 0. So what would we want to say? What would be some key words that we would want to use in order to explain this, right? Where we're going to get as many points as possible. Well, the first thing we want to know is we want the electric field from the slab to be equal to the electric field from the parallel plates. And I'm kind of shorthanding here, right? So first thing we want to say is we want those two electric fields to be equal in magnitude, but opposite direction. And then we would explain how we know which of those directions are, right? We know the electric field is going down the bottom half to that positively charged slab, and we know that all the time the electric field is uniform and upwards due to those two plates. So where's the region where it would cancel out? It would be in that bottom region. Okay. Now let's actually find where that would be equal. So we already started that right here. We know that the electric field due to the slab has to equal the electric field due to the plates. Well, we nicely already have our relationship, right? They gave it to us, and we derived it. It's that the electric field is rho naught times Z over epsilon naught. But if we're looking for the exact position, we want to say that it is rho naught times Z naught over epsilon naught. So an exact position Z. That's got to equal. Now we got to look really quick at how do we find the electric field due to those plates. And so I'm going to erase some of this so we can zoom in and we can Gauss one side of these plates. So if this is positively charged, if I want to find what the electric field is in this region here, well, I'm going to enclose that plate and I'm going to use Gauss's law to find what it is. Okay, we're going to adjust our two sides. First of all, is there flux everywhere? And this is where a lot of people kind of get thrown off here. If we look at these plates, this is negatively charged. So we've got electric fields coming in towards it everywhere, even over here, right? So, and really when we look at like the grand scheme of things, the distance between these two plates is very small compared to like the area around it. And so, but there's also that electric field going away from the positive plates. So if you look, and let me keep going, on the outside, we can say that electric field is pretty much zero. Compared to that electric field inside, the electric field outside our polar plates is zero. So what was the only surface that's going to have flux? That's going to be my surface here, right? There's going to be no flux here. So we just have one side of our Gaussian surface that's going to have flux, and we're enclosing that plate. So if we're looking at the Gauss's law here for that plate, well, this is just going to be one of those areas. And why that doesn't matter is because we're going to plug in that Q over area is the charge density. So Q is equal to sigma times A. So it doesn't matter what that surface area is. The bigger my Gaussian surface, the more charge I'm enclosing. It's proportional. So this becomes sigma times A over epsilon naught. A's cancel. The electric field due to a parallel plate is sigma over epsilon naught. So we can plug that in over here that this is sigma over epsilon naught. So what happens with our epsilon naughts? Those cancel out. If I want Z naught is going to be equal to sigma over that charge density. Interesting, right? It's that ratio of those charge densities. Okay, so being able to pick and describe your Gaussian surface and where there's flux, I think is going to be really important this year. So always keep those things in mind. Okay, and then the next thing I have here is not Gauss, but it's just a little bit more kind of fun with charge to kind of wrap up our charges and forces and fields. We're going to revisit it, but we're going to move on to electric potential tomorrow. So we're going to do this problem here that I found, and it is we have two pucks that are connected by a non-conducting rigid rod and given a positive charge QA and QB. Both of them given positive charge. I'm going to label that. The pucks are set on a smooth frictionless table along with a fixed puck C, right? So this one's not going anywhere. Just a negative charge QC. So in case one, we're going to say that QB is equal to 1.5 times QA, and it's free to, the rod is free to rotate, right? So our puck is fixed, but our rod is free to rotate. So I want you to draw me the forces that are acting on A, right? So draw arrows representing only the electric forces acting exerted on A and B. So you don't have to necessarily label them, but it is necessary that each vector be a distinct arrow and starts, right? So we're going to do that part quickly. I really want to focus on kind of the argument part here. So if we look at A, well, A has how many different charges that are interacting with it? Well, there's two interactions here. We have the interaction between A and B, which if these are both positively charged would give us an electrostatic force to the left, and it's also interacting with charge C. So if we look at those two charges, then there'd be an attraction. But we're going to look at how far they are apart, right? So I'm going to draw some distance is in here. So if we count the squares, this should be 6 squares here, and this is 6 squares. Well, this is more than 6 squares. And we remember that force, if we're looking at point charges, was KQQ over R squared. So if this is a bigger distance between them, then I know this force is going to be a little bit smaller. I'm going to draw a little bit smaller here. And then we do the same thing for B. Well, if B is creating a force on A is creating the same equal but opposite force to the right on B. And B is also interacting with C, attracting it, and it's got the same distance, so it will be the same force. So question is, in which direction does the center of the rod accelerate at the instant shown in the diagram? Does the rod rotate clockwise or counterclockwise, if at all? And justify your answer using the forces you drew, right? So this could be something you would see in the test. You probably wouldn't have to like submit and turn in your free body diagram, but you're going to have to draw these free body diagrams to be able to explain and justify your answers that you're going to be writing. Okay, so I'm going to give you just a couple of seconds here to compose your thoughts, write down some important good physics words to explain which way is the center of the rod accelerating, and is it going to be rotating at all? And how do you know? Okay, so when we go back to know if the center of the rod is accelerating, well, that goes back to net force. And how do we know if something is going to be rotating or have angular acceleration? Well, that goes back to net torque. So let's go back and look at these forces. Let's look at our ups and downs and lefts and our rights. Do we have a net force? Okay, well, if we look at our A and B, well, if this is a positive rightward force and this is a leftward force, but we could say negative, and we know they're equal in magnitude, then I can say, well, if I added force due to A and B to A, that those would equal 0. So really what we're looking at are our other two vectors, right here and right here. And what would those sum up to? Well, I've got an positive X component and a negative Y component here, and I've got a negative Y component here. If I added those together, we get a big downward, but also rightward force. So our acceleration would be both to the right and down. Okay, now let's look at torque. If we look at the center of that rod, I'm just going to redraw right here. Okay, we have to look at both like where those forces are acting, but also the magnitude, right? Because remember, torque is R cross F. And so if I look at the forces again here, well, if I look at the right hand side, then we've got a torque R cross F here, right? No torque here because that is acting through that pivot. But I do have a torque R, the half of this rod, times that force going downwards towards C. And if I look at this one, I've got R cross F, which would only be this component of the electrostatic force. Right? Again, no torque here because it's acting through that pivot. So if we look at the magnitude though, which one of these would have a greater magnitude? That would be the force on the right hand side here, which if we actually follow through R cross F, we can easily see that that's going to give us a clockwise torque. So we still can have torque with our charges. This is what we call a dipole here. So it would be a clockwise torque because there is a net torque on that right side. Okay, so we're going to stop for there today. And if we have time sometime, we come back and do the second half of that. But hopefully tonight kind of helps concrete some of those questions you had with Gauss's law. And I did have on here though what we are doing the rest of the week, I think. Yep, here we go. So here's our schedule for the rest of the week. Tomorrow we're going to do electric potential point charges. Then we're going to do electric potential and electric potential energy. And then we're going to go into back and revisit those kind of other distributions we saw the other day with like a line or an arc along with electric potential. And then we're going to do concentric conductors to lead us into capacitors. So hopefully you'll join us tomorrow. My name is Kristen Gonzalez-Vega from Frisco, Texas.
And my name is Roger Siegel from Sarasota, Florida.
All right, you guys have a wonderful night.
Evening. Happy Tuesday afternoon. Welcome to AP Live. My name is Roger Siegel, and I am working tonight, as always, with my partner, Kristen, in Frisco, Texas. Hi, Kristen.
Hello, Roger, everybody. How are you guys?
And so tonight, what we're going to be doing is we're going to be moving forward with our review for our AP Physics C E&M exam, which is 2 weeks from yesterday. I'm sorry, not 4 weeks from yesterday. Sorry about that. And so not to worry. And we're going to get you ready for that. So this is going to be a wonderful night. Thanks for joining us. So tonight, we're going to be talking about potential, electric potential. And I got to tell you, you might be mad with physics teachers after tonight because there's a difference between electric potential and electric potential energy. Don't ask me why they're called so close to the same thing. They just are. And so that does confuse us somewhat, but we are going to get into it today, and it should make sense too. Once again, my name is Roger Siegel. I'm coming to you live from Sarasota, Florida, and I teach at the Pineview School, and my partner is Kristen from Frisco, Texas. We wanted to remind you that our AP Physics C E&M exam this year is going to be on May 11th. That's a Monday, and that will take place at 2 p.m. Eastern. That's where I live, but wherever you live, you're going to find out your time. And remember, you're going to have 2 questions. One's going to be 25 minutes, and then you'll have 5 minutes to upload, and one will be 15 minutes, and then you'll have 5 minutes to upload. Okay, so let's review a little bit from where we've come from. So we started reviewing for the AP exam last Monday. We're still in the first section, which is electrostatics. And so we've been talking about charges and Coulomb's law, and we've been talking about the E field. Okay, and so basically, the force, Coulomb's law, and the E field are 2 big parts of electrostatics, and the 2 more that we're going to get into tonight. And as I said, those 2 parts are potential and potential energy. So that's what we're doing tonight: potential, electric potential, and electric potential energy. Now, tonight, what we're going to do is we're going to be able to calculate the value of the electric potential for point charges. We're going to say what the electric potential is. We're going to give you a sense of it. And by the way, we're going to ramp up to this. This is going to take us a few days to really get a sense of what is electric potential. So we'll talk about this a lot, and as we go through the whole semester review, we're going to keep coming back to this concept of electric potential and what it is. I'm pretty sure by the end of the unit this semester you will have a good sense of it. And also today we're going to do some math. We're going to represent the relationship between charge and difference in potential and work done. We're going to talk about work. We're going to calculate the electrostatic potential energy of a collection of two or more point charges. I'm going to calculate the amount of work needed to assemble some of these point charges. You can find this interesting problem. All right, so we're going to start with electrical potential energy. Okay, and by the way, the symbol for that is U, capital U sub E, electrical potential energy. Okay, now you probably remember potential energy from your mechanics class, whenever you took it, that near the surface of the Earth we have this gravitational field that points down G, and if you take a mass M and you put it in that potential, if you raise it at a certain height, then it has a potential energy UG is equal to mgh. But we also know that force is that work is equal to force times distance, and so that force is mg and that distance is h. So what we're showing is the amount of potential energy that we get is equal to the work we do to put that charge, to put that mass there. We're going to do the same thing today, except not with masses and gravity, but with charges. All right. So this would be true whether this was electrical or gravitational. That is true of potential energy, although we're not going to do any calculus now. All right. So now this is our formula that we will use for electrical potential energy. By the way, this does equal to, when I integrate from infinity to r, f dot dr. That's what I get. And I'm not going to do the work with you, but I'm going to show you that what we would put in here is k q over r squared dr. And when I did this work, I would get this answer over here. Now let's talk about, though not with the math so much, but let's talk about how we would solve the problem here. Okay. So we have two charges, okay, and they are 5 times 10 to the minus 9 each. That's each charge, and they are and those charges are 3 centimeters apart. So we want to know the potential energy of the system. So let's go ahead and see what that looks like. So we're going to take this. We're going to imagine doing this problem. We're going to imagine that we start off with nothing in our universe. So I'm going to draw a line here. And I'm going to this is my little private universe. That's the thing about being a physicist, is you can just draw a line on your whiteboard and you get your own private universe here. So here's my little private universe, and I've got nothing in my universe. I get to decide what I want to put in there. Now I'm going to take a single charge. I'm going to take this charge of 5 nanocoulombs. Remember, there's nothing in my universe. I'm going to put this 5 nanocoulomb charge in my universe, right? 5 nanocoulomb. There it is. Right? And then what we're going to do is we're going to I'm going to ask you, how much work did that take me? Did I have to do to bring that 5 nanocoulomb into this universe? And let's imagine it out near the edge of my universe. If we can talk about that, out near the edge of my universe. I made it here, and it was infinity away from this point, and I moved it here. Did I do any work? And the answer is no. Putting one charge in my universe, I can move it anywhere I want without doing work. And the reason that I don't do any work when I move this single charge around is because there are no other charges in my universe, and therefore no other force. And so that means that it takes 0 work to bring my first charge in. However, now I'm going to bring in another charge. I'm going to have another charge here, 5 nanocoulombs, and I just there it is. It appears at the edge of my universe. And first, it's infinity away from my first charge. And I'm going to move it from infinity over here. And now the distance between these two is 3 centimeters or 0.03 meters. Now, how much work did I do to set this arrangement up, to arrange these charges? Well, to put the first charge in, 0 work. But to put the second charge in, the amount of work that I did is equal to the electrostatic, the potential energy of my system. So this is k q over r. And so what we have is we have 9, k is 9 e to the 9 times, we'll put that in 9 e to the 9. And my two q's are 5 e to the negative 9. Then I've got those squared. And then my distance is 0.03. And so we have that and put that in. And what we get is 7.5 times 10 to the minus 6. Okay. Now, 7.5 times 10 to the minus 6. What? Well, this is energy. And so that means that the units for energy are joules. And so that's how much work I had to do to bring these two together. Remember, they're both positive, so they're pushing against each other, and I had to push them. And the amount that I push times the distance gives me that position. All right, so let's talk about this other thing called potential difference. Now, again, it's not my fault that we use the same word. We should call it something else, but we don't. So we really have to be clear. Are we talking about potential energy or potential? Right now, we just said that in order to have potential energy, you need 2 charges. But in order to have potential, you only need 1 charge. Just like in order to have a field, you only need 1 charge. Potential energy is an interaction from 2 or more charges, or a charge and field. But where did the first field come from? It came from a charge. So there's got to be more than 1 charge. However, if we only have 1 charge, we can still have a potential difference. All right, now this is how they are related, and this is one of our golden formulas. And so as you get ready to take the test, we're going to show you the ones that are the most important. But there it is. All right, now let's talk about potential difference. The potential difference is the difference in potential energy per unit charge between 2 places. All right, so here I have a point A here, here's a point A, and here's a point B. And suppose I've got my UA and my UB. There's the potential energy I have here, and the potential energy I have there. Well, what is the voltage? What is the potential difference between those two? AB. Well, that's going to be Q times delta U. Okay, and I'm sorry, divided by delta U divided. Okay. And so that's how we're going to get that. That's how they're related. The units for volts are joule per coulomb, and I wish I could get you to remember that. That is so important, joule per coulomb. And then remember the potential difference between 2 places. It's a scalar field. It tells us how much energy I could extract or expand if I were to move that charge to that position from infinity. Now, this is going to make a little bit more sense when we look at this formula. This is the potential difference from a point charge compared to V0 at infinity. So what does that mean? All right, so imagine that I have a one-dimensional universe, and I start out with no charges in my one-dimensional universe. And then at some point, well, I say, I'm going to put a positive charge here. Now, if I want to draw my potential, it's now no longer 0 everywhere. Potential looks like this in this universe, in this one-dimensional universe. And the value of that potential, which is going to be V, remember the value of this distance is R. V is equal to K Q over R, where that's my charge Q. Now, if I brought a negative charge into a universe and a positive charge, suppose I had, let's see, a positive charge here and a negative charge here, well, then my potential in my one-dimensional universe would look like this, and it would then go like this, and we have a well, and then we have something like this. And that's a one-dimensional universe, okay? I want to show you a two-dimensional universe. So let me hop over here to a simulation that I have for us today. And this is a simulation that someone made on GeoGebra, and named Alan Olson. Thank you, Mr. Olson. And this is a really good simulation. I think you're going to like this as soon as my computer starts responding here. We'll not try that again. Okay. And I'm going to exit this page, and we're going to try and reload this. Just give us a second. All right, much better. Now, if you look at this situation, I'm going to show this to you like this. So we're looking at an XY axis. There are 2 charges that have been brought into this universe. Look at how they work the universe. Look at that. My negative charge creates a well over here, and my positive charge creates this big hill. Now, we're going to talk more about those later as we get into as we go through this and learn more about it. But and in a few days, we'll talk about equal potential surface. But for now, we're going to send it over to Frisco, and Kristen is going to help us to understand some of these concepts with some really good problems. So, Kristen.
All right. So we are going to look first at 4 point charges and what happens if we have them in this arrangement, how they are here. So we have our 4 point charges. Each of them have a charge, positive Q. I'm going to zoom in here, positive Q on each one. Okay. and the square has sides each of length a. So we want to know what is the potential energy of this arrangement of charges. And so that would be the energy required to take them from infinity away to where they are now, right? So we want to look at what are the possible different arrangements we can look at, right? If the electric potential energy is equal to KQQ over R, well, we want to look at all these possible pairings of Q, right? So we could have this Q, the top left Q, and the bottom left Q. We could have it with the bottom right Q or with the top right Q. And I kind of make some different colors here so we can see it stick out. I could also have these two, and I could have these two. And let's see here. We could also have these other two quarters here, right? So there are 1, 2, 3, 4, 5, 6 possible arrangements. But if we look at these, we want to look at the distances. So I've got the, and I really should have done, here, we color this real quick. I want to look at these outside four first. Why do I want to look at these outside four first? Because if the energy is KQQ over R, well, all four of these pairings have that same distance A between each of those charges. So each one of these is KQQ over R. Well, if Q is the same, that becomes Q squared. The distance between them is A, then really I can say, well, these four is 4 times KQ squared over A. And then we also have those diagonals, right? So here and here. Now those are equal distance away, but that's not A. We gotta look at what that distance is, right? And I also have plus these two, which are K. It's still Q times Q, which is Q squared, but we gotta look at what is that distance between them. So let's look at just that distance between them. So if this is our square, and this is A, and this is A. We know by Pythagorean theorem that this is the square root of 2 times A. So then this becomes over the square root of 2 times A. And so we can combine these together. We can pull out our KQ over A, and then it becomes KQ squared over A times. We're left with the 4 plus 2 over the root of 2. And so we want to look at those arrangements. We can look at each of those individual pairings to find what that total potential energy is of the arrangement. It's kind of the same thing when we had masses, right? When we had multiple masses, and we were looking at, well, what is the gravitational? Make another one here. What's the gravitational potential energy of those three masses, right? We had to look at the gravitational potential energy of all of those different possibilities of arrangements. We do the same thing here with the electric potential energy. Okay, and then what if we wanted to know what the electric potential was at the very center, right? So these are still all positive Q, A on each side. So we want to know what the electric potential is. Well, the electric potential comes from each of the individual charges. So the electric potential V is KQ over R. Well, I've got a KQ over R to each one of these charges, right? So I've got from this point here to this charge here, that point charge is going to contribute to the electric potential at C. Charge 1 we'll call it. Charge 2 also contributes to the electric potential. Charge 3 and charge 4. All of them contribute to that potential at the center. And all of those charges are equal distance away. So really I can say, well, there's 4 KQ over R's. So really we gotta look at what that R is, right? Well, if we just said that the whole distance across here was equal to the square root of 2 times A, but we're only looking from the center to one of these, so that's 2 of them. So that R would be the square root of 2 times A over 2. And we can say it becomes 4 times KQ over R, which is the square root of 2 over 2 times A. So if we want to simplify that, we can bring that 2 up, and it becomes 8 KQ over the square root of 2 times A. Okay, so looking at that potential due to each one of those charges of that arrangement. Okay, the next thing we can look at here is looking at the electric field and how we can determine which place in an electric field has a greater potential or lower potential, what would happen to the energy to a charge, when the work on that charge in that field. So sometimes we like to look at and compare 2 different places in an electric field or in potential and look at that energy work. So here we have an electron that's placed in a uniform electric field at point A and is later found at point B, right? So the electron, I'm going to put a negative here, is starting at position A and then later on going to be at position B. So we want to know, is the work done on this electron positive or negative? And explain, is A or B at higher potential or are they equal? And explain, and does the electron gain or lose potential energy? Maybe just a second here to think about that. So what do we think about the work done on the electron? Is that going to be positive or negative? Okay, well we know, and this goes also back to gravity, spring, and in general, the definition of work and energy for those is that if we have a conservative force, right? A conservative force is anything associated with potential energy, right? So we're talking about spring force, gravitational force, anything associated with potential energy is a conservative force. And then we can say in general that the work done is equal to the negative change in potential energy. So if we think about gravity, right? So when you are losing potential energy, gravity is doing positive work. And when you are gaining potential energy, then it's doing negative work. So if we look here and we look at our charge, this is a negative charge, right? So we can think of also work being equal to the force over the displacement of our object. So here we look at which way is the force on this electron. Which way do electrons experience forces in an electric field? Is it with the field or the opposite direction field? Well, positive charges experience forces in the same direction, so negative charges experience electrostatic forces in the opposite direction. Okay, so if we look at the work here, then the work is going to be equal to the force times that displacement. And if our force is in the negative direction, then we can say that the work is negative. But since if we multiply out also that the force is equal to Q times E, if we look at the force and force is equal to Q times E, then we can say that this is equal to Q times E times D. Okay, so but that negative charge, and we have, if we multiply that out, then we get negative Q times E times D. Okay? But is it going to gain or lose potential energy? Well, if work is equal to the negative change in energy, and if work is negative, then that means we are going to be gaining potential energy. Okay? And then is A at B or B at a higher potential? We know those field lines always run from a higher to a lower potential, and so B would be at a lower potential. Okay, so we're going to toss it back to Roger over there in Florida.
Okay, thanks. Well, so we're getting a sense of time. Remember, there's a lot of invisible things we're talking about, so we're going to try and make sure that we can help you sort them out. All right, let's go ahead and take a look at some other problems. They'll hopefully help us to get the concept of potential down. Also, to keep it, let's keep talking about potential, but also how is that different than potential energy? How is that different than the electric field? All these things that are related. So let's take a look. All right, so we actually did some of these from this very same problem a few nights ago when we were looking at the electric field. And so now we're going to revisit this problem. We're going to redo the electric field problem, but we're also going to add potential. And so hopefully that will give us a good sense of what we're talking about. So we've got the square of side A once again, and we've got these point charges. Here's Q plus in the lower left-hand corner, and here's 3 Q minuses in these 3 corners. So that's what we got. Those are our 3 Q minuses and 1 Q plus. Right? And for those now, and also we have this point E, which is right here in the middle. All right, it says indicate with an arrow the direction of the net electric field at point E. So again, I did this last time. Let's label these 4 charges: capital A, capital B, capital C, and capital D. And let's talk about the electric field at P due to those 4 charges A, B, C, and D. Well, I know that a charge Q means the electric field points towards it. And so I'm going to go ahead and point this electric field here, and I'm going to call that E sub A because that's the electric field due to charge A. Same thing with E sub B, we're pointing towards it, E sub B. And E sub C, a negative charge, that means the electric field points towards it. And let's get a little tighter here so we can see this a little bit better. And then E sub D, well, that's a positive charge, which means it has a field in this direction. And so that's going to be E sub D. And so if we look at that, we can see that these two, E sub A and E sub C, are going to cancel. And what am I going to be left with? I'm going to be left with 2 of these. So if I can just find the value of one of them, since all these charges are the same in magnitude, then I can go ahead and add those two together. Well, I know that the electric field from a single point charge is equal to KQ over R squared, where Q is the charge and R is the distance. So let's go ahead and look at this and see if we can get this distance. What is the distance from here to here? That's what we want to know. What is that distance? Okay. Well, if you look here, you can see that we've got a right triangle that's going to help us find that distance. Since the side of my square is A, that means this distance from here to here is A over 2. And that means that this distance here, since this is a 45, 45, 90 right triangle, that's going to be the square root of 2 A over 2. It's 2 square root of 2 more than that. And so that means that what I have is I have 2 of KQ, and it's a capital Q, over the distance squared. And that distance is the square root of 2 over 2 A squared. And so what we have now is we have 2 KQ over, let's see, that's going to be 2 over 4 A squared. And so that's going to be 2 to the top. And so what that gives us is 4 KQ over A squared. And that is our field at that point. That is our electric field. All right, now that's something we did the other day. Now let's look and find. I'm sorry, I just found the magnitude of the electric field. So the work that is asked for down here, I did that. So we'll go ahead and previous slide. Now, what is the electric potential at that point? Well, let's go ahead and so the beauty of doing the electric potential, and this is what I love about teaching potential versus the electric field, it's a scalar, which means I do not have to add vectors. I don't have to worry about direction, and life gets a little easier. So, well, let's look and see. I know that the potential due to this q plus and this q minus, they're equidistant, and each one of those, one's going to be kq over the distance called a small r, and the other one is going to be k negative q over small r. So when I add this one to this one, I get 0, and so these two cancel, and what we have are 2 of these. So I have 2 negative, and remember, v, the potential is kq over r. So that means that we have 2 times negative q for k over r, and the distance again is the square root of 2 over 2 times r. And so I've got 2 of those, and that's going to be 4 over the square root of 2 negative q k, and there's an a downstairs as well. I said r, I should have said a squared is r. So that is the electric potential at the middle. Notice it is negative because I've got these 2 negative charges that do not cancel, and so that's my electrical potential. What does that mean? Well, that means that if I start at infinity, it means that the potential here is lower than it is at infinity. If I have a positive charge, it's going to roll in that direction. If I want to put a negative charge, I'm going to push it. All right. Now, it says a positive charge is placed at point Q. It is then moved. I think, let's put a D there. It is then moved from point B to point R, which is the midpoint. So we start and we put a positive charge here, positive little q. I'm going to put a little q there, and we're going to move that. We're going to walk it down to here. Now, it doesn't say that I went in a straight line, and it doesn't have to, because as Kristen said, the electric force is a conservative force. So the path that we take is not important. The change is going to be the same. So the question is the work done by it, by the field, is it positive, negative, or 0? So let's kind of say what the field is doing. Now, remember, a few minutes ago, we said that the field was in this direction, okay? And so what would happen if I took this positive charge and I just let it go? I took this positive charge, here's the center, I know that this is the net field, E, and I let it go. What would it do? Well, hopefully what you're going to say is that it would accelerate in this direction. Now, of course, as it gets closer, the field is not uniform. It could change its acceleration, but right from there, in general, it wants to go in this direction. It wants to, if I let go of it, it's going to move in that direction. So if I have to move it in this direction, this is a positive charge. Check it out. The force is in that direction, and my displacement is in the opposite direction. So the work done by the field, right, which is the one that's exerting force, you can see that the field is anti-parallel, or the force is anti-parallel to the displacement. So work done by the electric field is the electric force, right, dotted with the displacement. That dot is cosine theta. So if these are about 180 degrees, or if they go in opposite directions, that means the cosine is more than 90, because cosine is negative. So it means that the electric field has done negative work on this charge. Now, whoever pulled it, like if I'm the one who brought the charge, and if I grabbed it and I pulled it in this direction, then I do positive, but the electric field does negative. So that's very important that we make that distinction. All right, let's move on. We've got a couple more, and then we'll call it in. All right, it says describe one way to replace a single charge in this configuration that would make the electric field at the center of the square equal to 0 and justify your answer. All right, so here we have our box. We want to know what can we do just one charge such that we're going to get rid of such that we will have no electric field. All right, and so when I look at this, well, I know that if I have symmetry, if I have a negative and a negative, those electric fields are going to cancel because those are in this direction. So those electric fields cancel due to symmetry. So if I could replace a single charge to create more symmetry, what I would do is I would get rid of this one, this positive charge, and I would make that Q minus. And if I did that, I would have a minus. I would have an electric field in that direction, and the total electric field would be 0. So what I'm going to say is I would replace, all right, the bottom left with negative Q. The symmetry causes E equals 0 at the center. All right, so we got that. Now let's do this next one. We got a to describe a single charge in this configuration that would make the electric potential at the center of the square 0. Well, potential is a scalar. So if we have 2 plus Q's and 2 minus Q's, and they're all equidistant from the center, that's going to do it. So I can replace any one Q minus Q with a single plus Q. Okay, if I do that, that means the sum of all the voltages is going to be equal to K negative 2KQ over what did we say this was? This is that's square root of 2 over 2A, and then we have a positive 2KQ over square root of 2 over 2A. And so this negative and this positive add to 0, and so I replace any one Q minus, either this one, or this one, with Q plus, and I am good to go. All right, now let's go ahead and do one more, and then I think we'll get you out here maybe in a minute or two. All right, good for Tuesday. All right, here we go. Now this one is a problem that we have to think a different way to do, different than the square one. It's a 6 positive charges set in a circle of radius r, so they're equidistant apart as shown. Answer the following in terms of KQ and R. Write expression for the electric field strength at the center of the circle. Well, I think that you could easily convince me that due to symmetry, that the E at the center of the circle is 0. Okay, now write expression for the net amount of work that must be done to bring a 7th charge Q plus from a location far away to the center of the circle. Now let's talk about that. I got a charge. It's very far away. It's a Q plus, right? And I'm going to bring it from here at infinity all the way, and I'm going to smack that right there. That's where we're going. All right. So how much work do I have to do? Well, what I could do is I could figure out. Let's see how much. I could figure out how far. I can figure out the difference in potential energy from here to here. However, it's much easier to find the amount of work by finding the change in potential energy, and so that's going to be delta V times Q. Now, what is the potential here at the center? Well, it's the sum of all of those KQ over R, and they're not vectors. So each one has a charge Q, and the distance is R, and there are 6 of them. So that is the potential at the center. What is the potential at infinity? It's 0. That is the definition. That at infinity, when we say conventional, at infinity, the potential is 0. But here in the middle, the potential is 6KQ over R. So what is delta U? Well, that's going to be delta V. So that's going to be delta V is 6KQ over R times Q, which is again Q, and so we get 6KQ squared over R. And if you think about it, hopefully that makes sense, because the first one we brought in, if we bring in the first one, it doesn't take any energy. So we then brought 1, 2, 3, 4, 5, 6 more, and that last one, that's how much energy it took because I was working against all this. So that is how we would do that. And there's one more thing I want to show you before we go for the night, and that is the magic square of electrostatics. Now I taught this for many years, and this is just a mnemonic that helps me and help my students to remember electrostatics. And so I always start in the top left-hand corner with the force, and the force is I'm so used to it. I know force from mechanics, and so we know the force is equal to KQ1 Q2 over R squared. That's called Coulomb's law, and the units for that are newtons. Okay? Now, if we take the force and we divide it by a charge, what we get is the E field, which is KQ over R squared. Notice I divide it by Q to get from here to here. All right, now the units for this are newtons per Coulomb, not too different from the units for a gravitational field, which are newtons per kilogram. All right, now we're going to talk about what over here we're going to put U of E, which is of course potential energy. I'll go ahead and write that because that's new today. Potential energy, right? And the potential energy is force times, usually when we get energy, work, we do force times distance. Well, if I multiply this by R, I get KQ1 Q2 over R, and so that is the formula for the potential energy for 2-point charges in a particular arrangement. The units for potential energy are joules. We learned that in mechanics. All right, now this is the other one. Remember, we're dividing by Q when we go here. So here we have the potential difference, and that's KQ over R. And the units here are joules per Coulomb because I divided by Q as I went down this way. Now, one more thing I want to show you, because we'll see this as we go this way. Another way to say the electric field, newtons per Coulomb, it has another set of units. And if we go to the right and we multiply multiply by distance. That means then we go to the left, we're going to divide, and we're going to divide by distance. And so what we get here are volts per meter. And so the electric field units are either newtons per coulomb or volts per meter. They're both okay. We'll probably visit this guy again because it's just really helpful. And it's kind of something I'm going to tell my students, hey, put this up on the wall when you're taking your AP exam on the left. So you see this in front of you. It'll help you to navigate back and forth. And of course, we can fill in a few. Not everything is done in here. We can say also we know that delta U is equal to Q delta V, right? Because this is, if we're dividing by Q, here we're multiplying by Q. And so you can see how this all helps us find some relationships. Okay, so that's what I wanted to show you today. We decided that we wanted to give you a chance to find the electrical potential, okay, and also talk about the electrostatic potential energy. And these two are not the same thing. And we calculated the amount we're going to arrange a system of charges, and that is the potential energy of those charges. So that's where we are. Tomorrow night we're going to keep looking at potential, and we're going to talk about something called an equal potential surface, which is a really cool way to look at a two-dimensional E field and potential. Until then, keep working hard. We're really just so happy to see you here tonight. Kristen, anything for our great students?
No, just can't wait to see you guys again tomorrow, same time.
Excellent. So once again, thanks for tuning in. We hope these are helpful, and can't wait to see you Wednesday night, same place. Take care and have a good night.
Well, good evening, everybody. This is AP Physics C, Electricity and Magnetism, and my name is Kristen Gonzalez-Vega. I'm coming to you from Frisco, Texas, where I teach at Reedy High School. And tonight, as always, I have with me Roger.
Hello, everybody. My name is Roger Siegel, and I live here in Sarasota, Florida, and I teach at Pineview School, and we're glad you joined us.
Okay, and we are getting closer and closer every day, guys, to the big day and being done. So we are reviewing today electric potential and electric potential energy in uniform electric fields. We started talking about point charges yesterday, so we're just kind of continuing on from that. If you didn't catch it, it might be good to go back and look at that even after tonight. You can still watch this tonight; it'll be perfectly fine. But go back and take a look at that. Our objectives today are to be able to describe the relative magnitude and direction of an electrostatic field given a diagram of equal potential lines. We want to be able to describe characteristics of a set of equal potential lines given in a diagram of an electric field. Right? So we need to be able to kind of translate between one and the other. If you're given the electric field, can you create or describe the equal potential or the potential lines, and vice versa? And then lastly, use the general relationship between electric field and electric potential to calculate the relationships between the magnitude of the electric field or the potential difference as a function of position. So kind of a review from last night. What is electric potential? It is not something we can measure, but it's something we can kind of qualitatively say or quantitatively say is the amount of energy per charge. So that is something we can calculate. So we don't have an electric potential meter. Now we can find the electric potential difference between two places. So that is something that generally we find a little bit more meaningful to talk about is what is the electric potential difference between 2 points or 2 regions, parallel plates or terminals of a battery. And that is something you can measure. We are can relate the electric field to the electric potential, and we're going to derive that right now. So what is the relationship between the electric field and the electric potential? Well, we're going to start with our old relationship that we go back to all the time with forces and energy, potential energies. And that is that relationship that the force is equal to the negative derivative of the potential energy with respect to position. So if we start there, we're going to get a relationship for the electric field and the electric potential. So if we know that the force is equal to the negative derivative, why is it that negative derivative, right? That's one of the big questions in physics. We see a lot of mechanics, right? Any of those forces that are related with potential energy, we mentioned this last night, are conservative forces, right? Spring potential energy, US, gravitational potential energy, UG, and now electrostatic potential energy, electric potential energy. Those are all conservative forces. They're associated with a potential energy. They're also do not depend on the path, right? Independent of the path taken, the amount of work done. So it's always negative because the force is positive and doing positive work when you are losing potential energy and doing negative work when you're gaining potential energy. Okay? So I can turn this force though, because if this is the electrostatic force, it's the negative derivative of potential energy. We'll say it's the electric potential energy then over dx. Well, how can I find that electrostatic force if we're in a uniform electric field? So if we're in a uniform electric field, how can I find what the force on a charge is? Well, that's Q times E. So that equals our negative derivative of the potential energy. Okay. Well, if I want the relationship of the field, I'm going to divide out by the charge to get rid of the charge. So really, I get the electric field is equal to the negative derivative of the energy over dx times Q. Well, we said just a second ago and last night we talked about it a lot. What is the relationship between the electric potential energy per charge? Well, that is that electric potential. So then we can say that E is equal to the negative derivative of the potential with respect to distance. If we were to see that in a graph, what would be significant about that? Well, we call that derivative is equal to the what on a graph? The slope. So if we have the potential versus position graph, no matter what shape it is, that slope is equal to the electric field. The slope of the potential is the electric field. That's if it's changing, right? We can use that dV over dx. But if it's not changing or if it's uniform or just a nice straight slope, we can also say this is delta V over delta x. So that one we use a lot too. Okay? So just kind of a way that we can look at that relationship. So we kind of put a little list of important equations here off to the side. Well, we know that the potential is the amount of electric potential energy per charge. We know now that the electric field is the change in potential over the change in distance. We know force is Q times E. We know that work is the negative change in energy. And we may add to that, right? But that's just some things that we can be thinking of those relationships because we have a lot of kind of back and forth and ins and outs and relationships that we're going to substitute into. So I'm going to show you now how we can also graph this. So one way we can graph and talk about potential is we can look at the potential as a function of position, right? So if we have a charge on an axis, x-axis here, and I just want to know as a function of the position, what is the potential, right? And we know that when we looked at point charges from a couple of nights ago, or maybe that was even just last night, it's all blending together, right? That the potential of point charges is equal to kq over r. So if we look at that relationship, it's a 1 over r relationship, right? So we could graph that potential as a function of the position. We could also look at what those equal potential lines look like around a charge, because if I am the same distance around my one charge, well, what's going to be true about the potential everywhere on that one spot? It should be the same. So we can plot these equal potential lines where they have the same potential, right? Equal potential means equal potential. So I have a PhET simulation here that I have pulled up to show you. I'm going to switch my shares here, and I have already plotted some equal potential lines here. So I've put 2 positive charges on here, and what I've done on the left side here, on that left positive charge, if I show you my little potential meter, right, which we don't really have, but I kind of graphed it and plotted every 10 volts. So if you notice, as we go out every 10 volts, what happens to, and I couldn't really go further out here because again, we have the other charge interacting, but if you notice those lines, they're getting further and further apart. And so another way we can kind of give another comparison to are those topographic maps, right? If we kind of imagine this as a topographic map, we know that as elevation goes up, we can draw those lines closer and closer together. So we can also imagine that potential as these nice peaks, which kind of sometimes helps think about what objects or charges are going to do when they're in this potential, right? If I'm at the top of a hill, a marble wants to roll down. Well, if I have a charge at the top of our equal potential hill, it wants to roll down too. And so we can draw these lines, and the main thing to remember that everywhere on these lines, that potential is the same. So we're also going to look at how the electric field looks with regard to these potential lines. So if I add in our electric field, let's just take a minute and what do you notice? What do you notice about these electric field lines? If you look at one of these field lines with respect to the equal potential lines, what do you notice? Well, they're perpendicular at every single point here on these potential lines. And so that's one thing that is always true. Our equal potential lines and our electric field lines are always perpendicular. And we know that our electric field lines always point away towards lower potential. So if we look closer here, if I get my meter out here, we can see we've got 31.07 volts here. I've got 19.66 here, right? That field line is pointing towards the lower potential. So those are the couple of things I wanted to show you on that. So let's go back here. And those are kind of our takeaways, right? On one contour line, the electric potential is the same everywhere. And the electric field vector is going to point perpendicular to that electric potential and points towards the lower potential. So let's kind of also look at here if we have a parallel plate. If I have this parallel plate and it has an electric field in between, uniform electric field, and I know the distance between my two plates. What kinds of things could I find out about this? Well, one thing I could ask you is what charge does the left side of the plate have? And you would all tell me the left side has a positive charge. Therefore, the right side has a negative charge, right? Because the electric field lines are going to point from positive towards negative because they're pointing away from the higher potential towards the lower potential. Okay, so the next thing we're going to look at here is which way would a proton have to move in order for the work to be done by the electric field to be positive, right? So if I want the work done by the electric
screen, please.
Oh, sorry, I thought I clicked share. There it is. Thank you, Roger. So if I have a positive charge here, let's just place it right in the center. Which way would this positive charge have to move in order for the work done by the electric field to be positive? Okay, and vice versa. I also want you to think about which way would an electron have to move in order for the work done by the electric field to be positive. Okay, so those are the two questions I have for you first. Which way would each of those have to move in order for the work to be done to be positive? I'm gonna make a little chart here. Okay, so the first thing I want you to think about is which way would the force be acting on each of these charges. So if we have our positive charge, which way would the electrostatic force be on this positive charge? Well, the positive charge wants to be forced towards the negative side. The electrostatic force on the positive charge is always in the same direction as the electric field, and the opposite direction for the negative charge. So I'm going to say, well, for the positive charge, if we're calling to the right positive, then this has a positive force acting on it, and the negative charge has a negative force acting on it. Okay, well, how do we get work? Work is force times that parallel displacement, the parallel component, right? This is already parallel. We don't have to worry about that dot product. So I want to look at, well, if I want to have positive work on the positive charge, the force is already positive. So which way does the distance have to be? Do we want a positive displacement or a negative displacement? Well, to get positive work, I want a positive displacement, which means it has to be moving to the right. Okay, let's look at the negative charge. The negative charge has a negative force acting on it. So if I still want positive work, what do we have to do with the distance? Well, the displacement has to be in that negative direction. It'd still give us a positive work. So the negative charge has to be moving to the left. Okay, and then the opposite, obviously, for negative work. My force is still positive. That I can't change unless I change the polarity of the plates, right? So if the force is still positive in this direction, to get negative work, I have to have a negative displacement. And same thing for the negative charge. If the force is still negative, if I want a negative work, I want positive displacement. So it is moving to the right. So in general, for the work to be done by the electric field to be positive, the charges have to move the way they kind of want to move, right? If a positive charge wants to move away from the positive side towards the negative side, then the electric field is doing positive work when the charge is doing what it wants to do. The negative charge wants to move towards that positive side. So positive work is done when it's doing what it wants to do. Okay? And when we have a change in energy, well, we know the change in energy, work is equal to the negative change in energy, or change in energy is equal to negative work. So a lot of times this might be sometimes easier to think about with like the gravity and gravitational fields, right? The gravitational force is doing negative work when we are gaining potential energy, when you're lifting a box up. So kind of the same thing here. If I'm moving the charge and the charge is gaining potential energy, that means that's when the field is doing negative work. And so our change in energy when it's going to the right, so let's link this up. When does it have a positive gain in potential energy? Well, that's when our work is negative, or when it's going to the left. And for a negative charge, that would be when it's going to the right. Okay, so those are kind of some main things I want to point out with you. Sometimes looking at these fields and the charges and the work and the energy can get really confusing. But if you kind of put that analogy with the gravitational fields, it's really easy to remember. If you lift a box up, you're doing positive work, but gravity's doing negative work on it. And anytime you're lifting it up, you're gaining potential energy. Okay, so I'm going to toss it back to Roger. He's going to do some practice problems with you.
Okay, thanks a lot, Kristen. And hi again, everybody. So yeah, we're going to keep learning about potential. So let's go ahead and let me share my screen with you guys, and we can look at some problems that we're going to do. Okay, so of course, this is what we call an equal potential diagram. And so again, as Kristen mentioned this, I'm going to keep coming back to this analogy. In Florida, we don't have a lot of terrain because it's flat everywhere, but I always manage to get to some place that's hilly, and I love to hike around. And this tells me if this were a not a electrical potential diagram, if it were a gravitational potential diagram, it would tell me the contour of the land. It would tell me where the land is, where it's steep and where it's gradual. And so if we think about that, if we think about these potential surfaces as if we think of height as a potential metaphor, not 100% ironclad the best metaphor, but a really good one. I think it's going to help us a lot. So let's look at this equal potential surface. So we got 3 point charges, and they create this surface, and that really doesn't become a big part of it, but just know that there are point charges that create this surface, and here are contours. Now it says draw an arrow each of the labeled points indicating the direction of the electric field. So you can see we have all these points. Now there's a couple things that Kristen told us about electric fields and equal potential surfaces. So let's go ahead and take a look at that and see what that is. So if we come here, just get this thing to fit. Perfect. Okay. And so here's our point A, and every place where we have an equal potential surface, the electric field is perpendicular to that equal potential surface. So there's A, I'm going to draw perpendicular, B, perpendicular, C, perpendicular, D, perpendicular, E, perpendicular. So every place, the electric field everywhere is always perpendicular to the equal potential line. Now the question then is, okay, we know that the electric field is a vector. I've got the direction in this way, but is it down? Where do I put the arrow? Well, again, the electric field always points towards a lower potential. So you can see here, up in the upper left-hand corner, we have our negative 60, and down here we have our positive 80. So clearly the lower potential is in this direction. That's my lower potential. So I'm going to go ahead and say that my electric fields are all in this direction towards these lower potentials, say from 30 to 20 in that direction, or from 0 to negative 10. So this is my direction. So that's my direction there. All right, great. Let's go ahead and look at the next piece. It says draw the electric field line that goes through point C. Well, I thought we did that, but let's, the electric field line, I'm sorry. So the electric field line goes through point C. Well, we know that it's going to be perpendicular, parallel here, but look, it's also perpendicular here. It's also going to be perpendicular here, and perpendicular here, and perpendicular here, and then it's probably going to be like this. Now, please do not confuse this line with a path that the charge would take, okay? The charge is not going to take this path. However, this tells me in which direction it will be accelerating. Again, don't confound acceleration, and velocity, because since this is the direction of the electric field, this is the direction of the force, because F vector is equal to Q E vector. All right, so that would be the electric field line through point C. At which point is the electric field the strongest? Now, this is where we go back to our analogy of a terrain map or a topo map. If you recall, if you've ever seen a topo map, you can imagine what it's telling me. It's telling me equal areas. So wherever there's a cliff where the terrain is very steep, I have these very close together. And so in the same way with potential, remember potential is also the negative, I'm sorry, let me back that out, not true. All right. The electric field, all right, is the negative derivative of potential. So what does that mean? Well, that tells us that wherever this is closest together, wherever these lines are closest together, that's where we have the strongest electric field, because the electric field is essentially the slope of this terrain, the magnitude of it. So if I look at A, B, C, D, and E, well, clearly A is where we have the lines closest together. So we'll say close together lines. So we remember that equal potential lines. And it's the weakest where they're furthest apart. So if you look over here, B, C, not E, but maybe D, that looks like a really big distance to the other line. So I'm going to go ahead and call it on D, although it is close one. All right, let's go. Suppose the distance between D and E is 6 meters. Estimate the electric field strength. Now look, electric field strength is, in a calculus sense, negative, and we'll put it
over here again, is equal to negative dV dx, and that's, in one direction. We'll do it one direction at a time. Well, that if we approximate that, we can say that the electric field approximates to the change in voltage. That's not velocity, that's voltage over the change in x. So we see from point D to point E, look at this, we're going from 0 volts to point E at negative 30 volts. So that means we have negative 30 minus 0, and the change in distance here is 6 meters. And so that is, by the way, volts. And so what we get is 5 volts per meter. And remember that the electric field has two different units. One unit for the electric field is newtons per coulomb. The other one is volts per meter. All right. And then we got two more on this page, and we'll move on. This is a 5 kilogram object with a charge of 0.1 coulombs is released from rest at point A. It follows a path point E. How fast is it moving when it reaches point E? Now, it's released from rest. Now, again, do not confound this line with the actual path. This is the direction of acceleration, not necessarily the path. But let's imagine that it is released here, and it follows some line, and it gets over here to point E. And so let me try that again. And so it'll go here, and it gets to point E. And so the question is, what is its speed? Well, remember, again, this is our analogy that works well for us. It's rolling downhill. Positive charges roll downhill. And so that means that its change in kinetic energy shows up because there is a change in potential energy. Now, let's go ahead and take a look at that, try that a little bit, and I'll do some work here. A lot of algebra coming our way, so let's give it a try. All right, so we have 1/2 mv squared is equal to delta U, and that's going to be Q delta V. Now, let me just stop for a minute. This V is voltage. This V is velocity or speed. They're not the same, obviously, so be careful. That's why I put the little line under this V. All right, so that means, ladies and gentlemen, if we do a little algebra, we get V squared is equal to 2Q delta V over M, or V is equal to the square root of 2Q delta V over M. So we can go ahead and fill that out, and we have the square root of 2. The charge is 0.1 coulombs. The voltage, the change in voltage, let me put that, I forgot, I told you I'm going to write that. That's the voltage, the big V, and I put a little line to tell me that's big V. And the change in voltage, so we need to go back to our picture here and take a look at it and see what we have. And so here we can see, if we go from point A to point E, we're going from 70 volts to negative 30 volts. So the change in potential is going to be negative 100 volts. All right, now I'm going to put a positive 100 because we're under the square root, and we don't want to do anything to mess that up. We'll talk about why that's negative. And our mass is 5 kilograms. And so when we do this work, what we get is that this equals 2 meters per second. But I want you to notice that what this is our classic conservation of energy problem, except instead of getting its kinetic energy from rolling downhill from a change in gravitational height, we get a change in potential, electrical potential. All right, now, same object placed point B, an external force acts on the charge and causes it first to move to point B, then point C. How much work is done by this force? All right, so let's take a look now. If I start over here, and again, I'm going to move from point, let's start at point B, and it is moved by an external force to point D, and then it's moved to point C. So that is how much work is done by the force. Well, the change in energy is equal to Q delta V. But look, delta V, I started at B, I went to D, and then I came back to C. That means that the change in energy is 0, and the work done is 0 as well. All right, let's go down and do real quick a couple more. We've got two charged cylinders running parallel in and out of the plane as shown, page is shown. And the question is, you can see here's our equal potential lines. And so is the conductor on the left positively or negatively charged? Well, since it's making a positive, causing a positive potential like this, we say that it's positively charged, and as well as the conductor on the right. A particle is brought from point D to point B. Through what potential difference does the particle pass? Well, the particle goes from D to B, which means it goes from 200 volts to 75 volts. And so that's going to be negative 125 volts. It loses 125 volts potential. That means that it's going to gain kinetic energy. It's going to be moving faster because it lost potential. All right, and then finally, a particle that carries a charge of 1 coulomb moves from point F to point G. How much net work is done by the force of the field, by the electrical force? Well, the work done by the force is going to be, again, Q delta V. And so that's going to be 1 coulomb. And the change in voltage from F to G is 100 volts. And so remember, a volt is a joules per coulomb. So that's going to be 100 joules of energy that will be given to that object. And then finally, down here, same picture, we're asking the same question. What direction is the electric field at point B? So let's look at B. Well, we know the direction is going to be perpendicular to B. Is it to the left or to the right? Well, remember, the electric field always points in the direction of decreasing potential. And so that's to the left or 180 degrees. If a proton is placed at point F, what direction will it feel a force? Well, a proton is positive, and the electric field is going to be perpendicular pointing to the lower potential. And so the direction it will feel a force is in the direction of 135. And then if an electron is placed at point E, what direction will it feel a force? Well, the electric field at point E is in this direction. But ladies and gentlemen, it is an electron. And so an electron is negative. It will feel a force in that direction or negative 90 degrees. So I hope that helps you to understand a little bit more about equal potentials and how they tell us what's going to happen to a particle and how its energy is going to change. So again, just keep trying to picture those terrains, and that should help a lot. Kristen, I know you're going to take us home. What you got?
I'm super impressed at how efficiently you got through those, Roger. We have maybe 1.5 questions to look at. The first one here is from 2016. If you want to go back and look at it later, it is an electric field diagram above, right? So we've been looking at some equal potential lines, equal potential mapping. Now let's turn and look at, now we have the electric field lines. So points A, B, and C are all located at y equals 0.06, right? So all on that same kind of horizontal level there. And we want to know at which of these 3 points the magnitude of the electric field is the greatest, and justify your answer. At which of these 3 points is the electric potential the greatest, and justify your answer. And then B, an electron is released at rest from point E. Qualitatively describe the electron's motion in terms of direction, speed, and acceleration, and calculate the electron speed after it's moved through a potential difference of 10. So we give you just a couple of minutes here. I want you to, first of all, I want you to mark up and write some different things on that electric field line diagram. What kinds of things stick in your head that maybe you would do, or you could label or draw on that mapping. Okay, and then I want you to answer A and B for me. And I'm going to give you a couple of minutes to think about what you would say, jot down some stuff on a piece of paper, and then we'll discuss. And you might need some more time, especially on part BII, but we'll go ahead and go over it if you need to stop and pause at any time you can. So when I'm looking at this electric field mapping, the first thing I'm going to look at is I want to look at which way those arrows are pointing. I want to look at where those lines are close together, where those lines are spread apart, because those are going to tell us things, right? When we have these lines really close together, what does that mean when those electric field lines are close together? Well, that tells me that there is a bigger magnitude of that electric field. When they're more spaced apart, I know I have a smaller magnitude of electric field. Okay, which way do those lines point? Well, electric field lines are always pointing from that higher potential to lower potential, right? So I'm kind of thinking these things through when I'm looking at these diagrams. If I were to draw the potential, equal potential lines, well, what can we do? We know that they're always perpendicular to the electric field at every point. So if I wanted to, I could draw some of those lines on there. Okay, we'll save that. But let's look first at A. So which of these points, A, B, or C, are going to have the greatest magnitude of electric field? Where is the magnitude of the electric field the greatest? Right? Well, if we were already kind of looking through those diagrams and thinking about it, we know this is going to be greatest at C. What would we write for our justification? Right? We want to use those good physics terms in our justification, right? So at C, it's the greatest. And how do we know it's the greatest? Well, it's because the electric field lines are closest together. Okay. What about where the electric potential is the greatest? Well, again, if we were looking and we were analyzing that before we even read the question, oh, I'm kind of frozen here, aren't I? I'm going to stop and reshare. So if we're looking at where that potential is the greatest, we're looking for, I'm gonna pull it right back up. I'm just chatting away while I get it working again. So what are we looking for on the electric field mapping? Well, we're looking for where we know that the electric field is pointing, because we know the electric field is going to point from that higher to lower potential. So which side is closest to that higher potential side that we identified? That would be point A. So A would have the greatest potential, since the electric field points away from the higher potential towards lower potential. So we want that leftwardmost point. Okay, let's look back at this and say, what's going to happen to an electron if we place it at B? I'll change colors here. Okay, so if we place an electron at B, what is going to happen to it? And we want to describe over a long period of time what's going to happen to it. So first thing I want to know is, if I want to be able to describe this in terms of the acceleration, the direction, and the speed, well, if I'm going to describe the acceleration, which really relates to the speed and the direction of everything, it depends on which way that force is. So we want to think about which way is the force going to be on that electron. Remember, electrons feel forces in the opposite direction of the electric field. And so that would be to the left. So we know that the force is going to be to the left. So if the force is to the left, what does that tell us about the acceleration? Well, if we know F equals ma, if the force is to the left, then the acceleration is going to be to the left. So we know it's going to accelerate to the left. But what does the magnitude of that force and therefore the magnitude of the acceleration relate to? Frozen again. Sorry, guys. Well, force is equal to Q times E. Let's try this one more time. It doesn't work. We're just going to go back to the PowerPoint. Okay, so we know the force is related to Q times E. So we can say, well, is this field the same? Well, no, because as this goes towards the left, what do you notice about the distance between those field lines? It's getting bigger and bigger. So if the distance between those field lines is getting bigger, we know the magnitude of the electric field is getting smaller. So if the magnitude of the electric field is going down, then we know the acceleration has to be going down. Okay, but it's still speeding up, right? So it's speeding up to the left, but the acceleration is going to be decreasing. So it's still speeding up, but it's kind of like free fall, right? When there is air resistance, we start with that big acceleration downwards because our drag force up is really small. Remember, drag relates to the velocity. And as you are falling and that drag force gets bigger and bigger, you're still speeding up as you go down, but the rate at which you're speeding up is getting smaller, right? This is the exact same thing. You're going to be speeding up to the left, but the rate at which you're speeding up is going to be decreasing. Okay. And then how would we calculate? So I just want you to describe it. How would you calculate the speed of it, of the electron, after it has moved through a potential difference of 10 volts? So I'm going to switch over while you're going to describe that. I'm going to switch back over because this is going to keep freezing up on me. Okay, so we're on this part right here, B, calculate the electron speed after it has moved through that potential difference. So how are we going to get the speed? Well, when it's at that original location, we're going to relate, just like Roger did in the last problem, that our change, our potential energy is changing, that electric potential energy is changing because its location in this electric field is changing. That's going to turn into our kinetic energy. So whatever potential energy I'm losing by changing through that potential difference of 10 volts is going to be gained into kinetic energy. Okay, so we can say, how do we get that electric potential energy? Well, we know that it's equal to, if V is equal to U over E, then our V is equal to Q times V. But if we want delta U, then really I want delta V, and that's going to be equal to our 1/2 mv squared. And then we can find out what that velocity is using that potential difference of 10 volts. Okay, so I want you to look at then points B and C, and if they are separated by a potential difference of 20 volts, estimate the magnitude of the electric field midway between them, and state any assumptions that you have to make to do that. So I want to know if the distance, the separation of these two is 10 volts, then how could we find what the magnitude of the field is at a region at point midway between them? What's that relationship between the electric field and the electric potential? The electric field, remember, is equal to the slope or the derivative of that potential, negative. So since we're talking big here, let's use that negative delta V over delta X, right? So I'm using that B to C, that's what I know the potential difference of. So if they're just giving us that it's separated by a potential difference of 20 volts, then we can say that 20 volts, well, we've got to estimate what that distance is between B and C. Well, B is at 0.08 meters, and C is at 0.09, so they're separated by a distance of 0.01 meters, which would give us then 20 over 0.01, we move that decimal two places, and we get 2,000 volts per meter. Okay, what was an assumption that I had to make in that? Always everything about those assumptions, right? What are the things that we are assuming? I'm assuming that that is a uniform field in that region, right? That is a constant electric field between B and C that's not changing if I'm using that whole change between them. Right? And on the diagram, draw an equal potential line that passes through D and intersects at least 3 electric field lines. What's the key? We have to stay perpendicular to that electric field at every point. So if we wanted to go through D, all right, if we wanted to go through D and we want to be perpendicular everywhere, going through at least 3, we can go through more than 3, can't we? And I would be drawing my equal potential line like that. Okay, we are out of time. I'm going to put up one just for you to think about. Just the first question I have here, we're not really going to look at these. What I want to know is, looking at these two charges and looking at these equal potential lines, I want you to tell me for tomorrow which of these charges, well, we know that the magnitude of charge 2 is 2 nanocoulombs, right? So looking at these equal potential lines, I want to know, is Q1, the magnitude of Q1, bigger than, less than, or equal to the magnitude of Q2? Okay, so that's our $1 million question for tomorrow when we come back. Is Q1 bigger than, less than, or equal to magnitude-wise to Q2? Okay, well, that is all we have then. We will talk about that tomorrow. So you should be able to relate those electric fields and electric potential, the graphs of each, how can you go back and forth from one to the other, and what was that relationship between the field and potential. Tomorrow, we're going to do electric potential of our fun other distributions of charge, meaning that ring, that arc, and that line of charge. And then Friday, we're going to finish out potential with concentric conductors. So, Roger, what have you got for the rest of tonight?
What have I got? Just a big thanks for tuning in, and a big good luck, and we hope these are helping.
All right, have a great night.
Well, good evening. Happy Thursday. Welcome to AP Physics C, Electricity and Magnetism Live. We're coming to you live tonight. My name is Roger Siegel, and I'm coming to you from Sarasota, Florida. And with me, as always, is my friend and co-teacher, Kristen. Hello, Kristen.
Hello, Roger. Everybody else. I'm glad you know it's Thursday because I have no idea what today is. But I know I am in my house still.
Okay, great. Well, I've heard it been described as Blur's Day. What day is it? It's Blur's Day. So maybe it feels that way. But it will be a little different tonight. Tonight is not just a Groundhog Night because we do have a slight mix-up tonight. We're going to throw it back and forth one more time tonight. I'm going to start, though, by kind of getting us, situated on where we are. And so let me go ahead and bring up our, for tonight, our presentation here. And let me start up here. All right? And the first thing that I want to make sure I say is what we're doing tonight. So tonight we're going to continue with electrostatics, and we're going to continue with the concept of electric potential, but we're going to look at electric potential due to distributed charges. Charges that are not point charges, but charges that are smeared out in stays, bars, lines, arcs, and things like that. And then we're going to, again, my name is Roger Siegel, and join Kristen. And so I do want to remind you that your AP Physics exam, AP Physics C E&M exam is going to be on May 11th. Please note the times because they're different in every time zone. So please make sure that you're cognizant of that, and as it gets closer, that you make plans to have that space all set aside where you're going to take your exam. We will talk a lot more about the exam, especially the week before. As far as our progression through our review, getting ready for the AP Physics C E&M exam, we started a week ago, Monday, so we've been at this now for 9 days, and we started reviewing electrostatics. There's 3 units in the physics curriculum. The first one is electrostatics, so it's got a lot in it. So we've been doing charge, electric field, electric potential, electrical potential energy. We're going to talk a lot tonight specifically about electric potential. And then tomorrow night we're going to do concentric conductors. We will do spheres
spheres and I think cylinders as well, so that should be okay. So, but for now, if you recall, if you were with us last night, we were doing equal potential surfaces, which I think is a really cool topic, but very challenging. And so we didn't get to finish that, so I want to throw it back to Kristen, and she's going to walk us through the electrical potential, equal potential problem, and then we'll come back and talk about tonight's stuff. All right, go.
Okay, thanks, Roger. Yes, let's wrap up this problem because I know everybody's been thinking about it overnight. I asked a question yesterday, and that was, first of all, looking at our equal potential map here. We know the charge of Q2, but I wanted to know, does Q1 have a greater magnitude, less than, is the magnitude smaller of the charge, or is it equal in magnitude to Q2? Okay, so how do we know? Well, let's look at these lines. We can look at the lines around the charge that we know, that Q2. And if you look at the closest equal potential line, that corresponds to a potential of 8 volts. Now let's look at our closest potential line for Q1. If I look at the closest potential line, first potential line to Q1, it's negative 24 volts. And so we're looking at that equation for a point charge for a couple of days now, that the potential of a point charge is KQ over R. And so if I am looking at that charge and looking at the potential, a bigger charge is going to give me, and even if I were to compare like the same distance away, right, is going to give me a bigger magnitude of charge. So Q1 we know has to have a greater charge because if we look at those potential lines, they have a much greater magnitude. But how do we find what Q1 is if I know what Q2 is? Let's look at that next. How do I know what Q1 is going to be? Well, let's see what else we know. I know Q2, okay? And we can look at some potential. I want to look specifically at point B. If we look at point B, it is on an equal potential line that has a potential of 0 volts. So if its potential is 0, what does that tell us about the potential? Well, where is there potential here? We have potential due to charge 2, and we have potential due to charge 1 in that region of space. In order for it to be 0, we know that we have to have the potential from charge 1 equal to the potential of charge 2. And so if we set those potentials equal, and we know the potential is KQ over R, then we can say KQ1 over R1 equals KQ2 over R2. So we're not necessarily going to plug in today, but let's look at what those R's would be, right? Where is that R going to come from? Well, R, remember, is the distance from our charge to that region of space that we're looking at, right? So for R1 would be from Q1 all the way to point B. And if we identify what Q2 is, what R2 is, that would be from Q2 all the way to point B. Okay, so just remember that it's from that region of space to where your charge is. Then we can rearrange, case cancel, and we can solve for what the Q1 is. Okay, if you want to go back later and do that, I can tell you that it should be 5 nanocoulomb. Okay, part B says at point C on the diagram, draw a vector representing the direction of the electric field at that point. So let's look at point C. Erase this stuff so we can just look at this link now. Okay, so we look at point C, we want to know which direction the electric field is at point C. Well, what do we say was true about our electric field lines and our potential lines? We know they're perpendicular, first of all, so I know that it's going to be perpendicular at that point. And if the electric field lines always point towards lower potential. So if we put our arrow here on here, we know that our electric field is going to be pointing down towards that left. It's perpendicular to the equal potential line at that point and pointing towards a lower electric potential. Okay, part C says calculate the approximate magnitude of the field strength at point D on the diagram. So now we're looking at point D right here, and I want to know what is the electric field there. So how can we find that electric field? Well, what was the relationship between electric field and potential? We know that the electric field is equal to our, since we're talking kind of big scale here, our change in potential over our change in position. So if we want to know that magnitude, we can look at, well, what is the change in potential between these two lines? It's 4 volts. And what is that change in distance, right? We have our scale here. Each square, if we know this whole block of squares is 0.5 meters, then one square is going to be just 0.1 meter. And so I have 2 squares here, so that would be 0.2 meters. So if we take 4 divided by our 0.2, we get 20 volts per meter. And then lastly here, D, the equal potential labeled 0 is the cross section of a nearly spherical surface. Calculate the electric flux. Look, we're bringing electric flux back into this. Or we talked about that before with Gauss's law. There's 2 ways we can find electric flux. It's either side of Gauss's law. So we could say it's the integral of E dot dA, or we could say that it is Q enclosed over epsilon naught. Well, I think the easiest of these two is going to be this one, right? Because here we cannot really use the left side of Gauss because the electric field isn't the same everywhere here. So we want to know what the electric flux is for that surface where the cross section is a nearly spherical that goes through 0. Right? So we're looking through that one right here. So if we want to know what that flux is, well, what charge do we enclose? We've only enclosed charge 2 in there, so it'd be Q2 over epsilon naught. And so again, we won't worry necessarily about math. We're going to talk kind of conceptual. How would you do it? We could plug in that 2 times 10 to the negative 9 divided by epsilon naught. All right, and then let's move on. A proton is placed at point A and released from rest. Zoom in a little bit here. So we're going to release a proton from point A, and we want to calculate the work done by the electric field in the proton as it moves from point A to point E. So how are we going to find the work? How can we relate work here? Well, we know work is that negative change in potential energy. And how do we get the electric potential energy? Well, it's Q times V. So change in work would be negative Q times delta V. Okay, so we want to know as it moves from point A to point E. So if we look at where E is right here. So we want to know what is our change in potential from point A to point E. So we can say that the work is equal to the negative. We're just going to leave Q as that charge on our electron. And then we say delta V is going to be, well, our final position is at E, which is at negative 4. We follow that potential. Remember, everyone one potential line has the same potential. So if it's negative 4 volts here, it's also negative 4 volts here. Minus, well, we started at A, so that's our initial, and that was at 0 volts. So we could cancel out those negatives, and we could determine what that work is. And then what would be the speed of the proton? What would we set that work equal to? We would set that equal to what kind of energy? Negative energy. So again, we could solve for once we get that work. Set equal to our 1/2 mv squared. We know the mass of an electron, so we can solve for the velocity. And then lastly, if an electron is released from rest at point B, which of the following indicates the direction of the initial acceleration at N. So we're releasing an electron at point B. So we'll get rid of some of this other stuff here. So we're going to release an electron now from point B. So I want you to tell me which way would the initial acceleration be for this. Think about which way the force would be to find which way the acceleration would be. So if I'm drawing the electric field here, remember what we can relate electric field to the force. So how do we draw the electric field at this point? Well, the electric field would be pointing perpendicular to our line at point B towards lower potential. Which way is lower potential? To the right. So the electric field at point B would be pointing to the right. And we know that electrons experience forces in the opposite direction of the electric field. So the force on that electron would be to the left. So if the force is to the left, which way is it going to accelerate? To the left. So our justification would be which way is the electric field? The electric field is pointing directly to the right, or the positive direction on the x-axis. Since an electron, our force must be to the left, and since Newton's law says second law says force equals ma, then our acceleration would be in the same direction as our force. Okay, so we are going to give it back to Roger in Florida to go over some of these other charges with.
Okay, thank you so much, Kristen. I appreciate you finishing that one up. Let's move forward and see what we can learn tonight about the potential from these distributed charges. Now, remember, these vocabulary words, they mean specific things, and so make sure that you're concentrating on how we're saying it and what it means. We'll say it as clearly as we can. Let me share my screen with you, and I want to start not at that problem, but where Kristen left off. Let's go ahead and start going down here. And let's see, where are we? Here we go. All right, so tonight, what we're going to do is we're going to derive expressions for the electric potential of a charge distribution using integration and principle of superposition. Describe the electric potential as a function of distance for the different types of symmetrical charge distributions, and identify regions of higher and lower electric potential by using a qualitative or quantitative argument to apply to the charged region of space. So, what does that mean? Well, let's look at what we've learned so far about potential. I think it was 2 days ago when we started talking about potential from a point charge, or maybe even 4. Maybe that was Monday. And we have this idea that if I have a charge, let's just say it's a negative charge, that somewhere, that everywhere in the universe now, there is a potential, and that potential is given by the value V is equal to KQ over R, where Q is the size of this charge, and R is the distance from that charge. And so that's our point charge. That's right here. And we can see that we create a potential everywhere in the universe when we do that. And by the way, remember, when we say potential, even if we don't say where we're comparing it to, it's always the potential difference. And if we haven't specified it, we're saying compared to 0 at infinity, this is what the potential would be here. So it's always a potential difference. All right, now what's different about tonight? Well, let's keep going. So we also learned that when we're doing a potential problem, we add up the potential from different point sources by superposition. So this problem, remember this was 2 nights ago, says 4 charges q plus each occupy the corners of the square of side A. What is the potential at the center of the square? Well, what we do is we find the potential from just one of these, from this distance r and this value q, and we say, well, the potential from one, and then we just add it up to the potential from the other, and there are 4 of them, and they're all the same. And so what we're saying is the potential at one point in space is the sum of the potentials from all of the charges that we're looking at. So let's see how that plays out in a problem with distributed charges. Okay, so when we have distributed charges, like for example, if we have a wire that's got charges all over it, and we want to know the potential here, what we're going to do is we're going to integrate. We're going to integrate each little dq on my surface, and each little dq is going to give me a dv, and I'm going to add them all up. And so that's what we're going to do now, is we're going to actually try and do this. It's not really a big conceptual jump from where we are. Now I'm going to tell you one thing that's going to play out in the next few problems when Kristen does some of these, and then when I do some of them after that. One of the things that's going to play out is the big difference between the potential and the electric field. And that big difference is the electric field is a scalar, is a vector, and the potential is a scalar. And why is that so important? Here's why it's important. It's much easier to add up scalars than it is to add up vectors. Remember what we have to do to add vectors? We have to break them down into their x and y components, and then add the x and y, and then reconstitute them back using trigonometry and Pythagorean theorem. We will not have to do that if we can find the potential. And so that's really what you want to look for in a lot of the problems that AP throws at you, is if they ask for the electric field, well, could you find potential first? And that's something we want to look at. All right, so I'm going to go ahead and stop sharing. I think Kristen's going to take you through some of these problems, and then I'll be back to do another one.
Okay, thanks, Roger. So yeah, let's look at a couple of these different things. And I think that you are right, Roger. It's much easier with scalar, and these look scary when you look at them. And when we did them with fields, remember, it was sometimes they were a little ugly, but because now potential is scalar, it's much easier to kind of look at these problems now with potential. So if we have a thin plastic rod that has a uniform linear positive charge density, lambda, and is bent into a semicircle of radius r as shown, we want to find what is the potential at the origin here, at the center of the circle. And we're going to indicate on the diagram which direction the electric field would be at that point, and calculate the electric field. Right, so let's start with that potential, and let's kind of look at that charge. So if this has charge, positive charge, uniformly distributed everywhere over it, and we know that it has a charge density lambda, which remember what lambda is, right? We can think of lambda as 2 ways. Big scale, I can say lambda is the total charge of this over the total length, and sometimes we may have to break it up and say, well, it's also, if I took a little tiny piece here and said, well, this is dq, I could say it's dq over dl, this small tiny little arc length here of the whole circle. Okay? So if we look at the potential, so the potential we know was equal to the integral. If we take the whole thing through, the Roger said, is the integral of a dq over r. And so that may seem really scary at first, but if we look at this, we can say, well, I can find what the integral, because what's really changing here? Not r. R is the same distance everywhere around, right? If I took a little dq over here, right? The r from the point where I want that potential to where my charge is the same everywhere. K obviously is constant, and so the dq is the only thing that's changing here. But if I were to integrate all the way across, that's just finding the total charge. So really, I can say the potential is k times big Q over r. So let's find what that total charge is. If lambda is q over l, then the total charge is going to be lambda times the total length. So how do we get this total arc length here? Well, it's half of the circumference. So if the whole circumference of the circle is 2 pi r, then the half of it is just pi times r. So our total charge would be lambda times pi times r. So if we plug that in, the potential becomes k times lambda times pi times r over what is that distance all the way around it, big R. So what happens with that r? It cancels out, and the potential of this entire half circle of charge is k times pi times lambda. Okay, so easy to simplify these ones. Okay, let's look now at what the electric field is at point 0. Well, let's again look at all these little dq's that I've drawn on here, right? We have a dq here and a dq here. Well, if I look at those at the point in the center, if I take that top left one, well, remember electric field points away from positive, the electric field will be pointing this way. And if I look at my dq over here, the electric field will be pointing this way. Well, if this is uniformly charged across, then the amount of dq for that same spot would be the same as here. So these magnitudes of these fields would be the same. So what would happen with those x components, did we say? They cancel out. So the only thing we're left with is one downward component of the electric field. And then how could we calculate it? I'm going to scroll over here. How do we say we can get the electric field? Well, remember, we said that dE was equal to k dq over r. And so if we do this, we can go back to the way that we did it and say, well, if I look at dq, how do I get now just the dq? Well, if dq over dl is lambda still, then dq is equal to my lambda times my dl with that small little arc length there. Well, if arc length s is always theta times r, well, then that would be r times my small angle or d theta. You guys probably remember doing this, yes? So if we plug that in, then we get that dE is equal to k dq is now lambda times r times d theta over r. But we have to be careful because we wanted just that y component, right? So we have to multiply by the cosine of theta. So let me put that in between that d theta. So that's r squared. So if we simplify this down, we have to take the integral of both sides. So e just becomes equal to the integral. What are we integrating to and from, right? We need to set our limit. We need to set our limits here. So there's two things you could do. I see it as negative pi over 2 to positive pi over 2 times, well, I can cancel out 1 irs here. I'm left with k times lambda over r times the cosine of theta. This is constant. Really all we're integrating for is that cosine, which gives us our sine. And when we plug in and simplify, we should end up with 2 times k times lambda over r. Okay, so if we now look at our ring of charge, and let's look at what happens when we have a ring of charge. So still positively charged. Now we do know the total charge, right? So sometimes you'll be given lambda, sometimes you may know what the charge is, but so we have this uniformly distributed charge q centered at the origin. We've got our x-axis going out this way. We've got our radius still, and so let's find what the potential is as a function of this distance x, right? So maybe we're right here, or maybe we're up here. We want to know anywhere on that x-axis what would the potential be. So if we go back again to that our potential is equal to the integral of k times dq over r. Again, if we go all the way around, what would all those q's equal? Just q. So really, it's kq over r. But we want to put it in terms of, remember, this r is not the radius of the ring. That r is the distance from our charge to where we want it, right? So that r, let's just pick a random point here, would be from the charge to that point, right? Anywhere on there, and it's going to be the same everywhere. What is that r? Well, that r is equal to, this is x, and this is r, is going to be equal to the square root of x squared plus r squared. So really, we get the potential is kq over the square root of x squared plus r squared. Okay? And then let's get an expression for the electric field. Okay? Well, the electric field, let's do the shortcut here we can do with this one is that we know the electric field is the slope of potential, right? We introduced this last night. The field is that change in potential over that change in displacement. So this is negative dv over dx. So let's take the derivative then of our potential. So we can write this as that negative d over dx of our kq. And I'm going to write this a little bit different. How else can I write the square root 1 over the square root of x squared plus r squared? Well, that's the same thing. Turn this into a bracket as x squared plus r squared to the negative 1/2. Right? You can see it's going to be easier to take the derivative if we bring that power up like that instead of leaving it into that square root. So if we take the derivative of that, well, we get, let's multiply by that outside. So we're going to get that e is equal to, we still have that negative there, that negative d over dx times my, I take the derivative of this, I get negative 1/2 times k cubed times x squared plus r squared. We're going to raise this now. If we subtract 1 from that, we get to the negative 3 halves, and then times, we take the derivative of the inside, 2s. Okay, well, I've got my negative, that cancels out. I've got 1/2 and 2, so what am I left with? E will be equal to k times q still times my x. And then let's go ahead and bring this back, this negative 3 halves back underneath. So now this is x squared plus r squared to the 3 halves. Do you guys remember that? We got that the other day. So this way is a little bit easier than the way we did the other day, where we had to find the components and do it kind of like I just did the ring. But so there's a couple for you, and then Roger's gonna give us some AP practice.
Okay, yeah. So let's do a few more, and then we'll say great Thursday night. Let me give you back to my screen here, and let's pop over to my, not there, okay, and let's take a look, excuse me, at, sometimes OneNote is a little fussy. A second. There we are. Okay, great. So moving on, I love that problem so much that you guys just did. That is such a cool problem. That's really neat. All right, so here's another problem, and this problem is going to show you how to keep your grace under fire, because you may look at this problem and you go, oh my goodness, what are they doing to me? They want to kill me, but just read it, it's not bad. So actually, we've seen something like this. The night before last, we did a distributed charge, or a charge cloud, and so we've got the spherical charge cloud of radius r. It contains a total charge of q, but the q is smeared out all over this sphere, and it's smeared out in such a way that its density falls off as a function of the radius, like that. So it gets thinner and thinner, and when we get here, there's no more charge. Okay, rho is equal to 0 for r greater than big R. Big R is my radius. Okay, so we're going to go ahead and express all of our algebraic answers in terms of q, big R, and fundamental constants. All right. So the first one says determine the following as a function of r for r is greater than r. And I'm really glad they said that, because when they say r is greater, that means it's going to be a little easier. And why is that? Well, if I'm looking at r is less than r, that's going to be inside of this circle, and that is not something I want to deal with. I can deal with it, and I will if I need to, but it's easier if I can be on the outside. Why? Because now, if I'm on the outside, when I draw my Gaussian surface to use that to find the electric field, I know exactly very easily how much charge is inside my sphere without doing any calculus. I know that the charge inside my sphere is q. And so what I'm going to do is I'm going to come over here, and I'm going to say that we have the to find the electric field, we're going to say that E, the closed surface integral of E dot dA, is equal to the charge enclosed over epsilon naught. Okay, and that's these are. All right, so now we know, since we have spherical symmetry in our charge, and we chose a spherical Gaussian surface that is coincidental, they have the same centers, then we'll say that the E can come out front, because it will not be variable. It will be a constant value along that sphere. And I'm going to now add up the area of my sphere, of all my dAs, to see what I have. And over here, I have the total charge. They give me q over epsilon naught. And so when I add up all those areas, all those little dAs, well, what does that give me? Well, it's a sphere, and its area, when I add it up, is 4 pi r squared, because that is the surface area of a sphere. And so what we get then is E is equal to q over 4 pi epsilon naught r squared, or q over r squared. And so that's our good old formula for a point charge. What's the takeaway? If you've got a spherically symmetrical charge, and you're outside, you're away from the charge, you're not inside of it, then that spherically symmetrical charge acts just like a point charge. You can imagine all of its charge is concentrated at the center of that sphere. Okay, so that one is not so tough. All right, let's go ahead and move down to the next one, and we will get you out here at good times. All right, so let's go ahead and try this. All right, so this one, it says a rod of length L lies along the x-axis with its left end at the origin. It has a non-uniform charge density. Lambda is equal to ax, where a is a positive constant. What are the units of alpha? All right, good. So first of all, let's just stop and read this and go, what did you just say? Hold on, what does this mean? A non-uniform charge. I think this is the first time that we've done a non-uniform linear charge. The other night we did a non-uniform spherical charge. This one's a little bit easier. What does that mean? That lambda is equal to alpha x. Well, x is my distance from here to wherever. That's x. And so what that means is the further I move from the origin, or my lambda is equal to alpha x, and alpha is a positive constant. So the further I go to the right, the denser my charge becomes. The more there's so much more charge here on this end than there is very, very little charge there. As a matter of fact, it's linear. And so if I could draw it as a kind of graph, I would say that over here the charge is 0, and over here the charge is a whole lot more. And so we don't know exactly how much, because this is a qualitative problem with just variables, but we can still do it. All right, now what I've got to do is I've got to ask, okay, so what are the units of alpha? That's the first thing. I'm going to go to the next one first. Let's do that. So what is alpha? Well, I know that the units for lambda, that's the linear charge density. Well, the linear charge density is coulombs per meter, okay? And that's equal to alpha times distance, which is in meters, okay? And that's x. And so that means that alpha would be coulombs per meters squared. If I divided that out, that's what I'm getting, right? So that is our value for the units. Now, let's go ahead and look at what it says next. Write, but do not solve an integral expression for the potential difference, and it should say at point A. Sorry about that. Express your integral in terms of LD, alpha, and fundamental constants. All right, here we go. Now, we want to find the potential difference at this point. What is V here? And remember, the potential difference is always compared to somewhere else. If I don't say where, then the answer is compared to 0 at infinity. So the potential difference is 0. If I'm infinity away from this, the potential difference is 0. And as I get closer, I get to this point right here. What's the potential difference there between that and infinity? Well, what I'm going to do is I'm going to go ahead and I'm going to treat each little dq as a point charge. And I'm going to say that dv is equal to dq over r, and there's a k in there, I'm sorry. And that's from my point source equation. Okay? And so now, let's see, well, what is dq? Well, look, I'm going to integrate this thing. We already have said we're going to look for an integral. And my distance here, between here and here, that's a dx. And so dq, and we've done this before, I don't know if you remember, dq is lambda dx, because that is coulombs per meter times meters gives me coulombs. Now, this is a real tiny amount of distance, so yes, we've got a very tiny amount of charge. Now, we know in this problem that lambda is not just lambda, it actually depends on the position. It's alpha x, and that's going to be dx. So now we can say that dv is equal to k dq. I'm sorry, I'm going to replace dq. That's what I'm needing to do in this one. And so that's going to be k alpha x dx. Now, in my bottom here, in the bottom part of this fraction, we're looking for r. R is the distance from here to here, from my dq, from my tiny little dq, all the way over to point A. That's my distance. Well, what is that distance? Well, this distance is always d, and this distance is x. So the distance down here is going to be d plus x. So that's my dv. So that means my v is equal to k lambda x over d plus x dx. And how do I get from dv to v? I integrate. Now, the last thing that we need to do is we have to have the limits of integration, or else we don't get all points. And so what are the limits of integration? Well, what does x go to? Well, x starts at 0 and it goes all the way to L. Now, I would not be surprised to see this type of formulation of a question on the exam. I don't have a crystal ball, but we've been told that there's less math and more concepts. So we've seen write but do not solve an integral expression before. We've seen write but do not solve a differential equation before. So again, feel like it's okay to do that. If some students might ask, do I need to pull out the constants? And the answer is you don't need to pull out the constants, only for you if it makes you feel better. But I would not worry about integrating this, because this is an integral that we probably are not going to see this year. All right. So that's our idea for tonight of spreading out these charges. Of course, there's other ones we could do if we had unlimited time, but you get the sense of it. We're having to integrate, right? So I do want to once again encourage you to remember all the things we've been learning as electrostatics. We have the force is equal to k q1 q2 over r squared. We divide out a q and we get E is equal to k q over r squared. Over here we have U, our electrical potential energy, and that's equal to k q1 q2 over r. And And over here we have V, which is our potential difference, and that's KQ over R. Units, newtons. Going down, I divide by coulombs, newtons per coulomb. Over here, my units for energy are joules. Going down, volts are joules per coulomb. Or if I go this way, E field is also volts per meter. All right, more that we could add to this as we start to review. We know that E is also equal to the negative dV dx, and we know that V is equal to the negative integral of E dot dO. So there's so many ways we could do this. Okay? V is equal to U over Q, or U is equal to Q delta V. So you want to have fluidity around this. You want to be able to bounce back and forth and hopefully use it. All right, thank you again for spending your your evening time with us. We hope that we're able to answer some of your questions and help you understand the physics we're doing. Kristen, what are we doing tomorrow night?
Tomorrow night, we're going to do potential difference of concentric conductors. So some spherical conductors, can't talk potential difference between or different regions, a little bit more integration.
Okay. All right, great. Well, thank you so much. Thanks for joining us, and we can't wait to see you again tomorrow night, same time.
It is Friday, and we are watching, or you are watching, AP Physics C, Electricity and Magnetism. My name is Kristen Gonzalez-Vega, and I am coming to you from Frisco, Texas. And I have with me my friend Roger, like always.
Hi there, my name is Roger Siegel, and I teach physics here in Sarasota, Florida. Good to see you on a Friday night. Thanks for joining us, and I am wearing a nerdy physics shirt, so I just want to let you guys know.
Awesome, thanks, Roger. And I am wearing pants that button, jeans, not elastic. It's a good day here. I know you guys at home can relate to that, so probably been a week, and they still fit, so that's the other good thing. Quarantine, the jeans still fit. All right, so tonight we're going to talk about electric potential, continue on. We're going to kind of wrap up potential almost. It'll still relate to capacitance that we're going to start discussing next week. But as far as just strictly potential goes, we're going to kind of wrap up how we can find electric potential, mainly electric potential difference between 2 points with conductors and concentric conductors. So again, my name is Kristen Gonzalez-Vega, and we are joined by Roger and Porta. We got a couple of things that we're going to be able to do after today. One of those is to use integration techniques to calculate the potential difference between 2 points on a line, given the electric field as a function of position on that line. Or you're going to use Gauss to find that electric field as a function of position first. And then for charged conducting spheres or spherical shells, describe the electric potential with respect to position. Okay. So we're going to quickly kind of review through what we've been talking about the past couple of days with potential, and that is the electric potential and how it relates to the electric fields. Right. So first thing I want to remind you, since we're going to be dealing with all conductors tonight, aside from this little graph example I have, is that where does the charge lie with a conductor? Well, it's always on a surface, right? Could be outside surface, could be inside surface. The charge is on a surface, no charge within the conductor itself. So we also want to remind ourselves of our relationship between the electric field and potential, and that is the electric field is the negative derivative of the potential with respect to position. So what does that say then? If we look at a conductor, we're going to take a look at the conductor first. Find the conductor, let's just say the charge is Q, radius is big R. If this is a conductor, we know the charge lies on the surface. What do we say the electric field was everywhere within that conductor? So for E of R, when R is less than big R, what do we say the electric field was using Gauss? It was 0. So if the electric field is 0 everywhere within the conductor, what does that tell us about the potential inside the conductor? Is that also 0? Well, if the slope of the potential is the electric field and the slope is 0, right? If we go ahead and plot this electric field, it's 0, 0, 0, 0, 0. The minute we got outside here, what did we say the electrical relationship was? It was the same as a point charge, or KQ over R squared. So it jumps up right at that surface, and then we said it had that inverse square relationship. Okay, so let's look at that and then look at what should happen with the potential then. So if the electric field is 0, well, that means the slope of the potential should be 0. But that doesn't mean that the potential has to be 0 too, right? So really, when we look at it, the potential inside there is a constant, and if this is a positively charged sphere, it's a constant positive potential. And then once we get outside again, it's still kind of like a point charge. And we said our potential of the point charge was K over R. So then we get a 1 over R relationship. Okay, let's compare that then with an insulator, just so we can again practice going back and forth between these graphs. Because we derived already the electric field when R is less than R. And if you remember, as we went out, we had that linear relationship. The electric field was increasing at a linear rate. We got a direct relationship when we derived it. And then once we got back out, it's the same as the conductor. We had that 1 over R squared relationship. Oops, sorry, Dad. So then we have to look at how we graph the potential. So if the slope of potential is the electric field, but negative, right? There's that negative in the equation. So we want the negative slope to be equal to the field. So we look, I kind of always like to tell my kids, if you don't know what the graph should look like, let's look at points where we know. So we know initially at the very center, what was the electric field? It's 0. So that means that we should have 0 slope on our graph. Okay. And then we reach a field is increasing. So that means my slope should be increasing. But I have a positive field, so what should that tell me about the potential or the slope of the potential? Well, if my field is positive, that means the slope should be negative, and the slope should be increasing. So we start at 0, but our slope is increasing. And where do we have a maximum field? At the radius R. So we should have a maximum negative slope at that radius R. So that slope should increase, and so we reach a maximum at R. And then we have that 1 over R squared relationship. Well, if the slope of this guy, the derivative of this is this, then we know this one should then go back to that 1 over R relationship. And so the slope of potential is electric field, negative slope of potential. Let's go back the other way because we've used Gauss a lot to get the electric field. So how can we then use the electric field to get the potential? Well, we can start by saying that we know that the change in potential energy is equal to the negative integral of force with respect to distance, right? This is a relationship we use over and over again with potential energy and force. And so that means I could rewrite it like I did down here, right? We take 2 points. Let's say I want to choose a point way far away out here, right? Maybe we're at infinity. So we're going to call that our position A. That's where we're starting. But we're going to end up, let's say, at position B right here at point D, right? And that's kind of maybe where I want to know what potential is. Right? I'm looking for what is the electric potential at point D. So we want to look at what that change in potential energy between those is, right? So the potential energy at B final, right, minus the potential energy at A initial should equal the negative integral of the force with respect to that distance. Right? So if you look at these things, I want you to really look at that. These limits and the subscripts that we're looking at it, right? So when we're looking at that change in energy, well, that's always our final minus initial. But when we have our limits on integration, that's always from where we are starting to where we are ending. Okay? So we can plug in, we know that potential energy is Q times V. And we know the force, the electrostatic force on this is Q times V. So if I sub those in, U is QV. So we can say Q VB minus Q VA equals the negative integral from A to B of Q times V dl. And really, let's just say for this case, we're going to call this R. Okay? Well, if we pull out those Q's because the Q constant, the same charge in both places. So if we pull the Q's out, they're going to cancel. And so we end up with just V at B minus V at A will equal the negative integral from A to B of the electric field. That's dr. And so this is really our relationship we can use to find what that electric field is. So if you look, this left side is a potential difference, right? So it's not the actual just potential. If I want to know the potential at one location, I have to be able to know the location, the potential at some other location, right? It's a difference in the potential from those two spots. So the easiest thing to always pick if you don't know is infinity, because what is the potential? Infinity away, right? If it's related to 1 over R, well, 1 over infinity is 0. So we can always call the potential at infinity equal to 0. So if you're ever looking for some place to compare back to, sometimes you're asked to find what the potential difference is between the two spots where you're just integrating. But sometimes you may be looking for, well, I just want to know what the potential is at point P. Right? So we want to call our infinity 0 so that it becomes 0, and then I really am just finding the potential at P. Okay? So we're going to look at a couple of examples with Roger.
Okay, thanks a lot, Kristen. All right, let's keep going with potential. I'm going to share my screen here, and we're going to have fun. All right, so let me zoom on down here, get this guy out of here, and all right. Now, this first problem is one that I like a lot because it tells us a lot about how potential relates to the movement of charge and the nature of static charge. So we've got sphere A and sphere B. They're far away from each other, very far from other sources of charge. The radius of sphere A is 4 centimeters. I'm going to go ahead and write that right in here, that this radius is 4 centimeters. And the radius of sphere B is 7 centimeters. And initially, A carries a charge of 33 nanocoulombs. So let's put that over here, 33 nanocoulombs. I'm sorry, I said nano, but it's microcoulombs. And sphere B carries a charge of 11 microcoulombs. One thing I did forget to say, sphere A and sphere B, B, it's very important. They are conductors. And if you remember, that means that charges can flow freely back and forth all around that. All right. So we've got two charged spheres. Now, if I take a wire and I connect these two spheres with this wire, what's going to happen? And a more specific question is, what will be the charges after they come to a new equilibrium? Okay. And so we have to ask ourselves, well, what is that thing that is in equilibrium? Okay. Is it a force? Well, that would be kind of hard to measure. Force of what? Force of what on what? Well, we know that all the charges want to get as far away from each other as possible. But this is where the concept of potential really comes in. Because if we have a system, that system will want to come to its lowest potential. And so the lowest potential is when each of these is at the same potential, when VA is equal to VB. Now, what does that actually mean? When I say the V at A, I remember it's always potential difference. Oh, goodness me. Are you serious? Of course. I'm not sharing because right now I have a share thing. Let me try again. Okay. I just hit stop share. So can you see my OneNote?
Yeah, you're good.
Thank you so much. Okay. So here we have, if you didn't see that, well, I apologize. What we have are two spheres, and they each have they have an initial charge, 33 microcoulombs, 11 microcoulombs. They have different radii. And so we're going to connect them with a wire. And the question is, what will the charges come to when we come to equilibrium? And where we start with that is we set the potential equal to each other. And it's not dissimilar from a problem if you had a liquid in a tube and you asked, and the liquid was like this, and you said, well, what would happen when we come to equilibrium? Well, all of the water would be at the same potential. And so that's its lowest potential of everything. So that's what we want to bring together here. So when I say potential, what I mean is the potential at A is really the difference from 0 at infinity to A. Okay. So the potential at A is compared to 0 very far away. Same thing. All right. So let's see what that potential is. All right. So if I want to find the potential, what I'm going to use is I'm going to use the negative E dot dr, and I'm coming from infinity to this point A, which is going to be 4. And so what do we have there? Well, I'm sorry, I'm going to call that small r. All right, here we go. Well, this is negative, the integral. When I use my Gauss's law, I've done this so many times, I'm going to trust that you remember that this is going to be kq over r squared. And so when I integrate this, I'm going to get positive kq over r, which is the same thing as the point potential. And we said that last night, that if something is spherically symmetric and you are away from it, then it acts like a point with all the charge concentrated at the center. So we can set these two equal to each other for each of these. So I'm going to come back here and I'm going to say k and, let's say kqa over r is equal to k ra is equal to kqb over capital R. Now, what are these charges? Well, we know that they together are sharing the same charge. This one starts out with 33 microcoulombs. This was with 11. So that means that 44 microcoulombs has to be split between my two charges. And so this is going to be, I'm going to call this q, not a or b, just unknown. And I'm going to say that's kq over r. And this one is going to be k. How much does it have? Well, it has 44 microcoulombs less q. It has the total 44 microcoulombs minus q. And so this is going to be capital R. And so the math is pretty simple with this. I'm going to go through it rather fast so you can see the k's cancel. And so what we have is 44 microcoulombs minus q times r is 4 is equal to 7q. And so we have 44. And so that gave us to all the way down here. Q is going to be equal to 16 microcoulombs. Now, once I get the q on my smaller sphere is 16 microcoulombs, then how much charge is on my other sphere? Well, 44 minus 16 or capital Q is going to be 28 microcoulombs. All right. And I'm going to trust you to do the math. It's pretty easy, but I do want to get to the next part. And so I don't want to get too bogged down in this. All right. Let's go ahead and move on because this one is a lot. Okay. Now, we've done this problem a lot. You must wonder what's has to do with concentric conductors. Well, imagine a spherical chicken is usually the way a physicist looks at a lot of problems. A lot of things are spherical, and so we're going to go with it. So we've got a conducting sphere of net charge Q and radius A. It's surrounded by a concentric metal spherical shell of radius B and net charge capital Q. Answer following question should be in terms of quantities in the diagram and fundamental constants. All right. So the first question is using Gauss's law, write expression for the electric field at a distance r from the center of the sphere for the regions defined. And it says to use K instead of 1/4 pi epsilon naught to replace it. Well, if we are going to do a little bit of Gauss's law, we know that that means that the integral of E dot dA is equal to Q enclosed over epsilon naught. Now, if I'm inside of R, ladies and gentlemen, if I'm inside of A, let's take a look at that. I'm in here, and there is no excess, there's no charge here. Now, what I mean by that is not that there's no atoms or positive or protons or electrons. What I mean is they're all neutralized, they're all equal. There's equal number of protons and electrons. However, on the outside surface, there's this Q. So as I move through this sphere, there is no enclosed charge. And so my first answer here is going to be that E is equal to 0. All right. Now, my second one here is a little bit more interesting. And if I'm between these two, my enclosed charge is Q, and the radius is small r. And so when I integrate that one, E dot dA is equal to Q enclosed over epsilon naught. Well, that gives me E. Remember, my Gaussian sphere has an area of 4 pi r squared, and that's going to equal to my enclosed charge Q over epsilon naught, which means E is equal to Q over 4 pi epsilon naught r squared, or E is equal to KQ over r squared. Again, it acts like a point charge, okay, for the electric field and for the potential difference. Now, if I'm past B, if I'm all the way out here, what's different? Well, the only difference is now I'm enclosed more charge. How much charge? Well, I'm not going to bore you with this, but you can see what's the charge that I'm enclosing. It's the inside sphere Q and the outside sphere big Q. And so this is going to be capital Q plus little q times K over r squared. So we can make those adjustments. We know how to do that. All right, let's keep going. Now, at this point, I want to slow it down a little bit because this is where we're talking about potential. We've done electric field for long enough, but we're still working through this concept of potential, and it is a challenging one. So remember what potential is. So potential is the negative integral of the electric field. It's the difference in height, if you will. I keep coming back to the height analogy. If you're hiking along a path in a mountainous range, well, the difference in height is a difference in potential energy, except for you're just dividing out the mass. Well, now we're dividing out charge. So when I say what is the potential difference at B, and remember B is right here at the outside. What I'm saying is if I take a charge at infinity and I bring it in all the way to B, how much work have I done? Divide that work by the charge itself, and that's the potential. That's the potential difference. And so we're going to say that we have the negative integral of E dot dr, and we're coming from infinity to B. Now I know what this is because I just found it. That is the negative integral of from infinity to B of K capital Q plus small q. We just found that before over r squared dr. Now when you take the integral of 1 over r squared, that's r to the negative 2. We're going to add 1 to that using the power rule. And so what we get is we get positive K Q plus Q over r, and we're going from infinity to B. And so at B, what we have is K. Well, that's our answer there. So from infinity, to R up to B. All right. So our answer here is V is equal to. Put that in there. So here we have V is equal to K Q plus Q over R. And I want you to notice because again, it's behaving like point charge, strictly symmetric or away from. Now, if I'm between these two, this is where it gets a little tough, because if I want to know what the potential is here between between A and B, I'm going to have to integrate again from infinity all the way to this new R. Now, I already know how much it is from infinity to B, and so I can say that my potential at R is going to equal my potential at B plus the potential difference going from B to some new R. Okay? And so that's going to be we have KQ plus Q over R plus the negative integral of E dot dr, and this is going from B to R. And so this, and I'm sorry, this number here is not R, it's B, because I've come from infinity to B and now I'm going from B to R. And so this is going to be KQ. I'll just leave this for a second. We'll bring this down in a minute, and let's keep working on this side. So we know what happens when we integrate. We've already done this. This is B to R. This is KQ small q over R squared. And why is it small q? Because now when I'm between these two, I'm just encircling. Oh my goodness, I'm getting tired. I'm just encircling the small charge. And so that's what we have. And so again, what we get is it acts like a point charge. We're treating it like that. And so I'm going to say that this is going to be KQ over R. Now, what is KQ over R from B to R? Well, what that is that's KQ. I'm going to do that. KQ 1 over R minus 1 over B. Now this down here, let's write this again. KQ plus Q over B. Now I'm almost done. The fun is almost over on this one, but I'm going to take it out. So check this out. This is very nice. I think you're like this. Right. So this can be written as KQ over B plus KQ over B plus KQ over R minus KQ over B. So the KQ over B's go away. And so what we're left with is KQ over B plus KQ small q over R. And doesn't that kind of make sense now that you're seeing it? Doesn't that kind of make sense? I hope it does. If it doesn't, rewind this, watch it again. I think it will. All right, last part, and we'll send it back to Frisco, Texas. Almost ready. What about if I come inside of R? What's my potential difference here? Well, again, I'm going to have to integrate, from infinity all the way to here. Now, once I get to this point, what's the E field inside of here? Oh, remember we said the E field is 0 because it's a conductor, and the E field is always 0 in a conductor. So if the potential as a function of R is equal to this, okay, if this is how much I have going from infinity to R inside, how much more does my potential add up? I'm going to add, for this one, I'm going to take the previous part, and I'm going to say plus the integral of E dot dr from A to R. But E there is 0. And so my answer here is going to be that I have KQ over B plus KQ over A, because that's the smallest my R can be. And so the last thing, before I send it back, Kristen won't be mad if I do, is to go ahead and again draw the potential and the electric field, because it's really worth looking at. And so if we look at the electric field, and we start here at 0. We start here at 0, and over here we're at infinity. And we go out, and our electric field is 0 for a long time, and then all of a sudden it bumps way up, okay? And then I have this falling over 1 over R squared, my E field. This is E. And then I get to this other charge. This is when I get to Q. That's A. And this is when I get to B, and I get more charge, and then it falls off as 1 over R squared, and the electric field is 0 to infinity. Now, to find the potential difference, what I want to do is go backwards from infinity all the way to 0 and see how much it adds up. And so if I'm adding this up, you guys know how integrals work. It's an addition problem. So we're going here, we get added here, and then we get more here, and then we get 0 here. And I should line these up. And so let me do that again, and then like that, something like that. But that hopefully gives you a sense of what happens, how the potential and the E field are related. Okay, so for the week, that's my part. And are you ready to take us home, Kristen?
Sounds good. Thank you, Roger.
Awesome.
Okay, let's do one more practice, guys, and then you can enjoy the rest of your weekend. I have a question from an exam a few years ago that is two thin, concentric conducting spherical shells insulated from each other. They have radii 0.1 meters and 0.2 meters as shown. The inner shell is set at an electric potential of negative 100 volt and the outer shell at positive 100, with each potential defined relative to the conventional reference point. Let Q1, I, and QO represent the net charge on the inner and outer shells, and let R be the radial distance from the center of the shells. Express all algebraic answers in terms of QI, QO, R, and fundamental constants. Okay, so first thing I want to ask you is, which one has the greater charge? So there's our conceptual question of the day. Which shell has a greater charge? Q inner, Q outer, or are they the same? So let you pause there for a moment and think about it. And how do you know, or how would you explain this if it were a free response question, that you know whether they have the same charge or they have the same charge? Okay, what do we think? I wish I could take a poll right now. That's what I would do in my classroom. How many of you say Q1 inner is bigger? How many of you say Q outer is bigger? How many say it's the same? Okay, I'm gonna let you think about it for a while. We'll come back and answer that. But let's do some numbers and let's look at some things. So let's find using out the electric field in our two regions in between the two and greater than 2. So we're going to look at the electric field in between and the electric field greater than 0.2. So real quick, you're gonna write me Gauss. We should be Gauss experts at this point. It should be automatic. Boom, boom, boom. So we're gonna derive an equation for the electric field as a function of R for both of those two regions. So we're gonna come right over here and we're gonna write Gauss, right? Gauss is the integral of EDA equals Q enclosed over epsilon naught. So what shape do we have? What Gaussian surface? We have sphere, our beloved sphere, which is 4 pi r squared. Remember, we're leaving that as a little r because that is for any radius in between there. Okay? That equals, well, what Q is going to be enclosed in my purple Gaussian surface here? Everything inside, which is the Q inner over epsilon naught. So if we rearrange, E is going to be equal to that inner charge over 4 pi epsilon naught r squared. Super familiar, yes? Okay, what about on the outside? Let's rewrite out. What's different? Left side different? Nope, same shape, same left side. E times 4 pi little r squared again. Any r outside here. But now, what charge is my new Gaussian surface on the outside here enclosing? Well, what's inside? All of that inside, which is Q inner plus Q outer. And so over epsilon naught. So if we rearrange that, sorry, we've got E equals Q inner plus Q outer over 4 pi epsilon naught r squared. So those are our two relationships that are going to be important for us. Should be the Q, sorry. Always want to use the variables they give us as they are. Okay, now let's look at the next part. Determine an algebraic expression for the potential for R greater than 0.2 meters. So we want the potential at R greater than 0.2. So I'm going to erase this up here for a second. I want you to set it up for me. So any R outside here. So let's just pick a random point, right? Let's say I want to know what this R with the potential is. How do we go from field to potential? They lead you into it, right? We had to find the field first because we know that the potential difference is equal to the negative integral of the electric field. Okay, so let's plug in. Where do we know it? Nowhere inside here, but where do I always know it? I know it at infinity. So let's go ahead and compare to infinity. So I want final position, right? Which is we're moving always from that outside and always from infinity in. So my final position is going to be V at R. So I'm going to say, well, V at R minus my starting potential was V at infinity equals my negative integral from we're always our starting position to the final position. We started at infinity away, now we're at some R away. And which electric field are we using? The electric field greater than that 0.2, which was RQ plus Q over 4 pi epsilon naught r squared. Q inner plus Q outer over 4 pi epsilon naught r squared. Okay, well, what's the potential difference at infinity? 0. So really we can say that V at R is equal to the negative integral. So all this other stuff is constant. Really the only thing we're integrating is that R squared. So the integral of 1 over R squared is R to the negative 1 times negative 1. So our negatives are going to cancel out and we're going to end up with, go over here, that V at R is going to equal Q inner plus Q outer over 4 pi epsilon naught times R, right? Again, if we're really being picky about it, we're going from infinity to R, but we know when we plug in infinity, that's 0. So really we just get it. Okay. Using the numerical information given, calculate the value of the total charge, right? So explain to me how we can find the total charge on the two shells, right? Q total, which we know is going to be equal to the sum of the two, Q inner plus Q outer. Well, we have a function for potential, don't we? And so I have Q inner plus Q outer right here. Well, what's Q inner plus Q outer? That is the total charge. I'm going to rewrite that over here. We have some more space. So we know the potential for any R bigger than 0.2 is equal to, or really right at 0.2 bigger, Q total over 4 pi epsilon naught times R. Okay, but I know something somewhere, don't I? Let's look back at our diagram. What do I know at 0.2? Do I not know the potential already at 0.2? I sure do. So if I go ahead, I can plug in. The potential at 0.2 was 100 volts. So that equals Q total over 4 pi epsilon naught. What is the R at that location? At 0.2. Now, if it were anything in between, right? We're looking for, if we had the potential in between here, right? I could not use that, right? If only from this point on that this function is valid. We have to reintegrate for the in between using our in between equation to find what it would be in between, right? But we can use it right at 0.2 and onwards. And so we could go ahead and solve for that. We won't necessarily need to do the math right now. It should be 2.2 nanocoulombs of charge total. Okay, so let's go back and talk about again that charge thing. Which one has a bigger charge? So we know they have the same magnitude of potential, right? The inside has a magnitude of negative 100 volts. The outside has a magnitude of 100 volts also. So they have the same magnitude of potential. We know that one's going to be negatively charged though, right? This is going to be a negative charge. So which one's going to be bigger? If they have the same potential, how do we say that potential related to that charge, right? Well, that smaller sphere, if we can relate in general potential, we're looking at a point charge of Q over R. If they have the same potential, what's true about the surface area of this L1? Well, the outside one has a bigger R. So for the same potential, it can hold a bigger amount of charge. So the greater charge is going to be on that Q outer. So Q outer will have a greater magnitude of charge than Q inner. Okay? So that's going to help us out here in a second because I want you to graph for me a couple of graphs. So our last thing for tonight is more graphing. So what should the graph of each of these look like, right? And you're not going to be graphing on the test, but you sure could be given a graph and you have to identify good things and bad things about a graph. So you still have to know how to do it anyway. So I want you to graph for me or sketch what the potential and the electric field function should look like. I'm going to pause just for a second here, grab a drink of water, you sketch away. And you don't have to guess, right? Because we have functions. We have a function for when E was in between. This was for R greater than 0.1, but less than or less than 0.2. So it's in between 0.2. I can never find inequality today. Okay? And this one was for an R greater than 0.2. What's true about the electric field anything less than that? Well, if you look at Gauss for anything less, what's our Q enclosed? Anything less than 0.1. 0, big fat 0. So there is no electric field on the inside here, right? Because there is no charge on the inside. Where's the charge lie? It lies on the inside and outside surfaces of the sphere. So I would start with the electric field if I were you, because you can use that Gauss function equation to describe it. So from 0 to 0.1, the electric field is 0 all the time. Make it nice and so we can see it. And then in between, we can use our function Q inner over 4 pi epsilon naught squared. Again, what relationship do E and R have? Inverse square relationship. So my electric field is going to jump way up at that raise of 0.1, but we haven't zoomed in here for you. But we have an inverse square relationship. So it is going to decrease. It's not going to, but I did something wrong here. So if that is a negative charge, and if we're looking at going out this way as being positive, the electric field would be pointing inwards toward this, right? So it should really be negative. Right? So we're starting with that big negative field, but it is decreasing exponentially, right? Until we get to 0.2, but it won't be 0 quite at 0.2. Right? And then we have our function Q1 inner plus Q outer over 4 pi epsilon naught. Well, what should the net charge of this be? If we know that outer sphere has a greater magnitude of charge, and we know that one's positive because we have that positive 100 volts here, and we should have a net positive charge. So we have a net positive charge, and the electric field is going away, then now we have a positive electric field. But it's not a very big net charge, and our R is getting bigger, so it's not as great of a magnitude as our initial negative was. And again, it's going to exponentially go down. So that's what our graph should look like. I hope that conceptually I explained how we can kind of know that. But if you need to, you may have to watch a couple times to understand, because those graphs can be really tough. Okay, how do we get potential from this? Well, we know the slope of this should give us this. So, and we can also look at, we did derive one equation for potential, so we could always use that. But we should be able to look at a graph and be able to translate back and forth, because you guys did that in mechanics a lot too, right? Position, velocity, acceleration. So it's kind of like going from a velocity graph, right? What is to a position graph? And so the slope of our velocity should give us that. So if we want to look, we know the slope should be 0 to begin with, but we do have potential to begin with. Okay? But since that inner sphere was negative, we have a negative potential until we get to 0.1. Okay? And then what should happen? What happens to the electric field? Well, we start with a electric field, a negative electric field, which if this is a negative slope, if we're starting with a negative electric field, what should the slope of our graph be? It should be positive. So we should have a positive slope, so it should be approaching that axis. But if we look, it should be reaching, and where should we cross? Where should the potential be 0? Should it be right in the middle? Well, we go back to that magnitude of charge, right? If the outside ring is a greater magnitude of charge, it needs to have a greater distance away from when those potentials are equal, right? When our KQ over R will equal our KQ over R. So really, our 0 is going to be closer to that inner ring since it has a smaller charge. So we should cross that axis. And really, they weren't super picky this year on the exam when looking at the rubric, as long as you crossed and knew the potential was 0 somewhere in between. But for being picky, we know that it should be not right in the middle, right? And then we're going to reach some at 0.2 maximum positive potential, because that's where we're having that positive charge. But then it's going to decrease back off again. That's what the shape of that graph should look like. But hopefully that helps out a little bit there. And that's what we have for our potential this evening. We are going to go in next week. I have what our schedule is for next week here. We are going to lead into these kind of concentric conductors, lead us into capacitors, right? So if I have 2 of these conductors, well, really what we did, if they're opposite charges, we get capacitors. So we're going to start working on capacitors next week, and then we get to start circuits, which are really fun. So I hope you guys have a wonderful evening. Roger, you can close us out tonight.
Well, thanks, Kristen, for doing that excruciating problem. I love doing that problem. It's a good one, and you guys should study that because you'll learn a lot from it. Thanks so much for joining us tonight. We can't wait to see you Monday night, and have a great weekend. Well, good evening. Welcome. You are tuned into AP Physics C, Electricity and Mechanics Live, and my name is Roger Siegel, and I'm coming to you tonight from Sarasota, Florida. As always, co-teaching with my friend Kristen. Hey, Kristen.
Hello, Roger. Yes, my name is Kristen Gonzalez Vega, and I teach at Reed High School in Frisco, Texas. And Roger, I have to know, what is that behind you on that big post-it note paper?
That thing up there?
No, the post-it note paper, the little.
Oh gosh. Oh, these are what are these? These are seals.
Yeah.
Yeah. One of my students said, would I bring the seals? They hadn't seen them, so I told her I was going to school, and she said, would I pick up the seals? And I said yes. So now I'm going to make her watch this. All right, we'll move that out of the way so it doesn't distract anybody. That's kind of thanks, Kristen. All right, well, let's move on to what we're here for again. So good to see you guys tonight. My name is Roger Siegel, and we are going to be talking tonight, working with you to get you ready for your AP Physics C exam. And so let's go ahead and get started on here. Okay, good. And tonight we are going to be talking about conductors, capacitors, and dielectrics, and particularly capacitors. That's what tonight is about. The whole unit is called conductors, capacitors, and dielectrics. Tonight we're just going to talk about capacitors. Tomorrow night will be about dielectrics, so you're going to want to tune in for that. So tonight, again, my name is Roger Siegel. I'm here at Sarasota, Florida, and working with Kristen Gonzalez Vega from Reed High School in Texas. We wanted to remind you that our exam time, depending on where you live, is going to be 1 hour only, and you have to be there for the whole time. You will do 25 minutes on the first question, and then you'll have 5 minutes to upload, and that's it. And that will be the window. And then after that, you will have 15 minutes to do the second question, plus 5 minutes to upload, and that's it. And that's your whole AP exam. So please make sure you mark it in your calendar. We want to get you ready for that, and we have more coming in future about that. Here's where we are this week. As you can see, we are trying to make this work. This week we are working on conductors and capacitors, dielectrics tomorrow, and on Wednesday as well. And then we're going to start circuits. And circuits takes us all the way through the curriculum of AP Physics C.
Right. Going down here, objectives tonight. I don't want to spend a lot of time reading them for you. You can come back and look. But really, everything is about learning about capacitors and capacitance and talking about what they are. And so that's going to be our guiding light. So let's talk first about what is a capacitor, because it's possible that you've never even heard of one, unless maybe sometimes, of course, as a physics teacher, people say, well, what about the flux capacitor? And that's from, of course, the movie Back to the Future. So not a flux capacitor, but we do study flux and we do study capacitors. But a capacitor is an object that usually goes in a circuit, but it doesn't have to. But what it does is it stores electric charge, and it has two conducting objects placed near each other but not touching. So usually what we'll talk about are two parallel plates being a capacitor. I'll show you a better drawing in a minute. But they don't have to be plates. They could. What a lot of capacitors are is they're two conductors that are not charging, an insulator in between them, and then what you do is you roll this up like a big roly-poly, and so you have this kind of sandwich where the two breads never touch, two pieces of bread, but it does create this capacitor. So what we do is this is what a capacitor is. You have basically two plates, and what you do is you charge this up with a battery or a voltage source, and that's what a battery looks like. And you can see the difference between these. What does a battery do? Well, a battery pushes charges. It's like a pump for charges, positive charges. It pushes them here. Now, positive charges. Let's move on to the next slide, and then we'll draw this down here. All right. So we've got this is a better picture here of our plates, and let's see what we're doing here. So our battery is taking positive charges and pushing them onto this metal plate. Okay? And can you imagine these two are going to be pretty close to each other in space? And so what's going to happen to any positive charges that are living on this plate? Well, they're going to try and go out of here as fast as they can. And what that's going to do is that's going to leave, since the positive charges have all left, it's going to leave this plate all negatively charged. Okay? And what that does is that creates in this space an electric field. Of course, the electric field. And this electric field, if these plates are pretty big, is uniform. It's the same throughout, left, right, up, and down. It's the same. So that is what a capacitor is conceptually. Here is the roly-poly one that I showed you, and you can see that there's two plates that are separated by an insulator. And so that's another kind of capacitor. And so that's what a capacitor is. Let's go down and see some pictures of ones. Here's some capacitors. Excuse me. Here's some capacitors that you might see in a circuit. If you looked into an electronics or a stereo or the back of a TV, you would see capacitors and working in what they do. And again, they're storing charge, storing energy in the electric field. Now, what is capacitance? Okay, well, it's how we measure a capacitor, how we compare them one to another. And capacitance is measured in farads. This is the unit. So I want you to look at this relationship. This formula is one of those that's on your formula sheet. I hope you haven't ditched those formula sheets that we've been using all year. These are great. You want to keep using them, and we're going to add to them. All right? But this is the capacitance of a capacitor is equal to the amount of charge that you can push on it per unit voltage that you're pushing it with. Right? So imagine I've got a certain voltage battery. If I've got a bigger capacitor, I can put more charge on that with the same battery. Okay? So the capacitance is actually like what it sounds. It's the object's capacity to store things, just like the capacitance of a cup or a tank. So this is a new unit for us, farads, and usually we'll do microfarads or nanofarads, even picofarads, 10 to the minus 12. You can find those in electronics. These ones here, let's see. I think this one says 4205, and that should actually be a mu, but that's a microfarad there. So anyway, that's what we have. All right, let's take a look. So that's capacitance. Now, something about the capacitance. The capacitance of a capacitor depends only on its physical properties. It doesn't change its capacitance as you put more charge on. Okay, at least in our treatment of it. All right, parallel plate capacitor is the kind of capacitor that we're going to be talking about tonight. However, tomorrow night we're going to do spherical capacitors and cylindrical capacitors, and these are also part of the AP curriculum. These are really going to challenge our concepts of geometry and how we look at the electric field, and we're going to look at Gauss's law again. We'll look at that again tonight. All right, parallel plate capacitor, as we said, consists of two parallel plates separated by a distance d, and let's say that the plates have an area a. This is the relationship. I should have had that a little bit bigger, so let's zoom in on it. It's a big one. This is important. This is the relationship that tells me what the capacitance is of this capacitor. And let's go through these. The A, of course, the A is the area in meters squared. The D is the distance in meters, area in meters squared. Epsilon naught is the permittivity of free space. That tells us how easily an electric field can move through space. And then this number K over here, that is the dielectric constant, D-I-E-L-E-C-T-R-I-C. And that number for today is going to be 1 because we're not going to have a dielectric. So if you have air or if you have a vacuum between your plates, you can pretty much call your dielectric constant 1. Tomorrow night, or either tomorrow night or Wednesday, or both, we'll look at the dielectric constants that are not 1. All right. Now, I wanted to show you real quick a simulation that really gives us a good idea of how this might look. And so let me pull this up and let me actually get this larger so we can fill the whole screen, even though we're only over here. Try to pull your attention here. So here we have our plates. Let me see if I can do a double screen actually. Over here. And let's open this. Let's see what's on. Try go Microsoft. Okay, that will. Oh, I think it is. Okay, good. All right. So let me come over here. So I've got my simulation over here. Let's take a look. And it consists of a capacitor. Over here. Here's the capacitor. And I can change the area of the capacitor and I can change its separation. And those are the things. Remember, the only things really that I can affect the capacitance of this capacitor, except by changing the dielectric, which we'll do in a few nights, as I said. So if I click on my capacitance meter, you'll see if I increase the area, that's going to increase my capacitance because I can store more charge per unit of voltage. If I increase the distance, that will decrease my capacitor. The distance is, we know that C is equal to K epsilon naught A over D, and the distance is in the denominator, so when that gets bigger, the capacitance gets small. If I start to push charges on here like this, I get now a positive plate and a negative plate. Vice versa, if I go the other way, I can push charges in this direction, but I'll keep pushing them this way. This makes sense. Now, if I change the size or the properties of my capacitor, notice that the charge on this will change. However, what will not change will be the voltage because I've got it hooked up to the battery. But if I disconnect it, now I've stranded the charge on there. Now the voltage can change and the charge cannot. And so that's something that you'll be looking at in a little bit. We'll look at with some of our problems tonight. All right, let's talk about this last thing before we want to try some of our problems to see how we understand this. And that is the energy stored in a capacitor. And I said earlier that the capacitor stores energy in an electric field. It works kind of like a spring does in a mechanical system, believe it or not. It has some of the same functions that a spring has, but it stores energy. So we want to be able to calculate that energy. Now, that formula for that is given here. It's on your formula sheet. And these two are the formulas that are given. I'm adding this third one, which you could derive easily from the definition of capacitance, but it's good to just have in your pocket, especially since this year we know that you have open book, open note, and access to all the formulas you want. A couple more things. If we put capacitors in series, they will add up like resistors in parallel. So they just behave the opposite. And the charge on each plate is equal. So no matter what the capacitance is, the charges are the same. And you'll see how that plays out in a minute in one of the problems. Now, if we put the capacitors in parallel, we're going to add their capacitance. Remember, these formulas are all there on your formula sheet. And the voltage drop is now the same regardless of the capacitor. But what's different now is the charge. And so we want to try some of these problems tonight to give you a sense of what's going to go on. So I'm going to ask Kristen to go ahead and take it from here, and then we'll see how it goes. I'll do some more, and we'll have a great time at it.
All right, thanks, Roger. So let's look at a couple of what-if situations, because we know that if we're going to be asked some conceptual questions, most likely on this, we're going to be explaining. And so we want to look at two different things that you can do, because you can charge up a capacitor. And I actually have a super capacitor. So yes, mostly we deal with microfarad. I have a 1 farad capacitor here. to see how big that is. So if we connect the capacitor, we can then disconnect our voltage source that we were using to charge up the capacitor and see how that behaves. Or we can keep it connected to our power supply and change the capacitor and see what happens. So we're first going to look at what happens if you have a charged capacitor. So we have a parallel plate capacitor. Let me go ahead and draw that up to the side here. And it is connected to a voltage source that has a voltage V0. And we are going to let this capacitor charge up, right? So we connect it to the battery, that current starts low. And as we get into circuits, we'll talk a little bit more about it. It takes some time for that capacitor to fully charge up the plate. So we're going to wait until the plates are fully charged. They are going to have a charge Q0 on each one. Right? This one's going to be positive, this one's going to be negative. But the magnitude of that charge will be the same. And it is separated by a distance of D between those two plates. So what we want to do is we're going to disconnect it from the battery. So now we have just our two plates. Not only are we going to disconnect it from the battery, but we are going to increase that distance between them so that now it is 2D. So what I want to know is what happens to the capacitance of that capacitor, what happens to the potential difference across the capacitor, the charge that's on the one of the plates, and then also let's look at what would happen to the energy that is stored on that capacitor. Right? So let's say our initial energy that's stored within that capacitor is mu naught. Okay? So what happens to the energy, the charge, the capacitance, and the potential difference once we disconnect it from that battery and then we separate it to twice the distance it originally was. Right? So there's a couple of things you want to keep in mind here. When it's disconnected from that battery, what that means is that whatever charge we had is all the charge we get, right? Because those charges that were being pushed out from the battery, now we don't have that kind of continual charge on there. So if we have disconnected from the battery, the charge that we have on there is conserved. Right? We have conservation of charge. We can't gain more charge. The charge isn't leaving unless we then are going to discharge the capacitor. So our charge is going to stay the same. So when you disconnect the capacitor from the battery, we know that Q has to stay the same. So our new Q is going to be the same as the initial Q, or it's one time the charge. However you want to think about that. When it's disconnected, the charge is going to stay the same. Right? So then we can look at what that's going to do to also look at what happens to capacitance. So capacitance is equal to K times epsilon naught A over D. Well, we didn't change what was between the plates. Obviously, epsilon naught's a constant. Did we change the actual surface area of each plate? No, that's all staying the same. So if we're putting a 1 in for all these things, well, if this is twice the distance, then this side's changing by half, which means my new capacitance is now half of what the original capacitance was. Okay? And then we can look at the potential difference across the plates because we can relate the potential difference to the capacitance and the charge because we know that our delta V is equal to Q over C. So if we look at what we changed, our Q stayed the same. Our capacitance is now half as much. But if we have 1 divided by 1/2, that's really saying that we have twice the potential difference. Okay? And then what about the energy? What are we going to do to the energy? Well, Roger gave us a handful of different equations there. So let's use 1/2 Q delta V because my Q stayed the same. So let's pick an equation where I'm only going to have one thing that's changing. So if Q stays the same and delta V is now twice as much, well, that means we can store twice the original amount of energy that the capacitor stored when it was just D apart. So if you're removing it from that voltage source, then you're having the same amount of charge. It's kind of the immediate thing I want you to think about. Okay, let's look at it the other way. Let's say that we keep it connected to the battery. So we have our same plates that we had just a minute ago, and initially when they're D apart, we store charge Q. Potential difference that it's connected to is V0, and capacitance is C0. Energy U0. So what's going to happen if I keep it connected to the battery, but we change that separation distance to twice the original distance? So now the plates are 2D apart. What happens to all those things? So now I want you to think about what's going to stay the same and what's going to change. Okay, so if they're still not connected to the battery, the power supply is the same. Well, what's got to stay the same? The voltage is going to stay the same. The potential difference across those plates is going to be the same as it was. So when it's connected up together, potential difference stays the same. When it's disconnected, charge is conserved and stays the same. Okay, so now let's look at again the capacitance because we know capacitance. I'm not changing the shape of those plates, the geometry of those plates. I'm not changing the area. The only thing I'm changing again is the distance. So same case here. We have now 1/2 of the original capacitance. Okay, so if the voltage stays the same and we have half the capacitance, let's look at what's going to happen to the charge and the energy. Okay, delta V is still Q over C, and we know our V stay the same. That's 1. We have half the capacitance. Well, the only way we're still going to get 1 is if I also have half the original amount of charge. Okay, and then again, let's look at what's going to happen to the energy. The energy is 1/2 E Q times B, and our potential difference stayed the same, but our charge is half as much. Now I'm storing half as much as my original amount of energy that could store. Okay, so always be thinking about what's going to stay the same, what's going to change, what are those relationships, and how that affects all of the variables. Okay, I got one more here. Let's look at now an arrangement of capacitors. We're going to do a lot more to the circuit, but just to kind of get us thinking about how we combine these capacitors, we've got 3 capacitors here: a 12 microfarad capacitor, 2 and 4 microfarad capacitor. And if it's set up in this arrangement connected to a 12-volt source, let's determine A, what the total capacitance of this arrangement is, and how much energy would be stored total amongst the capacitors. So what are our steps here? What are we going to do first? How can we find the total capacitance of this equivalent capacitor? We want to look at, are they in series or are they parallel? Here we have a combination of both. So if I look at C2 and C3, that sticks out to me first. Those are in parallel. And then, so let's combine those first. Let's not get ahead of ourselves. So let's combine those two first. If they're in parallel, how do we combine capacitors in parallel? The opposite of resistors, right? So resistors in parallel, we have to do the inverse 1 over capacitors. We simply add up. So capacitance between 2 and 3 is just going to be my 2 microfarads plus my 4 microfarads, which gives me 6 microfarads. So almost like this now is one capacitor that has a capacitance of 6 microfarads. And that would be in series with my 12 microfarad capacitor. So how do we add those up in series? It's 1 over the total capacitance will be 1 over C1, which we'll call that 12 microfarad, plus 1 over my now 6 microfarads. So I can change my 1/6 to 2/12. That gives me 3/12, but that is 1 over C. So C would be 1 over that, or would be a total of 4 microfarads. That's so. In series, we have to do 1 over C, add up all the inverses, and then in parallel, we simply add them all together. So we want to know if this has been connected for a long time. How can we find the total energy stored? Well, we can go back to that total energy stored and use any of those equations that we used before. So let's use for this one our 1/2 C delta V squared, because we don't know the charge on any of these. And we could find it, we could rake it, and I think that would be a good thing to try to think through is which one of these capacitors would store the greatest amount of charge. Okay? And again, we'll get back to that a little bit more when we get to circuits, but I can plug in then that this is using our equivalent before and our potential difference of our battery. Now that we're actually plugging in, we got to actually turn this into 4 microfarads is 4 times 10 to the negative 6 farads times our potential difference of 12 volts. Right? If we calculate that out, let's see, we get 2.4 times 10 to the negative 5 joules. Okay? So there's some practice for you. Roger is going to give us a little bit more practice for that AP exam.
All right, excellent. All right, folks, I got one more problem for us tonight, and I'm looking at the clock and I'm going, there's no way that this is going to take me 19 minutes. So you're definitely going to get out of here before 6:45 tonight. All right, let's go ahead and see what we've got. So I'm going to bring you back to my screen here, and I want to look at a couple of problems here. All right, so let's pick up where we left off, where Kristen left us, and looking at, excuse me, charge on capacitor, and what's going on with our, come back. Okay, what's going on with our capacitor? Okay, so we've got a parallel plate capacitor, charge Q plus on one plate and Q plus on minus on the other. By the way, these are always exactly opposite. They have to be. And the plates of each area are A, and the distance D apart and separated by a vacuum. A single proton of charge E plus is released from rest at the surface of the positively charged plate. Will arrive at the other plate with kinetic energy proportional to how much? So we want to know what its kinetic energy is. I'm going to draw this out because I think I'm a physics teacher and I like to draw. All right, it goes well with the drawing. So let's go ahead and draw this out. We've got you should draw with me if you can. We've got a positive plate here, and we've got a negative plate here, and their charges are Q plus and Q minus, and we want to know what if we have a positively charged particle here, like a proton, all right, a single proton, not like a proton, it is a proton. It's released from rest here. How much kinetic energy does it have after moving this distance D through the vacuum? All right, and so it sounds to me like a conservation of energy problem. I hope you heard it that way too. And so we're going to set the energy change in potential energy, right, of our particle, electrical potential energy is going to become kinetic energy. It's always good to think about what that is. And so if you recall Well, I hope you do. This is a couple things. So we've said that this field is uniform. It's the same everywhere. So since it's the same, I can use a very, very simple approach to this and say this is Q and this is delta V. So whatever the charge is on here, not this capital Q, but this tiny little q. So let's let that be E delta V right away. And that's going to be equal to R delta K. Well, that's easy, but we want it in terms of everything else. What's delta V? Well, I learned also, we learned tonight that capacitance is equal to the charge on our plates divided by its charge per volt. It's coulombs per volt. And so that means that our delta V is going to be Q over C. And so I can replace that. So that's going to be E Q over C. But then I look up here and again, none of these have a C in them. So they're all in terms of something else. Well, what's the capacitance of a parallel plate capacitor? Well, I know that C is also epsilon naught. Well, it's K epsilon naught, but K is 1. Epsilon naught A over D. So I'm going to replace that. That's my delta K. I'm going to replace that. So I have E Q over C. And so the C is now epsilon naught A over D. And so if you remember, when we have something in the denominator that comes up front. And so we have EQD up top over E naught A. Well, I look at these and none of them have this, epsilon naught in it, but it doesn't say equal to, it says proportional to. So I'm going to just say, forget about you for a minute. Which one is it? And we look, it's right here. And so that's how we can look and see how we can get energy in that. Now, that's not a problem that's asking me how much energy is stored in the electric field. I want to be clear about that because we just talked about that a minute ago. This is not that problem, even though that's a good problem too. Don't confound the two. This is a different kind of problem that AP sometimes asks us to solve. All right, let's look at this last one for tonight. A parallel plate capacitor consists of two conducting plates separated by a distance d. In this case, notice they're using a capital D. The plates may be considered very large so that the effects of the edges may be ignored. The two plates have an equal but opposite surface charge per unit area. The charge on either plate resides entirely on the inner surface facing the opposite plate. On the diagram below, draw the electric field lines in the region between plates. All right, so up here, this is very small, but I'm going to go ahead and circle it. This is sigma, this is plus sigma, and this is minus sigma. And remember, sigma is our charge density. That's going to be coulombs per meter square. All right. All right. So I'm going to write that over here. This is my plus sigma, and this is my minus sigma. And I'll even remind myself about that they said these positive charges are all residing on the inside surface. So I'll draw that. And then what is my electric field? Well, the electric field is the direction of the electric field is the direction of a positive test charge in that field. And so a force on a positive test charge will push it from the positive plate to the negative plate. And so that's what the electric field would look like. And remember, with a parallel plate capacitor, I have uniform electric field lines. Okay. Now it says by applying Gauss's law, by applying Gauss's law to the rectangular box whose upper surface lies entire within the top conducting plate, as shown in the following diagram, determine the magnitude of the electric field E in the region between the plates. All right. Now I'm going to draw this a little bit bigger because I think it will help us to see this. And I'm going to draw it just straight on so that I'm not going to worry about perspective. But here are my two plates, again separated by this distance d. And they want me to use Gauss's law to find the electric field within this range, so within these plates. So let's do that. I'm going to draw a Gaussian surface that is a box. That's what they're asking me to do. And so I'm going to have this cube. And this cube is just, we're looking at it at the side here. We're not going to draw any depth to our cube, but it's a cube. So every side has a dimension A, and this dimension A is also evident here going back in the cube. And so if we ask, well, what is and remember the electric field lines are like this. They go from positive up to negative. So when I use Gauss's law and I say, what is the flux? Well, the flux is E dot dA vectors is equal to the enclosed charge divided by epsilon naught. So let's apply that. Well, once again, we can bring the E out because it is uniform and it is only penetrating. Actually, it's only going through this surface. And so we're going to say the integral of dA, and that's going to be just the area of this bottom face because the 5 other faces of this cube have no electric flux going through them. And so that's just going to be A squared. And over here, what we have is the enclosed charge. Well, if I look up here, how much charge have I enclosed? Well, the area of this face is A squared times sigma. That's going to be my charge. That's going to be A squared times sigma because that's the charge density of my plate. So the charge density times the area gives me the charge. Coulombs per meter squared times meter squared. I end up with coulombs over epsilon naught. Well, this becomes one of the most boring algebra problems you've probably ever done in AP Physics 6. And there it is. And so that's the electric field between those plates. Now, I would be remiss if I did not show you one other take on this that was shown to me by one of my favorite physics teachers. And it stuck with me, and I wanted to show it to you too. There's another reason that we can identify and really understand what that one is. And that reason has to do with this. Remember, you may not remember, but a few days ago when we were working with Gauss's law, we said, what is the electric field due to a big sheet? Okay. And if you recall, that electric field, we said when we did Gauss's law, that electric field turned out to be sigma over 2 epsilon naught. All right. So if this is a positive plate, it has an electric field pushing out from it in all directions. And what was really interesting, I want to remind you about this, is notice that there's no D here. This doesn't matter how far I am from the plate. So it's everywhere in the, as far I want to be from the plate as possible. Remember, this is relative to the size of the plate. Now, this would be my negative plate, and a negative plate would have electric field lines pointing towards it like this. And they also would have an electric field of sigma over 2 epsilon naught. But you can see what would happen. This is pointing toward the negative plate. And so let's add this up. And so if I come over here, one of the things we can see is that up here, the blue is all down, the red is up. They're going to add to 0. Same thing down here. We've got electric field in this direction, electric field in this direction. They're equal in magnitude, opposite direction. They cancel. And in this one, we have sigma over 2 epsilon naught superimposed with plus sigma over 2 epsilon naught. And that gives us sigma over epsilon naught. So E is equal to sigma over epsilon naught. Okay. Now the last thing, which will probably come up tomorrow, is this is also equal to V over D, potential difference over that distance. So I just wanted to throw that one at you. That one is something that should show up pretty soon. All right. Let's see. We hope that this has been helpful for you in understanding our capacitors. And so please stay tuned because we're going to be doing some more capacitance work tomorrow night. Tomorrow night, we're going to do cylinders and spheres, and the geometry is awesome. You're going to love it. Kristen, are you going to take care of the spheres for us?
Yes, I also have one more thing. I forgot to square that potential difference. I'm going to go back just to show that real quick. I forgot to square the potential difference on my voltage in the energy equation. So it should be, sorry guys, 2.88 times 10 to the -4. But there's one more thing I wanted to add on if I could piggyback off what you were just doing, Roger.
Yeah.
Let's find the capacitance between these two plates. Sorry if I do that real quick.
Ooh, yeah, I love it.
Sorry everyone. I'm going to do just a couple more minutes. It'll be real quick, but we're going to get that equation that we got at the beginning with it. So it's really cool. So we got that the electric field is sigma over epsilon naught, and we know that the relationship for potential difference. Let's find the potential difference between the two plates. The delta V here between the two plates. Because we did this last class, that the potential difference is the integral of the electric field. So if we do that, right, we're not finding the potential at one point. I just want to know between the two plates. So I can leave it as just delta V rather than having to pick two spots like we were doing the other day. So if we plug in then we get delta V is the integral of sigma over epsilon naught with respect to that distance. And if we integrate that, well, we've got this imaginary R in here to the 0, right? So when we integrate that, that becomes sigma times R over epsilon naught. But what is R between the two plates? It's D. So this becomes sigma times D over epsilon naught. So that's going to be the potential difference between the two plates. And so now let's turn that into capacitance, because from there it's easy, because if delta V is Q over C, what's C? Well, it's Q over delta V. So then C becomes Q over sigma times D over epsilon naught. There's 0 I'm going, right? Epsilon naught comes up because so this becomes Q times epsilon naught over. Well, let's plug in for sigma. If we're looking at the whole plate in itself, sigma is the amount of charge per area. So if we look at the total charge in that total area, then I'm going to put sigma is equal to Q over A times D. Well, what happens to the Q's? They cancel out. The A's 1 over 1 over comes up to the top, and we end up with sigma times times A over D, which is what we got in the beginning. We have to add in that dielectric constant later, but that's just air. We're not going to worry about it tonight. All right, thanks, Roger. I just wanted to add that in really
No,
quick.
I'm glad you did that, because that shows again how we can always circle back. If we're consistent with our physics and we really are representing it correctly, we should get the same answer. And I love how that came back like that. So that's awesome. All right, well, ladies and gentlemen, again, thanks so much for joining us tonight. It's been a pleasure to be able to share some physics with you, and we can't wait to do it again tomorrow night. Have a great night, and we will see you at 6 on Tuesday.
Kristen Gonzalez Vega, and this is AP Physics C, Electricity and Magnetism. We are live every day. I am in Frisco, Texas, and my friend Roger.
Hi, everybody. My name is Roger Siegel, and I also teach physics. I am in Sarasota, Florida.
All right, so we are going to pick up today with some more capacitance. We are going to talk about some different shape of capacitors tonight. We did nice parallel plate capacitors last night, so tonight we are going to do spherical and cylindrical capacitors. So my name again is Kristen Gonzalez Vega, and we have Roger in Florida. And our two objectives today are to use integration techniques to calculate potential difference between 2 points on a line given the electric field as a function of that position, and then also derive expression for a cylindrical capacitor or a spherical capacitor in terms of the geometry of the capacitor and fundamental constant. So I kind of wanted to start off with a little review here of what we did last night and kind of our steps. So by now we have done Gauss's law a million times. We're going to do it a few more times tonight, maybe even a couple more times tomorrow. But Gauss's law is fundamental because we have to have a function for the electric field in order to be able to determine the potential difference or the potential at one, because the potential difference is related to the field because the potential difference is the negative integral of the electric field with respect to that position. And then we added on last night that we can then take that potential difference and find the capacitance if we have two conductors. So we have two conductors and we charge them up to the same charge, that becomes a capacitor. We did those two parallel plate capacitors last night, and we talked mostly about how the geometry of that capacitor affected the capacitance. We said the capacitance was equal to the dielectric constant, which we were just still sticking with air or vacuum for tonight. We will get into different materials tomorrow, times epsilon naught times A over D. So that's set for those parallel plate capacitors. We also talked about how that relates to the amount of charge that can be stored on a capacitor, because the charge and the potential difference are related. That potential difference is equal to Q over C. So we have all these kind of relationships that we were talking about with the plates. If you increase the surface area of the plate, well, that's going to increase the capacitance, and so we can store a charge for the same potential. We also talked about the energy that you can store on the capacitor as well. So tonight let's look at another type of capacitor. So we have a spherical capacitor here. So we have a spherical conductor that has a radius of A on the inside, carries a positive charge Q. Where is that charge, guys? Remind me again. Remember, it's always on the surface of that conductor. And it is surrounded by a concentric spherical conductor that has a radius of B, inner radius, and outer radius of C. And its charge is negative Q. So again, they are equal charges, one positive, one negative. What's going to develop in between there? An electric field. So first I want to know though is how can we say that if we have an R greater than B, really could even be inside here, right? Let's look at that specifically. So if I draw my Gaussian surface on the inside here, okay, anything bigger than that radius of B is going to have an electric field of zero. So going way out to infinity, everywhere in between the electric field is zero. So I want you to tell me why. Why even here? Why does it not have to be out to C before it becomes zero? Anything greater than B, why is the electric field zero? What I want to look at is those charges. And if we look at where those charges are residing, we said they're on the surface. So we've got a positive Q, let's stick with the red for now, positive Q on the surface of the inside conductor, and we're going to have a negative Q. Where is that charge going to want to lie? Well, if the inside conductor is a charge of positive Q, those negative charges want to be on the inside surface. So those negative charges are going to be on the inside surface, not on the outside. They want to be close to those positive charges. So if I look at my Gaussian surface here, that's enclosing the in-between part there. And if we did Gauss's law, remember Gauss's law, the integral of E dot dA, which equals the Q enclosed over epsilon naught, right? Both those sides are electric flux. If we look at the surface area, that's 4 pi r squared. But if we look at the Q enclosed, well, what's enclosed in my Gaussian surface? It's all of the charge, all that positive charge and equal amount of negative charge. So my Q enclosed is zero. If my Q enclosed is zero, my electric field is zero. And that's all the way going out forever because we've got that charge as long as there's nothing else, right? But why is the potential also zero in all of this region? Well, let's take that infinity spot, right? We know that we can use that reference point that at infinity the potential is zero. Right? We also know that the electric field is the slope or the change in potential. So if the electric field is zero here and the electric field is zero at infinity, then what's the change, or what does that slope have to be? The change in potential has to be zero, because remember, E, we can say in the grand scheme of things, is delta V over delta X, or dV over dx. So if the electric field is zero everywhere, that means the change in potential is zero. So if it's zero at infinity, what does it also have to be up here? It's also going to be zero. It is constant. That's different than we looked at what inside a conductor is, right? If I just had one conductor that's positive charge, and that positive charge is again on the surface, well, the electric field everywhere is zero inside because there's no Q enclosed, but there was potential inside. Remember, it's a constant potential everywhere in there. Okay, so let's move on here. Let's look then at when we are in the region in between. Clear this out, give us some room. So when we're in between the two plates, in between A and B, what is the electric field? We've done this a million times. I'm going to go through it pretty quick here. So we're going to write Gauss though, because we always should. It's a sphere, so Gaussian surface is a sphere also. I'm now enclosing just that inner Q. So if we rearrange, we get that E is equal to Q over 4 pi epsilon naught r squared, which we can also write 1 over 4 pi epsilon naught is K. You could leave it like this, or you could also say this is KQ over r squared. Sounds really familiar, right? Okay, now let's use this then to determine what the potential difference is between the two. So from here to here, what is the potential difference? Right, let's remind ourselves our E is KQ over r squared, or Q over 4 pi epsilon naught r squared. And how do we get from field to potential difference? Well, we know the potential difference is the negative integral of the electric field with respect to that distance. So here's where we want to be careful about where we're saying like to and from, and comparing the 2 points. So you can either go, I always say, always work ourselves outside in, right? Or but we could say from here to here, but we're going to say the final position delta V, but we don't really put V here. We can leave this as delta V because I want the potential difference. Now, if I wanted to know what it was right at point A or right at point B, then I'd have to turn this into like V A minus V of B. But since I just want potential difference, I can leave that. And so what we need to look at then is what are the limits on my integration here? Well, I'm integrating from B to A, right? Initial conditions, we know it's zero at infinity, so we always kind of work our way back in from that infinity. And my electric field is KQ over r squared. Right? Well, what is the integral KQ or constant? We can pull those out. So really we're just taking the integral of 1 over r squared, which becomes negative 1 over r. So my negatives are going to cancel out. My delta V will equal then KQ over r from B to A. Which when we plug it in, we get KQ A, so KQ over A minus KQ over B, which we can simplify to KQ times 1 over A minus 1 over B. So that's our potential difference between the two shells. Okay? And then lastly, we can take this one step further, we can find the capacitance. And we kind of started this at the end of last night. We can relate capacitance and potential because the potential difference is the amount of charge divided by the capacitance. So C is equal to Q over delta V. So the charge on one of those is Q, and my delta V is KQ times 1 over A minus 1 over B. Oh, we notice happens to Q. Cancel. And so we get our final answer, which is R 1 over A times 1 over A minus 1 over B. So that's a little bit messy for our capacitance. Okay, so we start with Gauss's law. We derive the electric field in between our capacitor, but no matter what shape it is. We then use our integration of that electric field to get the potential difference, and then we use our relationship between potential and charge to get the capacitance. Okay, so I'm going to give it back over to Roger. He's going to do a couple more examples for us.
All right, great. Thanks, Kristen. All right, so let's go ahead and figure out how we're going to apply this. And, that's how we always really fit our knowledge in new ways as we try and solve problems. So let's go ahead and see what we've got here. So in this problem, tonight we're doing this integral capacitor. And so we've got this capacitor, radius A, A on the inside, this space in the middle, and then another shell on the outside. So this is our coaxial cylindrical capacitor, and our length is L along this way. Now, an important piece that they'll say here is ignore edge effects. And so that means that we can pretend, similar to a way in a mechanics problem when we say assume frictionless surface. Well, we know that's a rare surface indeed. In the same way, we can ignore these edge effects in this class. And as you move up into electrical engineering or into physics, you will take a different approach. But we're going to ignore these edge effects. It makes it an easier problem to do. What that means is all of my electric field lines, if I can imagine I'm looking straight down the barrel of this coaxial conductor, all of my electric field lines are perfectly radial between from one electrode to the other, from the outside or inside to the outside. That's my electric field line. And there's no electric field lines sneaking out. If I look at it on the side, there's no electric field lines sneaking out here that we have to worry about. No edges. All right, so it says write an expression for the electric field for the region between A and B in here. And so let's go ahead and we're going to draw our Gaussian surface as we do. And if you recall, there's some Gaussian surfaces that are going to show up again and again and again. One of them's a sphere, one of them's a cylinder. And so here we have a cylinder. And I hope you recall that when we do a cylinder, what we are looking at is our surface is this, and we're looking at this area, the area of this part of the cylinder. And so what is that area? Well, that's a big rectangle. Remember, if we think about our cylinder as a net diagram here, here's our cylinder. And this is the radius of our cylinder. And this is the length L. And so this length from here is the circumference 2 pi r. So to find the electric field, we're going to use Gauss's law. The closed surface integral of E dot dA is equal to the charge enclosed by that Gaussian surface divided by the constant epsilon naught. And so we have the E, since it's constant everywhere along this Gaussian surface, everywhere along here, my Gaussian surface, the E field is constant, it can come out, and then I'm going to have the closed surface integral of dA. And my charge enclosed is just Q, that's given in the problem, and again, the constant epsilon naught. Now, looking at this, if I add up all this area, what is this area? Well, this area is 2 pi RL, that's 2 pi RL, and so this is going to be is equal to Q over epsilon naught. So what I'm going to get finally here is E is equal to Q over 2 pi RL epsilon naught. And so that is our electric field in this region. Now, the next cut for us, the next thing to do is to determine the potential difference in that area. And so let's go ahead and do that. And so, I'm sorry, I said the potential difference in the area. I want to use that word difference. We're always thinking of the potential difference. And so if we say the potential difference between the cylinder and the shell, we mean compared to at infinity, the potential difference from infinity out to this point here in the shell. And so what we're going to do is we're going to use our definition of potential difference. We can't just say that V is equal to ED or E times distance. We can't say that because this is not a uniform electric field. So we're going to have to add up. This is negative E dot dr. And we're coming from infinity all the way to this point. I'm sorry, we want to know, well, let's go ahead. Yeah, we're coming from infinity. I don't want to go from infinity because earlier what we had learned is since when we're out here, we're enclosing a charge of 0, then my potential difference doesn't start until I get to here. So I can go from infinity to B is 0, and then from B to A. And so that's what we want to find out in the shell. And so what we have then is we have Q over 2 pi RL epsilon naught times dr going from B to A. And so that's going to be, and that's a negative. And so when we do this, the Q comes out, let's change actually the negative to a positive. And so let's go from A to B of Q over 2 pi RL epsilon naught dr. Now the only thing that is a constant, that's not a constant, is R. Everything else comes out front. So that's going to be Q over 2 pi L epsilon naught integral of dr over R from A to B. And so that becomes Q over 2 pi L epsilon naught natural logarithm of R from A to B, or Q ln B over A 2 pi L epsilon naught. Well, that was a long way to go, but that gave us now the potential difference between this plate and this plate. All right, now let's go ahead and determine the capacitance. And this is the easier part. We know that C is always equal to Q over delta V. And so the Q is, that's our charge on both plates, either plate, over Q ln B over A time divided by 2 pi L epsilon naught. And so what we can see is the Q's cancel. And so we get 2 pi L epsilon naught over ln of B over A. And so that's our capacitance for our cylindrical capacitor. Now, I don't know about you, I think that's pretty cool that we can do that. I want you to give yourself a pat on the back for being able to do that derivation. And if you can't do it, you're gonna have to rewind the video and give it a try because it's a good one. All right, so let's go ahead and come back to our next piece here. And that's going to be right down here, cross section. Now we've got spheres. And so the cross section of two concentric spherical metal shells is shown. So we've got one sphere inside another sphere. They have concentric, they have the same center. Let's go ahead and give the outer shell again a radius of E. We won't worry about units. And the inner shell will be a radius of A. We won't worry about units. And the Q plus will be 1 nanocoulomb. That's fine. And sometimes, by the way, sometimes AP will show this support in here. Sometimes they won't. They'll just draw two circles and they'll say inside sphere, outside sphere. Don't worry about it if you don't see a support. Just know that physics teachers can make things appear and disappear just like that by drawing them. That's the fun of doing it. Okay, so let's go ahead and find the potential difference between the shells. Well, again, I'm going to have to find the electric field to be able to find the potential difference. All right. So again, I know that I've got Q on the inside sphere and Q negative on the outside sphere. But once again, my E field is going to be by Gauss's law. So we're going to have E dot dA is equal to Q enclosed over epsilon naught. And I'm going to integrate all over this sphere, my Gaussian sphere. And so again, because of a constant E, I can pull it out front. And then I can say, well, my charge is my charge. And so E times, and the surface area of a sphere is 4 pi R squared is equal to Q over epsilon naught. And so what we get is E is equal to Q over 4 pi epsilon naught R squared. Ladies and gentlemen, that is the same as E is equal to KQ over R squared. So this is what we have again, since it's a sphere and we're outside of this charge, we don't care about any of the charge that's on the outer sphere, just on the inner sphere. We only have to worry about that enclosed charge. And so it acts like point charge. Now, what's the potential difference? Well, we're going to go now we're going to integrate from B to A of negative E dot dr. And so that's the negative integral of KQ over R squared dr from B to A. Now that's going to give us the negative integral. Let me go ahead and pull out the Q and the K. That's KQ times negative KQ times the integral of dr over R squared. And again, from B to A, that is going to be negative KQ times a negative 1 over R from B to A. Now we have a negative and a negative, so that's going to be a positive. So we get KQ times 1 over A minus 1 over B. And so that is our voltage difference from B to A as I go in that direction. KQ times 1 over A minus 1 over B. Now I want to clean it up a little bit because let's see. Well, no, that's okay. We'll leave that there. Now the last thing I'm going to do tonight is I'm going to find the capacitance between these two. And so once again, now this is the easy part. C is equal to Q over delta V. And so the Q is again Q. That's the charge on each plate. And the delta V is what I have over here. So that's going to be KQ times 1 over A minus 1 over B. And if this were the exam, I'd probably walk away from the problem now. But I, as a teacher, am loath to leave a compound fraction. And I think it's important to finish it. So let me go ahead and finish it for us. And so this Q cancels. And so what we have then is we have 1 over K. And I'm going to get a common denominator here. I'm going to get B over AB minus an A over AB. And so that means we have 1 over K and we have B minus A over AB. And so my final answer is C is equal to AB over K times B minus A. And notice that the sign works out to be positive, which is what we would look for the capacitance. So that means we had all of our directions correct. All right, I challenge you to do that problem, to
rewind it and try it yourself, work through it. It's a great problem to really get these ideas solidified into what we're getting at here. So I know that Kristen's got a good one for you next, and keep working hard.
All right, thanks, Roger. Yeah, we got one more thing tonight, and it's going to seem repetitive, but it's a little bit of a different view on the same kind of problem. And I'm going to give you some time. I'm going to pause and let you, since we have some time tonight, let you work through this now that we've done a couple practice. Now I would like you to kind of work along. So we have an isolated conducting solid sphere of radius A shown above that is charged to a potential of V. So we want to first determine what the charge on that one isolated conducting solid sphere is, okay? And then we're going to hook up two shells and connect them together surrounding it. So they're brought up without contacting the solid sphere and connected to form a spherical shell surrounding and concentric with the solid sphere. The outer shell is then grounded. By means of Gauss's law, determine the electric field in the space between. Okay? So I'm going to give you a few minutes and mute myself here, and I would like you to work those two parts for me. Determine what the charge on that sphere is, and use Gauss's law to determine what the electric field between the two is. So ask yourself, what is that? And also, what is this grounding going to do? We haven't really talked about grounds too much. So what would happen when we ground that outer one and then find the field? Okay, if you need some more time, you can pause and wait till you're done, but let's talk about these two. So part A, we know it's charged to a potential of V, and we know the radius is A, so let's find the charge. So if the potential is V, and we know that the relationship once we get here is that V is equal to KQ over R, then we can say really this is KQ over A is equal to V, and let's rearrange and solve for Q. If we do that, we get that Q will be equal to V times A over K. So that's our charge on that. Okay, so then if we connect up this outside shell here and we ground it, what's that going to do? We talked a little bit about grounds with charging and with our electroscopes and things. So what does introducing a ground do? Remember, it allows for charged electrons to flow either into or out of our conductor. So which one of those two things do you think will want to happen? Well, the negative charges want to flow into our conductor or out of our conductor. Well, if this one has a positive charge, then we want to have negative charge. So there would be now negative charge, equal amounts. So our inside sphere has a charge of V times A over K, and our outside sphere will have a charge of negative V A over K. And so then let's use Gauss's law. Not that you had to do that to do Gauss's law, but conceptually we want to be thinking about what's going on. So if I use my Gaussian surface, we do Gauss's law. It's going to be the same way we do it always. We're just dealing here with a little bit of different variables, a little bit of a different scenario. Q enclosed over epsilon naught, still a sphere, but we're going to plug in for our Q enclosed. Our Q enclosed is V times A over K, still times our epsilon naught. Okay. Well, if we divide by our 4 pi r squared, then we get that E is equal to V times A over 4 pi epsilon naught times K times R squared. And if you recognize what is 1 over 4 pi epsilon naught equal to, that's K. So really we get K over K, and our K's are going to cancel. So really the field becomes V times A over R squared. So what you guys got? All right, we're going to move along. Now I want you to find what the potential of the solid sphere is relative to the ground and the capacitance of the system. Okay, so again, I'm going to give you a couple more minutes. Find the potential of the solid sphere and determine the capacitance. Okay, if you need more time, again, go ahead and pause, but let's look at it. Let's find that potential difference. So we want to find that integral, that negative integral of the electric field. So if we plug in then that our electric field was VA over R squared, well, we can pull out that V and that A. Really, we're just integrating that R, so we get delta V equals V times A over R from A to B. So if we plug that in, we get VA over A minus VA over B. So if we cancel out those A's, we multiply to get a common denominator, then we get V times B over B minus V times A over B. So really, we get V times B minus A over B. And then lastly, we can get the capacitance. How do we get the capacitance, guys? Capacitance is going to be equal to our Q over our delta V. So we got to go back to what our Q is, right? We don't want to leave it as Q because we already solved for Q. Back in the beginning, Q was V times A over K. So we get V times A over K divided by our potential, which is V times B minus A over B. I'm going to multiply by the reciprocal just to simplify this for us. So this becomes B over V times B minus A. Okay? And when we simplify that down, we can cancel out, and we end up with A times B over K times B minus A. So process was the same, just a little bit different variables there. So we have done lots and lots with putting all these things together, right? Doing Gauss's law to find the field, using the integral to find the potential difference, plugging in the capacitance. What we're going to talk about tomorrow is what happens if I take a different material, and let's fill in maybe this bottom half of my capacitor with this different material that has a different dielectric constant in there. We want to look at what's going to happen to that capacitance now of that capacitor. So we're going to look at what we call dielectrics tomorrow and how that affects our capacitance, our energy, our charge stored within our capacitor, and all of that. So Roger, anything you want to add or anything you want to say to wrap up tonight?
Yeah, thanks, Kristen. Just thanks for tuning in, working so hard. I don't be discouraged if these problems seem hard because they seem hard to us too, and we're working to understand them. So please keep working hard, and can't wait to see you next time.
Okay, come back tomorrow. Hello, everybody. My name is Kristen Gonzalez-Vega, and once again, you are joining us for AP Physics C, Electricity, and Magnetism every day. And I am coming from Frisco, Texas, and I have with me tonight, as always, Roger in Florida.
Hi, everybody. I'm Roger Siegel, and we're coming to you from Sarasota, Florida. This is where I live and teach, and thanks for joining us.
Okay, so we have been talking about capacitance, capacitors, the past few days. We wrapped that up yesterday with dielectrics, and today we get to start on circuits. So that is always a really fun topic, circuits. We're going to spend quite a few days on circuits. Today, we're going to do just real kind of basics of what is current, resistance, and voltage or potential difference in a circuit. And talk a little bit about drift velocity, multiple resistors in a circuit, how you treat those, and resistivity. And we're going to do a web-based question at the end. So lots to get through. Again, my name is Kristen Gonzalez-Vega, and we have Roger also joining us this evening. And we are so happy that you're joining us and watching these. Tonight, we're going to describe the relationship between current, potential difference, and resistance, explain how the properties of a conductor affect resistance, use microscopic definition of current in a conductor, describe the properties of the conductor and the idea of drift velocity, and then describe the relationship between the electric field strength through a conductor and the current density within the conductor. So we're going to start off with just a basic review of what current and voltage really are. So a lot of people get confused about these quantities that are, abstract and kind of hard to see. But the easiest analogy I like to use is using a post office and mailman analogy. But the short of it is that the voltage or the potential difference in a battery in a circuit is the amount of energy per charge, right? So as those charges are flowing through the circuit, the amount of energy or joule that those charges are carrying. And then the current is the flow of the charge through the circuit. So how much charge per time passing through one point in our circuit. And our conventional flow of current is positive charges going up positive terminal of the battery and coming back around the negative terminal of the battery. And that's what we still talk about and use today. A couple other things to know is that not only do we measure the voltage in volt, but we could also measure it in joules per coulomb. And a lot of times we kind of go back and forth with voltage and current and with their kind of alternate units, right? So 1 volt is 1 joule per coulomb and 1 amp is 1 coulomb per second. So kind of using those other units to kind of help you get through some things. So I'm just going to do a real basic kind of showing you of our circuit, and I'm going to switch over, and I've got a FET simulation here. And we're just going to look at a basic circuit that has a battery and 1 light bulb start. We're going to close the switch, and we're going to see that current coming out that positive terminal going through the light bulb and back and around, right? So obviously we have to have a closed circuit in order for that current to flow. That potential difference within the battery is what's giving that push to those charges to go through the circuit. And that energy that those charges are carrying is being dissipated as light in the light bulb. And those charges go back to the battery, they gain that potential energy as they travel through that potential difference, and around we go. If we were to add another light bulb, we'll kind of make predictions. We're going to do a little bit more detailed circuits later, but let's just get out here my amp meter and my voltmeter, and let's look at what's going on real quick. So I just want to look at what is the current going into that light bulb, right? So if we look at the current, it's 0.9 amps. I can look everywhere. What is it? 0.9, 0.9, 0.9. Let's also look at the potential difference. Let's look at the potential difference across the battery from one terminal to the other. That's 9 volts. Let's look at the potential difference across our light bulb. Also 9 volts, right? Okay. So if I were to just real quickly here, let's open this back up. Let's cut this open. Let's add in one more light bulb. All right. And let's close this again. So if we look now at the current, what do you think is going to happen if I measure that current? 0.45 amps before this light bulb, after that light bulb, after this light bulb, everywhere it is. Let's go to the potential difference across the battery. It's still 9 volts. I go across this one light bulb. There we go. 4.5 and across this one. Also 4.5. So some things to be thinking about here as we're talking about circuits. And I also want you to kind of notice how I was measuring those. And this really is not this is more, if the current is more of like a tool, that's not really how we would measure the current, but we're going to talk about how we measure those things tonight. So let's go back here to the PowerPoint and keep on trucking along. Okay, so we've got that current and that voltage and what those are. And then we also have resistance within our circuit, right? So the resistance is what kind of is restricting or resisting that flow of the current in the circuit. So it depends on the material and the shape of the resistor. Our equation that we use is that the resistance is equal to rho times L over A, where rho is the resistivity of the material. So the different materials have different resistivities. So if you want a good wire for your circuit, right, we don't want our wires in our circuit to have a lot of resistance. So if we want to make a wire, do we want high resistivity or low resistivity material? Well, if we want our resistance to be low, we want our resistivity of our material to be low. Right? And then we can relate all these quantities together with Ohm's law. And Ohm's law is that the potential difference is equal to the current times the resistance. We can look at that as the circuit as a whole. We can look at each individual element, so we can apply Ohm's law everywhere in our circuit. The other thing I wanted to touch on tonight, which might not be a review for you, is drift velocity. So if we look at, I'm going to draw here a wire. So here we have a conductor, maybe it's a piece of wire, right? Copper wire. But I'm going to look at, let's say it's connected to a battery. But if I just have a piece of copper wire not connected to a battery, there are still charge arc carriers within that material. And they're going to be bouncing kind of all around within that. Now, if we apply a potential difference to that wire, then that's going to push those charges through the circuit. But they're still not like nicely traveling straight through from one side to another, right? They're still bouncing around as they go through the circuit. And so the drift velocity is kind of that velocity as they move through. So they're still bouncing up and down, but they're traveling along through the wire as they go. And what way we can find out to relate that drift velocity is that the current in the wire is equal to N, which is the charge carriers per volume in your conductor, times E, that charge of an electron, times that drift velocity times the cross-sectional area of your wire. And so that's a formula that's on your formula chart that can be useful to find that drift velocity, or if you know the drift velocity, to find the current. What really kind of stands out here, though, is that a lot of people, a big conception that people have is that when you turn on a light switch and that light comes on right away, it's because those charges are moving at the speed of light and lighting the light bulb. And that's not really what happens. So we have all of these charge carriers in this wire, and when we have that current, well, it's creating a domino effect. So we have one charge that's going around that's going to transfer and propagate that current through the wire, and that propagation happens at near the speed of light. But it's not those individual charges that are moving at the speed of light. So we can kind of compare this to a wave. And when you have, let's say, a transverse wave, and the matter within that wave, or those molecules are vibrating up and down, right? Think about the wave in the stadium, right? I'm going to stand up, I'm going to set that down. But the wave is transferring through the stadium. I'm not running physically around the stadium to make a wave, but the wave goes around really fast because people have that domino effect to transfer the wave. The same thing happens within our circuit, is that those charges create that domino effect, which are lighting that light bulb, and it's not one charge moving right through that circuit. The other thing we can talk about current is the current density. And so the current density, which is J, is the current per cross-sectional area that flows through the surface. So we can have different wires of different cross-sectional areas. But if this were, let's say, part of one circuit, what would have to be the same throughout this whole thing? Well, if these are in series with each other, the current has to be the same. But if you change that cross-sectional area of your wire, you're changing the current density. So the electric field inside that conductor is providing the force to move those charges through. So we can relate that electric field and that current density. So this is what you get on the formula chart. But it's good to know where that comes from, but also to be able to go back and forth to Ohm's law and relate the resistivity, right? So the electric field is equal to the resistivity of your material times that current density. But we want to be able to go back and forth between the two. So if we start with Ohm's law and V equals IR, well, how can we relate potential difference and electric field? We've been talking about that a lot, right? We know that the electric field right up here, the way, was equal to that change in that potential difference over the change in position, right? So if we're talking the length of the wire, then I could say that the V is equal to the electric field times the length of the wire times the current. Well, I can plug in for resistance. We had that equation earlier here that the resistance is equal to the resistivity times the length over that cross-sectional area. So if I plug that in, that R is equal to the resistivity times L over A. Well, what can we do with the length in the equation? We can cancel that out, and I can say that I over A, that's the current per area, that is J. And then E simplifies down to the resistivity times the current density. So what happens when we have this junction here, when we have this wire that's going from one cross-section to the next, is that we get a buildup of charge at that junction. And we can find what that charge is by using Gauss's law, because we have a relationship for the electric field with Gauss's law. So let's walk through that together. If I have here two wires, one with a cross-sectional area A1, and then a bigger one with a cross-sectional area of A2, and I have this current I going through the wire, how can we find what charge is built up here? Well, we can look at the charge building up here. We can look at Gauss's law. So let's still review Gauss's law, right? The integral of E dot dA equals Q enclosed over epsilon naught. I'm kind of writing the line here so we can go down. Okay? Well, if we look at the junction here, what we want to look at is what is the change really in flux of those two. So remember, each side of these is flux. So if I turn this into E2, that's a bigger surface area, right? Times A2 minus E1 times A1, right? Let's find that difference in the flux of the surfaces. That's going to equal that Q that's going to build up at the junction over epsilon naught. And then we can say, well, what is E equal to? E is equal to the resistivity times the current density. So we can say this would be rho 2 times J2 times A2 minus rho 1 times J1 times A1 equals that charge buildup at the junction over epsilon naught. Okay, but what is, if we go back to our current density, J is equal to I over A. Well, here I've got J times A. So what's J times A? Well, that's going to be the current there. So I can say this is rho 2 I2 minus rho 1 I1 equals Q over epsilon naught. But can we have a different current in these two? No, it's the same current going through both of these. So I1 and I2 are really the same. So I can say this is the I going through that conductor times the difference in the resistivities over epsilon naught times epsilon naught is going to give us what that charge is that will build up at the junction. And so both of these topics, both drift velocity and current density, are very small topics. It's not commonly seen within the exam, but just it's still on the objective there. So still something that we want to go over with you. But back to kind of the basics in the circuit. How do we measure the voltage and the current in the circuit? Because knowing how we measure that is really important. So if we have a circuit, say we have a battery, we're just going to keep it simple with one resistor in it. If I wanted to know what the potential difference was across that resistor, then how would I measure that? We always want to measure potential difference in parallel. Okay, I'm going to draw you so you can see that better. Why do we want to measure? And the way that we symbolize that is a circle with a V in the middle. So any of those circles are going to tell us our meters. So a voltmeter is a circle with a V in it. Why do I want to measure it in parallel? And what should the resistance of if we're using an ideal meter, what should the resistance of an ideal voltmeter be? Well, if we look at Ohm's law, and we'll get a little bit more into the loop and junction rule tomorrow, but as we go around in one loop or one path in the circuit, well, if this is, let's say, a 5-volt battery, if I'm gaining 5 volts across my battery, well, I have to lose 5 volts throughout the circuit before I get back to the battery. So if we go around in one loop, voltage is always the same in parallel. So we measure that voltage in parallel because the potential difference across the meter should be the same as the potential difference across the resistor. But what should the resistance of this meter be? Should it be really high or really low? Well, we don't really want the current traveling through that meter, right? So because then the current is splitting and we have less current going through our resistor than what we really have if we didn't have our meter there. So we want the resistance in a voltmeter to be really, really high so that all of that current is still traveling just through the resistor. Right? So we're measuring voltage in parallel, and an ideal voltmeter has a really very, very high resistance. Right? If we look at this now instead and say, well, I want to know what the current through that resistor is, how are we going to measure the current here? Well, if I put the amp meter, so an amp meter is what measures current. Right? If I put an amp meter in parallel with that, now that would create another path of the current flow. So some of our current would go through the resistor and some of it would go through the meter. That's not really telling us what's going through just the resistor. So we always have to measure currents in series. It could be before, which will be my whole line. It could be before, or it could be after, but we're always going to measure the current, which is a circle with an A in it, in series. Now, do we want the resistance of the amp meter to be really high or really low? Well, that we want to be really low. We want the resistance of our amp meter to be pretty much zero, because otherwise we're increasing the resistance of our whole circuit, which again is going to decrease the resistance or decrease the current that's actually going through my resistor. And so we measure current in series, and ideally, an ideal amp meter has a very low resistance. And if we have multiple resistors in a circuit, we need to know how we can combine them to find the total resistance of our circuit. Usually we do that because we want to know what the total current being delivered from the battery is. And so let's look at two different ways, right? So here we have a series circuit. How do we know it's a series circuit? Because if my current goes through one resistor, it has to go through the other resistor. So one lane road, nowhere else will that current go, no junctions, no branches. So if this is a series circuit, if I want to find the total resistance, well, the rule is we add up all the individual resistors. So this total resistance would just be R plus R or 2R. So as you can see, as you add resistors in series, what happens to the total resistance? It goes up. So adding always increases the total of the equivalent resistance. That's important to remember. But if we add resistors in parallel, the rule for adding resistors in parallel is the inverse rule. So 1 over the total resistance equals the sum of all the inverses of the individuals. So for this one, 1 over R would equal 1 over, let's just call R1 and R2, but they're the same. So we'll just leave it as R. Okay. Well, 1 over R plus 1 over R. If we want to find what the total resistance is, well, if we add these together, we get 2 over R, but that's 1 over R. So we have to inverse it at the end. So we get R over 2. If you add resistors in parallel, you are always decreasing the total resistance. So those are things that you want to remember. If you're adding resistors in series, you're always going to increase the total resistance. And if you're adding resistors in parallel, you're always decreasing the total resistance. So we're going to look at some practice problems here with Roger, and then he's also going to talk to us about if we have non-ideal batteries and what that means.
Okay, great. Well, thanks, Kristen. So yes, we are going to look at some examples to try and get our brains around this crazy thing called physics. And so join me here, and let's take a look at this problem. Now, the first problem is a problem about resistivity, and remember, and resistance. And so remember, resistance is the current is something inherent in the material that makes it hard for the current to go through. And so we've got two different materials here, two different wires, if you will, and they're the same length. So we've got silver and we've got brass. And I'll tell you right now, silver is one of the lowest resistivities of any material. If you want to make a very, very conductive wire, make it out of silver. And as a matter of fact, during World War II, a lot of the silver in the United States that had been stored in Fort Knox was sent to Oak Ridge, Tennessee, to help make the magnets to create the material for the atomic bomb. So that was all that wire was made into silver. But anyway, I digress. Okay, so we've got silver and brass, and so we've got these two pieces, and they got the same length. So I'm going to draw the same length, but they tell me that the brass is much bigger. It's got 5 times the diameter of the silver, so it's a big old wire. Same length, but really, really fat. Okay, and so this distance here, this is R, or I should say, they talk about diameter. I don't like diameter, but I'll stick with diameter. And so here we have diameter, and here we have 5 times the diameter. Okay, much bigger. And then we know that the resistivity, as I said, the silver is very low, and the resistivity of the brass is 5 times the resistivity of the silver, and the diameter of the brass is 4 times. Sorry, I said 5 here, and that was wrong. I'm confounding my changes. It's 4 times the diameter, so this is going to be 4ds4. We'll put it over here as well. Okay, so this one's much thicker. This one is, but they're the same length, and so we want to compare the resistance. So as Kristen just showed us, there's a formula on your formula sheet for resistance, and that's the resistivity times the length divided by the area. And so let's go ahead and look at each of these. So the resistance of silver is the resistivity of silver times the length over the area of the silver, the cross-sectional area of this wire. That's what we mean when we say the area is the cross-sectional area. And the resistance of the brass is the resistivity of the brass times this length over the area of the brass. Now I'm going to replace this with 5 rho s times L, and then look at the bottom here. We said that the diameter is 4 times. Well, what does that mean about the cross-sectional area? Well, the relationship between the area and the diameter is square, right? You square the half of the diameter to get the area. And so let's go ahead, and if we're going to have 4 times the diameter, that means we're going to have 16 times the area of the silver. And so you can see that rho s LAS is the same as here. Rho s LAS. So RS, resistance of the silver, is 5/16 of the the resistance of the brass. Here we go. Is 5/16 the resistance of the silver, and so that's what we get. Okay. All right, next one. Now coming down here, we talked about Kristen just we were talking about the resistance of resistors in series and in parallel. So let's look at the circuit. So first of all, one of the things that we hope you're going to remember how to do, and you'll get better at during this time, is figuring out where the circuit is in series and where it's in parallel. And so sometimes I will tend to draw these in exaggerated ways to kind of show or to attempt to show a little bit better why they're the way they are. Now I want to remind you of or tell you about something. These pieces here, these junctions, it's very important when you're doing circuits to be able to use your imagination, because the junctions in and of themselves, it doesn't necessarily matter where they are. For instance, I could put this wire over here instead of over here, and if I did that, if I just got rid of this part of the wire right there and just had it look like that, well, it would still function in that same way as long as we had this joining here. And so this means that we can use our imagination to see what's going on. So I hope you'll see what I mean by this. So watch, I'm going to redraw this. Actually, I'm going to start up here, and here's my battery of 12 volts, and then I'm going to draw this first resistor of 10 ohms. I'm going to draw this second resistor of 10 ohms, and then down here I'm going to draw this resistor of 12 ohms. And so these are the 3 resistors I've drawn. Please take a look and see. Here's our 10 ohms, okay, 10, 10, and 12. And those are the 3 that I've just drawn. Now I'm going to draw the rest of the circuit. I'm going to draw now this branch of the circuit, but watch the way I draw it and see if it shows you something. Instead of drawing the junction here, I'm going to put it over here, and now we have 15, 10, and 15. And so what I hope you can see by this is these 3 resistors are in series. We have one after the other after the other. However, you can see now that they are in parallel only with this one, only with that one. And so that's what I wanted you to see in drawing it that way. So since these 3 see are now, we can say, okay, these are definitely in series, right? We go like that. Well, we just add them like this, resistors in series. And so we're going to add 10 plus 15, I'm sorry, 15 plus 10 plus 15, 15 ohms plus 10 ohms plus 15 ohms, and that gives us 30 ohms. I'm sorry, 40 ohms. All right, now what I'm going to do is I'm going to redraw this now, and I've got the 12 volts here, the 10 ohms, I've got these 10 ohms, I've got these 12 ohms, these three, 1, 2, 3, 1, 2, 3. But now I am in parallel with this 40 ohm resistor, or these three resistors that are 40 ohms. And what do I do with this? Well, when you have resistors in parallel, we know that 1 over RP is 1 over R1 plus 1 over R2 plus dot, dot, dot. We have to add their inverses to amps. Now, the way I always do this, and I tell students, please use your calculator for this, because when time is of the essence, you don't want to be messing around with fractions. So what I'll do is I'll say we have 10 inverse plus 40 inverse, and that's how we're going to do that problem. Now, I'm a big believer in arithmetic. I think it's good to be strong in arithmetic, so it's good that you can do 1/10 plus 1/40 and take the inverse of that on the paper. And so we have 4/40 plus 1/40 inverse, and so that's going to be the inverse of 5/40, which is going to be 40/5, which is going to be 8. Now, that took some time, right? That took a little bit of time. So please, I'd like it if you got better at using your calculators, okay? And so, please use those calculators that you spend so much money on. And look how easy this is to do. You're going to get really good at just plugging this in super fast, and you're going to plug in 10 inverse plus 40 inverse, close parentheses, inverse. And that's how you're going to do it really fast. Because remember, you only have a certain amount of time to answer these questions, and so that's our 8 ohms there. All right, I hope that wasn't too easy for you. All right, good. So now we can see that these two together make 8. So we're almost done. I'm going to go back this way now. You draw a lot of pictures when you do these circuits. And so now we have 10, 8, and 12 all in series. So 10, 8, and 12. This 10, 8, and 12. And remember, 8 was all of these together. That's 8. And so 10 plus 8 plus 12 gives me 30 ohms. And so that's our answer. And that's how you do that problem. Again, you're going to find these get really easy with a little bit of practice, and you're going to find that they're a lot of fun as well. All right, now Kristen was telling us about something called internal resistance. And I meant to go grab a battery, but I didn't. But oh wait, there's a battery right here. Okay, I knew I had one close by. All right, let's see. Now I'm going to go ahead and show you this really close. So you guys have seen batteries before. It's not your first rodeo here. Okay, there's our famous battery. Now, if you look at the battery, every battery has on it a voltage, and that voltage for this is a AA battery is 1.5 volts. Okay, now that is called the EMF, electromotive force. We have a special name for that. But that specifically means the amount that the battery is pushing its pressure, its voltage, when it's not doing anything. Okay, this is the so the EMF that is stamped on the side. This is what is written stamped on the battery. Okay, that is the unloaded potential difference, or the unloaded voltage. And we say it's unloaded because it's not doing anything. It's not pushing current. We're not loading it up with a job to do, basically. Now, all batteries have this resistance inside of them. It's built into the physical nature of the battery. It's got chemicals in there. This is not a chemistry class, but if you studied chemistry or electrochemistry, you know that it's a complex reaction that's happening in here, and there's always resistance involved. Now, once we start pushing current in this circuit, right, the current starts to go through this circuit. Once that starts to happen, the internal resistance in the battery, notice we draw this tiny little resistor. Now, listen, there's not a little resistor in here. You won't crack it open and find it. There is the internal resistance we're talking about is about the physical, chemical nature of what's happening in the battery. That it's always there. And so that internal resistance is always there. Most of the problems that we're going to do in AP E&M, AP Physics E&M, do not have internal resistance. Again, this is kind of a very small concept, or not treated a lot, but once a year we do see a question about internal resistance. So we wanted to make sure you know about it. So let's look at this. It says ideal batteries, we ignore their internal resistance. And again, 95% of the problems that you do in this class will be ideal batteries. There will be no internal resistance to talk about. But let's look at this problem and see if we can figure out what this one would be like. Now I'm going to draw this similar to the problem we just saw, and I'm going to draw this little resistor inside. Usually that's denoted with a tiny r. And then I'm going to have this other big resistor. And the reason I have this big resistor is you're not allowed to connect the volts of a battery, the terminals of a battery, without resistance on them. Otherwise, you cause a short circuit. Okay. So here's our battery, and remember, there's no little resistor in there. This is just my symbol for it. And so it's a 12-volt battery, the EMF. That's what's stamped on the side of it, right? And we hook it up to this circuit. And remember, we saw that the ammeter goes in the circuit. It goes in series with the circuit, and this ammeter is reading 0.5 amperes. Now that means that everywhere in the circuit, the current is 0.5 amperes. 0.5 coulombs per second are going past this point. 0.5 coulombs per second are going around this corner. 0.5 coulombs per second are going here. This is 0.5 coulombs per second everywhere in the circuit. Oh my gosh, I better speed up. Sorry, going too slow. All right, so now we got to find the we're going to find the resistance, internal resistance of the battery. Now we know that we've got a 12-volt battery when I don't hook it up to the load, but when I hook it up to the load and I put a voltmeter on here, I see that it says 10 volts. So that means I've got a voltage drop delta V of 2 volts in this internal resistor. And since I know the current is the same everywhere, I know that I is equal to V over R. That means that R is equal to V over I. And so then we're going to have 2 volts. That's our potential difference divided by 0.5 amperes. And that's going to give me 4 ohms. And so notice that's a tiny resistance that's consistent with what we would think in a situation like that. Okay, Kristen, sorry to take too long. All yours.
No, that was fine and very impressive at the end there. So we're going to do one problem today. It's a lab-based problem. The parts that we're going to spend a little bit more time on, and parts that we're going to kind of go a little bit quicker on because you might not be asked to actually make a graph this year. You're going to have to analyze a graph, but actually physically drawing and graphing is not going to happen this year. So that part, the question we're going to go a little bit quicker on. But the other parts we're going to really talk about because there's a lot of other good conceptual things going on. All right, so we have a circuit here that is shown consisting of a source of variable EMF, an ideal ammeter A, ideal voltmeter B, a resistor of resistance R, and a sample of wire with resistance R. So a couple of things here. When you see this symbol of the arrow on an element, we see this sometimes with resistors. We have a resistor that's got an arrow. What that means is it's adjustable or variable, right? So your dimmer switch in your dining room, those are variable resistors. Okay, but this time we have a variable power supply. I can adjust the voltage on that. We have a resistor, and then we also have a sample of wire. And really, wires do have resistance, right? Small amount. And so we want to look at the situation. We have an ideal voltmeter and an ideal ammeter. We talked about what that means earlier, right? We have an ideal ammeter, very low resistance. Ideal voltmeter, very high resistance. So if we look at the first part, A, how does the current through the wire sample compare with the current through the resistor? Take just a second. If we look at the circuit, we want to know how does the current through our little resistor compare to the current through our resistor, not necessarily little resistor. We don't know what the resistance of the wires are. It could be a really high resistivity material. But how does the current through the wire compare to the current through our resistor are? And you guys all know this, right? What kind of circuit is this? Remember, this is really just our meters. These are not physically a part of our circuit. So if we're looking at our actual circuit and we're going around the circuit, we can see that this is a series circuit. So what should be true about the current in both of those? They should be the same. Okay. How would we justify our answer? We will justify our answer by saying that the circuit is a series circuit. And what does that mean? That the current is the same everywhere in that circuit. Okay. But what about the potential difference? How does the potential difference across our resistor compare to the potential difference across our wire sample? So is the potential greater across the resistor? Is it greater across the wire sample? Is it the same in both? Or does it depend on the resistance of the sample? Well, if we're using Ohm's law and we want to know the potential difference across either one of those, and the current is the same, then what does the voltage drop depend on? It depends on the resistance. So which resistance depends on the resistivity. So we don't necessarily know if it's going to be greater through the wire sample or greater through the resistor. Because it depends on the resistivity of the wire. If the wire has a very low resistivity, then we could say that it would be greater through the resistor. But if it has a greater one, then it could be greater through the wire. We don't know. Okay. Next part. With the sample of wire in place, the EMF of the source is set to a given value, and the current through and potential difference across the resistor are measured. This is repeated for several trials of EMF, and the data are recorded in the table below. Right, so we're going to change the voltage on our power supply. We're going to measure the potential difference across the resistor. We're going to measure the current in the circuit. So we've got what do we want to graph in order to be able to determine what the resistance of the wire sample is. So this is one of those where we're trying to figure out what are we going to graph to get something else. So what do we have to do? We have to come up with a relationship. We have to come up with an equation. Always when you're trying to graph something, you got to start with your equation. So what would be an equation that we would use for the situation? Well, if we go back here, and again, we're going to talk a little bit more about loop and junction rules and Kirchhoff laws tomorrow. But if we look at the circuit and if we take these as two separate elements and they're in series, well, we know the potential gains should equal our potential losses. So we're gaining across the battery, but we're losing potential. We have a potential difference drop across our resistor here, and we also have a potential difference across the resistance of our wire. Right? So we have two losses and we have one gain. So if I were to write an equation, I would say, well, the EMF of the battery has to equal the voltage drop across my resistor big R plus my voltage drop across my little r. Right? So if we know what the voltage drop across our big R is, and we know what the potential difference of the battery is, the EMF of the battery, then really I could say, well, the EMF of the battery minus that potential difference across my big resistor will equal the potential difference across my little resistor. And what can we plug in there? We can plug in Ohm's law, and we can say that the current through times that resistance of the wire. So this is kind of what we call a working equation, right? This is what I'm going to look at and what I want to graph. So we identify what are variables, what are constants, right? So the EMF, well, that's variable. The resistance, that's a constant. That voltage drop across my resistor, that's a variable too. And my current is a variable, right? So really we've got kind of three variables here. But if we're going to solve and we want to know R, well then let's just bring my current over and say that the EMF minus VR over I is going to equal little r. So whatever's on top of my equation is what I'm graphing on the y, whatever on the bottom is what I'm graphing on the x, whatever's left on the right side is my slope, because we've got y over x always equals slope. So what would we graph on the vertical? We graph the EMF minus that voltage drop across the resistor. On the x, I would graph my current through the circuit, right? So horizontal is going to be current, and vertical is going to be the EMF minus that voltage drop. And then it's nice if I do it that way, because if I were to graph it, that should be a straight line, and the slope of that is going to be what? R. That's the only thing that was left on the right side of my equation. So we won't take time to do that because you won't be asked to do that on exam, and just for time's sake, because I really want to talk about this last part. If we graphed it and found the slope is our resistance. We could use that to get the resistivity, because resistance is equal to resistivity times length over that cross-sectional area. So this is the slope, right? They're giving you the length of the sample, they give you the radius, and so we can use that radius to get the area. Okay? But G is what I really want to focus on, and I want you to take a second to really think about, because this is something that I could predict and would probably bet a lot of money that would be something that it would be really good to ask, because this is always what we like to ask on the experimental type questions is what happens if your results are not what you expect? What does that mean? Can you reason through what happens, right? What assumptions are you making in your experiment where something changed? What does that mean? Okay, so in part GI, suppose the ammeter used to collect the data was not ideal. Would the actual value of the resistance of the wire sample be greater than, less than, or equal to that calculated in part E? So I'm going to give you a minute. I'm going to think about what does that mean? What would that change? And would our actual value of the resistance of the sample be greater than, less than, or equal to what we just calculated? Okay, what are our predictions? So what would that change? Let's think it through and reason through it. If our ammeter is not ideal, what does that mean? That means our ammeter has resistance. So this ammeter would have its own resistance. So what would that do to the total resistance in the circuit? Well, what that means is, well, I used to just be saying the resistance that I calculated was just the wire. Now I really have that resistance being the R of the wire plus the R of the meter. Right? What does that mean the actual resistance of my wire was? Well, it's got to be less than what we just calculated, because we were taking everything, all that resistance as being from the wire, but some of it's actually coming from the meter, so the resistance of my wire has got to be a little bit less. Right? And now what if instead our voltmeter is replaced by a voltmeter that is not ideal, and the experiment is repeated with the readings of the ideal ammeter? Right? So I'm going back now, so my ammeter is now ideal again, but my voltmeter is not ideal. So would the current reading through my ammeter be greater than, less than, or equal to that than we had before when this was ideal? Right? So we're changing out that meter for a non-ideal meter, increase my current in my circuit, decrease my current in the circuit, or keep it. So again, think about that for a second. What would that change and what would that mean? Okay, if you want some more time, pause it. Let's discuss. Well, our ideal meter has a resistance essentially of infinity, right? But now it is not infinity anymore. So now this has some resistance that is not infinity. So if we put in another resistor here in parallel with this resistor, what does that do to the equivalent resistance in my circuit? What did we say earlier? If you add resistors in parallel, the total resistance in our circuit goes down. So by adding that resistor of the voltmeter in parallel with our resistor R, we're going to decrease that equivalent resistance. But without changing the EMF, if I decrease resistance, what happens to the current in my circuit? It's going to go up according to Ohm's law. If resistance goes down, current's going to go up for that same potential difference. So we're going to have a greater current now through my ammeter because I decreased the resistance of my circuit by adding in that non-ideal meter in parallel with the other. Okay? So I really want you to think about these, and if you want, redo them, take more time to think about it, make sure they make sense, because this I think is something that's really, really important, a skill that you need to have, especially this year. Okay, that is all we have for today. So we should be able to talk about what resistance, voltage, and current is, be able to find resistivity or resistance, know about driven velocity, and about current density. So tomorrow, Roger, what are we going to do?
Tomorrow, we're going to start doing some slightly more complex circuits. We're going to start to look at finding the current in each branch of the circuit and the voltage drop across each part, across each resistor.
Awesome. I love doing that. It's like puzzles, like doing a Sudoku puzzle. Okay, well, tune in for that tomorrow, and you guys have a wonderful night.
Well, good evening and welcome. You are tuned into AP Physics Live, or AP Live, and tonight, my name is Roger Siegel, and we are going to be reviewing for the AP Physics C Electricity and Magnetism exam. I'm coming to you live from Sarasota, Florida, and as always, I have my friend Kristen Gonzalez Vega in Texas. Hello, Kristen.
Hey, Roger. Welcome, everybody. Happy Friday.
Absolutely. Happy Friday. I'm glad it's Friday. I'll bet you are too. Well, as I said, we're reviewing for the AP Physics C Electricity and Magnetism exam that's going to be on May 11th, and we're happy to help you get ready. We've been, tonight is our 15th night, or the end of our third week of review, so we've been reviewing for a long time, and got one more week of review next week to complete the curriculum. And then the following week, Kristen and I are going to be doing mock problems with you during the week, just as you would do mocks if we were in school. We've got mocks for you, and we're going to give you time to do them, and we're going to go over them with you and get you ready for the exam. All right, let me get into what we're doing tonight and start sharing here, and we'll get moving, get this boat moving. Here we are. So today, as I said, my name is Roger. Tonight we're doing more circuits, current and resistance, section 3.1, and I'm coming to you from Sarasota, Florida, where I teach physics, and Kristen is coming to you from Frisco, Texas. I did mention the time of the exam. I want to point out the date. I did mention it was the 11th. I want to mention the times. You can see that right here. Make sure that you have your computer hooked up. Make sure that you'll have a quiet place. Talk to whoever you need to, and if you need to make special arrangements, start looking into that now so you can be ready to take this exam and to be successful. And so let's go ahead and move on, see what's next. Here we are. This is, as I said, what we've been doing. This is our third week of review and one before the last, and we are finishing up with conductors and capacitors, and now we're doing circuits, current and resistance, Ohm's law. Okay, so today we're going to look at Ohm's law again, and we're going to talk again about resistivity, and we're
going to look at different geometries of material and see how that affects the particular resistance of the different resistors. And we're going to do some problems that have to do with internal resistance. Also, tonight we've got 2 problems that focus on labs. And Kristen and I don't know what's going to be on the exam. I wish we did. But we do get a sense of what AP is telling us. And so we think these are really good problems to help you get ready. All right, so what did we learn last night? What are we reviewing tonight? And we're going to start as resistance. So remember, resistance is what is blocking current, what impedes the current. The higher resistance you have, the less current will flow, and the less the charges will flow. Remember what resistance is, the symbol R, and I think we talked about this last night. Yeah, of course we did. The units for resistance are ohms, so we'll look at the different resistance ohms. We talked about current last night. Current is the flow of charge through a wire, and current is symbolized by the large letter I. We measure it in amperes, and amperes are coulombs per second. All right, and I really want you to think about that. When you say amperes, you might even say coulombs per second. And when I teach, I'm going to do that because I want to remind myself what is an ampere, what's really happening here, and I want to actually imagine charges moving through the wire. Now remember, they're moving very slowly, on the order of millimeters per second, okay, in most wires, but they are moving nonetheless through the wire. And so we talked about resistance. We'll see that again, the size and the shape of the material. We'll look at this formula again tonight, and that is the formula resistance. And the resistance of a substance or of an object is equal to its resistivity, rho, times its length times its area. We're also going to use Ohm's law again tonight. And so Ohm's law says that V is equal to IR, and we also very often will look at I is equal to V over R. And so Ohm's law is articulated either way. And we'll talk about what it means when these things change and how our circuits get affected. The other thing we're going to look at again tonight is internal resistance. The idea that the battery that is powering your whatever, your phone or your flashlight, when you hook it up to a voltmeter and you test it, it says 1.5 volts or 1.3 volts, and that matches the voltage that's printed on the side. That's called the EMF. But all batteries, except for the ideal ones that only exist on paper in physics classes, all batteries have internal resistance. And so tonight we're going to look at that concept of internal resistance, how we can measure it, how we can account for it when we do experiments. And so remember, the internal resistance is something that's in the battery. It has to do with the physical and chemical realities of how a battery works, which we don't go into in this class. You probably go into it more in a chemistry class. But the internal resistance is there, and so we're going to do some problems identifying it and mitigating for it. Okay, so as I explained, tonight is a continuation of last night's work. We're not really introducing any new concepts. We're going to continue to develop the concepts we did last night. And so it's kind of early, but I'm going to throw it over to Kristen I was going to say Plano, but she doesn't live in Plano. That's near there. I'm going to throw it over to Kristen in Frisco, Texas, and she's going to do some problems, and then we'll do some experimental ones after that. Take it away, Kristen.
All right, thanks, Roger. So we're going to look at some multiple choice questions here so we can kind of talk about the concepts going on. And the first one is we have 2 conducting cylindrical wires are made out of the same material. We have wire X and wire Y, and wire X has twice the length and twice the diameter of Y. So we can draw these out. We've got Y, and we've got X, and X has twice the length and also has twice the diameter. Now, but they're made of the same material, so they both have the same resistivity. We want to know what the ratio of the resistances is going to be. So we know resistance is resistivity times the length over area. So I'm going to write X in terms of Y first. So the resistance of X, we can figure out it has the same resistivity, right? So we can really put it as 1 times the resistivity of Y, and the length is twice times the length of Y. And now let's look at the area. If we were to find that cross-sectional area here, which is pi r squared, then really if this has twice the diameter, that means it has twice the radius, and therefore 4 times the area that Y has. So if we were to find that resistivity, the resistance of X is going to be 1 times 2 over 4, which is 1/2. So our X is equal to half the resistance of resistor Y. So if we want a ratio of our to our Y, well, I'm going to bring Y over by dividing, and I'm left with the 1/2. So our X has half the resistance that our Y has. Now let's look here at these. So you got 5 different shapes here of resistors. The lengths and the cross-sectional areas are indicated, and they are again made of the same material with the same resistivity. We want to know which of these 5 conductors would have the greatest resistance. So take a second, tell me what you get. If I want a big resistance, what kind of length do I want? Short length, long length. If I want a big resistance, I want a big number on the top. So we want one that's going to be long, right? So that's going to get rid of A and C and E. And if I want a big resistance, what kind of area do I want? Well, since area's on the bottom, there's an inverse relationship. I want a small area. So D changes. It starts with a big area, then goes small. So if we look at D, that's going to have an even greater resistance than D does. So if we want a big resistance, we want a short skinny wire. If we want a small resistance, we would want a short fat wire. What if we look at this one? We got a 12-volt storage battery with an internal resistance of 2 ohms being charged by a current of 2 amperes as shown in the diagram above. Under these circumstances, a voltmeter connected across the terminals of the battery will read. So if we were to define that potential difference across the battery, what we're really essentially looking for is what we call terminal voltage, right? So if I take my battery out of my route and I just measure what the potential differences across there will be a potential difference, even if it's not in a circuit, right? It's a 1.5 volt battery, then it would read 1.5 volts randomly out of the package. But the minute I put that into a circuit and there's a current passing through, then that voltage drop is going to change. And what that reading is across that battery once it's out in the circuit is what we call the terminal voltage. I like to kind of call the useful voltage, what you're actually getting out of that battery when it's in the circuit. So we're looking for the terminal voltage. And the way we can find that terminal voltage is the EMF of the battery, what we get when it's not connected to the circuit, minus whatever that voltage drop of the internal resistance would be, right? So another way we could write this is we could say, well, we've got a battery and we've got that little resistor R, right? That internal resistance of the battery. So the terminal voltage would be the EMF of the battery minus whatever the voltage drop or potential difference across that internal resistance would be. So I could say that's times IR. And then we can plug in the EMF of the battery is 12 volts. The current is 2 amps times our unknown resistance R. And if we put in that the terminal voltage is what we're looking for, the internal resistance is 2 amps. Sorry guys, thinking ahead, there's no we're going to do in a second at the reverse. So this is what we're looking for, and our resistance is 2 ohms. So we got our 2 amps times our 2 ohms, that's going to give us 4, and our 12 volts minus our 4 volts is going to give us 8 volts, which is B. Okay, back to resistance. We got 2 resistors, same length, same material, but connected in series to a battery shown above. Resistor 2 has a greater cross-sectional area than resistor 1. We want to know which of the following quantities has the same value for each of these resistors. So it's going to be the same for resistor 1 and resistor 2. So read those answer choices and let's see what you get. Hopefully what should stand up there pretty quickly for you is the current, because these are in what with each other? Series. And we know that if the current is flowing out through the battery, the positive side of that battery, well, as we go around, there's nowhere else for that current to flow. So if we have no junctions or no other branches in our circuit, then the current has to be the same everywhere in there. Let's look at some other things on why these other ones are not correct, right? Let's look at D. Why is the current per unit area not correct? Last night, we talked about what that current density is, right? That J is equal to the current per cross-sectional unit area of that. Well, there's cross-sectional areas are different, right? But their currents are the same, so they cannot have that same current density. Right? The resistance, why would the resistance not be the same? Because they have the same length and they have the same resistivity. If their area is different, the resistance has to be different, right? Okay, what about the electric field strength within the resistor? That one's maybe not as obvious as some of these other answers are and why it's wrong. Another equation that we derived last night was that the electric field within a conductor or wire, whatever it is equal to the current density times the resistivity. Well, here the resistivity is the same, but we just determined that the current density J is not the same. So they can't have that same electric field going through that, right? And the potential difference between the two ends. So if I were to put a voltmeter across each of these, why is the potential difference across each resistor different? Well, the resistance is different. So if the resistance is different and we used Ohm's law, if we know they have the same current current passing through them. But we know that I, or number one, or I, whatever you want to call this, that resistor, since it has the same length but a skinnier cross-sectional area, it will have a bigger resistance. And so since it has a bigger resistance for the same amount of current, it would actually have a greater potential difference across it than number two does. Correct? What about this one? The EMF of a battery is 12 volts. When the battery delivers a current of 0.5 amperes to a load, the potential difference between the terminals of the battery is 10 volts. The internal resistance of the battery is, I'm going to draw it out. I want you to think about it here for a second, how you can find that. Okay, so we have our battery here. Remember the way we indicate whether it has internal resistance or not is we have this little resistor R, and we've got this dotted line drawn around our battery. And so we want to know what is the internal resistance of this battery. So let's look at what we know. We know the current. I know that the EMF of the battery is 12 volts, and I know that the terminal voltage, potential difference across the battery when it's in the circuit, is equal to 10 volts. And so if we want to know what the internal resistance is, well, we go back to what we were saying before. The terminal voltage is equal to the EMF of the battery minus that voltage drop of that internal resistance, which is equal to I times little r. Still using Ohm's law right here. So this is the voltage drop across that little resistor. So we know now the terminal voltage is 10 volts. 12 volts is the EMF of the battery. 0.5 is our current, and we want to know what our internal resistance is. So if I find that difference between these, that gives me 2 volts. And so then if we solve for R, 2 divided by 0.5 gives us 4 ohms, which is E. Okay, let's do one more of these with internal resistance. So we've got our circuit here. We've got our battery, 20 volts is the EMF of that battery. There is an internal resistance, and we have two resistors, a 30 ohm resistor and a 60 ohm resistor, and we want to know the current is 0.8 amperes. So what is that internal resistance? So again, I'm going to give you a couple minutes here to think through how you would do this. What are your steps you're going to have to take to get that internal resistance? Where I would start is what I know. I know that the total current being supplied by that battery going through my circuit is 0.8 amps. And I know the EMF of my battery is 20 volts. So I would use Ohm's law, right? We got to find what should the equivalent resistance of my circuit be, right? Let's find what that equivalent resistance is. So if we use Ohm's law and we solve for R, well, 20 divided by 0.8 is going to give me 25 ohms. So my total resistance of my circuit should be 25 ohms. Well, let's see what these two resistors here in the circuit would give us for an equivalent resistance. So we got to recognize, are these in series or are they in parallel? And if we look at them, right, we've got this junction right here where current could split one way or the other, which means these resistors are in parallel. So how do we combine resistors in parallel? Well, 1 over that equivalent resistance would be 1 over 30 ohms plus 1 over 60 ohms. I make this 2 over 60, then I get 3 over 60, but that's 1 over R. So again, we got to put that over, and we get this is 20 ohms. So this portion of the circuit has a total resistance of 20 ohms, but I need to have 5 ohms total for performance. Okay? The way we treat that internal resistance is we treat that it's in series with the battery, right? So we treat it like it's almost a separate resistor that's in series with the battery. So if this is in series, we want to add on the resistance for it. So we want 20 ohms plus whatever our internal resistance is equal my 25 ohms, which gives us 5. Okay, so there's some practice with that resistance and with internal resistance of batteries. So let's take a look at a couple of lab-based response problems and give it back to Roger in Florida.
Sorry. All right. Thank you so much, Kristen. Well, I want to tell you, Kristen, and anyone else who's listening, that we got some good storms coming through Sarasota right now. So if I cut out, you're going to have to take over. All right. All right. Just so you're ready. I just looked at it. It's brutal, but we're safe in here. All right. Great. Now, let's go ahead and share. Let me share my screen here, and I'll show you something I've been working on. I think you're going to enjoy. And that is, again, the FET simulation. And this is a FET simulation that Kristen had showed you last night. And I wanted to bring it up again because it is so useful and so great for trying to understand these concepts of electricity. You know, one of the hardest things about teaching E&M is so much of it is not visible. And so we have to have so many proxies and metaphors and stand-ins, and they're important. And it's important to know them. So here, let's take a look at this. So this is my circuit. I've got the different. Let me just turn some things off here. I'm going to turn off the labels here. And so let me see if I can turn off. Okay. So what I have here in this circuit is I've got a battery over here on the left. I've got two resistors over here. I've got a switch and I've got an ammeter. And then over here I've got a voltmeter. And I have purposefully drawn this battery in a vertical orientation and these resistors in a downward orientation. Not because it has anything to do with how they function electrically. You can have this upside down, right side up. It doesn't. But how they function conceptually. If we can think of potential as a rise in potential, we use those words, or a drop in potential. If we can think of that and use the gravity as a stand-in, kind of a bridge for us to understand how this works, it's often very helpful. And there's other things that we can do to understand how this works, and that's why the simulation is so useful. So one of the things I can do is I can turn on. I think one of the things I'd like to do first is change over to the symbols that we would draw if we were drawing this out, because it's important to know that this is what it looks like if we were building it if we were building it in our lab. We'd have a battery, and these resistors actually look like this. The ammeter looks somewhat like this and this. But when we draw it like this with resistors and batteries like this. So here's what we're going to do. Let's go ahead and I want to measure the resistance across the voltage gain across this battery, and I want you to notice that I can control the resistance in the battery. Now, yesterday we said that ideal battery has no internal resistance. All right. Well, let's look at this battery. I'm going to make it ideal. I'm going to make its internal resistance 0. And so now there's no current. I'm going to say show current. Oh, let me show you one other thing. Watch. When I close the circuit, the switch, that shows these charges marching through here, which is, by the way, a little bit faster than they normally march, but that's okay. And so you can see that. Now, notice over here, I can choose conventional current. And because of a mistake of history, something that Benjamin Franklin said, or the way he notated it, he switched the positive and negative. So we have this conventional current of positive charges flowing out of the battery, out of the positive end of the battery, and returning to the negative end of the battery. That's not what's happening. This is more consistent with what we have. But when we do physics, when we do electrical engineering, most of the time we talk about conventional current, positive charges going positive to negative. Now notice that when I open the switch here, the voltage is 9 volts, and when I close the switch, the voltage is 9 volts. And there's a voltage drop across this resistor of 4.5 volts when that current switch is open, and there's a voltage drop across this resistor of 4.5 volts when the switch is closed. And so that's what we would expect. Okay, but watch what happens now when I put a little bit of resistance in the battery. I'm going to put about 2 ohms of resistance, similar to the problem you did a few minutes ago. Now I have 9 volts, but watch what happens when I close my switch. I only have 8.18 volts. What happens? Well, there is an internal resistor here. You can't see it. It's not actually in there, but it functions as a resistor. And that internal resistor is causing a voltage drop, and we can see the voltage drop is exactly 9 minus 8.18, or that's going to be 8.82 volts. We have the current, and it looks like we've got there's our 2 ohms right there. So that's where we can see the voltage drop. All right. I really want you guys to go to this site, PHET circuit analysis. Play with this. Try some different things. It'll make a huge difference for you. All right. Let's look at some of those AP problems over here. So this is the so-called lab questions. And so lab questions is a question where they actually give you data and they ask you to draw conclusions and comment on the lab. So this is a physics student wishes to measure the resistivity of slightly conductive paper that has a thickness of 1.0 times 10 to the negative 4 meters. The student cuts a sheet of the conductive paper into strips of width 0.02 meters and varying length, making 5 resistors labeled R1 to R5. So the student has 5 strips of paper of different lengths, not 1 but 5. And using an ohm meter, which is something that you can use to measure the resistance, the student measures the resistance of of each strip, and the data are recorded below. And so here's the different resistors, and here's the different lengths. And so it says use the grid below to plot a linear graph of the data points from which the resistivity of the paper can be determined. Include labels for both axes. Draw the straight line that best represents the data. All right, now let's take a look at this. I did not include this graph because I didn't want to do the graph. I want to take our valuable time drawing out the graph. I think certainly graphing is something that we certainly don't know, but we imagine that you won't be asked to graph on this year's exam. But we do imagine that you could be asked to comment on graphs or to talk about graphs or to modify graphs. So we don't know. We'll see. But let's look at this. It says we're going to plot a linear graph. Now my question for now, what I want us to look at right now is what would we plot? Okay, now we're looking for the resistivity. That's what the whole big enchilada. That's what we're looking for. And in every graph we have the independent variable usually on the x-axis and the dependent variable on the y-axis, and that's y and this is x. And so we say, well, what can we make up that will fit into this form of our best old friend y equals mx plus b, a linear graph? And so we look at this and we say, well, our relationship that we're interested in, the actual relationship is we know there's only one formula that has resistivity that we've studied. So that's going to be that R is equal to resistivity rho times L over A. And so we ask ourselves, what should we plot on the y-axis and what should we plot on the x-axis? Well, when we're doing a graph, we're looking to plot something on the y-axis like that, and then we say, well, what's our dependent variable? What are we changing? And you can see that what we're changing is the length, and the independent variable is the resistance. That's what is changing because I'm changing the length. So my independent variable R goes on the y-axis. My dependent variable is going to be the length. Now I have a choice. I can either graph the length or I could graph the length end divided by the area. Now the way this graph is this problem is written, it seems fairly obvious that they just want you to do the length. Okay, but the reason I mention it is because there's a question later on, and this is what we think could be something that could be asked. We think this is a very conceptual way that AP likes to ask questions, so we threw it in here. And so let's assume that I'm going to go ahead and go with the first one. I'm going to go with measuring, putting the length on the x-axis, and that's going to be measured in meters over here. And over here, let me make sure it's meters. And over here, I'm going to have the resistance, and that's measured in ohms. Always label your axes. AP gives usually 4 points for every graph that you draw, so if they ask you to do that. And so what we're going to get is we're going to get a linear graph. But let's look at the important question. What is my slope? Okay. And so if you look at this, I'm going to rewrite this. I'm going to say R is equal to, and then I'm going to write rho over A times L, and then right below this, Y is equal to mx. And look at that. So my slope is rho over A. All right, and that's how you would do this problem. Is you would set that up and you would graph that. Now look at this. After taking your data, you learn that due to a calibration error, the actual thickness of your paper is. Let's see. Hold on a second. I'm going to back up for a minute. I think I brushed over something a little bit too soon. I want to make sure that I make one correctly. So notice that your slope is rho over A. So if you were asked to find the slope, maybe AP is not going to have you graph something this year. Maybe they'll give you a graph and say what is slope. I don't know. And so you would find that that's going to be your delta R over here, and that's going to be your delta L. And then of course what you're going to do is you're going to say your slope is equal to rho over A. So you're going to say rho is equal to your slope times A. All right, let's go with that. Now let's move on down to the next question. It says after taking your data, you learn that due to a calibration error, the actual thickness of your strip of paper is 1.5 times 10 to the minus 4. So this is what you thought it was. You thought it was 1.0 times 10 to the minus 4. It's actually 1.5 times 10 to the minus 4. And if you've done enough physics labs, I'm sure that's happened to you. Usually it's a factor of 10 that we drop or we lose, so it's not unusual. Explain how your graph would look different when you correct it with a new thickness, or explain why it looks the same. Now, hopefully, what you would be able to say is, look, if you haven't graphed the area, which is what the thickness goes to. Let's kind of get some geometry here because maybe I'm going over this too much. Imagine this is your paper. All right, now your paper, the width, all of these widths are 0.02 meters. That's 2 centimeters, 2 centimeter strips. But the thickness, that's very tiny right here. And then here's our length here. So it was hard to see the difference between 1.0 times 10 to the minus 4 and 1.5 times 10 to the minus 4. Although come to think about it now, you feel the difference. But all right, but anyway, it was measured wrong, calibrated wrong. And so what's different about it? Well, here's the question. When you graphed your data, did you have the A in there, the area? And the area, remember, is the thickness here, this much, times the width. That's my cross section. I'm sorry, not this distance, but there's my cross sectional area right there. That's cross sectional area. And so did I have it in my graph? Well, if I graphed the resistance and the length and I didn't graph the cross sectional area, it's not in my graph. So I would say, the way I have it, that my graph is the same because the width doesn't get graphed. And then I would say maybe colon, it is used after I find the slope. I'm trying to convince the reader, and that's fancy AP name for the grader. I'm trying to convince the person who's going to grade my test that I understand that wasn't a part of the slope because I didn't put it in there. So anyway, that's what we thought about that one. Let's take a look at one more, and then we'll set you loose. It's Friday night. I'm going to get places to go and things to do. All right, so we've got this other problem here. We've got a student performs an experiment to determine the EMF and the internal resistance R of a given battery. The student connects the battery in series to a variable resistance R with a voltmeter across the variable resistor as shown in the figure above, and measures the voltmeter reading V as a function of the resistance R. The data are shown in the table below. And so here's our trials, here's our resistance voltage. And so what we're doing is we're varying that. That is our independent variable, and we are measuring this, and these are just numbers that are carried over. Okay, so they've done some math for us, but this is my independent variable, and this is my dependent variable. All right, so first it says derive an expression for the measured voltage V. Express your answer in terms of R, script E, little r, and physical constants as appropriate. All right, so let's do that. All right, so I want to kind of telegraph something that we're going to be getting into next week, and that is Kirchhoff's laws. And if you remember Kirchhoff's loop rule, it says that the sum of voltage gains and drops around a closed loop has to be 0. Now let's look at this loop. We always start at the battery here and we go this way, and then we will. I'm going to do this in another color. So imagine my current is moving around the loop this way through this resistor and then back. Okay? And this is a series circuit, which means my current is the same everywhere in the circuit. Now you might want to ask me, Roger, why is there no current this way? You've hooked this up to this voltmeter. Now that's going to come up later too, but I want to tell you why. Unless you hear otherwise, we assume that all voltmeters have infinite resistance. They are ideal voltmeters. Now all voltmeters, no voltmeter has infinite resistance, but most of the time it's a fine approximation. I'll talk about when it's not a little bit later. So that's our current, and it's going through there. And so they want us to put, we're going to use the loop rule to go ahead and figure out what this expression that they've asked us to find. So let's go ahead. We'll say that the voltage gain is right here. Okay, that's my voltage gain E. And then as soon as I pop out of there, I have a voltage drop across little r. It's a resistor, so I have a voltage drop. And then I have a voltage drop here across big R, and that all has to then come back to the battery, so that has to equal 0. Now let's say what these things are. We learned yesterday that due to by Ohm's law, and we said the current is the same everywhere. This is going to be I little r, and this is going to be I big R, and that's going to equal 0. Now you might ask me, well, Raj, if they asked you to find the voltage here, this V, right? This is V here. I'm going to actually let's kill the R because that's confusing. You want to find this V? Why did you change it to this? The reason is you'll see why I want to get rid of that I, and it'll be easier mathematically to do that. All right, so this is going to be I times big R plus little r is equal to 0. And so we're going to solve for V. Here's where my V comes in. Watch this. I've got this voltage and I've got this current, and I know that this current is V over R. That is known. This is known. And so E minus V over R times big R plus little r is equal to 0. I'm going to do some algebra on this. I'm going to get this to the other side. V over R positive R plus little r. And then I'm going to solve for V. I'm going to say V is equal to the EMF times R over R plus R. And so the first part of the problem is done. They've asked me to express the derived expression for the measured voltage in terms of R, E, and little r. and I get that. All right, so the next part is, the next thing that we are going to do is, okay, let's try that again. Okay, right now, the next problem says, rewrite your expression from the previous to express 1 over v as a function of 1 over r. Okay, so let's go ahead and look at that. And so we're going to say, well, if that's true, then 1 over v is equal to r plus r over script r. All right, now I don't yet see this, but I know I can do some math over here, so maybe it'll pop out. The 1 over r will pop out when I do this. So let's see, I could say, well, I could take it out here. I could say 1 over r times, and then what's left? We have r plus r over r, but that is not going to get me there apparently. So I'm going to go ahead and say this is r over epsilon r plus little r over e r. Now when they cancel there, now I can say that 1 over v is equal to 1 over r times over here r over e plus 1 over e. Now I want you to look at this. You might be scratching your head again going, well, why is that better than what I had before? Well, the reason is, here we go, r over e, is because look at what I have here. Now I have independent variable, the thing that I'm changing. I've got the dependent variable, I've got a slope, and I've got a y-intercept. And so that allows me to solve this crazy puzzle. And so now my y-intercept over here on the grid below says, plot the graph of 1 over r. Now I plotted it for us here and I've labeled it for us, but they want us to find the, using the straight line, obtain the values for the following. And so they want us to find e and r. Now we already said by our formulation here, let's put it back up here, 1 over v is equal to 1 over r times little r over e plus 1 over e. All right, now remember what's the unknown here? The unknown is that internal resistance. We don't know it, but look at where it shows up. It shows up in the slope, that internal resistance. I'm sorry, over here. I'm pointing to the wrong thing. That is my x, my y, that's my x, there's my slope, and there's my y-intercept. And so this is 1 over e, and so that's 0.08 is equal to 1 over e, which means that e is equal to 12.5 volts. And so that gives me my EMF. And then they want me to find r, and so that's going to come from the slope. So the slope m is equal to r over e, and that means that r is equal to m times e. When I find this point here, and I find this point here, and I do my slope, I find that the slope is equal to 0.052, okay? And my EMF is 12.5, which gives me a resistance of 0.63 ohms. And then finally, we have down here, so there's my 0.63 ohms. Let me put the 12.5 volts. Using the results, calculate the maximum current. I is equal to V over R, and so we have 12.5 volts over 0.63 ohms, and that gave us 19.8 amperes, which is nothing you want to be close to. All right, now last, I want you to look at this one, because this is, again, we're looking this year at probably a lot of explained problems. So let's look at this explained problem. A voltmeter is to be used to determine the EMF of the battery after removing the battery from the circuit. 2 voltmeters are available to make this measurement, one with low internal resistance, one with high internal resistance. Indicate which voltmeter will provide the most accurate measurement, the one with low, the one with high, or it will be equal X. All right, now this is a tricky problem. Let's imagine again, let's talk about what a voltmeter is and how it works. All right, so a voltmeter, we're going to put it on the battery, and we want to see how much voltage there's across here. Now we know there's a tiny little, let me draw it, I guess, over here. We know that there's this little invisible, unseeable resistor in there, right? That's part of that voltmeter. That's part of, I'm so sorry. We're talking about the resistor in here. So let me back up. A resistor, remember, a voltmeter, we mostly assume it has infinite resistance because we don't want any current to go through it. However, all voltmeters have some resistance, have non-infinite resistance, 10 mega ohms or something like that. So do we want our voltmeter to have a little resistance or a lot of resistance? I'm talking about that guy, right? All right. Well, if my voltmeter has a lot of resistance, that means that I will have a voltage drop across here that could become significant if it had a low resistance, because there would be a current through here. When there's a low resistance, there's going to be a good current. And if there's a good current, there'll be a voltage lost here and not showing up here. So I'll get a low reading because I have a voltage drop here. Now, I looked at this problem and it came over the heading of, is this a stupid problem? Because if you look in most physics textbooks, they'll talk about that all voltmeters have very large resistors. However, I called my friend who's an engineer and I asked him, he said, well, there's a very small niche of, if you're measuring a tiny voltage on the order of, well, he didn't say, but I'm imagining a very, very small voltage, picovolts. In those cases, you want to have a small resistance, not a big resistance. Anyway, there it is. I spoke too long, but I did want to tell you that you should work these problems hard. This is a really amazing opportunity to take this test with all your notes in front of you. So if you prepare that way, you have a really, really great shot this year. So we hope we can help get you there. Kristen, any word for our wise scholars for the weekend?
No, just enjoy it. Enjoy time with family. Hopefully there's some good weather involved. And yes, on these problems, just always be thinking, what is one thing you could change in the situation and how would that change it? So.
Excellent advice. All right, have a great weekend. Above all, be safe, and we'll see you back here next Monday, same time, same channel.
Hello, good evening, everybody. My name is Kristen Gonzalez-Vega, and you're joining us for AP Physics C, Electricity and Magnetism. I am in Frisco, Texas, where I teach AP Physics 1 and C at Reed High School, and I am joined, like always, by my friend Roger.
Hi there, everybody. Welcome. Thanks for joining us. This is I'm Roger Siegel, and coming to you live from Sarasota, Florida.
So, like we said, this is AP Physics C, Electricity and Magnetism. If this is your first time joining us, welcome, and if not, welcome back. We have been talking about circuit the past couple days, and we're going to continue that today with going over power in addition to our current and resistance. So we're going to add in that power. And my name is Kristen, and Roger is joining us as well from Florida. And tonight we have the following for our objectives that we're going to be able to do. So we're going to derive expressions to relate current, voltage, and resistance to the rate at which heat is produced in a resistor. We're going to calculate voltage, current, and power dissipation for any resistor in a circuit containing a network of known resistors. We're going to calculate relationships between potential difference, current, resistance, and power for any parts of the circuit, given some characteristics of the circuit, such as the battery voltage, if you have a resistor in series or parallel. And then we're going to start talking about Kirchhoff's laws and rules and going over that loop and junction rule, which we'll do more of tomorrow and the following night. So let's talk about what power is. We talk about power a lot in mechanics, and that power is work over time or force times velocity, the rate at which work is being done. So it's the same thing here, but really we talk about it more about the rate at which energy is dissipated in our circuit. So we can look at the heat that is being converted from that electrical energy and kinetic energy of those charges, and we can look at that in terms of the resistance, the current, the voltage. There's lots of different equations we can use to talk about power, and it's measured in watts. The variable is capital P. Another symbol or units we could use instead of watts is that it's a joule per second, right? The rate at which energy is being used in the circuit or dissipated. The main equation that we use for power is that P equals I times V. That I is the current, V is that potential difference. But we can also substitute in using Ohm's law and get that P is I squared times R or V squared over R. And these a lot of times I think are more useful because when you change something in a circuit, a lot of times you're going to be asked questions about brightness of a bulb, right? So the brightness of a bulb relates to the power. The greater that power, the greater the wattage of your bulb, that more that energy is being converted in that same amount of time. So you get a brighter bulb. But what we do when we put in another element into our circuit is we are changing that current and that voltage into each light bulb, right? So not from the battery, but for each element in the circuit, that's going to change. So your current's changing and your potential difference is changing. And sometimes that can get really confusing. But if we're looking at one bulb, the resistance of that one bulb won't change. So if we're adding or changing things in the circuit, sometimes it's easier to use one of those other two equations because you can easily see what's happening with the current and the potential difference in that part, and then that resistance would be changing, and you only have one changing variable instead of two. The other thing we're going to look at is we're going to look at our loop and our junction rule. So the loop rule, which goes back to conservation of energy, states that the potential difference that we gain in any loop of a circuit has to be equal to the potential differences that we lose, the sum of those potential differences in our circuit in one loop. So what that means is, if we look here at our circuit, well, we've got our battery that has an EMF of 42 volts. We have the positive terminal here, indicated by that longer side of the battery, and we have the negative terminal indicated by the shorter side of the battery. And we go by conventional current, which says that the charges are going to go from the positive terminal, so that current is going to flow out to the left here and around the circuit. But as we go around and we trace that current, it's going to go into our light bulb here, then we get to this part right here, right? This is what we call the junction. That current can split off, and some of that current's going to go here, and so this around, it gets back here and go back to the battery. This would be one loop. If I change the colors, well, what if instead we look at, as we go, we leave the battery, we go around, we go through this light bulb, some of that current's going to go down through this branch instead and go around to that. So that would be loop 2. So this circuit has 2 loops for it. So if we go around in that loop, our potential difference gains, which would be the battery. So if I write an equation using that loop rule, or right over here on that loop rule side, I would say, well, the gains, which is the EMF of the battery, that's a positive potential difference. Well, as we go through light bulb A, we're going to have a potential difference drop across here. So I would say minus whatever that potential difference across A is. So as we keep going around this outer loop, we get to light bulb C. So again, that's another drop. So minus potential difference across C. When I get back to here, by the time I get to the battery, I should have a potential difference now of 0, right? So our gains equal our drops. You could also write it as the EMF of the battery equals VA plus VB. Okay, we could do that for same thing then for the loop 1, or this top loop. That would be the EMF of the battery minus, again, we've got light bulb A in that loop, so the potential difference across A. And then as we go around, we've got bulb B, so minus the potential difference across B equals 0. And so this can be useful to for a couple of different reasons. A, this gives us why that potential difference is the same in parallel. Because if I only had 2 light bulbs that were in parallel with each other, and let's say it's a 10-volt battery, well, if we go around and we trace those loops, so if we go around this bottom loop, well, I'm gaining 10 volts, and I only have 1 light bulb in that loop. Well, that means that this potential difference across this one also has to be 10 volts. Okay, well, if I do the top loop and go around, I'm gaining 10 volts in the battery, I'm losing, there's only 1 bulb in that loop, so 10 volts here too, right? So it's not the same potential difference, but it's not like the exact same potential difference. But as we go around that loop, we end up having the same potential difference across this one as we do this one. So that's why our voltage is the same in parallel in the circuit. And we can use that to determine a lot of times what the potential difference is, or sometimes current is, but writing that loop rule can be really useful. The other rule that we have is the junction rule. And the junction rule, going to back up a little bit here, states that the sum of the currents going into a junction has to equal the sum of all the currents going out. So maybe we have 1 current going in and we have 3 branches. The amount of that current going into that junction has to equal the total amount going out. So if we look at that here, I'm going to erase this stuff again. Let's look at that junction. Well, I've got a junction here and I've got a junction here. So we can look at either. Let's look at the one here on the left. So if I'm tracing my current around, I've got currents going into that junction. Let's call that I1. But I have 2 currents coming out of that junction. I've got the current here and the current here. Let's call the current going into light bulb 2 I2, and let's call this one I3. Well, the ins have to equal the outs. So if I'm writing an equation for my junction rule, I would say, well, I1 going in, my ins equal outs. Well, how many go in? Just 1. How many go out? 2 I2 plus I3 go out. So we're going to use these a lot more later. We'll touch on a couple of these today, but we're really going to practice more these loop and junction rules tomorrow and the next day. But always be thinking about those. And this is why in series currents are the same, because if you have no junctions, the current has to stay the same everywhere. Okay, so I'm going to stop here for a second, and Roger's going to take us through some practice with power.
Okay, Kristen, thanks a lot. So let's go ahead and do some of these problems. We're going to actually circle back to the one that you just saw in a few minutes, and we're going to do what's called a VERP table, which is one of my favorites to do when I'm solving circuits. So let me go ahead and pop open the screen here, and let's get rid of that guy, and we'll say hello over here. Okay, great. All right, so let's look at this. First of all, okay, I'm not getting any registration here. I'm going to pause for just 1 second, Kristen. This is going to take me about half a second to finish, and then we'll go back. So stand by, everybody. Okay, excellent. Thank you. Okay, here we go. All right, so now let's take a look here. We've got a hairdryer, and it's rated at 1200 watts and 120 volts. Now, just so you know, anything that you plug directly in that's like a motor is probably going to be taking 1200 volts. Everything that we plug in our houses here in North America is 1200 volts. If we went to other places, it's 220, but that's what we use in our grid. And so 1200 watts, we want to know what's the resistance. Well, if you look on your formula sheet, you're going to see P is equal to IB, but with a little bit of manipulation, as we said with Ohm's law, we can say that that's equal to V squared over R, and it's also equal to I squared R. And remember, since this year's test is all open note, write out your formulas, write them all out. Okay, so let's go ahead and see. We're looking for, we've got power and voltage, and we want resistance. So it looks like we're going to be doing this formula. P is equal to V squared over R. And so then we'll say that R is equal to V squared over P. And so our voltage, we said, is 120 volts. And square that. And our power is 1200 watts. And so that gives us 1440 over 1200. 2 zeros cancel. 12 into 144 goes 12 times, or 12 ohms. So that's our resistance that caused that power. One thing, just a kind of rule of thumb is this: the more power that you're drawing in a circuit, the lower the resistance. Okay, so like your oven or an iron or your hot water heater, if that's electric, that's going to be a very low resistance because it's going to be drawing lots and lots of power. All right, let's keep going, and we'll do another one. So it says, now these are the kind of problems that we expect you might be asked to comment on, because this is the kind of what we call qualitative relationships that we hope that students who are proficient in AP Physics C are going to be able to do. And so let's practice this. Let's take a look. It says, which of the following graphs could represent the power dissipated as a function of resistance for a variable resistor connected to a constant voltage source? All right, so let's see what we're actually asked to relate here. We relate to power, and we've got a variable resistor and a constant voltage. Well, here we go. We're going back to math class. We want a function, power on the y-axis and resistance on the x-axis. So we're going to say that we want P as a function of R. And so power, we know, with voltage is V squared over R. So what we would say is P is 1 over R times V squared. Now look, they said V is constant. So P is proportional to 1 over R. That's our inverse relationship. So I'll bet you that's the answer. All right, let's go on. Now, this is the one that Kristen was showing you some. We are going to attack this guy. We're going to go full out on this. It's going to take a few minutes, but I really want to take some time to dissect the circuit, pull it apart. And what I kind of like to tell my students is we're going to deconstruct it, and then we're going to reconstitute it. We're going to kind of go backwards and make it super simple, and then we're going to go back to the more complex, and we'll fill in all the details. All right, so the first thing, we're just going to read the problem. So it says, light bulb A, B, and C are connected in the circuit shown above. List the bulbs in order of brightness from brightest to least bright. If any bulbs have the same brightness, state which ones justify your answer. All right, so let's really analyze this. Let's take a look at it. As I said, what we're going to do is we're going to come up with what's called a VERP table, all right? V-I-R-P, and voltage, current, resistance, and power is a VERP table. And I never taught this, but then I was grading the AP exams one year, and I saw a student drew it on their paper, and I thought, that's genius. I'm going to use that. So here we are. We're going to look at these different parts of the circuit. All right, so we have voltage, current, resistance, power, and they've been kind enough to label our resistors here. And so down here at the bottom, I usually, you got to kind of use your imagination with this one, but this is either the main branch. Sometimes we'll talk about the main branch, or the effective resistance if we're talking about the resistance. All right, and we'll see if that makes sense. All right, so the first thing we're going to do is we're going to take this circuit, and we need to deconstruct it. We need to look at it and make it simpler because it's complex. If you look here, we've got always start at the positive end of the battery and then go for a walk. So let's go for a walk. We walk along this way, and we say, okay, we now have come to a light bulb, which is a resistor. And so we're going to go through that light bulb. There'll be a voltage drop because that's a resistor. And then we're going to come to a junction, which means that some of the current is, as Kristen was telling us, some of the current is going to go this way, and some of it is going to go this way. And the current that goes this way will go through this light bulb. There'll be a voltage drop, and the current that goes this way will go through this light bulb, there'll be a voltage drop, and then we come to another junction, and the current that was separated here on the left is now reunited, and if I could sing, I'd probably sing for you, but I can't. So they're reunited, and the current then returns to the battery, and the current that we have here leaving the battery must be the same as the current that comes back to the battery. So in order to simplify this, we're going to take these three resistors and break them down to one. So the first thing I'm going to do is I'm going to draw those resistors, and I'm going to show, I hope you can see, I think you can, that these two resistors, right, these two batteries are actually in parallel. And how do I know they're in parallel? Well, because if you go from one to the other, you can go from one, you can easily go from one to the other like this without going through anything else. They're two sides. So let's go ahead and do that. And we will now say that we have here, this is 6 ohms, this is 12 ohms, and this is 10 ohms. Now, you would be fine to ask me, why did you draw it like this? Because it shows how they really look parallel. I like to draw like that. So you remember what we do with parallel circuits? We say 1 over R equals 1 over 6 plus 1 over 12. Okay. And so with our calculators, that's 6 inverse plus 12 inverse. And then we take the inverse of that. I think this is faster with your calculator. So if you can get good at that as we practice, that's a really good thing. All right. So we add this together, and this comes out to be 4. So that means that these two together equal to 4 ohms. So now I'm going to redraw this over here. And now I have 10 ohms. And then I'm going to now redraw this branch as 1 4 ohm resistor. Now we know the reality, of course, it's not 1 4 ohm resistor. It's two resistors in parallel. But from the battery standpoint, that's all it feels. Now these two resistors are in series. And so that means my final picture, and you don't always have to draw this. I'm the teacher. I'm drawing all the things. If you're pressed for time, please don't draw them. If we add these together, that's 14 ohms. And we were told earlier that this is 42 volts. So I'm going to go ahead and put some information in. We knew some of this before. In the main branch, we have 42 volts voltage gain, and we have 14 ohms of effective resistance. Now, what that allows me to do is to find the current in the main branch. And so I is equal to V, delta V over R. And so if I look at this main branch here, the circuit, I can see that there's a 42 volt gain right here. And so that delta V is 42, and my resistance is 14 ohms. And so that gives me 3 amps. So that means that I've got 3 amps going through this branch. So I'm going to go ahead and put 3 amps. And ladies and gentlemen, that's in the main branch. So I can put that here, 3 amps. I can put it here, 3 amps, and I'll put it here coming back in, 3 amps. All right, good. Now I'm going to leave the power until later, and then we'll come back and do that. Now let's look at, now we're going to move backwards. So just bear with me for a second. We spent a minute kind of going this way, right? Now we're going to go back the other way. We're going to start to fill in information in the reverse order. So now that we know that this is 3 amperes, we can find the voltage drop across this resistor. And how do I do that? Find that voltage drop. Remember, voltage is a drop from between 2 points. And I know that Ohm's law says delta V is equal to IR. So if I've got 3 amperes and 10 ohms, it's 3 amps times 10 ohms. That gives me 30 volts, a 30 voltage drop. All right, I'm going to put that in here. And that's my voltage drop across 10 ohms A. So I'm going to put 30 volts. Now, Crystal was telling us about Kirchhoff's loop rule. Always important. Let's look. In this loop, we're going to start here. We're going to have a 42 volt gain and then a 30 volts drop. Okay, so we go up by 42, we go down by 30. So if I gain 42 here, 42 volts up, and then I drop 30 volts, well, what's left here before I come back? What's left is 12 volts. So that means that I have 12 volts here. And C, notice that's across B. Okay, that's 12 volts across this. Notice these two are in parallel. And one thing I know about branches that are in parallel, they always have the same voltage drop across them. And so that means that C also has 12 volts drop across it. Now we've gone backwards. Now we found the voltage drop. Now we can find the current. We know, given at the beginning, this is 10 ohms. B is 12 ohms, and C is 6 ohms. And so now we can easily find the current. I is equal to delta V over R. And so that means we have a current. Well, we've already done this. That was 3 amperes. I just didn't write it in there. But now let's look at here. Let's look at what happens here. I want to talk about the junction because the junction rule is all important. Okay. Now here at the junction, we've got 3 amperes coming across here. So let's start with that. Right? So we've got 3 amperes coming out of our battery and going through this first light bulb. Now here we come to a junction. Some of it has to go one way. Some of it has to go another. Okay. And so and the total current going into the junction must equal the total current going out of the junction. That's Kirchhoff's junction rule. And so what we already found over here that the current we haven't found, we can find it really easily. The current I is V over R. Well, 12 volts divided by 12 ohms is 1 ampere. So let's go ahead and see that. That's V. And so over here that means that there's 1 ampere. Now check this out. If I've got 3 amps coming in and 1 amp going this way, well that means that this has to be the difference for 2 amperes. And so I have 2 amperes going this way. And notice now there's 2 amperes arriving at this junction from the bottom here. There's 1 ampere arriving from the left. And so now boom, they come together and they make 3 amperes. So that junction rule and the loop rule are what help us to figure out all this stuff. And we still haven't answered I didn't put this one in yet. So let me say we said that was 2 amperes. And so you can see also there's many ways that you can solve some of these problems. So don't be afraid to do it a different way if you see it that way. All right, now the last thing we want to do is it says, look, what is the brightness? And so the brightness is always going to be about power. So let's come over here and check that out. All right, so the brightness about power is equal to IV or amps. 2 other forms. So we got 90 watts, okay, joules per second. Here we got that's 3 times 30 times 3. We've got 12 times 1 or 12 watts. And we've got 12 times 2 or 24 watts. And if we look over here, we've got 42 times 3 or 126 watts. Okay. And so by the way, this is the only part of the table that is guaranteed to add up correctly. This will not add up to the bottom because these two are in parallel. You don't add them together. These won't add up because they're all parts of a whole, and these won't add up because we have reciprocal relationships. So that is another way. So now we can answer the question, which is the brightest. And the brightest one is the 10 ohm resistor, followed by the 12 ohm resistor. Followed by the 6 ohm light bulb. Then so here are orders 1, 2, and 3, or A, comma, C, comma, B. Boom, boom. Okay. I gotta tell you, it's important, ladies and gentlemen. Some of these problems are legacy problems, and it's not going to be long that we're going to be able to continue asking that because there was a time when all light bulbs were incandescent light bulbs, and this problem really made sense. But if you read the fine print nowadays, you know that a 12-watt LED light bulb is just as bright as a 100-watt incandescent light bulb, and just as bright as a 20-watt fluorescent light. So we're going to have to move away from this at some point. We got some legacy questions here that aren't going to make sense to the next generations of light bulb users, but we'll deal with that when we get to it. All right, last one, and then I'll send it back to Frisco. The last question, take a look at this. It says in the diagram, lamps L1 and L2 are connected to a constant voltage power supply. If L1 burns out, the power delivered to L2 will be multiplied by a factor of 1. So let's go ahead and kind of analyze this. I will not jump into the math because it's not that hard. So let's look. We have these two lamps in parallel. And what does that mean? It means that each lamp is individually and independently hooked up to the voltage source. And when I say independently, you might say, well, how can that be? Because doesn't the current split here? And you would be right, the current does split, but the voltage doesn't. So if this is 100 volts, then the voltage drop across this lamp is 100 volts, and the voltage drop across this lamp is 100 volts. Now, if one of these burns out, guess what? It's now an open switch. So how much voltage do I have now that when this one burns out? Well, 100 volts. In other words, the voltage drop across the light bulb is constant. So since power, which gives us, which is what we're asked to find here, how much energy is dissipated, since power is V squared over R, and V doesn't change when I lose one of my light bulbs, that means that the power is the same, and it's multiplied by a factor of 1. So if one of them burns out, the other burns just as bright. And that's a tricky question. So, it's easy to confound what would happen. I will also point out one thing, even though it wasn't asked, I have to answer it. The current does change in the circuit, okay? And I'll leave you to ponder that one. All right, Kristen, I think I've got him going here. So why don't you take us home with some more awesome problems? We need your
There we go. Thanks. Oh, you guys have to hear me? Oh. Okay, so let's look at this question right here. We have some different arrangements of resistors, and we want to know which one of these would dissipate 24 watts when connected to a 12-volt battery. They all have the same resistance. They're all 4 ohm resistors. So I want you to take a second to think this through, and we want to know which one of these combinations would dissipate 24 watts if we're connected to a battery that is the same in each case and 12 volts. And so we're only seeing part of it, but these are all connected to a battery. So we want to look at what we know, right? So we know what the power is, and we know what our potential difference of EMF of our battery is. So what I was like to think was, if I know two things anywhere in my circuit, I can always find something else, right? We can either use Ohm's law or we can use that power equation, right? Or one of the other power equations. So let's just stick with Div and Burr, right? If we use Ohm's law, V equals IR, then we use power is I times V. Well, if I know two things anywhere in my circuit, I can always find a third thing. So if we're looking at the battery and the EMF, and we want to know that we want the total power in the circuit to be 24 watts, and we have a kind of total voltage or voltage potential difference of 12 volts. Well, if I know two things, I can find a third. So let's look at, would current help us here, or would resistance help us more? Well, if we have a group of resistors, probably not going to help me to find current. That's going to be an extra step. I want to know really dealing with the resistance here. So let's find resistance. And so if I know, then let's use one of our other equations. The power is equal to V squared over R, and we know the power we want to be 24 watts. Our potential difference of our battery is 12 volts squared. And we can solve for what equivalent resistance we want, or what we want our total resistance of the circuit to be. If we do 12 squared and divide it by our 24, we get that we want the total to be 6 ohms. Okay, so each of these is 4. So right away, if we want the equivalent resistance to be 6, well, I'm probably eliminating anything that's all straight series, right? Because if this is 4 and this is 4, well, this is going to give me 8 ohms. Right here, 4, 4, 4, right? So we want to get rid of anything that's that. And if we are looking at just straight up parallel, we know that the more we add on, the less it's going to be, right? So I'm probably going to narrow it down to these, but really we could calculate it all out. But let's kind of look at these two. If I want it to be 6 ohms, do I want more in series, do you think, or more parallel? Because 6 is pretty close to 4. Right? I'm trying to use all these reasoning techniques. If 6 is pretty close to 4, I'm probably going to want something that has more parallel and less series. So let's look at E just for time's sake here. If we look at E, and these are each 4 ohms, well, I have these two that are in parallel in this branch. So if we want to find that, we know that 1 over R in parallel is 1 over 4 plus 1 over 4. That gives me 2 over 4. So that's again 1 over R. So if I put that, I get that this is 2 ohms. So these have an equivalent resistance together. It's like one resistor and a 2 ohms. But they are in series with this 4 resistor. So those we want to add. So if we added that 2 to that 4, then I get a total of 6 ohms. Whereas if we looked at C, and these are both 4 ohms, well, that would give me 8. And I would do over 8 plus 1 over 4. Right, it's not going to get us there. So E is the one that we want. Okay, I've got another problem here, which is actually a physics 1 problem, but I think it's good for the explaining, ranking, kind of reasoning through kinds of questions. So we have 3 circuits, 1, 2, and 3. The batteries are all identical, and the light bulbs are all identical. So in circuit 1, we have a single light bulb is shown connected to the battery. And 2 and 3, we have 2 light bulbs. As you can see in circuit 2, light bulbs B and C are connected in series, right? And circuit 3 is connected in parallel. If it's easier for you, it may be a good idea to kind of sketch out the schematic of this, right? Rather than looking at the picture, we can say, well, this is battery and 1 light bulb. This guy is battery and 2 light bulbs. And this one in parallel 2 light bulbs. Okay. And we want to first rank the magnitudes of potential differences across light bulbs A, B, C, D, and E, from the largest to smallest. If any of them have the same, then you can state that explicitly. And then briefly explain how you determine your ranking. So your ranking. I'm going to give you a minute. You tell me, rank the potential differences across these light bulbs and how you know. Okay, so these are where our loop rules and our junction rules are going to come into play. If we look at the schematics and change up my colors here, if the potential difference of the battery is the same in each case, well, if I compare circuit 1 and 2, well, circuit 1 has 1 potential difference gain and only 1 potential difference drop. So the potential difference across that 1 light bulb would be the same as the battery. So if it was a 1.5 volt battery, it would be a 1.5 volt potential difference across that light bulb. If we look at circuit 2, though, there are 2 light bulbs. Remember, our gains have equal drops. So if we have this same 1.5 volt battery, well, that potential difference has to be split between the two, right? If these light bulbs are identical, they have the same resistance, then it would be an equal. So this would be the EMF over 2, and this one would be the EMF over 2. Right? And if we look at circuit 3, I got 2 loops. It's almost like we have 2 different one light bulb circuits. Potential difference in each one of these, though, is going to be the same as the battery because they're in parallel with the battery. So if we were to rank these then, what would be first? Well, all A, D, and E have the same potential difference. And then after that would be B and C, but those are equal since they are the same resistance. Okay, so how do we know that? If we're using our loop rules, then we know that A's potential difference drop is the same as D. Okay, what about if we look at these same batteries and they're all going to start with the same amount of usable energy? They're all connected to the light bulbs at the same time, and we want to know which of them will run out of that usable energy first and which one will run out of that usable energy last. So I'm going to give you another second to think about that. So we're going to connect up these light bulbs to the battery, turn them on, and which one of these batteries is going to run out of juice first and which one's going to run out of juice last, and how do you know? So what do we think? Which one is going to run out of juice first? How do we know which one's going to run out of that usable energy first? Well, the key word there is energy. And what can we relate that energy to? Power. That's what we've been talking about, right? So we want to use up the most energy in the shortest period of time. So we want a large amount of power. So how do we find which one of these draws the greatest amount of power from the battery? Okay. Well, if we look at circuits 3 and circuit 1, well, we just said they all have the same potential difference across them, right? Okay. But if we're looking here at the totals, right, we want to know just about the battery. If I want a good power, we'll use I times V, right? So if they all have the same amount of potential difference, V, then which one of these is going to have the greatest amount of power? The one with the greatest amount of current being delivered from the battery. And how do we know it's going to have a big current? If we go to Ohm's law, we want a small amount of resistance. So which one of these circuits is going to have the smallest amount of resistance? If we want low resistance, how do we want our resistor in series or in parallel? We want them in parallel, right? This guy, if its resistance is R, there's only one, then it would have a total resistance of R. If we compare this in series, how do we add them? We add them up. So this would be a total resistance of 2R. And circuit 3, if we did 1 over R, 1 over R ends up being R over 2. And so the greatest power is going to come from the lowest resistance, which is circuit 3. And the other way we could think of it is that V squared over R, right? If all these batteries have the same potential difference, then we want the smallest amount of resistance to give us the biggest amount of power. So battery 3 is going to run out of juice first, followed by A, followed by B, C, right? Or battery into circuit 2, rather than naming those light bulbs. Okay. The last one I have here, which is kind of just driving it all home, is we have a beaker of water. So if we have this beaker of water and I have it attached to a battery with an EMF of E, and I ask you if I add a resistor here in series to the circuit that's submerged in the water, right? So instead, if this was our beaker, right, and it's in the water. So this is what we call resistive heating, right? We can heat water with a heating element with that resistive heating. So if I add another resistor in series with this, how's that going to change the rate at which my water heats up? Is that going to keep my water quicker, slower? How would that change the rate at which it's in the water? Versus if I added one in parallel. So instead, if we had our beaker, we had 2 of those resistors, sorry, in parallel, so it's strapped here, then how would that change the rate at which the water is heated? So I want to give you just a second with that. Right? And then lastly, what is another way you could change the circuit without actually changing what the resistors in the circuit, right? Like not the number of resistors, like not adding or subtracting, but what else could you change in here that would heat the water faster? Okay, so let's look at it. What's adding a resistor in series going to do to the rate at which this water is being heated. So really want to know what's going to do to the power. We've been doing this all evening. If I add another resistor in here, then what's that going to do to the power? Well, if we've got the same potential difference or EMF being supplied by the battery, let's look at what that does. If I add another resistor in series, what does that do to our total resistance? It's going to increase it. And if I increase that resistance, what does it do to my power? It's going to decrease it. So I'm going to decrease the power, which is going to actually make it take longer for me to heat up my water. Right? I need more time to get the same amount of energy than I had before. Right? What about if I add a resistor in parallel? What's that going to do? Well, adding a resistor in parallel is going to decrease my total resistance. So that's going to increase my power. Right? So I'm getting more bang for my buck. I'm getting more energy in that same amount of time. Right? What else can we do then to my circuit in order to make it heat up faster? So what can we do to that one individual resistor that is going to increase the power? Well, how do we get the resistance of one resistor? Right? We said that the resistance is equal to rho naught time L over A. So if I want to do what to the resistance to get more power, I want to decrease the resistance. So there's actually a few different things we could do here. We could change the material that my resistor is made up of. What do I want to do to the resistivity if I want a lower amount of resistance? Well, I want to lower that resistivity. Right? I could change that shape or length of the resistor. Right? The main idea here is that you want to decrease the resistance. The thing this makes me think of that I want to add on to the end here that we haven't necessarily talked about is the difference between an ohmic and a non-ohmic resistor. And we don't really see it that often, but I think this is a good time to bring it up because if you look at an ohmic resistor obeys Ohm's law, just like it sounds. So if I were to actually make a graph, I had a circuit with a resistor in it, and if I change the potential difference, like a variable power supply, if I change that voltage and I measure the current going through my resistor and I were to graph it, the potential difference versus the current, I would get a nice straight line, right? That resistance is constant no matter what potential difference or current is traveling through. The slope of that, right, is the resistance. But there are some things like a light bulb that typically are non-ohmic, where if you have that incandescent light bulb on, it gets hotter and hotter, and that changes that resistance. So a non-ohmic would not be a nice linear graph. That would change as you increase that potential difference across it. You would not get a nice straight line. So I just wanted to touch on that really quick to kind of draw it all together at the end. So what we did tonight is we talked about power, how you define the rate at which that energy is dissipated in your circuit. We calculated some of that. We used a little bit of those loop and junction rules that we're going to practice some more again tomorrow. So come back tomorrow. We're going to do lots more circuits. We're going to look at what happens when you have a bunch of resistors. How can you find again, kind of like Roger started, that current and that potential difference across any part of our circuit, and what happens as you change things in the circuit. So from Frisco, good night, and over to you, Roger.
Yeah, from Sarasota. Thanks so much for tuning in. Thanks for working so hard at this really hard stuff because it's going to pay off. You're going to pass and get the credit if you put the time in. All right. So thanks, Kristen. We'll see you tomorrow.
Yes, I'll be here.
Kristen and I are going to help you practice with some mock exams. All right. Where we are this week is we are looking at circuits, as I said, and so we've been talking last night and tonight about current, resistance, and power, and we're going to add some batteries in a little bit. We're jumping a little bit. We're still going to talk about power. Believe me, there's going to be plenty of power questions here. All right, let's keep going. So today's ideas, what you're going to do is you're going to have expressions that relate current, voltage, and resistance to the rate at which heat is produced. Calculate current and power. Calculate relationships between potential difference, current, resistance, and power dissipated in any part of the circuit, and single known current, potential difference, or resistance in a multi-loop current using Kirchhoff rules. Now we're going to talk. I should have thrown the Kirchhoff rules slide in there, but we're going to talk about those. Let's just review that real quick. We have the loop rule and the junction rule. All right, I'm going to tell you, and we're going to do them in about. We're going to do them a bunch in the next minute. But the loop rule tells us that if I go around any closed loop, the sum of the voltage gains and drops has to be zero. And basically, the loop rule is a conservation of energy rule. All right, so we can see here's a battery, and here we're raising the potential, and I don't know how much that is, but in a minute I think we're going to do a simulation with 12 volts. And so we've got a 12-volt battery, and we can see that the current is going to flow. We always say the conventional direction of current is opposite that of the flow of electrons, is out of the positive terminal around through the wires, and we say the wires are ideal. There's no voltage drop across the wires. They're perfect. And then we get to our first resistor, and we're going to have a voltage drop across that resistor. That means that I'm going to lose energy, my current. But what I don't lose is current, because whatever current I have here, and here, and here as well. And so the loop rule says that for each, that when I cross each of these resistors, I'm going to have a voltage drop, and the sum of those drops has to equal the voltage gain over here, so that the total is zero. So I've got a simulation for us to check out here, and this is the first one that I have. This is the series circuit simulation. Now I want you to let's take a minute and we'll look at this and try and orient yourself. Down here we have the battery, and there's a little voltmeter across the battery, and that voltmeter is telling me that I've got a 12-volt gain. You can see here's an ammeter here, and here. So there's ammeters everywhere throughout the circuit. 1, 2, 3, 4 ammeters, and then we have 1, 2, 3 resistors. So this is what we're trying to replicate: 3 resistors and a battery. All right? But what I love about the simulation is, first of all, we get the animation of the current, and we can actually play with this if we want to, and we'll see what happens. Now, so you can see here that I got a voltage drop gain of 12 volts. Now I'm just looking at this, and I'm realizing that when I built this simulator, I put these voltmeters on backwards. So my apologies, but that's live TV. So they should say minus 4 volts each of them, but they say plus 4 volts. But that's just the way it happened. So imagine they say minus. If I had them correctly, they would. And so we've got a voltage gain of 12 volts, and then we've got a voltage drop of 4, voltage drop of 4, and voltage drop of 4 across each of these resistors. And so those all add up to a minus 12, and so my voltage drop is 0. And so that shows us Kirchhoff's loop rule. So any place we have a loop of current, we can apply it and make sure that we can account for all the gains and drops in voltage. All right, the next thing that I want to look at is the junction rule. Now we're going to add the junction rule. We're going to keep looking at the loop rule, but we're going to add the junction rule. And so the junction rule says that the sum of all the currents going into, I'm going to zoom in a little bit here. All right, so first let's talk about a junction. Here's my junction right here. Here's a junction right here. And a junction is where I have a current splitting or coming together. And so what I've got here is I've got a current that is coming in this way. And that is, remember, current is measured in amperes, but let's talk about what that means. Amperes are coulombs per second. Coulombs are literally charges. Now it takes a lot of electrons or a lot of positive charges to make a coulomb, but that we're literally counting things. So coulombs per second, charges per second moving into this junction means that the current coming out this way, this I1, the current coming out this way, I2, and the current coming out this way, I3, all have to add to the current going into the junction. Now that's Kirchhoff's junction rule, and that's an articulation of the law of conservation of charge. We can't create any new charges, and we can't make any disappear. So however many coulombs per second are flowing into the junction is going to dictate the total amount of coulombs per second flowing out of the junction, just as if it were an incompressible fluid like water. Water is often used as a metaphor for electric currents. So let's take a look at the simulation for this parallel circuit. I'm going to go ahead and pop that up here. I think I've got that. Well, I'm going to have to open it up, and so here it is, the parallel circuit. All right, thank you, Falstead Simulator. I love these simulations. They are just so good. I'm going to try and drag this a little bit more to the center so I can get a little bigger. Kind of small. No, that was not good. Let's not do that. All right. So let's notice over here, we're trying to again replicate this circuit. So you can see over here the circuit, we have a battery on the left and 3 resistors on the top in the parallel circuit. So let's go ahead and get back to that. And so over here we have our battery, and I've given us a 12-volt battery and 6 amps coming up. We'll talk about that in a minute. And we have 3 6-ohm resistors here, here, and here. Okay. And so if we have 3 6-ohm resistors, and I'm going to use my formula, inverse resistance formula, to find out what the total resistance is, that's going to become 2. And so I've got a total resistance in my parallel branch of 2, which means means 12 volts divided by 2 ohms is equal to 6 amperes. And so I've got 6 amperes here coming through the main branch of my circuit. And so the 6 amperes flow into this junction, and now look what happens. I've got some flowing this way, some flowing this way, straight across, and some flowing down. I love how the simulator, take a look how it shows the speed at which the my dots are moving here, representing current, versus much slower here. And we would have to say a third as slow, because since each of these resistors is the same, the current is split up equally among the branches. And that doesn't always happen. It doesn't happen in the problems we're going to do tonight, but it does happen sometimes. If the resistors are the same, we'll split the current 2 amps, 2 amps, 2 amps. So 6 amps is equal to 2 plus 2 plus 2. We can also look at Kirchhoff's loop rule here, all right? And I'm going to actually try and freeze this for a second. So we'll do a snippet sketch, which I'm a little ambivalent about this particular problem. That's what I got right now. All right, so so here we are. Let me grab something to write with. All right, that's what we need. Great. And so let's take a trip around this one of these loops. And so here we've got a 12 volt gain, so that's plus 12. And then I come around here, and now look, I have a 12 volt drop, and these I put in.
Hey, it looks like we lost Roger, so I'm going to pick up where he left off, and we're going to look at some practice problems, because I think he was just wrapping up talking about that junction rule, and showing as we go around those loops, what happens, right? So if we go around that loop, we have one resistor, so the potential difference drop across that one resistor should be equal to the potential difference of the battery, and we can do that for any one of those loops, and it would be the same. So all of these resistors that are in parallel have that same potential difference. So let's look at some actual problems here. The first one is we have a student that is provided with a 12 volt battery of negligible internal resistance, and then 4 resistors. Now, I'll have different resistances, 100, 30, 20, and 10 ohms, but we also have plenty of wire that also has negligible resistance. So you can connect it any way you want. How would you connect those components up to create a circuit that all of the components have some current going through it, but we have as small a possible current coming from that battery? So you can't short anything out and have no resistors with it, and have resistors that have no current. Everything has to have current going through it, but we want the smallest amount of current possible. Okay, so take 1 second. How would you do those? Maybe sketch out what the schematic of that would look like, and how do you know that that's what it needs to look like? So if we want small current from the battery, what do we want to be big, right? I can't change the potential difference of the battery. So if we look at Ohm's law, if I want a smallest amount of current possible, what do I want to do? I want to make sure that I have a very big resistance. So how can we connect our circuit to have a very high resistance? Well, when we're combining resistors in series, remember we add them all up. So if I add all 4 of these resistors in series, no matter the order, it could be the 100 ohm first, or it could be the 10 ohm first. Doesn't matter what order they're in. If they're all in series, we could find what that equivalent resistance would be. If we add those all up, we get 130, 40, 50, 160 ohms, which is a really big resistance, right? We could find what that current is from the battery because it's a 12 volt battery. And if we did 12 divided by that 160, we get 0.075 amps. Okay, small amount of current. What if we wanted to do it the other way, where we want as large as possible of a current going through it? What would we do? Well, if we want a big current coming from my battery, what do I want the resistance to be? Very small. And how do we connect the circuit up so that the resistance is very small? Well, that we do in parallel. So if we draw that circuit with those 4 resistors all in parallel, again, it doesn't matter what order we have those in. But if we now find our equivalent resistance, remember we combine those resistors in parallel by adding their inverses. So if we did, and we found that equivalent resistance, then we get that it's only 5.2 ohms. You can see what that difference is. If we combine those resistors in series, we get 160 ohms. But if we combine those same exact resistors in parallel, well, now it's only 5.2 ohms. Okay? So if we then again found the current, this time we get 2.3 amps. So much greater current when those are in parallel than when they are in series. Okay, what if we connect them like this, where we have that 12 volt battery, and we have the 100 ohm resistor here, we got another branch with that 20 and 30 ohm resistor on it, and then the 10 ohm resistor. So first thing I want you to look at is when you look at the circuit, I want you to identify what parts of the circuit are in series and which parts of the circuit are in parallel. Do a quick glance at that. Tell me what's in series, what's in parallel. Okay, so what we want to know, really what I want you to do first is rank these for me. Like which one of these, so let's call this A, B, C, and D. Okay, so I want you to rank the currents through the resistors from greatest to least. If any of them are equal, you're going to put an equal sign. Right, so tell me which one you say has the most current, has the most current. Why? Why does the one you say they rank first have the most current, and why does the one that you say is the least have the least? Right, so give me a ranking and a justification. I'll pause for just a second for you. Okay, so I'm going to do this over here. So let's go back to which one of these are in series and which one of these are in parallel. If we look at B and C, well, they're on the same branch. So B and C are in series with each other. Okay, and then if we look at A, well, A, we have a junction before A. So if we were to write our loops here, well, let's do one loop. I could have current coming out of the battery this way, goes into the junction and comes out of the junction and back around like this. But we could have another one that comes out of the battery, goes again into this junction, but comes out this way and around and back to the battery. So we've got 2 loops here. So that means that A is in parallel with B and C. Okay, and then lastly, what do you notice about D? No matter which loop we take, both of those loops go through D. So D is in series with everything, with the battery. So then D is in series with the battery, and therefore everything. It doesn't matter if it's at the very end, right before we get back to the battery, if it's right after the battery, it's still in series with the battery. And so anything that's going to be in series with the battery obviously is going to have the greatest amount of current. So ID is going to be the greatest. Okay, so let's look at then this junction, and let's look at the current going down through B and C. We know since B and C are in series, they're going to be equal, right? But is the current going through B and C going to be greater than the current going through A, less than the current going through A, or equal to it? What would that depend on? Well, let's look at what the equivalent resistance is in each branch, because remember that potential difference is going to be the same because they're in parallel. But if we look at B and C, they have an equivalent resistance in this whole branch of 50 ohms, whereas the top branch has a resistance of 100 ohms. Okay? Well, the current's not going to equally split. We're not going to get half the current going through A and half the current going down through B and C. It's like when you're at the grocery store and you look to lane 1 and there's 3 people in line, and you look at lane 2 and there's only 1 person in line. Where are you going to go? You're going to go to lane 2. More current is going to go through your path of least resistance. So B and C are going to have equal currents, but they're going to be greater than the current that's going through A because it's a greater resistance in that branch. Now let's see, how would we find that current going through D? Well, since it's in series with the battery, well, let's find what the current coming from the battery is. What do we need to know for that? I want to know the I through the battery. What do we need to do? Right? Roger showed us the other night that diagram where you can make a table of the voltage, current, resistance, and power. If that's easier for you, you could do that. I like to kind of draw everything right on my circuit, so that's kind of what I kind of do here. So if I find that total resistance, well, I know that these are in parallel. The 100 ohm is in parallel with the 20 and the 30. So if we combine that 20 and 30 and we get our 50, that's in parallel with our 100. So if we want to find that resistance, we have 1 over 100 plus 1 over 50. And if we do that, then we get that that's 33.3 ohms. But then these are in series with D, so then we have to add on D's resistance of 10 and get an equivalent resistance of 43.3. So I'm going to write that by the battery, 43.3 ohms. Okay. And then again, if we know 2 things at any one point, we can always find the third, right? We've got Ohm's law, so we can always, if we know either the potential difference in the current someplace, we can find the resistance, or if I know the resistance in the current. Anytime you know 2 things, you can find the third, which is kind of why either doing this table is good, because if you've got 2 spots filled in your table, then you can see that you can do the third, or anywhere on my picture that I can see 2 things, I can find the third. Right? So if I know the resistance and I know the potential difference, what can I find? I can find the current being supplied by the battery because it's the voltage divided by the resistance. Right? So if we plug in that 12 volts divided by our 43.3, we get 0.277 amps. Okay, so we got 0.277 amps going into our junction here, but that's going to split not equally, right? If we have double the resistance in the top, that should be getting half the current, right? But we get back to this junction and it comes back out. So again, at this point, it's going to be 0.277. Remember, current in equals current out. Right? If we go around, well, since D's in series with the battery, that means there's 0.277 amps going through D. Right? Well, again, if I know two things at one place, what can I always find? I can find a third. So if I know the resistance and I know the current, then I can find the potential difference across D. Right? Because potential difference is the current times the resistance. So if we do that, we get 2.8 volts. Right? Why do we care about that? Well, I can start going around and filling everything in if I wanted to. Find everything at these elements, right? Because I started with a potential difference of 12 volts for my battery. Well, if I've lost 2.8 volts across resistor D, what does that mean is left with the rest of the circuit? Well, 12 minus 2.8 is going to give us 9.2. And since top branch is in parallel with that middle branch, that means the top branch has 9.2 volts. And total between B and C, we have 9.2 volts. And so we can apply, we're not going to find everything, but we could go then, and now that I know the voltage drop across A and I know the resistance is 100 ohms, I could find the current through A, right? And then we could find the current going into the bottom one. We won't spend all that time doing that. But we're using these loop rules and these junction rules in conjunction with each other to solve the current and the resistance and potential difference in different places. But the next thing I wanted to ask you, which is another kind of conceptual thing that we like to ask, is if the light bulb, let's say, I'm not here, yellow. Let's say that A goes out, right? Let's take A out of play. If light bulb A burns out, I want you to tell me what's going to happen to the brightness of light bulb B and the brightness of light bulb D. Okay? So if A goes out, does B, the brightness of B and D go up, down, or stay the same? So I'm going to give you another second here, and I want you to think about that and how do you know? They may both do the same thing, they may both do something different, but if A goes out, what happens to the brightness of light bulb B if these are light bulbs, and D?
Kristen, I wanted to tell you that I got back.
I'm glad. And we're going to come back to Roger here in just a second. So here's how I want you to attack these kinds of problems. When you're being asked to make predictions about things, when one thing goes out and we're looking at, like, if these are light bulbs and we're looking at brightness, well, what does that relate to? It relates to power. But what I want you to look at is how is your circuit changing? Are things going from series to parallel or parallel now to series? And how does that affect your total resistance and therefore the current, right? Because my resistor, B, is still going to have 12 ohms of resistance and D is still going to have 10 ohms of resistance. I'm not changing the resistance through those resistors. So let's use let's look at one of those power equations that doesn't have both current and potential difference because both of those are going to be changing. But if I look at, say, I squared times R, well, of resistor B and D, those R's aren't going to change. So what we want to look at is what's going to happen to the current. And really where we know that is what's happening to our circuit. So if I take A out of play, what does that now do to my circuit? Well, that gets rid of our blue loop, right? So now all we have is the green loop. And so now I go from a parallel circuit to a series circuit. So that's the first thing I want to write, that we're changing from a parallel to a series circuit. And what does that do to our resistance, total resistance, guys? That means my total resistance or my equivalent resistance is going to increase. And if my equivalent resistance increases, what's going to happen to the current being delivered by the battery? That means my current is going to decrease. That total current coming from the battery is going to decrease. So let's look at D. That's kind of the easiest thing to look at first because I know that D is in series with the battery. So if the current from the battery goes down, what's going to happen to the current through resistor D? It's also going to decrease. So if the current through resistor D decreases, then D is going to get dimmer. The brightness will decrease. Why? Because it has less current going through it for that same resistance. But let's look at B. What's going to happen to the brightness of B? Because our total current is now decreased. But what happens? We don't have this junction anymore. So there's no current going into that other resistor. Now all of the current from the battery is going through resistor B. So the current through B now is going to have to go up because it doesn't have to share anymore with resistor A, right? So B now gets brighter since it's now in series, and the current will increase through resistor B. So these are some predictions that are really good to be able to do. Is if one thing goes out, what happens to the other, and be able to explain why. Right? So we could find the total power, and there's lots of different ways we could do that because we know what the total current is from the battery, we know what the potential difference is from the battery, we know what the resistance is from the battery. So we could use E equals I times V, we could do I squared R, you could use any of those power equations to find it. Okay? And then what about if the current remains constant? How long will it take to provide a total of 10 kilojoules of electrical energy to the circuit? Right? So we've got energy, and we've got how long. What's how long measurement of time? So this still goes back to power because power, remember, no matter what we're talking about, mechanical power, electrical power, power is the amount of energy per time. So once we know our power from the first part, whether we say that that's I times V, and we want 10 kilojoules, which is 1,000 joules for 10,000 of E, then we can solve for our time because we know the power. I worked it out earlier in 3.32 watts. So we can find what that time is. We won't waste the time on doing the math. Okay. And then lastly, let's look at this last ranking here. Then I'll try to get through quickly so we can get back to Roger for a little bit. We've got this configuration of the circuit here. We've got our battery. We've got an amp meter here in series with the battery. And then we got a bunch of resistors and we've got two switches. And we've got all these different possibilities of things that we could do over on the right here. I could leave switch 1 open and switch 2 open, which was what A is doing. So just like you see in the picture. I could close switch 1 and leave switch 2 open. Right? We're going to change that circuit when we close the switches. So we want to be able to rank the amp meter readings for these 4 configurations. Okay, so what I want you to think about is, well, if we want to rank them from greatest, well, how do we know we have the greatest amount of current that's coming through the amp meter? Well, since the amp meter is in series with the battery, a big battery current is going to correspond to a small resistance. So we want to look at these and kind of find what would the equivalent resistance be for each case. Right? So if we look at A, and A is open. So just like the picture. Well, if we do our loop rule, we go around the circuit, I start with the battery, we go here. Well, switch 1 is open, we get to the junction, we don't have anywhere to go down there, right? Switch 1 is open, so we only can go through these 2 resistors that are in series. So let's just call this R and this R. So we got 2 R so far. I keep going, I go around. Well, switch 2 is also open, so I can't go left, I can only go up. And I go around, I've got another 1, 2 still in series. So now I've got a total of 4 R of resistance. Right, let's look at B. Write these lines here. So B, we've got 1 open, 2 closed. And I'm going to close switch 2. What does that change? Well, as we go around, it doesn't change anything in the beginning. I'm starting with 2 R. Okay? We're going to go around, around, around. Well, I get to this junction, now I got 2 choices. I can go up through this resistor or down through this resistor. So I've got those 2 resistors in parallel, since there's the same resistance, and total they're going to give me R over 2, or half an R. But I get here, and I'm series again with this one. So that series one will give me 3, and now I've got a half, so now really I've got 3.5 R. Guys following me? Okay, let's look at if we have S1 closed, but S2 open. So now we're closing S1. And this is something, I don't know if we've talked about this yet or not, but if I have this closed, do we have any resistors in this portion of the circuit? No. So when I have switch 1 closed, and the current gets to this junction, it's going to create what we call a short circuit. Right? There's no resistance in that bottom wire. If there is nobody in lane 1 in your grocery store, and there is even one person on the other line, so anybody go to this other one? No, just short circuit. So all of the current will go down here. None of the current will go through those resistors. So I got 0 resistance, 0 resistance, 0 resistance. I get to 2. Again, I can go up here or down here, which gives me only half an R resistance, and I get to here plus 1. So for C, if I had just a 1.5 for my resistance. And then if we do the last one, closed, closed. Oh, switch 1 is open, so it couldn't go down through the bottom. This one should be just 2 R, right guys? And then D, if they're both closed. Again, we got a short circuit, so as we go around, I got nothing, 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 nothing. Now I get here and switch 2 is closed. So now we get to have just that 1.5 R. So which one of those got the greatest resistance? That would be D. So this would be first, and then C. Really we're just going in reverse order. So looking at that equivalent resistance to find what your total current will be. Okay. Sorry, Roger. I'm so glad you're back. And we're gonna throw it back to you to wrap it up tonight.
Right, well, thanks for courage under fire there. Sorry that happened. I think it's because the computer heard me. I made a snipe about a Microsoft product and it just said, oh yeah, okay. Maybe that's what. All right, let's go ahead and move on. I've got a really good problem to finish out with you guys for tonight. This is a fun problem. Not a problem that you're necessarily ever going to see on an AP exam. This didn't come from an AP exam, but I want you to take a look at it. It says draw an electric circuit that is consistent with the values of this chart and label the resistors. Okay, so let's take a look at this. So consistent with the values of this chart. Let's look at this chart. This is the voltage, drop, current, and resistance chart. And we can see that we've got every resistor and then we've got the battery. And they also give us the current through the battery, which is pretty useful. Now, I just want you to look at this for a minute and see, do you see any patterns? What might mean, how can we start? So I'll show you. Well, I think we can all agree that there's one battery. And so I think that's a good place to start. So let's go ahead and start with the battery. And so here's my battery. And I'm told that my battery has a voltage gain. The EMF is 64 volts. Okay. And so we'll start there. Now, we know that the battery also has 12 amps of current. Okay? So we get that. So let's go ahead and we can actually put a little check mark there. We got those. Now what's next? Well, let's look. What is something that's obvious? Let's talk about the current first. Do we notice anything about the current? Well, we've got the 12 here, and we've got a 12 here, and a 12 here. And I think a lot of you probably remember the loop rule we just talked about, where the current going into a junction has to equal the current coming out of the junction. If I've got 12 amps, I can't have a junction because there's no place for the current to go. What does that mean? It means that these two resistors, R4 and R7, have to be in series with the battery and in parallel with no other resistors. So that doesn't prescribe exactly where they could go. So I could put this one, I could put one here, and I could put one here. I could put R4 here and R7 here. Or I could do it another way. I could put R4 here, I could put R7, and here I could put R4. That, for this problem, wouldn't make a difference. All right. So I can do that. And the reason I can do that, once again, is because these have to be in, they can't be in parallel because the current can't be reduced. And so once again, let's go ahead and say that we've got 12 amps of current through each one of these. There's my 12 amps. And for each of these guys, let's see, what do we have also? The resistance is 1 ohm and 2 ohms, and that'll be important later. All right, good. So let's go ahead and do that. Now I'm going to take these guys kind of out of the list just lately. We'll erase this in a minute, but I want to be able to see what I can focus on. Let's look at what's left. So we can see what's left here, and let's talk about the junction rule again. Now, what did the junction rule tell us? Well, it told us that when we have a junction, the sum of the current going into the junction has to equal the sum of the current coming out of the junction. Well, if I've got 12 amps speeding along in this direction, and then I've got 5 and 5 and 2, that's a hint that these three, since they add to 12, they could be in parallel. That would work. That would satisfy the junction rule. So then let's ask, well, what is the potential drop across resistors in parallel? And we've said it for a couple nights. When resistors are in parallel, when branches are in parallel, they have the same voltage drop. And so there's overwhelming evidence that these three resistors must be in parallel: R1, R2, and R3. And the resistors are, let's see, R1 is going to be 4 ohms, R2 is 10 ohms, and R3 is 4 ohms. Now, it does not matter for this problem in which order I put these. They are interchangeable for the way this problem is written. And notice they have the same voltage drop. Okay, good. So now we're going to come back together. Here's a junction. I can put the junction kind of like that, although that could confuse people. So I don't want. All right, let's go ahead and keep going on that. Now, so now let's look what's left. We got these guys handled. What's left are these two. Now look at this. They have the same voltage drop, which suggests they might be in parallel, and the sum of their currents sum to 12. Well, that's the overwhelming evidence right there. And so we're going to draw these two. We're going to have R5 out here, and that is 2 ohms, and we're going to have R6, and that is 1 ohm. And so that comes back to here. And then to go back and just, if you wanted to, it'd be really easy to double check and go back and say, okay, well, what about the voltage drop? Let's look at the loop rule. Well, the voltage drop says the sum of all the voltage gains and drops around a closed loop has to be 0. So here I have a plus 64. There's plus 64. All right. Now I have a voltage drop of IR 12 amps times 2 ohms. That's minus 24 volts. Okay. Now I have a voltage drop, and the voltage drop across this one we know is 20 volts. All right. And so that's a minus 20 volts because all of these resistors have a drop of 20 volts. And then here I have a drop of 8 volts. So as I go around the loop, gain 64, minus 24, minus 20, minus 8. And now here we're going to have another voltage drop across R7 of 12 volts, minus 12. And if you add that up, 24, 20, 44, 52, and 64. That's the loop rule. And so with that, we're going to close it out. I love this problem because it forces you to kind of reverse engineer some of the ideas that we've been talking about. So you might want to rewind that, pause it, take a screenshot of it, try it yourself. It's a great problem. All right, I can't let up on the magic square of electrostatics, ladies and gentlemen. When you're studying this, don't forget your force, electric field, energy, and voltage. This is so useful. Newtons per Coulomb. We have joules and joules per Coulomb. Go back and fill out your magic square. It'll help you, I hope, on the test. So great you came tonight. Thank you for coming. We had a great time. Tomorrow night, as I said, we're going to put the capacitors in, maybe if you have a lesson early. Kristen, is your equipment working fine?
Yeah, I'm still here, Roger.
Okay, great. Well, again, sorry about the equipment failure. Thanks for taking over so abruptly quickly there. Appreciate that. And can't wait to see you tomorrow night. Have a great night and study hard.